10. Self-organized oblique waves upstream the leading edge of a flat plate. Abstract. In this paper, for the first time, we report the formation of self-organized oblique waves upstream the leading edge of a flat plate. The flow structures are identified by a reflection method and a refraction method via the visualization of water waves. The results show that the interaction of oblique waves leads to the deformation of two-dimensional waves. The oblique waves propagate upstream from the leading edge at all flow velocity cases. As the flow velocity increases, the angle between the oblique waves and the leading edge decreases. Supplementary information. The online version contains supplementary material available at org 10100 7978 980 195 244 1910. This chapter is reproduced with permission from C.R. Yang, Z.H., and C.B. Lay, self-organized oblique waves upstream of the leading edge of a flat plate. Fluids 37-2, 21714, 2025. Copyright 2025 AIP Publishing. The content of the article has been slightly revised. According to S1 description of transition, environmental disturbances undergo a receptivity process before exciting instability waves in the boundary layer and follow different transition paths. 1. The key role of oblique waves in various transition paths is widely recognized. In traditional transition paths, a pair of oblique waves with identical wave angles but opposite directions is essential in triggering the transition too. Besides, when studying the bypass transition induced by free stream turbulence, a pair of oblique waves is often used to approximate the free stream disturbances 3, 4. To track the origin of oblique waves, the focus should be on the leading edge, a critical area within the realm of receptivity studies. 5. Classic receptivity theories can be divided into two parts. The forced receptivity theory 6 involves the use of a triple-deck structure 7 or the equation OSC 8, while the natural receptivity theory 8 was characterized by the high-number asymptotic analyses proposed by 9-10. It is worth noting that previous receptivity researches primarily focused on the internal region of the boundary layer, with limited attention given to the free stream region near the leading edge. Moreover, little focus was put on the generation and evolution of flow structures upstream of the leading edge. Though oblique waves gain much attention in transition paths and receptivity studies, there is no direct experimental evidence for their origin. In addition, when and where oblique waves appear, and whether they travel upstream or downstream remain questionable. Schematic view of the flow visualization setup. A reflection method, B refraction method, I side view, top view. The experiment was conducted in the Peking University Low Turbulence Water Tunnel, PWT. The test section is of 04M 04M 6M, and the turbulence intensity is less than 0.7%. There are no visible water waves without test model when the flow velocity is less than 0.3 ms. The flat plate of 1 m in length, 0.4 m in width, and 3 m in thickness has an elliptical leading edge with an aspect ratio of 2:1, the geometry of which is frequently used in receptivity experiments. 5. The plate spans the width of the test section of the tunnel and is placed horizontally 10 below the water surface. To display the flow structures formed upstream the leading edge of the plate, we applied two indirect flow visualization methods based on the principle of light reflection and refraction, namely the reflection method and the refraction method, respectively. The setup of the two methods is shown in Fig. 10.1. For the reflection method, Fig. 10.1 as a rough wooden board inclined at 45 to the horizontal plane was positioned as the background board on one side of the tunnel. The board was illuminated by scattered light from an incandescent lamp, and the diffuse reflection condition was established. A camera was set up symmetric with the background board on the opposite side of the tunnel to capture the reflected light from the water. For the refraction method, Fig. 10.1b, a parallel light volume was produced by the source positioned below the bottom of the tunnel. A white translucent plastic film fixed by strings with a flexible height above the water surface was set up to serve as the background plate. A camera was strategically set up to capture images of the background plate. Snapshots of the reflection method at different flow velocities. See 0.16 ms, 0.18 ms, 0.2 ms multimedia available online. Snapshots of the refraction method at different flow velocities. A D0.14 ms, 0.16 ms, 0.18 ms, and 0.2 ms multimedia available online. Evolution of oblique waves at flow velocity of 0.14 ms. The background plate was placed 10 above the water surface. The time interval between frames, a d, is 100. Evolution of oblique waves at flow velocity of 0.16 ms. The background plate was placed 8 above the water surface. The time interval between frames, a d, is 100. The variation of oblique wave angle relative to the leading edge with flow velocity. Flow velocity ms. Oblique wave angle 0.14, 37.85, 0.16, 32.25, 0.18, 27.75, 0.2, 21.15. The oblique wave angles at different flow velocity cases are also measured. Figure 10.5 shows that the dark fringes on the 2D waves in the direction are caused by the overlap of oblique waves. Based on this idea, the dark fringes of adjacent 2D waves are approximately composed of crossed oblique waves, and the absolute value of oblique wave angles relative to the leading edge can then be obtained from Fig. 10.3c at a flow velocity of 0.2 ms in Fig. 10.3d. The wave angle of the oblique wave is measured from the deformation of the bright fringe closest to the leading edge. Table 10.1 summarizes the measured oblique wave angles at different flow velocities, with mean values and error ranges. With the increase of the incoming flow velocity, the angle between the oblique waves and the leading edge gradually decreases. At a flow velocity of 0.14 ms, the movement of oblique waves is clear. New oblique waves are continuously generated from the leading edge and maintain similar wave angles as the previous oblique waves. At flow velocities of 0.16, 0.18, and 0.2 ms, the generation of oblique waves is stable and the wave angles remain unchanged over time. Finally, the interaction of oblique waves results in the deformation of 2D waves. Mathematically, the ratio of the oblique wave's wavelength to its wavelength equals the tangent of the oblique wave angle. From Fig. 10.3, we observe that, as the flow velocity increased from 0.14 ms to 0.16 ms, the wavelength is reduced by approximately half, whereas the tangent of the wave angle only decreases a little according to the statistic results in Table 10.1. Therefore, the wavelength of the oblique wave should be smaller at higher velocity case. Additionally, according to Figs. 10.4 and 10.5, the observed wavelength of the oblique wave can be represented by the distance between B1 and B2, which is larger than 1 in Fig. 10.4 and smaller than 1 in Fig. 10.5. Thus, we can also conclude that the wavelength of oblique waves decreases with the increase of flow velocity. Since no artificial disturbances were introduced in our experiments, the generation of oblique waves can be regarded as a self-organized process. Based on our present experiments, the existence of oblique waves did not depend on the distance between the flat plate and the water surface. We chose a distance of 10 between the plate and the water surface so that reflection and refraction methods could identify the oblique wave structures effectively. Here, the water surface was only utilized to visualize the oblique waves and did not affect the generation of oblique waves. Whether the surface would affect the oblique wave's evolution beyond this study's scope. In summary, we utilized the water surface to realize the flow visualization of the waves upstream the leading edge of a flat plate. By combining a reflection method and a refraction method, the shape and evolution of the oblique wave upstream the leading edge are shown in detail. We found that oblique waves occur under all flow velocity conditions. As the flow velocity increases, the angle between the oblique wave and the leading edge decreases, while the 2D waves become more pronounced, accompanied by the deformation process. The present results are both inspiring and significant for advancing the understanding of the receptivity process. In future studies, more careful measurements will be conducted. Competing interests, this research was supported by the National Natural Science Foundation of China grant notes. 12,072,002, 109,103,010,062, and 10,921,202, and the National Key Project grant no. GJXM 92579. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Data availability, the data that support the findings of this study, are available from the corresponding author upon reasonable request. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. MV in Viscous Drag Reduction, ed. by C.S. Wells, Springer, New York, 1969. 131. Org 10100 7978 14899557911. 2. CB Lay XY. Fluids 3111. 111,301, 2019. 3. Q. Dias Bull. IM. Social. 35-2288, 1990. 4. PJS Luo XS Wu J Fluid Mech. 677, 1, 2011 net. 5. WS HL Reed IJ. Rev. Fluid Mech. 34-1, 291, 2002. 6. EN 12 Aeroacoustic Conference, American Institute of Aeronautics and Astronautics, San TX USA, 1989, AIAA Paper 89-1109. Org 1025-14619-891109. 7. XS Wu J Fluid Mech. 431-91 2001. 8. M. Gaster J Fluid Mech. 22-3 433 1965 net. 9. M.E. J Fluid Mech. 154 509 1985. 10. M.E. J Fluid Mech. 127 59 1983 net. 11. J.H. Proc. R. Soch. Sir. A 377 1770 331 1981. 11. Soliton-like coherent structures of transitional flow in the wake of a sphere. Abstract. The soliton-like coherent structure, SCS, which has been to exist in both transitional and turbulent boundary layers, still poses a challenge in the understanding of its formation and behavior. In our previous study, LHS CJO WSU. Fluids 36-3, 34,127, 2024, the SCS was also found to exist in the transitional wake flow behind a sphere. In the present study, the formation and evolution of the SCS are further investigated at various numbers by numerical simulation. The results show that at the early stage of the turbulence transition, the SCS appears as a form of wave packet during the TS wave stage. With the increase of the number, the SCS reaches its maximum amplitude downstream, where the velocity discontinuity occurs. This position is located after the breakdown of the TS wave, and the three-dimensional structure is formed. Then the SCS conserves its shape and amplitude over a long distance downstream. The relationships among the SCS, the spikes, the vortex structures, and the high shear layers are further analyzed. It is found that the SCS in the wake flow has similarities to the phenomena observed in boundary layer flows during the turbulent transition. The vortex structures and high shear layers mostly wrap around the border of the SCS. The vortex structure is considered to be as a consequence of the development of the SCS rather than its cause. Keywords. This chapter is reproduced with permission from L, HS, CQ Joe, and WQ Su. Solitary wave structure of transitional flow in the wake of a sphere. Fluids 37-1, 14111, 2025. Copyright 2025 AIP Publishing. The content of the article has been slightly revised. 11.1 Introduction. In the 19th century, the British scientist observed a fast-moving boat on a canal coming to a sudden stop, while the mass of water it was propelling formed a large, well-defined packet of water that continued to move at a constant speed. Followed this packet of water and observed it moving steadily across the surface of the water until it dissipated after several kilometers. He named this unique water wave phenomenon solitary wave 1. A solitary wave is a special type of fluctuating phenomenon that retains its shape, amplitude, and speed as it propagates. This phenomenon has shown important applications in many fields, such as fluid dynamics, optics, plasma physics, and biology. In the field of fluid dynamics, researchers have gradually explored the elaborate details of solitary wave behavior in the context of turbulent transitions. They first identified the phenomenon of spikes when the boundary layer flow was undergoing turbulent transition, and then revealed the solitary wave properties of these spikes 2-4. When the boundary layer flow on a flat plate undergoes turbulent transition under low disturbance, it has been discovered that after the instability of TS wave, there exist three types of turbulent transitions, which are, respectively, K-type, O-type, and N-type transitions 4-6. As early as 1962, Al. 7 found that flash spikes in the K-regime are commonly attributed to laminar boundary layer breakdown and flow randomization. Several researchers then provided evidence for the solitary wave properties of the spikes and the relationship linking the spikes to the coherent structures. And Patera 8 were the first to describe the coherent structure of turbulence as nonlinear wave packets made up of two-dimensional and three-dimensional wave packets interacting resonantly. Al. 9 focused on exploring the transformation that low-amplitude wave packets, originating from air pulses of short duration under controlled circumstances, underwent to turn into a turbulent spot within a boundary layer. Subsequently, the existence of the solitary wave structure has been in both transitional and turbulent boundary layers 2, 3, 10. His team and Lee's team have conducted detailed studies on solitary wave in turbulent transition 2-4. Based on experimental and theoretical analysis, 11 proposed a theoretical concept for the early phase of the K-regime, i.e., the wave resonance concept of breakdown. Later on, 2 provided a comprehensive summary of the solitary wave features of spikes. He pointed out that there are spikes detected in the boundary layer flow, and that these spikes are coherent structures characterized by a deterministic and periodic nature, i.e., coherent structure solitons, CS solitons. These spikes are represented as ring-like vortices 12. Different from CS soliton ring-like vortices, Liao. 3.10.13 further studied the behavior of T-S waves and the flow structures in the boundary layer flow, and discovered that soliton-like coherent structures, SCSs, are actually three-dimensional waves. The evolution of this structure stems from the interaction of the two oblique waves, and it significantly influences the transition to turbulence. As the SCS evolves, they can induce strong shear layers that form at the SCS borders and can develop into secondary closed vortices. In terms of the signatures of SCS structure formation, CS solitons are the ring-like vortices and Lee's SCS is the three-dimensional wave 2-3. Using hot wire measurements, his team observed periodic spikes leading to the formation of SCS structures. Meanwhile, Lee's team repeated HAMA and experiments 14, using the flow visualization method with hydrogen bubble technique in boundary layer flow under natural transition conditions. They found that the lines of the hydrogen bubbles were parallel until a kink structure was formed. However, when the kink structure appeared, the bubbles first maintained their parallel shape and then developed into a three-dimensional 3D wave structure that emerged in front of the vortex. They suggest that this 3D wave structure constitutes the natural origin of the vortex and call it the Soliton-like coherent structure, SCS, due to the slow evolution of this wave and the generation of 3D localized flows. In recent years, Li and Four have discussed the important role of SCSs during the boundary layer transition and their interrelationships with other vortex structures. L. 1516 demonstrated that a traveling wave has the ability to trigger solitary waves while the wave energy is oscillating in the boundary layer. L. 17 further analyzed the evolution of SCSs in the K, N, and O regimes and proposed that the low-speed streaks, LSSs, may be composed of several SCSs. In addition, Al. 18 pointed out that the low-speed streak changes and appears as a 3D wave accompanied by ejection and sweeping behaviors in a turbulent boundary layer. They indicated that the amplification of the 3D wave plays a principal role in driving the development of LSSs. L19 had also confirmed the existence and evolution of SCS in increasingly turbulent stratified shear layers. Thus far, studies of the SCS in turbulent transition have mainly focused on the wall-bounded flows, including the channel flow and boundary layer flow 2, 4, 10, 15, 16, 18, 19. In contrast, there are relatively few studies of SCS in free shear flow. 20 showed that the mechanism of turbulence generation and the structure of turbulence in free shear flows are the same as those in wall-bounded flows. They are uniquely determined by the singularity of the Stokes equation. As such, it is reckoned that the Soliton-like structure found in wall-bounded flows in Liao 3.10.13 should also exist in free shear flows such as the wake flow. Then Al. 21 carried out numerical simulations on the wake flow behind a sphere at the number Ray 350 and found that the SCS really exists in transitional wake flow. It is also revealed that the SCS is produced by the negative spikes of the velocity, which are singularities of the Stokes equation. Since the SCS plays an important role in turbulent generation and turbulent transition, it is necessary to study the mechanism and the structure of this type of Soliton-like structure in depth to understand the mechanism of turbulence generation. In the present study, the characteristics and evolution of the SCS in the wake of a sphere are further explored through large eddy simulation, LIS, for various numbers. The behavior of the SCS in the turbulent transition is investigated as the number varies. Further investigations are made on the relationships among the SCS, the spikes, the high shear layers, and the vortex structures. It is found that the mechanism and behavior of SCS evolution in the wake flow are the same as those observed in wall-bounded flows. 11.2 Numerical simulations. Schematic of the geometry of the computational domain. Impacts of the number on the drag coefficient in the flow around a sphere. Ray 250, 270, 300, 350, 500, 700, 1000. Coarse mesh 0.64, 0.52. Medium mesh present 0.71, 0.69, 0.67, 0.63, 0.57, 0.52, 0.47. Refine mesh 0.63, 0.48. Wu and 22. 0.5. L. 23. 24. 0.68. 0.62. Johnson and 25. 0.656. Lay 26. 0.61. 0.54, and 27, 0.7, 0.62, 0.56. Luo al. 28, 0.757, 0.654. Al. 29, 0.673, 0.485. Al. 30, 0.65, 0.622, 0.55, 0.5, 0.46. Al. 31, 0.71, 0.67, 0.63, 0.58, 0.48. Al. 32, 0.466. Pressure coefficient around the sphere, array 300 and B-ray 1000. Comparison with results in literature, and 33 Claire al. 34 al. 23 Li 26 Wu and 22 al. 32. Furthermore, the non-dimensional root mean square of the velocity, URMS, as well as the non-dimensional averaged velocity, at the center line is clearly shown in Fig. 11.3. This result not only intuitively reflects the flow characteristics, but also shows a high degree of consistency with the findings in the existing literature. Taking into account the distributions of the drag coefficient, the pressure coefficient, the non-dimensional root mean square of the velocity, and the non-dimensional averaged velocity at the central line, the current results agree well with the literature data, thus confirming the accuracy and reliability of our research methodology. A non-dimensional RMS velocity at the central line of the wake, for ray 1000, B non-dimensional averaged velocity at the central line of the wake, for ray 1000. Comparison with results in literature, Wu and 22 and 36, al. 32. 11.3 Simulation results of flow in the wake. 11.3.1 Kink, structure and 3D wave packet generation in the wake. Vortex structures identified by at ray 250, T152S, a top view and B-side view. Generation of kink structures in the wake at ray 270, vortex structures identified by left, top view, contours of UU on the YD04 plane right, side view, contours of UU on the ZD0 plane. A T55S, BT65S, CT69S, and DT73S streamlines in the wake at ray 270. Vortex structures identified by orange, contours of vorticity magnitude on the ZD0 plane and the XD 3.937 plane, T73S during the kink formation. The outer side of the positive velocity disturbance region, red, is adjacent to the mainstream region, while its inner side is adjacent to the negative velocity disturbance region, blue. As a result, significant velocity gradients are generated at the boundaries of the traveling positive velocity disturbance region, and shear layers are formed at their junctions, as shown in Fig. 11.6. As the time increases, these shear effects accumulate in the downstream of the wake, eventually contributing to the formation of the kink structure. In particular, it can be seen that the shear layer attached to the sphere surface does not separate during this formation stage. This observation suggests that the kink structure does not stem from the shear layer shedding, but rather results from the instability of the zone. This instability leads to velocity disturbances, and these velocity disturbances cause local velocity distortions, which ultimately contributes to the formation of the kink structure. Therefore, the kink structure is a sign of the wave packets of the velocity disturbance. In this evolution, the initial velocity disturbance in the wake originates in the zone located at the rear of the sphere. Meanwhile, under the influence of this disturbance, the flow itself remains a laminar. The phenomenon of the kink structure has already been found in a similar number range in previous studies 38, 39. Al. 38 observed the vertical velocity fluctuations from the numbers 262 to 291 through visualization experiments. In particular, they recorded harmonic fluctuations in the vertical velocity fluctuation at ray 266 and hypothesized that such fluctuations are associated with the kink phenomenon. L. 39 further suggested that the kink phenomenon serves as an early sign before the periodic appearance of the hairpin vortices. Furthermore, the kink structures have been found in studies on turbulence onset within the boundary layer flow. Lee 3 repeated Hama and 1963 experiments 14 under natural transition conditions. The results of his experiments demonstrated that the kink is a 3D wave structure which interacts with the boundary layer to form a high shear layer, and this ultimately results in the generation of a vortex. As it comes to the kink generation stage, the velocity fluctuation mainly shows up as a T-S wave with an amplitude that is rather small, around 0.25% of the incoming velocity. In contrast, the velocity fluctuations in the other two directions in the wake are even much smaller in amplitude, with amplitudes of about 0.07% and 0.06% of the incoming velocity. L. 9 noticed in boundary layer experiments that during the linear stage of the wave packet's evolution, the amplitude amounts to around 0.3% of the incoming velocity, and then it grows significantly to reach 5% in the subharmonic stage. These findings suggest that the velocity fluctuations within the wake at Ray 270 already exhibit three-dimensional properties. Although these three-dimensional properties are relatively weak, they have some similarities to those properties of the boundary layer flow. The wave packets with 3D velocity disturbances represent the initial phase of the SCS and indicate the onset of a more complex flow structure. 1132 SCS generation. Vortex structures identified by at Ray 280 T254S, a top view and B-side view. Solitary wave structure identified by non-dimensional velocity disturbances at Ray 280 T254S on YD0787 plane. A non-dimensional velocity disturbance UU, B non-dimensional velocity disturbance VU, and C non-dimensional velocity disturbance WU fluctuations of velocity components. Array 280 T, S wave behavior, B ray 300, vortex shedding behavior, and C ray 350, onset of velocity spike formation. The velocity fluctuations in the three directions corresponding to the numbers 280, 300, and 350 are presented in Fig. 11.9. The monitoring points are represented as red dots in Figs. 11.7, 11.1, and 11.12, respectively. This location is one of the most unstable regions of the flow in and around the hairpin vortex 21. At Ray 280, the velocity fluctuations in three directions show synchronized cyclical variations, where the flow is almost two-dimensional and can be expressed by waves of U and V, exhibiting typical T-S wave characteristics. Respectively, the amplitudes of U, V, and W velocity fluctuations are approximately 6.3%, 3%, and 0.06% of the incoming velocity. At this time, the amplitude of U and V velocity fluctuations exceeds 2% of the incoming velocity, and the wake begins to enter the nonlinear collapse phase 2. The three-dimensional characteristics of the velocity fluctuations under the current number condition are significantly enhanced, amplitude increased by approximately 20 times compared to those at Ray 270. The 3D wave packet moves downstream at about 78% of the incoming velocity, which is similar to the SCS velocity measured by Al. 18 in the boundary layer flow. Al. 18 show that the moving speed of the SCS is about 60%, 80% of the incoming velocity. It can be seen that in the wake of a sphere, after the formation of the three-dimensional kink structures, it is hairpin vortices rather than vortices that are commonly formed as the number rises, and this is different from the transitional flow in the boundary layer. Vortex structures identified by at Ray 300 T309S, a top view and B-side view. Solitary wave structure identified by non-dimensional velocity disturbances at Ray 300 T309S on YD0787 plane. A non-dimensional velocity disturbance UU, B non-dimensional velocity disturbance VU, C non-dimensional velocity disturbance WU vortex structures identified by at Ray 350 T165S, a top view, B-side view. Solitary wave structure identified by non-dimensional velocity disturbances at ray 350 T165s on YD0787 plane. A non-dimensional velocity disturbance, UU, B non-dimensional velocity disturbance, VU, C non-dimensional velocity disturbance, WU relative positions between the hairpin vortex and the wave packet of the velocity disturbance UU, vortex structures visualized by isosurfaces of 023 in yellow, wave packets identified by isosurfaces of UU, negative in blue and positive in orange. Array 250, B ray 270, C ray 280, ray 300 and E ray 350. The location of the negative velocity spike along the flow direction is the monitoring point, which is marked as a red dot in Fig. 11.12. A velocity discontinuity takes place when the energy transfer between fluid layers ceases. Because of the viscosity of the fluid element that has velocity discontinuity cannot come to an immediate stop, but rather decreases its velocity significantly, which leads to a negative spike. At this point, the flow is compressed along the flow direction, causing an almost simultaneous positive spike in the velocity v and triggering an ejection motion at the red point in Fig. 11.12b. The motion is in the direction shown by the red arrow, and this marks the start of turbulence generation. At the same time, as a result of the continuity equation and the conservation of mass, the velocity w exhibits a corresponding positive spike. From the perspective of the time sequence, the negative peak of the U component forms first. This is followed by the positive peak of the V component, and finally the positive peak of the W component. Consequently, the turbulence that originates from the spikes of U and V velocity components is generated through the ejection motion. The negative spikes of U play a key role and are the main driving force in sustaining velocity fluctuations. It is the component of velocity U that transfers the energy from the main flow to the fluctuations by its discontinuity 2021. The occurrence of these spikes denotes the onset of the turbulent transition in the wake. At ray 350, the formation of spikes in the wake gives rise to the sharpening of the 3D wave packets, which is a feature of the SCS. Such sharpening, which represents the singularity of the Stokes equation, indicates the beginning of the laminar to turbulent transition, and throughout this transition, the flow dynamics become more complicated. Figure 11.14 shows the relative positions of the hairpin vortex to the wave packet of the velocity disturbance UU for different numbers. When the number is less than 270, the velocity disturbance UU within the wake is weak and almost negligible. However, once the number reaches 270, the amplitude of the velocity disturbance UU is still small, but significant velocity fluctuations begin to appear with the appearance of the kink structure in the wake. When the number goes up from 270 to 280, the velocity disturbance UU in the wake begins to form a distinct regular wave packet. The wave packet of the negative velocity disturbance UU is positioned in the middle of the two vortex legs. Furthermore, as the number goes up from 280 to 300, the position of the wave packet of the velocity disturbance UU changes significantly. In this evolution, the negative wave packet moves from the middle of the two hairpin vortex legs toward the central area of the hairpin vortex head, while its positive wave packet always occurs at the vertically symmetric position of the negative wave packet. With the continuous increase of the number, the position of the negative wave packet in the central area of the hairpin vortex head remains unchanged. These features of the velocity disturbance, in particular, the appearance of spikes and the stable relative position of the negative wave packet, together indicate the formation of the SCS structure. L. 43 showed that in the early stages of SCS formation, the structure develops mainly along the two flow directions, usually flow and spreading, with relatively little change in the third direction, which is normal to the flow direction. When they are in the two-dimensional phase, SCSs take on a spiky morphology. Additionally, these spikes rapidly recede from the wall as they form and propagate within the boundary layer with a relatively conserved morphology. This shows the conservatism of coherent structures, i.e., their morphology and amplitude remain almost constant during propagation in the boundary layer. Li3 has shown that within the SCS, the negative spikes in the flow direction are synchronized with the positive spikes in the propagation direction, y-axis. The three-dimensional features of the SCS within the wake of a sphere also experience a transition from a T-S wave morphology to a spiky morphology. As the number rises from 280 to 350, the velocity fluctuation changes from a T-S wave morphology to a spiky morphology. At rate 350, the velocity spikes in the three flow directions occur almost simultaneously. At first, there is a negative spike in the U component, followed by a positive spike in the V component, and finally a positive spike in the W component. The spike in the third direction was not discussed in the studies of Al. 43 and Li 3. 1133 SCS evolution. Position of monitor lines. Array 350, B-ray 500, C-ray 700, and D-ray 1000. Two monitoring lines are defined. Line 1 is positioned at those points where the values of XD, YD, ZD span from 40-4 to 404. In contrast, line 2 is located at the points where the XD, YD, ZD values range from 040 to 0-40. The configuration makes it possible to monitor and analyze how the flow goes in both directions, and the positions of the two lines relative to the vortex structure are presented in Fig. 11.15. Solitary wave structure in the wake, UU distribution along line 1, array 350, C-ray 500, E-ray 700, and G-ray 1000, UU distribution along line 2, B-ray 350, ray 500, F-ray 700, and H-ray 1000. Relative positions between the hairpin vortex and the wave packet of the velocity disturbance UU, vortex structures visualized by isosurfaces of 023 in yellow, wave packets identified by isosurfaces of UU, negative in blue and positive in orange, array 500, B-ray 700, and C-ray 1000. For different numbers, ray 350, 500, 700, and 1000, Fig. 11.18 shows the velocity fluctuations in the wake at a monitoring point located in the XD3937 plane. This monitoring point is located directly on the side of the wake, at the lower edge of the head of a primary hairpin vortex, which is one of the most unstable regions of the flow around the hairpin vortex 21. The ejection motion formed by the velocity fluctuations can be identified in Fig. 11.18. In the initial phase of the turbulent transition of the wake, ray 350, from the time sequence analysis, the velocity component U direction of flow first shows a negative spike, followed by the velocity component V vertical direction of flow, and finally the velocity component W direction of spreading, with a sequence as shown by markers 1, 2, and 3 in Fig. 11.18. The magnitude of the spike shows that the negative spike of U is the most significant, followed by V, while the magnitude of W is relatively small. This difference in time sequence and amplitude suggests that the negative spike of U component is key and dominant in the turbulent transition. It is the main driving force for the onset of turbulence generation. Velocity fluctuations with time at fixed monitoring points on the XD 3.937 plane where the ejection motion can be identified. Array 350, B-ray 500, C-ray 700, and D-ray 1000. Evolution and characterization of the SCS with increasing number. Ray, vortex structure, velocity fluctuation, 3D wave packets, SCS, SCS speed relative to the incoming velocity, 250, parallel vortices, faint TS wave, 270, kink appears at around D6, faint TS wave, exist, early pattern, 48%, 280, hairpin vortices, TS wave, exist, early pattern, 78%, 300, hairpin vortices, vortex dislocation, transitional form between TS wave and spike, exist, early pattern, 81%. 350. Hairpin vortices, vortex dislocation. Spike. Exist. 81%. 500. Asymmetrical hairpin vortices, secondary vortices. Spike. Exist. 79%. 700. Asymmetrical hairpin vortices, secondary vortices. Spike. Exist. 90%. 1,000. Asymmetrical hairpin vortices, secondary vortices. Spike. Exist. 87%. In the study that focused on the large-scale turbulent structure generated by a broken solitary wave on a 150 plane slope, Ting 45 found significant correlations among the velocity disturbance components U, V, and W. Moreover, these obtained correlations reveal the influence of coherent structures on turbulence characteristics. Al. 15 made a discovery in their study on spike-like solitary waves, which are driven by a traveling wave in an incompressible boundary layer. They found that as the amplitude of the driving wave gradually increases, the flow structure experiences a transition from being regular to becoming irregular. Moreover, it was observed that the velocity U component holds the majority of the fluctuating energy within the solitary wave, and the V and W components are related to the three-dimensional properties of the flow. The key role of the negative spikes of U in the turbulence transition is supported by these results. The variations of the velocity components V and W change significantly with increasing number. When there is a negative spike in the velocity U, the spikes in the velocity components V and W tend to be either positive or negative, as depicted in Fig. 11.18bd. Additionally, the dynamic behaviors of the velocity components U, V, and W must conform to the fundamental principles of fluid mechanics, such as the continuity equation and the law of conservation of mechanical energy, so as to guarantee physical consistency. Relative position between the SCS, identified by UU on the YD0787 plane, and vortex structures, identified by 023, array 350 and B-ray 1000. 1134 SCS, high shear layer hairpin vortex. Three phases of the SCS effect on vortices by velocity fluctuations. A one-dimensional effect, ray 270, B two-dimensional effect, ray 350, and C three-dimensional effect, ray 1000. During the first stage, when the number is low, its three-dimensional features, see sect. 1131, amplitude of the velocity components at ray 270 are not prominent, and this impact is primarily exhibited as a one-dimensional effect in the direction. The instability of the zone behind the sphere gives rise to this fluctuation. As a result, there are fluctuations in the velocity difference between the high-speed fluid of the main flow and the low-speed fluid of the wake flow along the flow direction. As shown in Fig. 11.2, this velocity fluctuation at locations with large amplitudes generates a shear layer, which promotes the formation of the kink structure. The formation of the kink structure is the result of velocity fluctuations caused by the instability of the zone. During the second stage, with the number rising to 350, the instability of the zone is intensified, see sect. 1132, amplitude of the velocity components at ray 350. The SCS transitions from one-dimensional effect to two-dimensional effect, although the fluctuation of the third dimension, z direction, is still small, less than 0.2% of the incoming velocity. At this stage, the velocity fluctuation in the wake undergoes a change from a T-S wave to a spiky morphology, which marks the formal formation of the SCS. As depicted in Fig. 11.12b, in the XY plane, the velocity disturbances in the X and Y directions play a dominant role in the ejection motion. They take the low-speed wake flow fluid into the high-speed main flow zone, make fluid mix better, and form a big high shear layer at the main flow and wake junction, as shown in Fig. 11.2b. At the same time, sweep phenomena occur on both sides of the vortex legs, and these ejection and sweep motions are the energy sources for the generation and development of turbulence. These velocity fluctuations interact with the ejection and sweep motions that are brought about by the primary hairpin vortex. Collectively, they influence the fluid and give rise to a robust high-shear layer, which provides favorable circumstances for the creation of secondary vortex structures in the upstream region of the primary hairpin vortex. Relative position vortex structures identified by method, SCS identified by UU02, and high shear layer contours of vorticity magnitude on XY plane, high shear in yellow, Ray 350 T135S relative position. Vortex structures identified by method, SCS identified by UU02, and high shear layer contours of vorticity magnitude on XY plane, high shear in yellow, Ray 1000 T98S. The hairpin vortex is located at the periphery of the SCS in the wake of a sphere, and the high shear layer wraps further around the outside of the hairpin vortex as shown in Figs. 11.21 and 11.22. This structural arrangement is similar to the phenomena observed in boundary layer flow by Lee 3. In these studies, it was found that the high shear layer and vortex structures usually form and then evolve along the borders of the SCS. This suggests that the hydrodynamic behavior follows a similar pattern in both boundary layer flow and wake flow, where the SCS has an important influence on the flow properties. 11.4 Conclusions. 1. Appearance of the initial wave packets. In the initial phase of the turbulent transition, 2 alternating unique three-dimensional wave packets are found in the wake of a sphere. This flow structure marks the initial appearance of the SCS. This structure is formed before the vortex shedding in the TS wave stage of the wake flow. In the initial stage, Ray 270, a shear layer is formed at the junction due to the velocity difference. The instability within the zone following the sphere results in periodic velocity fluctuations and contributes to the formation of the three-dimensional wave packets. As for the wave packet between the 2 vortices, it accelerates the roll-up of the shear layer, which ultimately leads to the formation of a kink structure. The appearance of the kink denotes the beginning of the formation of the wave packet featuring velocity fluctuation, which is the incipient stage of the SCS. The amplitude of the three-dimensional wave packet is rather low in this stage. Appearance of the initial wave packets. In the initial phase of the turbulent transition, 2 alternating unique three-dimensional wave packets are found in the wake of a sphere. This flow structure marks the initial appearance of the SCS. This structure is formed before the vortex shedding in the TS wave stage of the wake flow. In the initial stage, Ray 270, a shear layer is formed at the junction due to the velocity difference. The instability within the zone following the sphere results in periodic velocity fluctuations and contributes to the formation of the three-dimensional wave packets. As for the wave packet between the 2 vortices, it accelerates the roll-up of the shear layer, which ultimately leads to the formation of a kink structure. The appearance of the kink denotes the beginning of the formation of the wave packet featuring velocity fluctuation, which is the incipient stage of the SCS. The amplitude of the three-dimensional wave packet is rather low in this stage. 2. Soliton-like coherent structure. The SCS in the wake of a sphere is in the form of a three-dimensional wave packet. This wave packet brings about a negative spike in the velocity and is located right at the head center of the hairpin vortex. The three-dimensional nature of this structure is mainly reflected in the distribution of velocities. As for the negative spike of the velocity u, it is caused by a velocity discontinuity, at which point the energy transfer among the fluid layers ceases. Because of the fluid's viscosity, the fluid element in which the velocity discontinuity occurs cannot be stopped immediately, but is instead transitioned by a sharp decrease in velocity, resulting in the negative spike. The position of this discontinuity gives rise to a singularity in the Stokes equations. The superposition of the velocity vector u and the velocity vector v in the central plane of the hairpin vortex produces an ejection motion zone. This ejection motion produces a high shear stress in the Q2 quadrant of the two-dimensional velocity fluctuations 43. Subsequently, a high shear layer is formed at the junction of the high-speed fluid and the low-speed fluid, which is precisely the exterior of the hairpin vortex. As the high shear layer increases, so does its instability, resulting in intense fluid instability. In addition, the high shear layer rolls up to form a secondary vortex structure. Soliton-like coherent structure. The SCS in the wake of a sphere is in the form of a three-dimensional wave packet. This wave packet brings about a negative spike in the velocity and is located right at the head center of the hairpin vortex. The three-dimensional nature of this structure is mainly reflected in the distribution of velocities. As for the negative spike of the velocity u, it is caused by a velocity discontinuity, at which point the energy transfer among the fluid layers ceases. Because of the fluid's viscosity, the fluid element in which the velocity discontinuity occurs cannot be stopped immediately, but is instead transitioned by a sharp decrease in velocity, resulting in the negative spike. The position of this discontinuity gives rise to a singularity in the Stokes equations. The superposition of the velocity vector u and the velocity vector v in the central plane of the hairpin vortex produces an ejection motion zone. This ejection motion produces a high shear stress in the Q2 quadrant of the two-dimensional velocity fluctuations 43. Subsequently, a high shear layer is formed at the junction of the high-speed fluid and the low-speed fluid, which is precisely the exterior of the hairpin vortex. As the high shear layer increases, so does its instability, resulting in intense fluid instability. In addition, the high shear layer rolls up to form a secondary vortex structure. 3. Relative position of the SCS and hairpin vortex. In the SCS's initial stage, the wave packet of the negative velocity is located between the two vortices, while the positive wave packet is located at the position of the kink structure. When the velocity spikes are generated in the wake, the position of the SCS moves with the ray increase, moving from the middle of the two hairpin vortex legs toward the central area of the hairpin vortex head. This state maintains until the number reaches 1000. During this evolution, the high shear layer always covers the surrounding area of the hairpin vortex. Relative position of the SCS and hairpin vortex. In the SCS's initial stage, the wave packet of the negative velocity is located between the two vortices, while the positive wave packet is located at the position of the kink structure. When the velocity spikes are generated in the wake, the position of the SCS moves with the ray increase, moving from the middle of the two hairpin vortex legs toward the central area of the hairpin vortex head. This state maintains until the number reaches 1000. During this evolution, the high shear layer always covers the surrounding area of the hairpin vortex. 4. Power for turbulent generation. In the early stage of the turbulent transition from the time sequence, the negative spike of the U component is formed first, followed by the positive spike of the V component, and finally the positive spike of the W component. The magnitude of the spike indicates that the negative spike of the U component is the most significant, followed by the V component, while the magnitude of the W component is relatively small. This difference in time sequence and amplitude suggests that the negative spike of the U component is key and dominant in the turbulent transition. It is the main driving force for the onset of turbulence generation. Power for turbulent generation. In the early stage of the turbulent transition from the time sequence, the negative spike of the U component is formed first, followed by the positive spike of the V component, and finally the positive spike of the W component. The magnitude of the spike indicates that the negative spike of the U component is the most significant, followed by the V component, while the magnitude of the W component is relatively small. This difference in time sequence and amplitude suggests that the negative spike of the U component is key and dominant in the turbulent transition. It is the main driving force for the onset of turbulence generation. 5. The fluctuation pattern of the SCS varies with number. When the number is between 280 and 300, the velocity fluctuation takes the form of a T-S wave. As soon as the number exceeds 300, the velocity fluctuation in the wake begins to show significant spikes until the wake changes completely to a turbulent state. At the stage where the hairpin vortex has not yet formed a secondary vortex structure, 280 Ray 350, the SCS in the wake shows a regular pattern, i.e., a single peak alternating with a single valley. When the number further goes up, the primary hairpin vortex begins oscillating and distorting, while the secondary vortex structures begin to form around it. This change leads to a more complex structure of the SCS, and the fluctuation pattern changes from the original regular single peak and single valley alternating to a complex multi-peak and multi-valley fluctuation pattern. This multi-peak and multi-valley pattern is morphologically more complex and moves downstream with a propagation speed of about 80–90% of the incoming velocity. The fluctuation pattern of the SCS varies with number. When the number is between 280 and 300, the velocity fluctuation takes the form of a T-S wave. As soon as the number exceeds 300, the velocity fluctuation in the wake begins to show significant spikes until the wake changes completely to a turbulent state. At the stage where the hairpin vortex has not yet formed a secondary vortex structure, 280 Ray 350, the SCS in the wake shows a regular pattern, i.e., a single peak alternating with a single valley. When the number further goes up, the primary hairpin vortex begins oscillating and distorting, while the secondary vortex structures begin to form around it. This change leads to a more complex structure of the SCS, and the fluctuation pattern changes from the original regular single peak and single valley alternating to a complex multi-peak and multi-valley fluctuation pattern. This multi-peak and multi-valley pattern is morphologically more complex and moves downstream with a propagation speed of about 80–90% of the incoming velocity. 6 effects of the SCS. There are 3 stages in the evolution of the SCS. The first stage is the one-dimensional effect, which represents the formation of the kink structure and the appearance of 3D wave packets. The second stage is the two-dimensional effect, which indicates the appearance of a high shear layer. The third stage is subjected to the three-dimensional effect, reflecting the formation of secondary vortices. Effects of the SCS. There are 3 stages in the evolution of the SCS. The first stage is the one-dimensional effect, which represents the formation of the kink structure and the appearance of 3D wave packets. The second stage is the two-dimensional effect, which indicates the appearance of a high shear layer. The third stage is subjected to the three-dimensional effect, reflecting the formation of secondary vortices. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Data availability, the data that support the findings of this study, are available from the corresponding author upon reasonable request. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References. 1. In Proceeding of the 14th Meeting of the British Society for the Advancement of Science, 1845. 311–390. 2. YS. Rev. Fluid Mech. 26 411, 1994. 3. Sibile. A 247-6, 397, 1998. Org 101016 S0375960 198005829. 4. Sibile XY. Fluids 30 111, 111,301, 2019. Org 10106315121810. 5. BJ SAT. Rev. Fluid Mech. 21 359 1988. Org 1011462010188002 043. 6WS HL Read IJ. Rev. Fluid Mech. 34 291 2002. Org 101146 Fluid 34082701161921. 7 PS KD LM J Fluid Mech. 12-1-1962. Org 101017 S0022 112062000014. 8 SA AT Patara J Fluid Mech. 128 347 1983. Org 101017 S0022 112083000518. 9J KSJH J Fluid Mech. 225 575 1991. 10 CB Lai JZ Wu. Mech. Rev. 613 30802 2008. Org 10111512909605. 11 YS J Fluid Mech. 184 43 1987. Org 101017 S0022 112087002805. 12S Bake HHYS. J Mech. B Fluids 19-1 2000. Org 101016 S0997754600001084. 13 CB Lay ZX YSVI VV Exp. Fluids 28-3 243 2000. Org 101007 S003480050384. 14 FR Hama J in Proc. 1963 Heat Transfer and Fluid Mechanics, University Press, 1963-1963. 7793. 15 PJW Chaos 266, 63104 2016. Org 10106314953015 net. 16 P Slay J Ywu. Nonlinear. Simul. 7725 2019. Org 101016J2019020003 net. 17 XY CB Lay X CR Smith PF Linden J Fluid Mech. 890 A11 2020. Org 10101720200107. 18 XY CB Lay CR Smith JW PF Linden J Fluid Mech. 903 A6 2020. Org 10101720200617. 19 XY ASB PF Linden J Fluid Mech. 947 A30 2022. Org 10101720222588. 20 HS Origin of Turbulence Energy Gradient Theory Springer. Singapore 2022. Org 101079789819008777. 21 LHS CQ Joe WQSU. Fluids 36-3, 34127 2024. Org 10106350199349. 22 JS Wu GM AIAJ 318 1448 1993. Org 102514311794. 23 J M J J Fluid Mech. 284 97 1995 net. 24 R AIAJ 373 388 1999. Org 10251427 722. 25 TA Johnson VC J Fluid Mech. 378 19 1999. Org 101017 S0022 112098003206. 26 S Lay. Fluids 29-6 639 2000. Org 101016 S0045793 099000237. 27 PS J Fluid Mech. 466, 365 2002. Org 101017S002 112002001490 net. 28K Luo Z J Fan. A 37430, 3046, 2010. Org 101016J201005036. 29C IGH. J Mech. B Fluid 65 213 2017. Org 101016J2017030002 MathNet. 30R SAAS Giamatti Powder Technol. 257 11 2014. Org 101016J2014020045. 31SS S Bale AWK JB. Fluids 31-4, 45108 2019. Org 10106315083917. 32I OMSML. J Heat Fluid Flow 76, 141 2019. Org 101016J2019020004. 33Y SI. Fluids 12-5, 949 1969. Org 10106312163685. 34 BPL Claire AIE HRJ. 27-2, 308 1970. Org 10117515200469197002 70308 ANSOTD 20CO2. 35J C. Fluids 31-6, 61704 2019. Org 10106315109437. 36AG SA J Fluid Mech. 416 45 2000. Org 101017S0022 112000008880 net. 37RH RL Bishop Can. J. 3910 1418 1961. Org 101139P 61 169. 38K JSPJ. Rev. E775 55308 2008. Org 101103 Rev E770 55308. 39M TMJ Fluids. 1534 575 2001. Org 101006 2000 362. 40HHJ Fluids. 112-4 386 1990. Org 10111512909415. 41 ATOMBULIDS SORCAG GKARNIDKIS in 31st Aerospace Sciences Meeting American Institute of Aeronautics and Astronautics Reno NV USA 1993. AIAA Paper 930546. Org 10251461993546. 42D M. Rev. 831 80 1999. Org 101103 Rev 8380. 43YS OS FT Smith J Fluid Mech. 251 273 1993 net. 44E J Fluid Mech. 62-2 209 1974. Org 101017S0022 112074000644. 45 FC Ting Coastal. 5356 441 2006. Org 101016J200 511004. 46J Joe RJ Adrian STM J Fluid Mech. 387 353 1999. Org 101017S0022 112099000467 net. 12. Similarity solutions of a class of unsteady laminar boundary layer. Abstract. The study of laminar unsteady boundary layer flows is essential for understanding the transition from laminar to turbulent flow, as well as the origins of turbulence. However, finding solutions to this phenomenon poses significant challenges. In this study, we introduce a novel method that employs a similarity transformation to convert the two-dimensional unsteady laminar boundary layer equations into a single partial differential equation with variable coefficients. By applying this transformation, we successfully derive similarity solutions for flat plate boundary layer flow expressed in terms of functions. For divergent boundary layer flow, we derive an approximate analytical solution that includes both shock wave and soliton wave solutions. The superposition of these solutions provides evidence for the existence of solitons or soliton-like coherent structures, SCS, within boundary layers. Additionally, this paper explores 2- and 3-dimensional laminar flows, as well as 3-dimensional turbulent flow equations, revealing that they all incorporate third-order derivatives with respect to spatial coordinates. This finding suggests that all viscous fluid motions have the potential to exhibit soliton-like coherent structures, SCS. Keywords. This chapter is reproduced with permission from B.H. Sun. Similarity solutions of a class of unsteady laminar boundary layer. Fluids 37-1, 14111, 2025. Copyright 2025 AIP Publishing. The content of the article has been slightly revised. 12.1 Introduction. It is well known that the state of motion of viscous fluids is determined by their corresponding number, and for a viscous fluid problem with a specific length scale, the flow velocity is the decisive factor affecting the number. Generally speaking, given a length scale and a viscosity coefficient, the higher the velocity, the higher the corresponding number. As the flow velocity gradually changes from low to high, the corresponding flow state will also undergo significant changes. When the number is less than a certain critical value, the flow is in a laminar state. Then, as the flow velocity continues to increase, the flow begins to fluctuate and become unstable, and once the number reaches a certain critical value, the flow enters a turbulent state. Physically, since the flow velocity cannot instantly reach the value that causes the flow to transition to turbulence, but can only gradually accelerate from low to high, any flow must necessarily undergo an unsteady laminar process, or rather, unsteady laminar flow is the precursor to turbulence, and its motion genes will be passed on to the subsequent turbulent state 118. From the perspective of dynamical systems, to study turbulent phenomena, it is necessary to investigate the laminar turbulent transition state before the occurrence of turbulence 1940, as well as the earlier unsteady laminar flow state. Research on unsteady laminar flow is of particular significance from the perspectives of scientific research and engineering applications, especially in the analysis of fluid flow in the boundary layer at the surface of solids. Since the Stokes equations for unsteady boundary layers are nonlinear, there has been no exact solution or similarity solution for their two-dimensional problems since the concept of the boundary layer was proposed in 1905-1. Although numerical methods can be used to solve the two-dimensional unsteady boundary layer, Stokes equations, the numerical results are a combination of various factors and cannot be decomposed into their components from the final numerical solution. This is similar to simple additive operations. For given a B, we can obtain a unique C from a plus BC, but given C, there are infinitely many A and B combinations, creating an ill-posed problem. Clearly, if an exact solution to a problem can be obtained, the components of the solution can be observed from its analytical structure, hence the importance of obtaining exact solutions. Since the formulation of the Stokes equation set in 1821, it has been more than 200 years. Many outstanding mathematicians, physicists, and engineers, including Stokes 1, 2, 19, 4, and others, have tirelessly sought the exact solutions to the Stokes equations. According to an email from 41, an authority on the study of exact solutions to the Stokes equations, there are infinite exact solutions to the NS equation. For example, flow has numerous unsteady plate motions, which yield closed-form solutions. However, new and significant solutions are few, numbering less than 150, increasing about 1 per year. In other words, in the 170 years since the establishment of the Stokes equations, fewer than 150 exact solutions have been obtained, most of which are related to steady laminar flow. There are only a few exact solutions for unsteady laminar flow, which is truly pitiful. Therefore, states that exact solutions to the Stokes equations are very rare and highly values the importance of obtaining exact solutions, 1416. Just after the formulations of the Stokes equations in 1851, Stokes himself studied two one-dimensional unsteady fluid mechanics problems, known as Stokes' first problem, later referred to as the problem and second problem. Various exact solutions obtained thereafter can be found in the review by 1415 and in his recent monograph on essential analytic laminar flow 16. It is particularly noteworthy that among the fewer than 150 exact solutions, those related to the boundary layer are of higher scientific and practical value, such as the solution for the two-dimensional steady laminar boundary layer of a flat plate 19. However, for the two-dimensional unsteady laminar boundary layer, no unsteady type equation has yet been derived, and consequently, no exact solutions have been obtained. Therefore, the finding of exact solution of the two-dimensional unsteady laminar boundary layer is a century-old challenge in fluid mechanics, and achieving of the exact solution would clearly represent a significant advancement in the study of fluid mechanics. Similarity transformation. In order to make it easier for comparison, the symbols from the original text are used here. UU constant. Transformations. Equations. 1951 4. Plus 2. 2 plus 2. Around XUYVX 1951 4. YX. Plus 2. A 2 2. At large time. UUYVUY. 1972 10. Y. Plus 12. 1. UUYVU x. A thin flat plate is immersed at zero incidence in a uniform stream flows with speed ux. Laminar boundary layer is x, which strictly speaking is not the boundary layer thickness, but rather a scaled measure of the boundary layer thickness, which is equal to the boundary layer thickness up to some numerical factor 13. As applications, we will study following three problems of unsteady laminar boundary layer. 1. A semi-infinite flat plate impulsively started with velocity u0. 2. The boundary layer flow in a diverging channel flow between two non-parallel plane. 3. Theoretical discussion on the existence of soliton-like coherent structures, SCS, in viscous flows. In order to facilitate an understanding of the overall picture of this paper, a brief to the main content is as follows, after introduction in sect. 12.1. The rest of this paper is organized as follows. In sect. 12.2. We formulate the two-dimensional turbulent boundary layers and introduce a similarity transformation. Under special conditions, the partial differential equations of the two-dimensional turbulent boundary layers can be reduced to a single partial differential equation with constant coefficients. In sect. 12.3. A semi-infinite flat plate impulsively started with velocity is studied, whose exact solution is obtained in terms of the functions. In sect. 12.4. Soliton-like wave solution of the boundary layer flow in a converging channel flow between two non-parallel planes are obtained. In sect. 12.5. The universality of soliton-like coherent structures, SCS, in viscous fluid is discussed. Finally, in sect. 12.6. Perspectives and conclusions are drawn. 12.2. Similarity transformations of two-dimensional laminar boundary layers equations. A thin flat plate is immersed at zero incidence in a uniform stream as shown in Fig. 12.1, which flows with speed ux and is assumed not to be affected by the presence of the plate except in the boundary layer. The fluid with the kinematic viscosity and the flow density is supposed unlimited in extent, and the origin of coordinates is taken at the leading edge, with x measured downstream along the plate and y perpendicular to it. In the analysis of differential equations, it is often useful to examine some special solutions, which allow us to make conclusions about the main properties of the phenomena in question. Such solutions can sometimes be found by dimensional analysis, which can reduce the number of independent variables adopted to characterize the question. Thereby, in some situations, the number of independent variables can be reduced, and partial differential equations can even be replaced by ordinary differential equations. The simplest case allowing for the construction of special solutions is that of a problem with the so-called property of self-similarity 1416. We can assume that the velocity profiles at different distances from the leading edge are affine or similarity to one another, i.e., that the velocity profile u at different distances can be mapped onto each other by suitable choice of scaling factors for u and y. A suitable scaling factor for u could be the free stream velocity ux, while for y, boundary layer thickness x, which increases with distance x, could be used. The similarity law of the velocity profile can thus be written as xuf with yx. Regarding the similarity of time t, it is known that the time for any bulk property of the fluid, such as vorticity or momentum, to diffuse through a distance, is of the order of 2/ the diffusion time proposed by Stewart 7, hence we can introduce a dimensionless time as t2. Dimensions of parameters. Parameters. Dimensions. YLTTX. L to T1. Since two basic dimensions LT are used if we choose Tx as repeating variables, hence two dimensionless parameters can be produced according to the theorem 42-43 as follows: 101b0y and 2c2d12. It can be clearly seen that 12.19 does not explicitly contain the coordinate x, indicating that we have successfully transformed the original partial differential equation, 12.7, with three independent variables x, y, t, into a partial differential equation with two similar variables. This not only facilitates solving the equation, but also allows us to express the obtained results as a single profile in terms of the similar variable. The solution with a single profile at a certain moment t is called as the exact solution based on arguments 1416. According to 1416, the Stokes-NS equation, basically nonlinear partial differential equations, has few analytic exact solutions. Aside from boundary conditions, the N-S equation has two fluid descriptors. Although the constant density can be absorbed into the pressure, the kinematic viscosity, the number in non-dimensional form, is a pertinent parameter. By an exact solution, we mean an analytic solution to the N-S equation, where the viscosity is arbitrary, is exact for all space and time. Evidently, all closed-form solutions are exact solutions. Numerical solutions and series solutions are not exact. Similarity solutions, where the partial differential equations transform to an ordinary differential equation and resulting in a universal curve with implicit viscosity, are exact solutions. The degenerate potential flow solutions, although satisfying the N-S equation, are excluded 1416. Although Four has also obtained transformed equations by introducing his similarity variables, he failed to obtain exact solutions due to inappropriate similarity transformations. In other words, an inappropriate similarity transformation does not necessarily result in a well-structured transformed equation. Therefore, the similarity transformations we introduced in 12.8-1210 are of essential importance for solving the flat boundary layer problem. 12.3, a semi-infinite flat plate impulsively started with velocity u0. The original Stokes' first problem is one-dimensional problem 1. As an application of our formulation in sect 12.2, let us consider its two-dimensional version. A semi-infinitely flat plate is immersed in a viscous and stationary fluid. At t0, the plate suddenly accelerates in its own plane to a velocity u0. At the moment of initiation, the fluid surrounding the plate remains stationary due to viscosity. As time passes, the fluid near the plate gradually starts to move layer by layer due to the effect of viscosity. Clearly, this is an unsteady two-dimensional flow. This problem was first proposed by Stokes in 1851, known as Stokes' first problem 1. For any value of when we always have f 3323c3c2. If applying the conditions in both 12.32 and 12.35 to f, we will obtain completely contradictory results. It means that these two conditions in 12.32 and 12.35 cannot be satisfied simultaneously. The concept of approaching infinity in 12.32 only holds mathematical significance and cannot be practically calculated in real-life calculations because it is already outside the boundary layer when y1. A semi-infinite flat plate impulsively started with velocity u0, f, and f. Using our equation and the exact solution, we can provide a clear explanation for this problem of how the solution can be transformed into the solution, which was proposed 70 years ago by Four. Our interpretation for this problem is that the transformation from the solution to the solution does not require passing through a singularity. It has been proven that 1-2 noted, 1 in notation 4 is not a singularity point. 12.4 The boundary layer flow in a diverging channel flow between two non-parallel planes. In case of boundary layer flow in a diverging channel flow between two non-parallel planes, which has been studied by 45, whose solution can also be found in page 162 in Fluid Mechanics by Landau and 46, the parameters 0, 1, 2 and m1, we have the divergent channel flow velocity function uxq, which simply expresses the of the discharge q0 in the flow, being the angle between the planes. Now we have the boundary layer thickness xxq12, similarity variable yyxq12, dimensionless diffusion time qt2, and the number is rexq is a constant. Region of unsteady laminar boundary layers past a flat plate, solution 2 and solution 19. The problem's initial boundary conditions, u000, v000, u0 v00, uu and v0. Taking into account the first-order approximation, we have the approximated initial boundary conditions as follows: f0000, f01, f000, and f000. Especially noteworthy is that within the approximate analytical solutions of the laminar boundary layer of a diverging flow, the components of the solitary wave solution and the shock wave solution are distinctly observable. This is an exciting discovery. It fully demonstrates that the approximate full solution to the problem consists of two parts, the solitary wave solution and the shock wave solution, which are superimposed. Alternatively, the shock wave has reshaped the solitary wave, causing its waveform to be slightly deformed and not entirely standard. That is to say, the full solution is a kind of wave similar to a solitary wave. We can also interpret this from the perspective of kinetic energy U2 plus V22, where the total kinetic energy includes the term 2, which represents the kinetic energy coupled by the solitary wave and the shock wave. This coupling is equivalent to an exchange of kinetic energy between the solitary wave and the shock wave, in order to maintain the flow as a motion resembling a solitary wave. Interpreting the solution to a problem in this way is actually sufficient for understanding, but the deformed solitary wave observed here might be related to a more important fluid motion structure, which is called as the Soliton-like coherent structures, SCS, that is discovered by Lee 3336. 12.5 Universality of Soliton-like coherent structure, SCS, in viscous fluid. The Soliton-like coherent structures, SCS, in different types of transitional boundary layers and turbulent boundary layers was experimentally discovered by Lee 3336. Furthermore, they have employed the tracking method to invert the Soliton-like coherent structures, SCS, revealing that the fundamental structure of near-wall flow is a solitary-like wave, and concluded that boundary layer flows all possess a common structure, namely soliton-like coherent structure, SCS, which has some typical characteristics as a soliton, such as traveling downstream at a finite speed with a strong localized pattern and decreases in the later stage of boundary layer transition. In particular, the SCS has the longest living time compared with other coherent structures in wall-bounded flow 3336. For the discovery of the existence of soliton-like coherent structures, SCS, in boundary layer flows, we believe that for such scientific discoveries, not only numerical explanations are needed but theoretical interpretations as well. To do so, it is important to investigate whether there exist solitary wave solutions in the Stokes equations, or in the unsteady boundary layer equations derived from the simplification of the Stokes equations using boundary layer concept. Ideally, it would be best to find an analytical solution for the unsteady boundary layer equations that clearly includes solitary wave solutions. Unfortunately, it was not until this article that the similarity solution was found. Although we have not obtained the general solution of the Stokes equations, we have only the solution of the boundary layer equation under a certain class of flow conditions. Since one of the goals of scientific research is to pursue the discovery of generally applicable laws, we have reason to raise such a question. Does the deformed solitary wave solution here reveal that the boundary layer flow has a certain universal structure? From a philosophical metaphysical perspective, the universality of laws refers to the commonality of laws, while the particularity of laws refers to the individuality of laws. The commonality of laws is unconditional and absolute, whereas the individuality of laws is conditional and relative. Any real existing thing is an organic unity of commonality and individuality. Commonality resides in individuality, and there is no commonality without individuality, nor individuality without commonality. The principle that the commonality and individuality of laws, as well as absoluteness and relativity, is the essence of the issue of the laws of things and the key to correctly understanding the doctrine of laws. The relationship of the unity of the commonality and individuality of laws is both the inherent dialectic of objective things and the scientific method of cognition. The general law of human cognition is the dialectical development process from understanding the individual to understanding the general, and then from the general to the individual. Therefore, we have reason to firmly believe that behind the deformed solitary wave solution lies the revelation that boundary layer flows possess a certain universal structure. This has also been confirmed by Lee's discovery, which found that all boundary layer flows share a common structure, namely the soliton-like coherent structures SCS. Since universality encompasses particularity, and particularity contains universality, this reminds us that we can obtain some universal information by studying just one problem. This means that we only need to study one or a few specific cases, as universal laws exist within these special problems. By obtaining a similarity solution for any two-dimensional unsteady boundary layer equations, we can analyze whether it contains soliton-like wave solutions. In Sect 12.4, we demonstrated the existence of soliton-like waves through specific examples. However, the question remains whether soliton-like waves are universally present in various types of flows. Analyzing specific problems individually is clearly not a viable approach, and therefore it is necessary to explore this question theoretically in order to gain a rational understanding and obtain general conclusions. To answer this question, let us first examine the phenomenon of water waves. Have observed the phenomenon of solitary waves and established the equation ut plus 6x for water waves with a free boundary. They obtain the exact solution uxt 222c1 plus c2x plus c3t 823 plus c36c2. However, the Stokes equations does not include third-order derivatives with respect to spatial coordinates, such as u. Even in the 1D nonlinear Burger's equation ut plus x, the solution uxt 2 to c1 plus c2x plus c3t c3c2 is not a solitary wave solution but a shock wave solution, where c1, c2, and c3 are integral constants. The third-order derivative respect to spatial coordinate is the source of soliton wave solution. Overall, the presence of a third-order derivative term is a key factor that allows for the existence of soliton-like solutions, but other factors such as nonlinearity and specific equation properties also contribute to the formation and behavior of solitary waves. In the same way, we can confirm that the general two-dimensional, three-dimensional flows and turbulent flows have soliton-like solutions. It is particularly worth noting that the conclusions drawn here are obtained without any modeling of the stress tensor, V, meaning that the soliton-like coherent structures, SCS, is independent of the turbulence prediction model used. This also illustrates from another aspect that the soliton-like coherent structures, SCS, is an intrinsic structure of the viscous flow, unrelated to the choice of turbulence computation model. 12.6 Perspectives and Conclusions. Although the Stokes equations are nonlinear under specific conditions, i.e., due to geometric symmetries, the flow uniformity can be reduced to a mathematical similarity solution of physical equations. For other cases, there is generally no similarity solution, which brings great difficulties to engineering applications. The school of applied mechanics represented by and developed the perturbation theory and obtained numerous asymptotic solutions. In 1904, his theory of the flat plate boundary layer divided the Stokes equations into two regions for solution. In the outer region, there is uniform flow, and in the inner region, the horizontal derivatives of the viscous terms in the Stokes equations can be neglected. This leads to the equation for two-dimensional steady boundary layer similarity solutions. However, the similarity solution of the two-dimensional unsteady laminar boundary layer problem has not been solved for more than a century until this study. For a wide range of flow conditions, this paper has obtained similarity solutions. Considering that several renowned scholars have attempted to solve this problem but were unsuccessful, one can comprehend the value and significance of our work here. The success of this study is due to the consideration that there is no characteristic scale in the x direction and no ready-made characteristic scale in the y direction. Therefore, we have resorted to using the undetermined boundary layer thickness x, which is a function of the x-coordinate, as the characteristic scale in the y direction. With the undetermined boundary layer thickness x, and considering dimensional factors, a characteristic time 2 can be derived. This characteristic time can be understood as the time required for vorticity generated at the wall to diffuse to the upper layer of the boundary layer, that is, the characteristic diffusion time. As a result, the three independent variables are reduced to 2 by introducing a reasonable transformation, x, y, t, y2. In particular, the time transformation uses the characteristic diffusion time 2. From the perspective of Lie groups 43, the transformation uxxf, yx, and 2 can be regarded as a stretching transformation using ux and x. Although obtaining a similarity solution and solving a centennial problem is an important advancement, it pales in comparison to the work that theoretically interprets the existence of soliton-like waves in viscous fluid motion. It is particularly gratifying to be able to provide a theoretical explanation for Lie's important discovery 3336, although other theoretical interpretations from different angles cannot be ruled out. In summary, this paper has solved a class of similarity solution problems for unsteady laminar boundary layer and theoretically demonstrated Lie's scientific finding that any viscous fluid motion possesses soliton-like coherent structures, SCS 3336. This study contributes to our understanding of the transition from laminar to turbulent flow, as well as the laminar genes underlying the occurrence of turbulence. My understanding of soliton-like coherent structures, SCS, can be traced back to 2010 when I was a professor at Cape Peninsula University of Technology in South Africa. During my academic sabbatical leave to visit Peking University, I had extensive interactions with Professors Shi and Lie. In particular, my discussions with Professor C.B. Lie helped me understand the concept of the SCS that he discovered. Since then, I have been hoping to obtain a theoretical explanation for the SCS and have tried various methods without making any progress. This problem has been haunting me and occupying my thoughts for over a decade. Starting from 2022, I realized that I needed to change my strategy and directly search for solitary waves and SCS from the Stokes equation. On the morning of July 5, 2023, I visited Prof. Lie at his office in Peking University, where he showed me again his experimental videos and further deepened my understanding of the SCS. He also mentioned that academician of Chinese Academy of Sciences speculated that the NS equation should contain solitary wave solutions. I was excited because this aligned with my own thoughts, and I believed that solitary waves or SCS should indeed be sought from the NS equation. Considering that SCS is a fundamental structure in fluid motion, it exists in different fluid states and is likely present in laminar boundary layers as well. After contemplating over the summer, I decided to start by investigating the simplest case of two-dimensional laminar unsteady boundary layer flow to see if there are solitary wave solutions. Unfortunately, the governing equations for time-dependent two-dimensional laminar boundary layers are a set of nonlinear partial differential equations that can generally only be solved numerically. Finding exact solutions is exceptionally challenging, and according to current literature, no exact solution has been obtained for time-dependent two-dimensional laminar boundary layer flow. Luckily, perseverance pays off. After days of tireless formulating and countless sleepless nights, I finally discovered a timescale similarity transformation on September 8, 2023, and achieved a significant breakthrough when I was in Liaoning Hotel, Beijing. Following this advancement, I engaged in discussions with several esteemed scholars. I wish to extend my heartfelt gratitude to Academician of the Chinese Academy of Sciences for his enlightening conversations on the derivative of with respect to coordinate in 12.11. I am also thankful to Professor CY for providing valuable information, positive feedback, and encouraging support 41. Additionally, I appreciate Professor Li for elucidating his discovery of the soliton-like coherent structures, as well as Professor for verifying my solutions using MATHEMATICA. Lastly, I would like to express profound thanks to all anonymous reviewers for their high-caliber academic feedback, which has significantly contributed to improving the quality of this paper. Competing interests: the authors have no conflicts of interest to declare that are relevant to the content of this chapter. Data availability: the data that support the findings of this study are available from the corresponding author upon reasonable request. Open access: this chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. Appendix 1. Functions. The function, also known as the confluent function or the degenerate Bessel function, is a special function in mathematics. It is named after the German mathematician Ernst, who studied this function in the 19th century. The function is a solution to the confluent equation and is usually denoted as u of bx or m of bx, wherein b are real parameters and is the variable. The function has wide applications in physics and engineering, particularly in solving differential equations involving exponential growth. It can be expressed through the confluent series or related to other special functions through transformations, such as Bessel functions, gamma function, and error function. The function has various forms and representations, including 1. Confluent functions, m of bx and u of bx, where u of bx is an alternative form of m of bx used when b is not an integer. 2. Modified Bessel functions. When a is a half-integer, the function can be expressed as a modified Bessel function. 3. Error function. The function is related to the error function and the complementary error function, especially at certain parameter values. The function can be calculated using mathematical software libraries or computational tools for special functions, such as Maple, MATLAB, and the library in Python. The function of the first kind is denoted by m of bz, is implemented in the Maple language as m of bz, and the function of the second kind is denoted by u of bz, is implemented in the Maple language as u of bz. Appendix 2, the functions g11, g12, g13, and h11, h12, h13. Appendix 3, the functions g21 and h21. References: 1 G. G. Stokes, trans. Cambridge, Zoj. 9/8/1985 ads. 2L. Mag. 21/126, 697/1911. 3 VM SW Shan. Mag. 12/7/865/1931. 4K QJ Mech. Maths. 4/182/1951. 5K Adv. Mech. 6/1/1960. Org 101016S00652156087010991. 6HA J Fluid Mech. 92 300 1960 net. 7 JT Stewart, Laminar Boundary Layers Press, Oxford 1963. 8K J Fluid Mech. 33-4, 657 1968. 9 MG Hull Proc. R. Soch. A 310 401 1969. 10 SCR J. Maths. 10-1 105 1972. 11K QJ Mech. Maths. 26-2 143 1973. 12N Riley Siam Rev. 17-4 1975. 13L Laminar Boundary Layers Dover Publications, New York 1988. 14 CY Mech. Rev. 4211 269 1989. 15 CY Rev. Fluid Mech. 23 159 1991. 16 CY Essential Analytic Laminar Flow Springer CAM 2024. 17 PKH Ma WH Hui J Fluid Mech. 216 537 1990 net. 18H Boundary Layer Theory 9th. Springer Berlin Heidelberg 2017. 19H Z Math. 56 1 1908. 20A Rev. Fluid Mech. 8 311 1976. 21 BJ SAT. Rev. Fluid Mech. 20 359 1988. 22 IA CG Miller. Rev. Fluid Mech. 22 419 1990. 23 YS. Rev. Fluid Mech. 26 411 1994. 24 HL RID WSD. Rev. Fluid Mech. 28 389 1996. 25 T. Rev. Fluid Mech. 29 245 1997 net. 26 WS HL Reed EB White. Rev. Fluid Mech. 35 413 2003. 27 P X Wu. Rev. Fluid Mech. 39 107 2007. 28 B TM BJ. Rev. Fluid Mech. 39 447 2007. 29 A. Rev. Fluid Mech. 43 79 2011. 30XX. Rev. Fluid Mech. 44 527 2012. 31J J Fluid Mech. 842 513 2018. 32X Wu. Rev. Fluid Mech. 51 451 2019. 33 CB Lai JZ Wu. Mech. Rev. 61-3 30802 2008. 34 CB Lai XY. Fluids 30 111 111,301 2019. Org 10106315121810. 35 CB Lai. Rev. E62-3 3659 2000. 36XY CB Lai X CR Smith PF Linden J Fluid Mech. 890 A11 2020. 37 BH Sun. Maths. Mech. 42 193 2019. 38 BH Sun Open. 19-1 853 2021. 39 BH Sun. Mech. 12-3 100,338 2022. 40 BH Sun Acta. Mech. Sen. 39,322,066, 2023. 41 CY, Private Email Communication 8 December, 2023. 42 A. Rev. 44, 345, 1914. 43 BH Sun, Dimensional Analysis and Lie Group, China High Education Press, Beijing, 2016. 44. Com-C for information about solutions of partial differential equations. Accessed 2024. 45K Z Math. Mech 1 252, 1921. 46 LD Landau, EM, Fluid Mechanics 2nd. 1976. 47 SB Pope, Turbulent Flows, Cambridge University Press, Cambridge 2000. 48 M.I. Handbook of Mathematical Functions, Dover, New York, 1972. 13. Existence and characteristics of soliton-like coherent structures in a transitional mixing layer. Abstract. Laminar to turbulent transition in shear flow can be complicated and may follow many possible routes. The scenario based on the soliton-like coherent structure, SCS, Li and Wu, transition in wall-bounded flows. Mech. Rev. 61 30802, 2008, has drawn much attention to the role of hairpin vortices and their origin. This letter reports the existence of such SCSs in a compressible mixing layer and explores how their interactions with the background shear flow generate the vorticity. Particle tracking based on direct numerical simulation data is employed to trace the dynamic evolution of such structures. Evidence shows that localized three-dimensional waves travel coherently during the early transition stage, in good consistence with the behavior of SCSs in boundary layer transition. Through visualization of disturbance amplification and statistical analysis of locally distributed high-strain rate regions, it is suggested that SCSs originate from local oblique resonance effects in mixing layers, with the motion of these structures along the mean shear flow contributing to the generation of hairpin vortices. This chapter is reproduced with permission from JL and ZL, Existence and Characteristics of Soliton-like Coherent Structures in a Transitional Mixing Layer. Fluids 37-7, 71704, 2025. Copyright 2025 AIP Publishing. The content of the article has been slightly revised. As one of the most fundamental shear flows, the mixing layer is widely encountered in both natural and engineering contexts 1-3. Numerical investigations of mixing layers are typically conducted using either temporally 4-6 or spatially 7-9 developing models, with the latter more closely representing the physical evolution of realistic flows. Previous studies primarily focus on linear stability characteristics, coherent structures, and Mach number effects 8, 10, 11. However, the origin of three-dimensional, 3D structures in spatially developing mixing layers at moderate Mach numbers remains unclear. This chapter is intended to address this issue. As for the origin of flow structures and the onset of turbulence, it is widely accepted that the transition in a mixing layer begins with the Kelvin, kH instability, or equivalently, kH waves in terms of structure. In the presence of 3D perturbations, these two-dimensional 2D waves undergo secondary instability and evolve into quasi-vortices. These secondary vortices are commonly observed as ribs between neighboring K-H rollers. For instance, 12 clearly visualizes the periodic streaks, with their spacing increasing downstream in proportion to the growth of mixing layer thickness. The theoretical interpretation of vortices is proposed by and 1314, who derive the anti-rotating vortices through the weak nonlinear interaction between a 2D wave and a pair of oblique 3D waves. The advancement of both numerical simulation techniques and computer-aided visualizations enable the high-resolution characterization of flow structures previously identified in experiments. For example, and Rogers 15, investigate the pairing mechanism of K-H vortices and the relation to origin of 3D structures. The spatial evolution of mixing layers has also been the focus of several studies 7, 8, 16. However, the understanding of causal mechanisms governing structural evolution remains limited. The redistribution of vorticity is believed to be the unstable response of the shear layer to 3D perturbations in the upstream conditions 17. However, the quantitative representation of vorticity concentration remains to be clarified. The structure termed Soliton-like coherent structure, SCS, in boundary layer transition has the potential to build such a bridge 18. The SCSs are found to trigger the formation of a high shear layer through interaction with the mean shear and give birth to hairpin vortex structures. These wave-like structures can be traced back to the experiments from Hama al. 19, who observe a special kink structure before the formation of hairpin vortex and suggested that the kink structure should be the origin of hairpin vortices. Al. 20 validate the existence of this kind of 3D wave structures and their contribution to the formation of vortex structures by using particle tracking techniques based on velocity fields obtained from high-resolution PIV measurement. In this sense, the 3D wave with soliton properties could have a more basic status in transitional and turbulent shear flows. Both the free shear layer and boundary layer have a basic configuration of plane shear flow, although their stability characteristics differ from each other. Recent studies 21-22 suggest that the SCS in free shear flows, such as wake flows, should be closely related to hairpin vortex structures and arise from the singularity of Stokes equations. The wave structures and the mechanism of their interaction with the mean shear motivate the present study. We seek to determine whether the wave-induced vortex mechanism also applies to a mixing layer. To this end, direct numerical simulation, DNS, is conducted for a compressible mixing layer with the focus placed on the early transition stage. The rest of this chapter is organized as follows. First, the basic setup of the DNSs for a spatially developing compressible mixing layer is introduced, along with the material element tracking framework, which is based on spatiotemporal flow field data. Special attention is given to the setup of two types of inlet disturbances, i.e., waves and artificial turbulence. Next, the evolution characteristics of coherent structures in the mixing layer driven by these two types of disturbances are discussed. The mixing layer driven by random disturbances provides general characteristics of the structure distribution, aiding in the objective identification of wave structures. The flow field driven by wave disturbances is then analyzed to further investigate the interaction between waves and mean shear, and its role in the formation of vortices. Finally, the results are compared with previous findings in boundary layers and density stratified flows, with the goal of exploring a universal mechanism through which waves induce vortices in shear flows. It should be mentioned that this chapter mainly focuses on the origin of 3D structures under moderate convective Mach number conditions, where such modes are known to become significant for, while high Mach number effects are left for further investigation. Numerical settings for the two simulation cases. The variables to be perturbed are abbreviated as denotes the velocity of the low-speed layer. U2 random 0.75 UV W13 200 200 40 1200 200 100 oblique 0.7 V12 579 400 35 4000 350 256. Validation of a mean velocity profile U for fully developed turbulent region. The coordinate is scaled by momentum thickness, and B growth rates of the unstable modes 0, 0 for the oblique case. The results from numerical simulation by Joe al. 8 and linear stability theory, LSD, are included in panels and B, respectively, for comparison. Spatial distributions of the perturbation waves and vortices in the mixing layer disturbed by inlet artificial turbulence. Evolutions of a timelines and B, a material surface in the mixing layer disturbed by artificial turbulence. Starting from the general results for random disturbances, the evolution of perturbations is investigated. Spatial distributions of the wave and vortex structures in the mixing layer with random disturbances at the inlet are shown in Fig. 13.2. The height of isosurface green is conditioned on the positive normal velocity, v0, at the plane of y015, visualizing the upward motion of the fluid 3D waves. Vortical structures are detected using isosurfaces, yellow, of the second invariant of velocity gradient tensor, Q8-10-3. At the inlet of the mixing layer, the distribution of vortex structures shows an indistinct pattern. Downstream, the vortex pattern gradually emerges, with the spatial arrangement of vortices resembling an N-type boundary layer transition. Further downstream, the vortices are stretched and elongated, forming hairpin vortices, which then undergo further instability and breakdown mixing transition. Figure 13.3 displays evolution of the timelines released at the inlet. The timelines are released initially at x20, y0 with 790 particles in direction, and colored by normal coordinate y. The timelines material lines, released at a fixed frequency, 105, follow the deformation of local flow structures, showing the dynamic evolution of the vortex structures described earlier. Particularly, the deformation of material lines can mimic the deformation of vortex lines under incompressible approximation. The distribution of material lines aligns with the distribution of vortex structures in the instantaneous field, with the key difference being that the timeline distribution exhibits a time accumulation effect. In other words, the upstream material lines represent the early forms of the downstream material lines. Spatial distribution of the perturbation waves and vortices. Timelines released simultaneously at the same normal position, y0025, but at different locations, x020, b x070, c x0120, and d x0170. To study the evolution of waves and their relation to the formation of vortex structure, controlled disturbances are further imposed, specifically by introducing waves at the inlet and tracking the growth of these waves. Distributions of waves and vortices in the instantaneous field of the mixing layer under oblique wave disturbances are depicted in Fig. 13.4. The wave structures are visualized by isosurfaces, blue, of the conditioned normal velocity at the plane of 0.25, which is located approximately at the mixing layer center. The vortex structures are represented by isosurfaces, red, of the second invariant of velocity gradient tensor, i.e. Q5-10-4. Visualization of the instantaneous flow field provides an intuitive picture of the coexisting state of coherent structures and the relative spatial relation between the vortices and waves. Evolution of a material surface disturbed by inlet oblique waves. A TT001, B TT051, C TT0101, and D TT01501. For any instance, T0 is the moment when the material surface is initially released. The visualization of a material surface evolution may help reveal how a wave structure triggers the formation of a vortical structure, as shown in Fig. 13.6. The material surface, colored by normal coordinate y, is composed of 400 particles initiated at y0017 x02 050z0530. Vortical structures at the same moment detected by Q criteria, Q5-10-4, are also locally presented to reveal their connection to the wave structures. The color maps represent the velocity. At the first moment, the material surface undergoes slight normal deformation, exhibiting the 3D waveform. Timelines serve merely as an indication, with amplitude increasing in both directions, consistent with the rising, ejection, and falling sweep events. At the second and third moments, the 3D bulge splits into peaks and troughs, indicating strong crossflow caused by vortex motion. At the fourth moment, the material surface becomes indistinguishable from the vortex structure. Based on the observations in Figs. 13.4, 13.5, and 13.6, it is evident that the 2D H-wave structures are not obvious in present simulations. To examine the effect of inlet perturbation amplitude, we have also considered cases with infinitesimally small disturbances. The results of these test cases, which are not shown here for brevity, indicate that the 2D KH modes grow prominently in the upstream region, making the linear growth stage clearly visible. However, the development of 3D modes requires a much longer domain. Therefore, in this chapter, finite amplitude 3D disturbances are used to directly probe the wave-vortex interaction mechanism, which characterizes the nonlinear transition stage. The material surface at T028.1, which is initiated at Y0017X02050Z0530, and colored by different components of the strain rate tensor, a S12, B, S13, C, S23, and the vortex stretching term ds. Scatter plots of the normal displacement, y of material surface versus different components of the strain rate tensor, a S12 and B, S13. We further correlate the normal displacement of particles and different components of the strain rate tensor in specific regions of the material surface shown in Fig. 13.7, and typical results are displayed as a scatter plot in Fig. 13.8. Each point in the scatter plot corresponds to a point on the material surface. Points of the same color in the scatter plot represent particles traversing along the material surface in the direction, and strong correlations can be observed between the normal displacement of particles and the local strain rate components within certain regions of the material surface. For the scatter plot shown in Fig. 13.8, particles are sampled in the range X4015572. Along line I, the corresponding region is characterized by a peak at the center and valleys on both sides. The maximum value of S12 appears at the position of maximum Y, while the minimum value of S12 appears at the position of minimum Y along line II. The corresponding region consists of valleys opposite peaks on both sides. The maximum value of S12 appears at the position of minimum Y, while the minimum value of S12 appears at the position of maximum Y, which coincides with the minimum Y of line I. The region between lines I and II is a transitional area. Line III also represents a transitional region, where the variation in Y is minimal, but S12 varies significantly. The correlation distribution in Fig. 13.8b samples particles in the range X4015450. The correlation shows strong self-similarity with a consistent cyclic pattern. Along lines A and B, as Y increases in both the positive and negative directions, the absolute value of S13 also increases accordingly, which corresponds to the distribution of S13 on both sides of the wave packet in Fig. 13.7. The localized 3D wave packet exhibits along. Lee 25 gives the definition of SCS based on experimental observations of boundary layer transition. The mechanism discussed in this chapter suggests that such structures also emerge during the early stages of mixing layer transition. The high shear mentioned by Lei and Wu 18 is interpreted here as the local concentration of strain rate fields. It is important to note that, while the mechanism by which waves induce vortices is similar, there are key differences between a boundary layer and a mixing layer. In a mixing layer, the absence of wall constraints allows wave packets to grow in two directions perpendicular to the central layer. This mechanism closely resembles the relation between internal waves and vortex structures in density stratified flows. In addition, the characteristics of wave packet deformation phase are similar to the bending wavefronts observed by Al. 26 in boundary layers. Moreover, a combination of two boundary layer streams from both sides of a splitter plate creates a more natural mixing profile 9, which may influence the dynamics of SCS. The preservation of SCS amplitude in mixing layers is primarily due to nonlinear saturation, though its isolation gradually decays as 3D waves split due to shear effects. The singularity of Stokes equations 22 may help explain these behaviors, and this mechanism could also serve to account for the sustenance of fully developed turbulence 27. In summary, this chapter presents a numerical study on the spatial development of coherent structures in a compressible mixing layer driven by two different types of inlet disturbances. By integrating multiple flow visualization techniques, we identify a common mechanism through which 3D disturbance waves evolve into vortices. Specifically, oblique wave resonance induces local fluid uplift and descent, which manifests as localized wave packets. The normal motion of these wave structures leads to the redistribution of local flow and strain rate fields, resulting in the deformation of wave packet within the background shear. Vorticity develops within the strong strain rate layer surrounding the wave packet, manifesting as the stretching of vortex filaments, or tubes, into vortices. These vortices are then further stretched and twisted into hairpin vortices. This mechanism underscores the pivotal role of wave structures in vortex formation, suggesting that, in a causal sense, wave structures are more fundamental than vortex structures in the development of a mixing layer. The authors would like to thank Dr. for contributing part of the simulation work and are grateful to Professor Lei and Dr. for many useful discussions. Numerical simulations were carried out on the Polaris computing platform of Peking University in Beijing. Competing interests. The authors acknowledge the financial supports provided by National Natural Science Foundation of China grants No. 92,152,202 and 12,588,201. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Data availability. The data that support the findings of this study are available from the corresponding author upon reasonable request. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 PA Rev. Fluid Mech 37 329 2005 net. 2A Rev. Fluid Mech 51 245 2019. Org 101146 Fluid 0105180403006 net. 3 RV Moore AGM Rev. Fluid Mech 55 157 2023. Org 101146 Fluid 1207200111132. 4 NDWC J Fluid Mech 224 133 1991. 5 AWND K Luo J Fluid Mech 320 235 1996. 6 JB SKP J Fluid Mech 421 229 2000 net. 7 CS in 39th Aerospace Sciences Meeting and Exhibit, American Institute of Aeronautics and Astronautics, Reno, NV, USA 2001. 8 Qzhou FE MY Shen J Fluid Mech 711 437 2012 net. 9 DR Le JZ AF Fluid Dyne 336 577 2019. Org 101007 S00 1620 1900 507 MathNet. 10 CE TL Jackson J Fluid Mech 231 35 1991. Org 101017 S00 22 112091003300 net. 11 Delay AZJF J Fluid Mech 910 A9 2021. 12 JH An experimental investigation of mixing in two-dimensional turbulent shear flows with applications to diffusion-limited chemical reactions. Tech Rep NASA SDI Recon Tech Rep N77 National Aeronautics and Space Administration 1976. 13 DJ J Fluid Mech 1002, 209, 1961 net. 14 DJ LH stud. Maths. 64-3, 185, 1981 net. 15 RD MM Rogers J Fluid Mech. 247, 275, 1993. 16 YMT. J Heat Fluid. 28-6, 1280, 2007. 17 JC JST J Fluid Mech. 172-1, 231, 1986. 18 CB Lai JZ Wu. Mech. Rev. 61-3, 30,802, 2008. 19 FR Hama JD Long JCJ. 28-4, 388, 1957. 20 XY CB Lay X CR Smith PF Linden J Fluid Mech. 890 A11 2020. 21 L HS CQ Joe WQ Fluids 36-3, 34,127 2024. Org 10106350199349. 22 L HS CQ Joe WQ Fluids 37-1, 14,111 2025. Org 10106350251193. 23 R ZL AIP ADV. 11-7 2021. Org 10106350054619. 24 M AJJ. 186-2, 652 2003. 25 CB Lay. A 247-6, 397 1998. 26 XY DW CB Lay CR Smith PF Linden J Fluid Mech. 914 A4 2021. 27 HS Origin of Turbulence Energy Gradient Theory Springer Singapore 2022. Org 1010-7978-980-1900-877. 14. Detection and analysis of soliton-like coherent structures in free-round jet flow. Abstract. Flow structures on free jet flow are investigated by means of direct numerical simulation, DNS, method. The flow structures within the jet are investigated by tracking material lines and material surfaces using the tracer method. The timeline tracking results revealed the presence of high and low speed regions within the jet. Further studies utilizing material surface tracking reveal localized kinks, bulges, and depression structures resembling the soliton-like coherent structure, SCS, within both high and low speed regions. The evolution of these three-dimensional, 3D wave structures follow patterns similar to those of SCSs in flat plate boundary layers. This finding provides evidence that SCSs are dominant flow structures for the turbulent generation in shear flows. This chapter is reproduced under CC BY from ZY, YT Yang and QD, Detection and Analysis of Soliton-like Coherent Structures in Free-Round Jet Flow. Fluids 37-8, 85,174, 2025. Copyright 2025 AIP Publishing. The content of the article has been slightly revised. 14.1 Introduction. Free jets as a common phenomenon in fluid dynamics are widely observed in both natural environments and industrial applications. Examples include atmospheric air jets, water discharge in hydraulic engineering, and engine exhaust plumes in the aerospace field. As a classical subject in fluid mechanics, free jets have long attracted extensive attention from scholars in the field of fluid mechanics. Since the 1960s, an increasing number of researchers have investigated jet flows aiming to achieve comprehensive and accurate characterization of circular jet flow fields. In 1963, Davies al. 1 employed a single hot wire anemometer to study the near field of circular free air jets, with Mach numbers ranging from 0.2 to 0.5. Their turbulence measurements revealed clear similarity relationships within the first 6 to 8 diameters of the jet flow. Sami al. 2. Conducted experimental investigations for the near-field jet using static probes and hot-wire anemometry. Their study observed similarity in root mean square pressure and shear stress profiles in the near-field region. The work of and 3 represents one of the most influential studies on circular jets, providing detailed measurements of mean velocity profiles, second and third-order single-point correlations, energy budgets, and length scales. However, subsequent research by SAFE-4 identified significant momentum deficits in the data of end. Regarding the universal self-similarity hypothesis for jets, researchers have expressed diverse opinions. The concept of self-similarity has long served as a cornerstone in the theoretical analysis of turbulent free shear flows. In his seminal work Turbulence 5, formalized the universal self-similarity hypothesis, proposing that fully developed turbulent shear flows exhibit statistical properties that collapse into universal scaling laws when appropriately normalized. Specifically, in the far-field region, where the flow is independent of initial conditions, the mean velocity profiles and higher-order turbulence statistics attain a self-preserving form governed solely by global conserved quantities rather than nozzle-specific details. While Richards and Pitt 6 supported the universal self-similarity assumption, George's 7, 8 theoretical analysis suggested that turbulent jets could asymptotically reach various self-similar states depending on their initial conditions. Meanwhile, Dowling and 9 discovered that the far-field decay rate of mean concentration fields and the radial distribution of root mean square concentration fluctuations depended on the number. al. 10 examined flow fields from nozzles with 2 different shapes, confirming that the turbulent scalar properties of the entire jet flow depend on initial conditions, thereby reinforcing the unlikely existence of a universal turbulent asymptotic state independent of initial conditions. Subsequently, Al. 11 provided a comprehensive review of initial condition effects, both steady and transient, on jet mixing. According to the perspective of Al, a jet never forgets its initial conditions. During the deepening of research into jet flow dynamics, significant progress has been made in understanding flow structures within jets. Initially developed about 50 years ago, approaches based on coherent structures are continually refined as we improve our ability to interpret flows. Coherent structures refer to ordered motion structures in turbulence that exhibit spatial and temporal correlations. In turbulent boundary layers, coherent structures play a crucial role in turbulence generation. The types of coherent structures mainly include horseshoe vortices, hairpin vortices 12, 13, quasi-vortices, low-speed streaks 14, soliton-like waves 15, 16, as well as some large-scale motions and very large-scale motions 17. List 18 provided a comprehensive review of seminal research on turbulent jet structures up to that time. The fundamental formation process of axisymmetric jets was summarized as follows. In the immediate vicinity of the nozzle exit, the high-velocity jet develops a laminar shear layer. This shear layer exhibits inherent instability and undergoes rapid growth, forming toroidal vortices, ring vortices, that entrain irrotational ambient fluid into the jet while simultaneously transporting turbulent jet fluid outward into the surrounding environment. And 19 demonstrated that the motion induced by each vortex interacts with neighboring vortices in a manner facilitating vortex pairing. 20 and Ewell 21 revealed that the vortex motion develops a secondary circumferential instability that causes each vortex to break up. Many researchers, Brown 22 and 19, 23, Freeman and 24, observed that under specific conditions, spiral waves develop and evolve into helical vortex structures. Following this sequence of events, the flow then becomes turbulent, and the jet begins to spread outwards by engulfing ambient fluid. To clarify structures, 25, in his seminal review on the role of coherent structures in turbulence, identified that one or more dominant modes, termed preferred modes, can typically be discerned in flow fields, representing the structures that occur most frequently. In axisymmetric flows, 3 uniformly distributed preferred modes exist: the toroidal mode, the single helical mode, and the double helical mode. In 1989 and 26 presented studies on the jet formed by the exhaust plume of a Titan IV rocket engine, with a number of approximately 218. Their results revealed that this high-number jet exhibited large-scale structural organization and propagation, behavior similar to observations in laboratory-scale jets at numbers of 104. They established that structural organization relates to viscous-independent instability mechanisms, with large-scale organization constituting an intrinsic component of jet evolution rather than transitional behavior remnants. At numbers Ray D2500 and Ray D10000, AL. 27 revealed persistent large-scale vortical structures in the far field, typically manifesting as axisymmetric or helical configurations. By using phase-lock sampling with controlled excitation, 28 confirmed azimuthal vortex pairing and conducted detailed topographic measurements of coherent rings, identifying two distinct pairing mechanisms based on number, jet column mode and shear layer mode. The role of vortex structure evolution in the near-field XD10 was examined by N29, who used laser-induced fluorescence to show that entrainment is determined primarily by vorticity beyond the end of the potential core regime. The initial Kelvin instability develops, followed by vortex rollup. Together, these processes lead to the formation of a series of unstable vortex rings. As these rings move downstream, they grow by entraining ambient fluid. After the potential core region XD8, the centerline velocity begins to decay, reducing the velocity difference between the ambient fluid and the high-speed core of the jet. This weakens the shear force sustaining the jet's vortex rings, causing them to break down into smaller structures. Meanwhile, small disturbances grow in the high-strain regions between paired vortex rings, forming a secondary instability that subsequently generates vortex pairs. Meanwhile, ALS 30 employed simultaneous Schlieren imaging and dye visualization techniques to characterize vortical structures in jets at moderate numbers, Ray D78000. Their experimental results demonstrated that these structures manifest as intrinsic secondary instabilities within the perturbed shear layer enveloping the jet column. In 2006, Bogey and 31 have performed large eddy simulation (LIS) of turbulent jets and investigated numbers effects on round jets in the region of 0xd20. Their results indicate that the number significantly influences the development of the mean flow and turbulence statistics in the shear layer and the transition region downstream of the potential core. At lower numbers, higher turbulence intensity, larger integral length scales, and more rapid development were observed. Recently, Joe 32 developed an artificial intelligence control system for turbulence manipulation aimed at maximizing the mixing rate of turbulent jets. Through AI-driven learning, the control process eventually converged to a hitherto unexplored forcing, generating complex turbulent flow structures characterized by periodically formed mushroom structures, helical motion, and an oscillating jet column that significantly enhanced the mixing rate. Although significant progress has been made in the study of free jets, there are still some shortcomings. Currently, most studies on coherent structures in jets focus on vortex structures from a perspective, which does not adequately capture the evolution of these structures as they move and develop with the flow. In contrast, research on coherent structures in flat plate boundary layers has reached a relatively mature stage. In flat plate boundary layers, these coherent structures can be broadly categorized into hairpin vortex-based and non-hairpin vortex-based structures. This paper focuses on non-hairpin vortex structures, specifically high and low-speed streaks, three-dimensional wave packets, and soliton-like waves. Streak structures refer to elongated distributions of high or low-speed regions, which are commonly observed in transitional and turbulent boundary layers. Research on low-speed streaks can be traced back to the experiments conducted by, in the 1960s, 14. They referred to the low-speed streaks in the transitional boundary layer and the turbulent boundary layer as transitional streaks and wall layer streaks, respectively. In 1989, Shen al. 33 employed a special laser light sheet hydrogen bubble flow visualization technique to investigate the direct relationship between high and low-speed streaks and vortex structures in a turbulent boundary layer. The study revealed that vortices are directly formed from the identifiable interface streaks between high-speed streaks. Additionally, hairpin vortices can only be generated when narrow high-speed streaks are spatially positioned farther from the wall than adjacent low-speed streaks. While there are considerable similarities between transitional streaks and wall layer streaks, they exhibit significant differences in terms of their respective scales and stability. At the time, a substantial body of indirect evidence suggested that the generation and breakdown of wall layer streaks played a central role in the turbulent boundary layer process. Moreover, experiments already allowed for the observation of the lifting phenomenon of wall layer low-speed streaks. In this paper, the proposed mechanism for the generation of wall layer streaks was based on the physical explanation put forward by 34. Specifically, the turning of the flow would advect and alter the vorticity component, thereby modifying the distribution of velocity. As a result, when tracers were introduced into the wall layer, the streaks became visible. Later, research based on the hairpin vortex framework of coherent structures provided a new explanation for streak formation. It suggested that low-speed streaks were either induced by the legs and head of hairpin vortices, causing upwelling of low-speed fluid, or were part of the uniform momentum zones induced by hairpin vortex packets 35-36. However, there is also a contrasting viewpoint which argues the formation of low-speed streaks does not require vortex induction. Proposed using a linear inviscid model, that low-speed streaks can grow from any initial three-dimensional disturbance as long as the net momentum in the wall normal direction is non-zero 37-38. And 39 also suggested that the formation of low-speed streaks results from the combined effects of three behaviors without requiring hairpin vortex induction. 1. The upward lifting of low-speed fluid. 2. The amplification of disturbances in the shear layer. And 3. Viscous diffusion. However, another perspective links low-speed streaks to three-dimensional wave packets, proposing that low-speed streaks are illusory structures generated by flow visualization. Lee 16 discovered a soliton-like coherent structure, SCS, suggesting that low-speed streaks are composed of a series of aligned SCSs. Due to the ease of fluid particle mixing between adjacent SCSs, the originally isolated SCSs combined to form streak structures. L found that persistent impulsive spikes exist in the outer region of the transitional boundary layer, which can propagate downstream into the fully turbulent region 40-41. Initially, they believed these impulsive spikes were coherent structure solitons in the transitional boundary layer, but later they identified such structures as vortex ring chains 42. However, experimental results by Lee 1643 revealed that early spike structures, single spikes, are not vortex ring chains but rather three-dimensional waves. Moreover, soliton-like waves, as typical three-dimensional wave packet structures, exist throughout the entire boundary layer. These newly discovered three-dimensional waves are referred to as SCSs. 44 confirmed the existence of SCSs and their dominant role in vortex evolution through DNS. L 4547 investigated the evolution of three-dimensional waves and vortex development in transitional and low-number turbulent boundary layers using both experimental and numerical approaches. The study incorporated hydrogen bubble flow visualization, PIV reconstructed flow fields, and NPSC numerical simulations, all of which consistently revealed similar flow phenomena. Furthermore, by employing tracking method, provided comprehensive details of the complete evolutionary process from 3D waves to hairpin vortices during three distinct types of boundary layer transition from a structural evolution perspective. In the tracking framework, timelines compared to streamlines and carry richer information about local flow behavior. Specifically, the coiling or distortion of timelines can help distinguish wave-like structures from vortex structures, whereas the coiling of a lone may not signify discrete vortex structures. In contrast, the coiling of does not necessarily indicate discrete rotational vortex motion. Recently, Al. 4849 investigated the flow structures of transitional flow in the wake of a sphere and discovered the existence of SCSs in the transitional wake behind the sphere. These SCSs in the wake exhibit similarities to phenomena observed in flat plate boundary layers. Vortex structures and high shear layers predominantly surround the periphery of the SCSs. The vortex structures are considered a consequence of the evolution of these SCSs. This study focuses on SCSs in free jets. By employing particle tracking and correlation analysis methods, we investigate the existence and evolutionary dynamics of SCSs within the jet flow. Furthermore, we aim to analyze the relationship between SCSs and vortex structures. 14.2 Flow Settings. The numerical simulation model for the free jet is described as follows. The model consists of a large circular pipe equipped with an injection tube. The fluid enters the circular pipe from the outlet of the injection tube and exits through the right outlet of the pipe. Using the jet nozzle diameter d 0.1 m as the characteristic length scale, the diameter of the pipe's base is dd40, and its length is ld70. Inside the pipe, the injection tube has a length of ld10. Given that the radius of the circular pipe is significantly larger than that of the jet orifice, the overall flow can be considered as a free jet. Schematic diagram of the mesh division on the cross-sectional plane, A in the orifice, B outside the orifice. The boundary conditions for the numerical simulation are set as follows. The jet inlet is defined as a velocity inlet boundary condition with a velocity of u0 ms. The domain outlet is prescribed as a total pressure boundary condition with a total pressure of P00. All walls are set as no-slip boundary conditions. At the initial time, both the internal velocity and pressure are 0. The numerical simulation is implemented using the OpenFOAM software. The solver is set to PimpleFOAM, which is a numerical simulation solver designed for solving pressure, velocity coupling problems in incompressible flows, combining the PISO pressure implicit with splitting of operators and simple semi-implicit method for pressure-linked equations, algorithms 50. The convection term is discretized using a second-order upwind scheme, while the diffusion term is discretized using a central difference scheme. The time term is treated with a second-order implicit scheme. The residual for velocity is set to 1e7, and the residual for pressure is set to 1e6. The flow number is defined as RAU0D20002500350. 3 simulation cases with distinct numbers were selected to examine flow field variations across different flow regimes. The case with RA2500 was then used for subsequent flow visualization analysis. The time step is set to 0.001 s, and the simulation terminates at T70s 14.3 numerical simulation results. Centerline velocity variation along the distance at different numbers. Temporal evolution of the velocity at fixed monitoring locations as 0.013 and 0.103, B0013 and -0.103. The coordinates are defined in the Cartesian coordinate system. Side view of the velocity field in the region where R0D10, a T60s, B time-averaged results over the span of T60-65s contour plots of the velocity field on various cross-sections under time averaging over the span of T60-65s, a schematic diagrams of various cross-sections, BZD4, CZD8, DZD13, EZD20. Graphs of velocity versus radius on different cross-sections over various time spans. A time-averaged results over the span of T60-65s, B time-averaged results over the span of T60-70s 14.4 fluctuating velocity field. Contour plots of the fluctuating velocity at ZD056, a RD07, BRD08, CRD09, DRD10. Scatter plots of fluctuating velocity at ZD056, a RD07, BRD08, CRD09, DRD10. 14.5 Tracking. Three-dimensional temporal evolution of material lines at ZD0 50 51 52 5, 22. Circular material line at RD09, the initial position of the material line is at ZD38, B the initial position of the material line is at ZD46. Material line located in a single low-speed region, a RD09 ZD3 8104, B RD09 ZD46 1728. To further investigate the evolution of the low-speed regions, we focus on a single low-speed region from Fig. 14.1 and place more refined material lines for tracking. The evolution is advanced over 50 time steps, and the results are shown in Fig. 14.11. From Fig. 14.11, it is evident that the material lines exhibit an upstream indentation in the central region due to the temporal accumulation of low-speed fluid. This phenomenon combined with the presence of high-speed regions on both sides. Additionally, the timeline evolution reveals that the fluid in the central low-speed region continuously moves closer to the axis, while the fluid in the high-speed regions on both sides gradually moves away from the axis. This behavior is consistent with the formation process of SCSs in turbulent boundary layers. In the jet flow, the velocity distribution is such that the velocity increases closer to the axis. Therefore, the movement of fluid toward the axis in the jet corresponds to the upward sweeping motion in boundary layers, while the movement away from the axis corresponds to the downward sweeping motion. This indicates that in the jet, the coherent structures follow the same principles as in boundary layers 47. The central low-speed fluid lifts up in the form of SCSs, while the surrounding high-speed fluid sweeps downward, forming a high-shear layer at their interface. Overlay diagram of material lines and of normal vorticity in the low-speed region. A RD09ZD38104, BRD09ZD461728. Trajectory pattern formed by the evolution of a single material line in the low-speed region. A RD09ZD3641104, BRD09ZD43491728 SV, vortex generation. Material line located in the region of a single high-speed region. A RD09ZD38212, BRD09ZD461321. Furthermore, we can utilize parallel distributed multiple timelines to better observe the overall structure of the low-speed regions, as shown in Fig. 14.13. Figure 14.13 displays the timeline patterns of 25 uniformly spaced arc-shaped material lines, initially located at RD09ZD3641104, after evolving over 100 time steps. Figure 14.13b, on the other hand, shows the timeline patterns of arc-shaped material lines initially positioned at RD09ZD43491728 after the same evolution period. From Fig. 14.13, it can be observed that the timelines located at the front portion of the low-speed region primarily exhibit local velocity deficits during evolution. However, neither within a single timeline nor between timelines do twisting or coiling phenomena occur. In contrast, the timelines at the rear portion of the region show positional overlap, indicating that wave crests of the solitary wave-like structures within this region exhibit a forward-tilting phenomenon toward the leading edge. Meanwhile, in Fig. 14.13b, the timelines at the rear portion exhibit coiling behavior, suggesting that vortex development is likely occurring in this region. These rolled-up timelines will gradually develop into the two legs of the vortex structure, while the central region lifts to form the head of the vortex. Meanwhile, the leading-edge timelines do not exhibit any rolling during the evolution process, indicating that the vortex structure originates from the development of a three-dimensional wave structure. Additionally, corresponding to the low-speed regions, the presence of high-speed regions can also be observed in the timeline patterns along the entire circumferential direction. Similarly, we can use material lines to reconstruct the development process of these high-speed regions. Figure 14.14 displays the timeline evolution of a single material line located in two high-speed streak regions. The material line in Fig. 14.14 is initially positioned at RD09ZD38212, while the material line in Fig. 14.14b is initially positioned at RD09ZD461321. As shown in the figures, over time, the central region of the material line protrudes forward, accompanied by lagging on both sides, forming a typical high-speed region. Meanwhile, observing its evolution in the radial direction reveals that the central part of the material line not only arches forward, but also moves away from the central axis, exhibiting radial changes opposite to those observed in low-speed region. Trajectory pattern formed by the evolution of a single material line in high-speed region. A RD09ZD3641212, BRD09ZD434913221 WS vortex generation. Schematic diagram of the material surface, a cylindrical material surface, B the arc-shaped material surface. Deformation of the cylindrical material surface initiated at RD0 609011 in cylindrical coordinates. A T0, BT0045, CT006, DT0075. Aside views of the evolving material surfaces uniformly distributed across RD0 6011, B initial positions on the material surfaces, along with the jet width development along the distance. Deformation of material surface initiated at RD09ZD3341104. A T0, BT0045, CT006, DT0075, SS2, S3, SCS. To further investigate the relationship between the inception location of the SCS on the material surface and its height from the central axis, Fig. 14.18 presents time evolution side views of 6 uniformly distributed material surfaces within RD0 611. Figure 14.18 clearly demonstrates that as the material surface moves progressively farther from the central axis, the inception location of the SCS shifts downstream and the wave amplitude diminishes. Figure 14.18b illustrates the correlation between the inception position of the SCS and the distance from the central axis, along with the variations of the jet width along the direction. Here, the jet width is defined as the distance between the jet boundary and the central axis, where the jet boundary corresponds to the position where the circumferentially averaged velocity equals 5% of the centerline velocity. The jet spreading angle is defined as the angle between the jet boundary and the central axis. Quantitative analysis of Fig. 14.18b reveals that the tangent of the jet spreading angle is approximately 0.1617. In contrast, the tangent of the angle formed between the central axis and the line connecting the SCS initiation locations across different material surfaces is about 0.455, significantly greater than the jet spreading angle. Deformation of material surface initiated at RD09ZD4252227. A T0, BT0045, CT006, DT0075S, SCS. Deformation of material surface initiated at RD09ZD3641212. A T0, BT0045, CT006, DT0075P, wave packet structure, R, warping. Deformation of material surface initiated at RD09ZD4351321. A T0, BT0045, CT006, DT0075P, wave packet structure, R, warping. Similarly, we can also observe the evolution of material surfaces within high-speed regions in three-dimensional space, as shown in Figs. 14.21 and 14.22. Figures 14.21 and 14.22 presents the evolutionary results of the material surfaces in RD09ZD3641212 and RD09ZD4351321 of the high-speed regions after 0.75 time units. The analysis reveals that the SCSs at the location of the high-speed regions exhibit a bulging deformation away from the central axis, while the middle section advances forward. The sides of the wave packet structure exhibit downward depressions that gradually deepen, forming distinct peak-valley patterns. The overall structure manifests as a three-dimensional wave packet, with the material surface at its edges beginning to roll up, indicating the onset of vortex formation due to fluid instability in this region. 14.6 Correlation Analysis. Speeds of SCSs in the low-speed regions of the RD09 material surface. A ZD4931 RD09, BZD6410 R/D09, CZD3628 RD09, DZD4106 RD09. First, select a time step when the SCS begins to develop. Identify the extremum points of radial displacement in the field. Record the distances of the 350 material points near these extremum points from the central axis as variable x, and note the coordinates of these material points as x1. Then assume a wave velocity. Based on the field at the next time step, interpolate the distances from the central axis for the points at coordinates x1 plus, and record these distances as variable y. Calculate the correlation coefficient Rx, y between variables x and y. Finally determine the true wave velocity. The true wave velocity is the one that maximizes the correlation coefficient Rx, y. Subsequently, evolve the material point coordinates based on this wave velocity. Diagram of the speeds of SCSs and the flow field velocity in high-speed region at ZD3421, RD07, BRD075, CRD085, DRD09. By employing correlation analysis, we can also measure the wave speed of the SCSs located within the high-speed regions. Selecting a specific region ZD3421, we measured the wave speeds of the three-dimensional wave structures at different heights from the central axis, and the results are shown in Fig. 14.24. From the figure, it can be observed that, due to the velocity distribution across the jet's cross-section, the velocity of the flow field decreases as the distance from the central axis increases. The velocity of the three-dimensional wave packet follows the same trend. Additionally, the wave packet's velocity is consistently lower than the local flow velocity, ranging approximately between 70% and 90% of the flow velocity. Diagram of the circumferential speeds of SCSs and the flow field velocity at the location ZD3421, RD07, BRD075, CRD085, DRD09. Speeds of the SCSs in the high-speed regions of the RD07 material surface. A ZD28066, BZD3516, CZD27191, DZD45049. 14.7 Conclusion. 1. This study employs DNS to solve the flow field of free jet flow. The tracking method is used to track material lines and surfaces at specific locations in the flow field, enabling the observation of the generation and evolution of the SCSs in the jet. Subsequently, correlation analysis is applied to measure the propagation speed of the SCSs, which is then compared with the local flow field velocity. This study employs DNS to solve the flow field of free jet flow. The tracking method is used to track material lines and surfaces at specific locations in the flow field, enabling the observation of the generation and evolution of the SCSs in the jet. Subsequently, correlation analysis is applied to measure the propagation speed of the SCSs, which is then compared with the local flow field velocity. 2. The tracking method tracks the motion trajectories of fluid particles, directly revealing the true path of fluid parcels. It is particularly suitable for turbulent and vortex-dominated flows, offering unique advantages in uncovering the physical essence and long-term behavior of fluid motion. Also, timeline patterns can more effectively distinguish whether a flow structure is a wave or a vortex. Furthermore, compared to the direct wave peak spacing method, the correlation-based approach for measuring wave speed is more adaptable to irregular waveforms. Even when two or more closely spaced wave peaks coexist, the correlation analysis method maintains its accuracy. The tracking method tracks the motion trajectories of fluid particles, directly revealing the true path of fluid parcels. It is particularly suitable for turbulent and vortex-dominated flows, offering unique advantages in uncovering the physical essence and long-term behavior of fluid motion. Also, timeline patterns can more effectively distinguish whether a flow structure is a wave or a vortex. Furthermore, compared to the direct wave peak spacing method, the correlation-based approach for measuring wave speed is more adaptable to irregular waveforms. Even when two or more closely spaced wave peaks coexist, the correlation analysis method maintains its accuracy. 3. The evolution of timelines and material surfaces in the tracing method reveals that the SCS can be observed in both the high-speed and low-speed regions of the free jet. These structures manifest as three-dimensional wave packets, with the orientation of their wave packet crests dependent on the local flow velocity. Specifically, the wave packets bulge outward in high-speed regions. As the timelines and material surfaces evolve, the interfaces between high-speed and low-speed regions near SCSs exhibit rolling of the timelines, indicating vortex formation at these locations. These vortices gradually develop into the two legs of the vortex structure, while the central region lifts up to form the head of the vortex. This observation further confirms that the vortex originates from the evolution of three-dimensional waves. The evolution of timelines and material surfaces in the tracing method reveals that the SCS can be observed in both the high-speed and low-speed regions of the free jet. These structures manifest as three-dimensional wave packets, with the orientation of their wave packet crests dependent on the local flow velocity. Specifically, the wave packets bulge outward in high-speed regions. As the timelines and material surfaces evolve, the interfaces between high-speed and low-speed regions near SCSs exhibit rolling of the timelines, indicating vortex formation at these locations. These vortices gradually develop into the two legs of the vortex structure, while the central region lifts up to form the head of the vortex. This observation further confirms that the vortex originates from the evolution of three-dimensional waves. The correlation-based velocity measurements of SCSs reveal that those in high-speed regions consistently propagate at 70%, 90% of the local flow velocity, demonstrating a clear sublocal velocity behavior. In contrast, SCSs in low-speed regions do not exhibit this consistent trend, primarily because the local velocity in these regions can be significantly lower than both the circumferential average velocity and the centerline velocity. When comparing the wave speeds of the SCSs with either the circumferential average velocity or the centerline velocity, they consistently appear slower than these reference velocities. The correlation-based velocity measurements of SCSs reveal that those in high-speed regions consistently propagate at 70%, 90% of the local flow velocity, demonstrating a clear sublocal velocity behavior. In contrast, SCSs in low-speed regions do not exhibit this consistent trend, primarily because the local velocity in these regions can be significantly lower than both the circumferential average velocity and the centerline velocity. When comparing the wave speeds of the SCSs with either the circumferential average velocity or the centerline velocity, they consistently appear slower than these reference velocities. Data availability: the data that support the findings of this study are available from the corresponding author upon reasonable request. Open access: this chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Poal Davies, M.J. Fisher, M.J. J. Fluid Mech. 15.3, 337, 1963. Org 101017 S0022 112063000306. 2S Sami T. H. Rouse, J. Fluid Mech. 27.2, 231, 1967. 3I H. J. Fluid Mech. 38.3, 577, 1969. Org 101017 S0022 112069000358. 4A Safe Higher Order Closure Model for Turbulent Jets, State University of New York at Buffalo, Thesis, 1981. 5JO Turbulence 2nd. Hill, 1975. 6 C.D. Richards, W.M. Pitts, J. Fluid Mech. 254, 417, 1993. Org 101017 S0022 112093002204. 7 W.K. George, M.M. Gibson, Exp. Fluids 13-4, 229, 1992. Org 101007 BF00, 189015. 8 WK George L. AIAJ 423, 438, 2004. Org 102514134459. 9 DR Dowling PIE J Fluid Mech. 218, 109, 1990. 10 J Me DS Knobs GJ J Fluid Mech. 432, 91, 2001. Org 101017 S002 2112000003384. 11 GJ Jamie ZT GJR DS Knobs Prague. Energy Combust. 3256, 496, 2006. Org 101016 JPEX 20060 7002. 12 MR Head P J Fluid Mech. 107, 297, 1981. Org 101017 S0022 1120 81001791. 13 J Joe RJ Adrian STM J Fluid Mech. 387, 353, 1999. Org 101017 S0022 1120990046 net. 14 SJ WC FA PW J Fluid Mech. 34, 741, 1967. Org 101017 S0022 112067001740. 15 Saibi Lai. A 247-6, 397, 1998. Org 101016 S0375960 198005829. 16 CB Lai JZ Wu. Mech. Rev. 613 2008. Org 10111512909605. 17 M SC RJ Adrian J Fluid Mech. 554 521 2006. 18 IJ List. Rev. Fluid Mech. 14 189 1982. Org 10114614 101820012001. 19 R in Boundary Layer Research, Symposium Freiburg. August 26-29, 1957, Ed. By H. Springer, Berlin, Heidelberg, 1958. 387-4-4. Org 10100 7978 3642 45885932. 20 PLAM Z. 45 307 1980. 21 AJ Yule J Fluid Mech. 89-3 413 1978. Org 101017 S0022 1120 78002670. 22 GB Brown Proc. Zogen. 47-4 703 1935. Org 10108809595309 474314. 23 P J Fluid Mech. 92-2 209 1979. Org 101017 S002 1120 790000598. 24 RW Freeman LL. Fluids 22-4 782 1979. Org 10106318622659. 25 HE Prague. 25-3 231 1988. Org 1010160376042188900012 MathNet. 26 MG DK. Fluids a 110 1615 1989. Org 10106318575527. 27 PAE RC Li DA. Fluids 2611 3185 1983. Org 10106318649090. 28 AKMF J Fluid Mech. 173 303 1986. Org 101017 S0022 11208600 1192. 29D M J Fluid Mech. 245 643 1992. Org 101017 S0022 112092000612. 30 COD TA long HE I exp. Fluids 123 189 1992. Org 101007 BF00 188258. 31C Bogey C. Fluids 186 2006. Org 10106312204060. 32 Ijo D Fan B Arlay BR J Fluid Mech. 897 A27 2020. Org 10101720200392. 33S LHMY Acta. Mech. Sen. 54 376 1989. Org 101007 BF02488011. 34 MJ in laminar boundary layers, ed. By L. Oxford University Press, 1963, p99. 35 RJ Adrian, CD, J Fluid Mech. 422 1 2000 net. 36 CR Smith, SB, J Fluid Mech. 129 27 1983. 37 MT, J Fluid Mech. 98 2 243 1980. Org 101017 S0022 112080000122 net. 38 MT, J Fluid Mech. 212 593 1990. Org 101017 S0022 112090002105. 39 SI MF J Fluid Mech. 544 99 2005 net. 40 YS in advances in turbulence 3. By AV PH Springer Berlin Heidelberg 1991 4251. 41 VI YSJ. Mech. Tech. 36 4 532 1995. Org 101007 BF023 71277 net. 42 VI VR YS DGW URIST QX CB lay. Fluid Dyne. 15 5 317 2002. Org 101007 S00 1620100054. 43 CB lay RQ lay J. 8 N55 2007. Org 101084146852406009251163. 44 W Numerical Simulations of Boundary Layer Transition by Combined Compact Difference Methods. D. Thesis, Technological University, Singapore 2013. 45 XY CB Lay X CR Smith PF Linden J Fluid Mech. 890 A11 2020. Org 10101720200107. 46 XY CB Lay CR Smith JW PF Linden J Fluid Mech. 903 A6 2020. Org 10101720200617. 47 XY DW CB Lay CR Smith PF Linden J Fluid Mech. 914 A4 2021. Org 10101720201023. 48 LHS CQJO WQSU. Fluids 36 3 2024. Org 10106350199349. 49 LHS CQJO WQSU. Fluids 37 1 2025. Org 10106350251193. 50 RI ESA J. 62-1-40-1986. Org 1010-1600-219999186900999 net. 51 HJ SB WK George J Fluid Mech. 258-31 1994. 52 OT AG Regas TGA J Fluid Mech. 855-953 2018. Org 1010-1720-18675 net. Soliton-like coherent structures in fluid mechanics, Lee. 1. Soliton-like coherent structure, a key opening the door of turbulence. Abstract. This review summarizes recent advances in the origin of turbulence. Soliton-like coherent structure, SCS, has been identified not only as a common structure in natural transition and K-type transition, but also as a fundamental structure in C-type, H-type, and bypass-type transitions, which dominates the turbulence generation. It has also been confirmed as an essential structure in turbulent boundary layers. Notably, SCS has been successively observed in pipe flows, stratified flows, mixing layers, jet flows, falling films, and wakes. These findings collectively indicate that SCS serves as a fundamental structure in shear flows, providing significant insights into the origin of shear turbulence. Supplementary information. The online version contains supplementary material available at org 10-100-7978-980-195-244-191. Keywords. 1.1 Definition of the soliton-like coherent structure, SCS. Turbulence is the last unsolved problem of classical physics and one of the 7 Millennium Prize problems in mathematics. A systematic summary of turbulence generation can be found in our earlier review articles 1-2. Readers may refer to these papers or earlier literature located through them. Without further ado, this chapter will directly focus on the role of the SCS, particularly research progress in the study of the SCS since 2020. 1. It is a localized three-dimensional wave. It is a localized three-dimensional wave. 2. Its convection velocity is generally lower than the mainstream flow velocity, typically 0.6 to 0.8 times the incoming flow velocity. Its convection velocity is generally lower than the mainstream flow velocity, typically 0.6 to 0.8 times the incoming flow velocity. 3. Its amplitude depends on the magnitude of the incoming flow disturbances. In cases of small incoming flow disturbances, it manifests as a linear three-dimensional wave. With larger incoming flow disturbances, it typically appears as a nonlinear wave. Its amplitude depends on the magnitude of the incoming flow disturbances. In cases of small incoming flow disturbances, it manifests as a linear three-dimensional wave. With larger incoming flow disturbances, it typically appears as a nonlinear wave. 4. Its frequency is roughly consistent with the frequency predicted by linear stability theory. After its formation, it amplifies and evolves in the shear layer before gradually diminishing. Due to its small shear gradient, it generally has a longer lifetime before dissipating. This is a key reason why we refer to it as the SCS. It shares certain properties with a soliton, but it is evolving and not a soliton in the mathematical sense. Its frequency is roughly consistent with the frequency predicted by linear stability theory. After its formation, it amplifies and evolves in the shear layer before gradually diminishing. Due to its small shear gradient, it generally has a longer lifetime before dissipating. This is a key reason why we refer to it as the SCS. It shares certain properties with a soliton, but it is evolving and not a soliton in the mathematical sense. 5. Previously, the SCS was believed to arise from the interaction of two oblique waves, either linear or nonlinear. Recent experimental evidence has confirmed that the SCS is indeed generated by the interaction of two oblique waves. Previously, the SCS was believed to arise from the interaction of two oblique waves, either linear or nonlinear. Recent experimental evidence has confirmed that the SCS is indeed generated by the interaction of two oblique waves. 6. The SCS is not the three-dimensional TS wave packet itself. The SCS is not the three-dimensional TS wave packet itself. Thus, we can define the SCS as a localized three-dimensional wave generated by the interaction of two three-dimensional oblique waves with the same frequencies. In the flow direction, it convects downstream at a speed lower than the mean flow. Its frequency is close to the frequency predicted by linear stability theory. Its amplitude first grows to saturation and then diminishes. The SCS has a longer lifetime than other coherent structures, exhibiting properties similar to a soliton, but undergoes evolution and dissipation. The two oblique wave interaction can be written in the following. The diamond-shaped structure of the perturbation field. Specifically, in the case of linear disturbances, the perturbation field exhibits a diamond-shaped structure, with its boundaries defined by the phase lines shown in Fig. 1.1. To confine the disturbances within the diamond-shaped region, the following two approaches can be employed. The two methods each have their own advantages and disadvantages. The primary advantage of Method 1 is its simplicity in construction, as it does not involve any undetermined parameters. Additionally, the base solution AXYZT can be either a linear or a weakly nonlinear solution. However, a significant drawback is that multiplying the solution by the limiter causes it to no longer satisfy the disturbance equations. In contrast, Method 2 retains the advantage of satisfying the linear disturbance equations. Nonetheless, it is relatively more complex to construct and requires the determination of undetermined constants, which can increase its complexity. 1.2 Difference between the SCS by Ley and the CS solitons by. The naming of the SCS has a rather intricate backstory, which traces back to C.B. Lee's participation in the 1993 IUTAM Symposium on Non-Parallel Flow Instability 7. At the conference, Y.S. presented his findings on CS solitons, which he later published in his seminal work in Annual Review of Fluid Mechanics 8. As young scholars, we were highly inspired and resolved to visualize CS solitons through flow visualization techniques upon our return. Remarkably, we discovered what is now referred to as the SCS. At the time, we genuinely believed we had successfully visualized CS solitons. Subsequently, we presented this work at the IUTAM Symposium held in Manchester, UK in 1995-9, later published in Physics Letters A10. We were confident that it confirmed his discovery. However, whose work was based on one-dimensional hot wire measurements, did not agree that our SCS was the same as his CS solitons. This disagreement was deeply disappointing to us. However, suggested investigating whether the SCS observed in K-type transition experiments could indeed be related to his CS solitons. This marked the beginning of a cooperation between China and Russia. There are three landmark experimental works in the K-regime of boundary layer transition research. The first was pioneering work 11, which for the first time in human history artificially generated turbulence, historically known as K-regime of boundary layer transition. The second milestone work was accomplished by Hama, who discovered the vortex, highlighting the importance of three-dimensional structure generation in transition research 12. The third milestone work was experiment 8, where he found that the breakdown of the vortex remains periodic. Discovered that vortex generated 4 high-frequency vortices termed a chain of ring vortices, providing the first solid experimental data in human history demonstrating the evolution of flow structures from low frequency to high frequency during transition. Were it not for the advancements in modern flow visualization, measurement techniques, and data processing methods, their work might have concluded research on K-type transition. Differences between the CS solitons discovered by and the SCS discovered by Lee. CS soliton 8.13.14. Lee's SCS 1.15. 1. CS solitons are vortex structures, as depicted in A. 1. Lee's SCS is a wave structure, as depicted in E. 2. CS solitons originate in the outer layer of the boundary layer. During the late stages of transition, X500 m, They are high-frequency vortices formed by the stretching and reconnection of vortices, as depicted in B. 2. Lee's SCS originates in the early stages of transition, X260, spanning from the lower to the outer layers of the boundary layer, occurring earlier than CS solitons, as depicted in F and B. 3. After 2000, referred to the CS soliton as a ring-like vortex, C. 3. Lee's SCS is generated by the interaction of two oblique waves, which give rise to the vortices and the secondary vortex rings. The interaction between the vortices and secondary vortex rings results in the formation of CS solitons, i.e., the ring-like vortex, as shown in G and B. 4. CS solitons are high-frequency structures relative to vortices, as shown in D. 4. Lee's SCS shares the same frequency as the vortices, while CS soliton is a high-frequency structure, as depicted in E and D. Table 1.1 shows the differences between CS solitons and Lee's SCS. The shared nomenclature between Lee's SCS and CS solitons originated from a misunderstanding of Lee 910. When we began natural transition experiments in 1993, we read literature but failed to fully grasp its depth. Moreover, key results derived from one-dimensional hot-wire data were challenging to interpret. When Lee observed three-dimensional waves during natural transition experiments, he assumed, perhaps too simplistically, that he had visualized CS solitons. However, subsequent findings proved otherwise, leading to significant misinterpretations among later researchers citing this work. A main characteristic of CS solitons are vortex structures. In its famous paper 8, it is clearly stated, thus, experimental studies which correlate very well with numerical experiments by RISC 1990-1992 and private communication show that the CS solitons at the 3D stages of their development represent very localized, toroidal, most probably vortices, observed in oscilloscope traces as a set of spikes. Main characteristics of CS solitons are vortex structures. In its famous paper 8, it is clearly stated, thus, experimental studies which correlate very well with numerical experiments by RISC 1990-1992 and private communication show that the CS solitons at the 3D stages of their development represent very localized, toroidal, most probably vortices, observed in oscilloscope traces as a set of spikes. B. Main characteristics. CS solitons appear at the late stage of transition, and they are generated by multiple reconnections of the vortex legs near its tip and the formation of ring-like vortices. Also pointed out, the most typical features of the CS solitons are the spikes observed near the external edge of the boundary layer. These solitons correspond to typical eddies, i.e., the coherent structures observed in the outer part of the turbulent boundary layer, and in the paper, comparison of these graphs with those obtained for the stage, where the soliton has just formed, X500 min figure 25 left and X550 min figure 29 left, visually demonstrates the wonderfully strong conservatism of the CS soliton properties mentioned above. In the paper by Baek al. 14, the authors believed that the CS solitons were generated by multiple reconnections of the vortex legs near its tip and formation of the ring-like vortices through an intermediate stage of vortices or hairpin vortices, which represent very stable, soliton-like coherent structures called CS solitons. They have very conservative, slow dissipation properties and are closely connected with the spikes. Main characteristics. CS solitons appear at the late stage of transition, and they are generated by multiple reconnections of the vortex legs near its tip and the formation of ring-like vortices. Also pointed out, the most typical features of the CS solitons are the spikes observed near the external edge of the boundary layer. These solitons correspond to typical eddies, i.e., the coherent structures observed in the outer part of the turbulent boundary layer, and in the paper, comparison of these graphs with those obtained for the stage, where the soliton has just formed, X500 min figure 25 left and X550 min figure 29 left, visually demonstrates the wonderfully strong conservatism of the CS soliton properties mentioned above. In the paper by Baek al. 14, the authors believed that the CS solitons were generated by multiple reconnections of the vortex legs near its tip and formation of the ring-like vortices through an intermediate stage of vortices or hairpin vortices, which represent very stable, soliton-like coherent structures called CS solitons. They have very conservative, slow dissipation properties and are closely connected with the spikes. See main characteristics of CS solitons. CS solitons are also called ring-like vortices. In the paper by Baek al. 14, the authors propose that these positive spikes are discussed in 12 and 17 and corresponds to a positive velocity fluctuation around the external edge of the ring-like vortex, the CS soliton attributed to the spike at late stages of K-regime of transition. Main characteristics of CS solitons. CS solitons are also called ring-like vortices. In the paper by Baek al. 14, the authors propose that these positive spikes are discussed in 12 and 17 and corresponds to a positive velocity fluctuation around the external edge of the ring-like vortex, the CS soliton attributed to the spike at late stages of K-regime of transition. D. Main characteristics of CS solitons. Believed that CS solitons were high-frequency structures compared with the vortices. The paper by 8 states that it was concluded that the eventual localization of high-frequency disturbances ultimately led to the soliton formation observed experimentally. Main characteristics of CS solitons. Believed that CS solitons were high-frequency structures compared with the vortices. The paper by 8 states that it was concluded that the eventual localization of high-frequency disturbances ultimately led to the soliton formation observed experimentally. Main characteristics of LI's SCS. SCS is the real three-dimensional wave instead of vortex. In the papers by Li 15 and Lei and Wu 1, the SCSs suggested by Lei, which are different from those observed by 1994, are typically three-dimensional wave packets, although they have the same frequency as the TS waves. Li 1 further emphasized that first, it is really a wave because it is an oscillating disturbance propagating downstream at a finite speed. Second, a SCS is a nonlinear wave, as exhibited by its pattern shown in Fig. 4, where the amplitude develops to a strong localized pattern very quickly in the initial nonlinear stage, and obviously decreases in the later stage of boundary layer transition. Third, a SCS is a nonlinear traveling wave rather than an ordinary vortex because it keeps irrotational from its birth to death. Main characteristics of LI's SCS. SCS is the real three-dimensional wave instead of vortex. In the papers by Li 15 and Lei and Wu 1, the SCSs suggested by Lei, which are different from those observed by 1994, are typically three-dimensional wave packets, although they have the same frequency as the TS waves. Li 1 further emphasized that first, it is really a wave because it is an oscillating disturbance propagating downstream at a finite speed. Second, a SCS is a nonlinear wave, as exhibited by its pattern shown in Fig. 4, where the amplitude develops to a strong localized pattern very quickly in the initial nonlinear stage, and obviously decreases in the later stage of boundary layer transition. Third, a SCS is a nonlinear traveling wave rather than an ordinary vortex because it keeps irrotational from its birth to death. F. Main characteristics of Li's SCS. SCS appears at the initial stage of transition before X216 from the leading edge and occupies the boundary layer thickness from the near wall region to the outer layer with the longest lifetime compared with other coherent structures. In Li's paper 15, it is shown that both the visual results and experimental measurement demonstrate the existence of the CS solitons from the initial stage of three-dimensional structure formation, X260, to the later stage of transition and the onset of turbulence. According to the definition of, and his coworkers 8, the CS solitons they observed are the outer part of the chain of vortices. The CS solitons are present not only in the near wall region, but also near the external part of the boundary layer. The main features of the CS solitons remain unchanged before breakdown, which is why they are called CS solitons. Main characteristics of Li's SCS. SCS appears at the initial stage of transition before X216 from the leading edge and occupies the boundary layer thickness from the near wall region to the outer layer with the longest lifetime compared with other coherent structures. In Li's paper 15, it is shown that both the visual results and experimental measurement demonstrate the existence of the CS solitons from the initial stage of three-dimensional structure formation, X260, to the later stage of transition and the onset of turbulence. According to the definition of, and his coworkers 8, The CS solitons they observed are the outer part of the chain of vortices. The CS solitons are present not only in the near-wall region, but also near the external part of the boundary layer. The main features of the CS solitons remain unchanged before breakdown, which is why they are called CS solitons. Main characteristics of Lee's SCS. SCS is formed by the interaction of two oblique waves, and it induces the formation of the vortex and a secondary closed vortex, and the interaction between the vortex and the secondary closed vortex generates a chain of ring vortices, i.e. CS solitons. In the paper by Lei and Wu 1, it is clearly shown the physical mechanism for the SCS generation and its relation with the low-speed streak is that a rhombus SCS comes from the nonlinear interactions between two oblique waves generated at the leading edge of the flat plate. All the dynamic processes for the formation of the secondary closed vortex and a chain of ring vortices are clearly shown in the related part of the paper by Lei and Wu 1. Main characteristics of Lee's SCS. SCS is formed by the interaction of two oblique waves, and it induces the formation of the vortex and a secondary closed vortex, and the interaction between the vortex and the secondary closed vortex generates a chain of ring vortices, i.e. CS solitons. In the paper by Lei and Wu 1, it is clearly shown the physical mechanism for the SCS generation and its relation with the low-speed streak is that a rhombus SCS comes from the nonlinear interactions between two oblique waves generated at the leading edge of the flat plate. All the dynamic processes for the formation of the secondary closed vortex and a chain of ring vortices are clearly shown in the related part of the paper by Lei and Wu 1. 1.3 SCS, the common flow structure in the boundary layer dominating turbulence production. Paths to turbulence in boundary layer flows. Figure adapted from Al. 16. Material surfaces for a K-regime transition, B. O-regime transition, C. N-regime transition 20. Reproduced with permission from XY, CB Lei X, CR Smith and PF Linden, structure evolution at early stage of boundary layer transition, simulation and experiment, J. Fluid Mech. 890, A11, 2020. Copyright 2020, Cambridge University Press. Hydrogen bubble visualization in the plane view for the turbulent boundary layer 21. The low-speed streaks can be seen clearly. Reproduced with permission from XY, CB Lei, CR Smith, JW and PF Linden. Experimental study on low-speed streaks in a turbulent boundary layer at low number, J. Fluid Mech. 903, A6, 2020. Copyright 2020, Cambridge University Press. Hydrogen bubble visualization in the side view for the turbulent boundary layer 10. Reproduced with permission from CB Lei, new features of CS solitons and the formation of vortices. A 247.6, 397.4 to 1998. Copyright 1998. A sequence of timelines generated at 50 based on PIV database, illustrating low-speed streaks in a turbulent boundary layer. The markers trace the location of the center of two LSSs, designated I and II21. Reproduced with permission from XY, CB Lei, CR Smith, JW and PF Linden. Experimental study on low-speed streaks in a turbulent boundary layer at low number, J. Fluid Mech. 903, A6, 2020. Copyright 2020, Cambridge University Press. Natural transition occurs in a water tunnel with a turbulence level of about 1%, where the flat plate boundary layer transitions from laminar to turbulent without any control. Since the incoming turbulence level is low, the positions of the low-speed streaks are relatively fixed in the direction. Figure 1.4 shows the results of hydrogen bubble visualization in a plane view, and as we can observe from these results, the flow is naturally blocked at the low-speed streaks. Because of mass conservation, the flow must move upward in the direction normal to the flat plate, and the side view visualization confirms this. Compared to Hama's classical work 12, we have improved the side view method by insulating the hydrogen bubbles in segments. This allows for parallel hydrogen bubble lines in the laminar flow, as shown in Fig. 1.5. We place the hydrogen bubble lines in the center of the low-speed streaks in the side view, which reveals the wave evolution process. Figure 15BD shows this evolution. In Fig. 1.5b, arrow A indicates that the flow is initially blocked by the low-speed streak and starts to move upward. In Fig. 1.5c, arrow B represents that the magnitude of the upward movement becomes larger and the flow is blocked more severely. Because of mass conservation, when the flow in the lower layer moves upward, the flow in the higher layer must move downward to compensate the mass. In Fig. 1.5d, around the upward movement at arrow C, there are downward movements. L21 applied tracking to marked particles based on the tomographic particle image, PIV data, and extracted the timeline patterns of the low-speed streaks in the turbulent boundary layer, as shown in Fig. 1.6, which is qualitative consistent with the hydrogen bubble visualization in Fig. 1.4. We conducted systematic experiments on K-type transition, which were carried out in 3 phases. The first phase was published in 1522. Both the SCS we discovered and the CS Soliton identified by were clearly visualized, and we distinguished between the two. As noted by N23 in their citations, Lee's SCS is different from CS Soliton. However, they were concerned about the universal existence of SCS in shear flows 23. The second phase of the experiment involved further improvements to the hydrogen bubble technique, enabling measurements closer to the wall. This time, we observed a secondary closed vortex. The SCS underwent primary instability to generate vortices, discovered by Hama, while the secondary instability of the SCS led to the formation of a secondary closed vortex, discovered by Lee. The interaction between the vortices and the secondary closed vortex produced the CS solitons of, i.e., a chain of vortices as identified by. Believed that the vortices, through self-induced stretching and reconnection, would form a chain of vortex rings 8. Based on our flow visualization results, however, we proposed that the boundary instability of the SCS generated the vortices, and its secondary instability led to the formation of a secondary closed vortex. These secondary closed vortex, interacting with the vortices, formed a chain of ring vortices. We do not deny findings. Our work presents experimental results directly derived from our observations. Our second set of K-type transition results were published in 24-26, and an invited review was published in Applied Mechanics Review 1. These works received substantial positive feedback, particularly from a remarkable summary 27, which regarded our work as one of the classic studies on boundary layer transition and praised its clarity in addressing several key issues. In 2019, we wrote a review article 2 on flow structures in transitional and turbulent boundary layers at the invitation of the Physics of Fluids editor. This review was widely regarded as comprehensive and insightful, ranking among the top 5 most cited reviews in the journal. Notably, doctoral dissertation from Technological University in Singapore 28 replicated our results in great depth for the first time using direct numerical simulation, DNS, offering high praise for our discoveries. Later, we repeated much of this work for a third phase, particularly using particle image, PIV, to replicate K-type transition experiments 2021-29. In particular, the 2021 paper was selected for the IUTAM special event, Fluid Mechanics in the Spirit of GK30. This article was granted an exemption from page restrictions, unlike other articles which had a 20-page limit, as the editor considered it particularly well written. To address this question, we also conducted computational studies on N-type and O-type transitions. NPSC analysis and DNS results for K-type and bypass transitions demonstrated that the SCS is the dominant structure in N-type, O-type, and bypass transitions 2021-29. Behavior of a material surface initiated in a low-speed region within turbulent spot at Y011, a T39, BT386, CT463, D31. Reproduced under CC BY from N, YD, CB Lee and CR Smith. Experimental and numerical investigation of turbulent spots in a flat plate boundary layer, J Fluid Mech. 1008, A37, 2025. Copyright 2025 Cambridge University Press. In the turbulent boundary layer, the origin of turbulence was first hypothesized by in 1952-33, who suggested the existence of a two-dimensional vortex tube, which when disturbed and lifted up, forms hairpin vortices in the boundary layer. Later, Al. 34 proposed that turbulence is generated by a burst phenomenon from their famous experiment. However, for many years, the nature of this burst remained unclear, until 2005, when we discovered that the burst behavior is controlled by the SCS-26. This discovery is of significant scientific importance, as it connects this widely accepted phenomenon to a tangible flow structure. Real turbulent boundary layer experiments must be capable of revealing this mechanism. Unlike the low-speed streaks observed during transition, the low-speed streaks in a turbulent boundary layer vary in position over time and space. Fortunately, PIV technology now allows us to track these structures, and we eventually obtained three-dimensional spatiotemporal data of the streaks. The PIV data analysis revealed that the streaks comprise SCSs. These SCSs dominate the turbulence burst phenomenon, directly linking transition and turbulence research. This work was published in Journal of Fluid Mechanics 21. At this point, all possible scenarios in the boundary layer have been studied, and it has been confirmed that the SCS is a common physical structure that governs the generation of turbulence. Since we have not obtained copyright for our article titled Transition in Wall-Bounded Flow in Applied Mechanics Review, we can only purchase the relevant images. Therefore, the entire transition process needs to be redocumented here. Step 1. Two oblique waves interact to generate localized three-dimensional waves, either linear or nonlinear. The linear results are relatively straightforward, but we have conducted supplementary experiments on nonlinear interactions. Figure 1.8 illustrates the interaction of two oblique waves producing localized three-dimensional waves, i.e., the early stage form of the SCS. For clarity, we have created an accompanying video 1.1, as shown in Fig. 1.9. Two oblique waves interact to generate localized three-dimensional waves, either linear or nonlinear. The linear results are relatively straightforward, but we have conducted supplementary experiments on nonlinear interactions. Figure 1.8 illustrates the interaction of two oblique waves producing localized three-dimensional waves, i.e., the early stage form of the SCS. For clarity, we have created an accompanying video 1.1, as shown in Fig. 1.9. Step 2. The instability of the SCS leads to the formation of a vortex. Figure 1.10 depicts this process. The underlying mechanism is consistent with our discussion in this paper and in the Physics Letters A article. The corresponding video 1.2 demonstrates this stage, as shown in Fig. 1.11. The instability of the SCS leads to the formation of a vortex. Figure 1.10 depicts this process. The underlying mechanism is consistent with our discussion in this paper and in the Physics Letters A article. The corresponding video 1.2 demonstrates this stage, as shown in Fig. 1.11. Step 3. The secondary instability of the SCS generate a secondary closed vortex. This process is discussed in detail in Lei and Wu 1, and the results are presented in Fig. 1.12. A related video 1.3 is provided, as shown in Fig. 1.13. The secondary instability of the SCS generate a secondary closed vortex. This process is discussed in detail in Lei and Wu 1, and the results are presented in Fig. 1.12. A related video 1.3 is provided, as shown in Fig. 1.13. Step 4. The interaction between the vortex and the secondary closed vortex produces a chain of ring vortices and two vortices on the two sides of the chain of ring vortices, where chain of ring vortices is the CS solitons identified by 8, as shown in Fig. 1.14. The corresponding animation is labeled Video 1.4, as shown in Fig. 1.15. The interaction between the vortex and the secondary closed vortex produces a chain of ring vortices, and two vortices on the two sides of the chain of ring vortices, where chain of ring vortices is the CS solitons identified by 8, as shown in Fig. 1.14. The corresponding animation is labeled Video 14, as shown in Fig. 1.15. Step 5. The interaction between the chain of ring vortices and the SCS first causes breakdown the ring vortices in the near wall region of the boundary layer, followed by breakdown at the heads of the ring vortices in the outer region of the boundary layer. At this stage, the power spectrum already satisfies the 3-scaling law, but the dynamics remain a deterministic process, Fig. 1.17. The animation for this step is Video 1.5, as shown in Fig. 1.16. The interaction between the chain of ring vortices and the SCS first causes breakdown the ring vortices in the near wall region of the boundary layer, followed by breakdown at the heads of the ring vortices in the outer region of the boundary layer. At this stage, the power spectrum already satisfies the 3-scaling law, but the dynamics remain a deterministic process, Fig. 1.17. The animation for this step is Video 1.5, as shown in Fig. 1.16. Flow visualization of the flat plate model leading edge receptivity process, showing the flow visualization of the flat plate model leading edge receptivity process using water surface reflection. Under the disturbance generated at the leading edge, position x0, the water surface exhibits oblique wave modes in the upstream and downstream regions. These oblique waves, characterized by stable wavelengths and wave angles, continuously emanate from the leading edge and propagate both upstream and downstream. Oblique waves generate localized 3-dimensional waves. A still image with Video 1.1.2 oblique waves generate localized 3-dimensional waves. Video 1.1 is available from the electronic supplementary material ESM-LE Video 1.1.4. Visualization of the formation of the SCS and the well-known vortex. The time interval between successive pictures was 1:12s26. Reproduced with permission from C.B. Lay and S.Y. in Transition and Turbulence Control, Lecture Notes Series, Institute for Mathematical Sciences, National University of Singapore. By M. Gadel, H.M., World Scientific, 2005. 3985. Copyright 2005, World Scientific Publishing Company. A still image with Video 1.2, SCS's led to vortices. Video 1.2 is available from the electronic supplementary material ESM-LE Video 1.2.4. Secondary closed vortex SCV formation. The time interval between successive pictures is 1:12s1. Reproduced with permission from C.B. Lay and J.Z. Wu, Transition in Wall-Bounded Flows. Mecca. Rev. 61.3, 30802, 2008. Copyright 2008 American Society of Mechanical Engineers, ASME. A still image with Video 1.3, SCS's lead to secondary closed vortex. Video 1.3 is available from the electronic supplementary material ESM-LE Video 1.3.4. Formation of the second 2, third 3, and fourth 4 ring vortices in a chain of ring vortices. The time interval between successive pictures was 1:24s24. Reproduced with permission from C.B. Lay and S. on the formation of the chain of ring-like vortices in a transitional boundary layer, exp. Fluids 33, 354, 357, 2001. Copyright 2001, Springer Nature. A still image with Video 1.4, chain of ring vortices induced by the interaction of the secondary closed vortex and the vortex. Video 1.4 is available from the electronic supplementary material ESM-LE Video 1.4.4. A still image with Video 1.5, chain of ring vortices induced by the interaction of the secondary closed vortex and the vortex. Video 1.5 is available from the electronic supplementary material ESM-LE Video 1.5.4. Breakdown of the first ring vortex in a transitional boundary layer. 1, 2, 3, 4 label the ring vortices 1. Reproduced with permission from C.B. Lay and J.Z. Wu. Transition in wall-bounded flows. Mecca. Rev. 61.3 30802 2008. Copyright 2008 American Society of Mechanical Engineers, ASME. 1.4 SCS, the dominant structure in turbulence generation in shear flows. 141 Similarity solutions. It is a significant challenge to find solutions for laminar unsteady boundary layer flows, which are essential for understanding the laminar turbulent transition. Sun 35 developed a similarity transformation to convert the two-dimensional unsteady laminar boundary layer equations into a single partial differential equation, and successfully derived similarity solutions for a flat plate boundary layer flow, expressed in terms of functions. The superposition of these solutions provides evidence for the existence of the SCS within boundary layers. This finding indicates that all viscous fluid motions have the potential to exhibit the SCS. 142 Stratified flow. Schematic view of the origin of a hairpin from wave and its evolution in the B, intermittent regime, and C, turbulent regime. Dashed lines indicate shear structure, and green segmented tubes indicate having direction R. The background indicates density stratification. Abbreviations are LU lift-up, SD sweep-down, LM lateral movement, R vector HS high shear 36. Reproduced under CC by from XY, A, SB, and PF Linden, the evolution of coherent vortical structures in increasingly turbulent stratified shear layers, J Fluid Mech. 947, A30, 2022. Copyright 2022, Cambridge University Press. To analyze and visualize vortices, the authors utilized the shear decomposition method. This approach separates the vorticity field into a vector, representing rigid body rotation, and a shear vector, facilitating the clear identification of vortex structures, particularly hairpin vortices. Figure 118 illustrates the evolution of the waves and their adjacent vortices. The constrained instability, chi, arises from the resonant interaction between a vorticity wave at the edge of the shear layer and a gravity wave at the density interface. This instability grows to a finite amplitude, enhancing and distorting the background vorticity until it saturates nonlinearly into the characteristic shear structure of the confined wave, CHW, as indicated by the dashed line in Fig. 1.18. Subsequently, a three-dimensional state with a pronounced vorticity gradient may develop, evidenced by the nucleation of vorticity on both sides of the wave. These regions are located beneath the wave head and above its body. Over time, the vorticity further concentrates at these positions, forming a shaped vortex. The newly formed vortices are labeled A and B in Fig. 1.18. This process is similar to the wave-induced vortex scenario described in boundary layers, where the amplification of three-dimensional waves, which are the same as soliton-like coherent structures, is a key initiator of vortices. This suggests that such structures may represent a universal feature of shear-driven turbulence, regardless of the presence of a boundary. 143 Wake flow. L37 presents a comprehensive study on the SCS within the wake flow behind a sphere. It investigates the SCS at different numbers by large eddy simulation, LAS. The authors used the method named to find the vortex structures of the wake flow. It has been found that the SCS exhibits similarities to those observed in boundary layer flows during the turbulent transition. The authors discussed the simulation results of the wake flow based on different numbers. One appearance of the SCS, at ray 250, the structure of wake flow appears as two parallel vortices in the flow direction. At ray 270, a kink structure forms between the two parallel vortices. Positive disturbances and negative disturbances appear as an alternating pattern. During the kink formation stage, the fluctuation amplitude of the flow velocity is about 0.25% of the incident velocity. The amplitudes of velocity fluctuations in the other two directions are even smaller, about 0.07% and 0.06% of the incoming velocity. This indicates that the velocity fluctuations at ray 270 already exhibit three-dimensional characteristics. Appearance of the SCS. At ray 250, the structure of wake flow appears as two parallel vortices in the flow direction. At ray 270, a kink structure forms between the two parallel vortices. Positive disturbances and negative disturbances appear as an alternating pattern. During the kink formation stage, the fluctuation amplitude of the flow velocity is about 0.25% of the incident velocity. The amplitudes of velocity fluctuations in the other two directions are even smaller, about 0.07% and 0.06% of the incoming velocity. This indicates that the velocity fluctuations at ray 270 already exhibit three-dimensional characteristics. 2. SCS generation. At ray 280, velocity disturbance of the wake flow generates regular three-dimensional wave packets. Compared with those at ray 270, the three-dimensional characteristics of velocity fluctuations under current ray 280 are significantly enhanced. The 3D wave packet moves downstream at about 78% of the incoming velocity. At and ray 350, the three-dimensional wave packets of velocity disturbance appear sharper than those at ray 280. In addition, the authors showed the relative positions of hairpin vortices and wave packets with velocity disturbances at different numbers, as shown in Fig. 1.19. The appearance of the spikes and the stable relative position of the negative wave packet indicate the formation of the SCS. SCS generation. At ray 280, velocity disturbance of the wake flow generates regular three-dimensional wave packets. Compared with those at ray 270, the three-dimensional characteristics of velocity fluctuations under current ray 280 are significantly enhanced. The 3D wave packet moves downstream at about 78% of the incoming velocity. At and ray 350, the three-dimensional wave packets of velocity disturbance appear sharper than those at ray 280. In addition, the authors showed the relative positions of hairpin vortices and wave packets with velocity disturbances at different numbers, as shown in Fig. 1.19. The appearance of the spikes and the stable relative position of the negative wave packet indicate the formation of the SCS. 3. SCS evolution. From ray 350 to ray 1000, the authors found that there is an ordered interaction between velocity disturbance and vortex structure, and their relative positions can be predicted. The wave packet of negative flow velocity disturbance still maintains regularity. Its shape and amplitude remain almost unchanged in the near-wake region, exhibiting the characteristics of solitary waves. In addition, the authors compared the velocity fluctuations in different directions of the wake flow at different numbers, ray 350, 500, 700, and 1000. The negative peak of U is the most significant, followed by V, while the magnitude of W is relatively small. The difference in time series and amplitude indicates that the negative peak of the U component is the key and dominant factor in turbulent transition. As the number increases, the fluctuation pattern also changes, from single peak or single valley to multiple peaks or multiple valleys. SCS evolution. From ray 350 to ray 1000, the authors found that there is an ordered interaction between velocity disturbance and vortex structure, and their relative positions can be predicted. The wave packet of negative flow velocity disturbance still maintains regularity. Its shape and amplitude remain almost unchanged in the near-wake region, exhibiting the characteristics of solitary waves. In addition, the authors compared the velocity fluctuations in different directions of the wake flow at different numbers, ray 350, 500, 700, and 1000. The negative peak of U is the most significant, followed by V, while the magnitude of W is relatively small. The difference in time series and amplitude indicates that the negative peak of the U component is the key and dominant factor in turbulent transition. As the number increases, the fluctuation pattern also changes, from single peak or single valley to multiple peaks or multiple valleys. Relative position between the SCS, identified by UU on YD0787 plane, and the vortex structures identified by 023, array 350b, ray 100037. Reproduced with permission from L, HS, CQ Joe, and WQ Su, solitary wave structure of transitional flow in the wake of a sphere. Fluids 37-1, 14111, 2025. Copyright 2025 AIP Publishing. In summary, the authors have determined that the SCS plays an important role in the wake transition process through numerical simulations. The structure of the wake flow is similar to the phenomenon observed by Li 1 in his study of boundary laminar flow. 144 Fallings Film. The experiment by Al. 38 was conducted in a channel with a sinusoidal bottom contour along the flow direction, characterized by an amplitude of 1 and a wavelength of 10. The inclination angle of the channel relative to the horizontal plane was adjustable, ranging from 10 to 45 in 5 increments. The working fluid was silicone oil, with the flow rate controlled by a frequency-adjustable pump, thereby regulating the number. The three-dimensional patterns of the free surface were identified using the shadowgraph method and light sheet imaging. In the shadowgraph method, a 400W halogen lamp illuminated the ceiling, and the reflected light illuminated the free surface. The camera was positioned perpendicular to the inclined bottom of the channel to capture the spatial distribution of the three-dimensional surface patterns along the and directions. Different three-dimensional patterns detected with the light sheet technique, a synchronous pattern and B checkerboard pattern. H height above bottom troughs, amplitude of the bottom contour, wavelength of the bottom contour, B distance in the direction from the sidewall, and L distance from inflow in the direction. Each line of the free surface contour corresponds to one profile in a light sheet. Ray 39, 15, and 45 B 38. Reproduced with permission from B, Al, T, and A, steady three-dimensional patterns in gravity-driven film flow down an inclined sinusoidal bottom contour. Fluids 35-3, 33307, 2023. Copyright 2023 AIP Publishing. The experimental results reveal that at low numbers, the thin film flow exhibits steady two-dimensional behavior, which transitions to traveling waves and eventually to three-dimensional steady waves. The three-dimensional waves on the free surface consistently emerge near the channel sidewalls, close to the inlet, before expanding to larger regions and reaching the channel center. The three-dimensional patterns can be classified into synchronous patterns and checkerboard patterns. The synchronous patterns have a wavelength matching the bottom contour of the channel, whereas the checkerboard patterns exhibit surface undulations opposite to the bottom contour. Synchronous patterns appear at all inclination angles, while checkerboard patterns only occur at high numbers and large inclination angles. By decomposing the free surface profile into a Fourier series using fast Fourier transform for quantitative analysis, it was found that both patterns are triggered only after the free surface amplitude reaches its maximum. This suggests that these patterns may arise from bifurcations caused by the nonlinear resonance of the original mode. The emergence of three-dimensional patterns suppresses traveling waves and stabilizes the steady flow. 145 Mixing Layer. A spatially developing compressible mixing layer is studied through DNS 3940. The mixing layer, initially in a laminar state, is characterized by a thin layer between two free streams with distinct velocities but uniform density and pressure. The dimensionless velocities of the upper stream U1 and the lower stream U2 are set to 1 and 0.5 respectively. The number and the reference Mach number are as 800 and 2.8. Assuming equal specific heats and temperatures yields a convective Mach number Ma1 Ma2 207. At the inflow boundary, the unperturbed basic inflow profile of the velocity is obtained by solving compressible boundary layer equations. In addition, the inflow is forced by 3D unstable waves, which calculated from linear stability theory, LST. The compressible Stokes equations are numerically solved using a finite difference solver. The nonlinear terms are discretized using a fifth-order weighted essentially non-oscillatory WNO scheme. The viscous terms are discretized using a sixth-order central difference scheme. Temporal advancement of the equations is achieved using a third-order method. The computational domain is as 0542202, where 202, with and representing the most unstable wave numbers from linear stability analysis. The grid sizes are 4160, 350, and 256 along the x, y, and z directions, respectively. Qualitative evidence shows that localized 3D waves travel coherently with vortex structures during the early transition stage. Figure 121 is an oblique view of the 3D flow structures, which displays the growth and metamorphosis of both disturbance waves, represented by the positive conditioned normal velocity field V, and vortical structures, identified by the second invariant of the velocity gradient, from inlet to the downstream regions. Initially, the vortex tubes near the inlet boundary are primarily in a two-dimensional form and rapidly become wavy due to the mode resonance of the oblique waves. Then the wavy vortex filaments either lift up or sweep down and are stretched into staggered-shaped vortices as they are convected downstream. The vortices further deform into hairpin-shaped vortices and finally break up into smaller-scale structures. Spatial distribution of the perturbation waves and vortices 39. Reproduced with permission from JL and ZL, existence and characteristics of soliton-like coherent structures in a transitional mixing layer. Fluids 37, 71704, 2025. Copyright 2025 AIP Publishing. 146 Jet flow. The wave structures in incompressible circular jets and their relationship to turbulence generation and evolution is investigated with DNS41, utilizing the OpenFOAM open-source software for the solution. By comparing the simulation results with experimental data from the literature, the average velocity distribution along the symmetry axis and velocity distributions at various cross-sections are compared, providing preliminary validation of the numerical simulation results, which align with the basic characteristics of circular jets. Next, for the three-dimensional flow field obtained from the numerical simulation, material line and surface tracking methods are employed to observe the evolution of flow structures. The combination of material line evolution and three-dimensional velocity field maps reveals that the generation of three-dimensional wave packets is closely linked to the presence of high-speed streaks. Furthermore, through material surface tracking on full circular pipe surface or local circular arc segment, the entire evolution process of one or more three-dimensional wave packets is depicted in greater detail, as shown in Fig. 1.22. For the wave phenomena observed on the material surfaces, the maximum correlation point method is used to measure the phase speed of the waves. The measured wave speed is then compared with the local flow velocity. After measuring the wave speeds of all three-dimensional waves within the high-speed flow region, it is found that the wave speed is consistently lower than the flow velocity, ranging from 60% to 90% of the flow velocity. This result is consistent with the soliton theory observed in early experiments on boundary layers in flat plate flows. Evolution of the material surface over time, a three-dimensional plot, B planar projection using radial displacement for color coding, which clearly shows the generation and propagation of the waves. Reproduced with permission from Professor QD 41 from State Key Laboratory for Turbulence and Complex Systems, College of Engineering, Peking University through Personal Communication in 2025. 147 Pipe flow. In the study by Wu al. 42, DNS is performed on a puff in the pipe flow at various numbers, Ray. Approaches are employed to examine the early-stage structures. The formation of low-speed streaks, LSSs, and the lift-up of 3D waves upstream of the puff are observed in a pipe flow using timeline visualizations. The hairpin structure surrounding relatively strong 3D waves is identified using the instantaneous vorticity deviation, IVD, criterion in an instantaneous flow field. The formation of vortices consistently follows 3D waves, with a spatial delay determined by the amplitude of the waves. Simulations at various numbers are performed to investigate their influence on these physical processes. Timelines initiated at Z18 R09 and 02 for Ray 2200. The ending time is 1342. Reproduced with permission from Py Wu, DW, XY, and CB Lay, three-dimensional wave structure within the puff of pipe flow. Fluids 37-2, 24125, 2025. Copyright 2025 AIP Publishing. The gradient of the axial mean velocity profile near the pipe wall increases as ray rises. The gradient of the axial mean velocity profile near the pipe wall increases as ray rises. B. Turbulence generation consistently occurs at the upstream front of a puff or slug in the pipe flow. Turbulence generation consistently occurs at the upstream front of a puff or slug in the pipe flow. C. For Ray 2200, 3D waves are generated during the early stages of the puff, as shown in Fig. 1.23. These waves are associated with regions of high vorticity. As a 3D wave propagates downstream, vorticity accumulates, leading to the formation of vortices. For Ray 2200, 3D waves are generated during the early stages of the puff, as shown in Fig. 1.23. These waves are associated with regions of high vorticity. As a 3D wave propagates downstream, vorticity accumulates, leading to the formation of vortices. D. When the amplitude of a 3D wave is sufficiently large and sustained, a high shear layer forms at its edges. This high shear layer results in the development of vortices on both sides of the 3D wave. When the amplitude of a 3D wave is sufficiently large and sustained, a high shear layer forms at its edges. This high shear layer results in the development of vortices on both sides of the 3D wave. E. The 3D wave lifts away from the near-wall region, and the upward movement of fluid creates a low-speed streak upstream of the 3D wave, observable in most timeline figures, AG. Fig. 1.23. Twisting timelines on both sides of the 3D waves. The 3D wave serves as the initial structures responsible for turbulence generation at the upstream front of pipe flow. Low-speed streaks consist of several 3D waves, which generate high shear layers and vortices, destabilizing the flow and contributing to turbulence within the pipe. The flow transitions to turbulence more rapidly at higher Ray due to the enhanced energy extraction and increased instability. While the patterns of the upstream front vary slightly across different Ray values, the fundamental physical process of turbulence generation remains qualitatively consistent. The 3D wave lifts away from the near-wall region, and the upward movement of fluid creates a low-speed streak upstream of the 3D wave, observable in most timeline figures, AG. Fig. 1.23. Twisting timelines on both sides of the 3D waves. The 3D wave serves as the initial structures responsible for turbulence generation at the upstream front of pipe flow. Low-speed streaks consist of several 3D waves, which generate high shear layers and vortices, destabilizing the flow and contributing to turbulence within the pipe. The flow transitions to turbulence more rapidly at higher Ray due to the enhanced energy extraction and increased instability. While the patterns of the upstream front vary slightly across different Ray values, the fundamental physical process of turbulence generation remains qualitatively consistent. 1.5 Further discussion on SCS. The hairpin vortex model by in 1952-33. Reproduced with permission from T in 50, Festschrift in Ed. By H. W. plus Wiesbaden 1955. 5562. Copyright 1955 Springer Nature. Low-speed streaks in turbulent boundary layer 34. Reproduced with permission from S.J., W.C., F.A., and P.W., the structure of turbulent boundary layers, J. Fluid Mech. 34, 741, 773, 1967. Copyright 1967, Cambridge University Press. Periodic turbulent bursting in the K-type transition. Reproduced with permission from C.B. Lay and J.Z. Wu, transition in wall-bounded flows. Mech. Rev. 61.3, 30802, 2008. Copyright 2008 American Society of Mechanical Engineers, ASME. A still image with video 16, periodic bursting phenomena due to the behavior of the SCS during K-type transition. Video 1.6 is available from the electronic supplementary material ESM-LE Video 1.6.4. A still image with Video 1.7, a shadow forms on the upper side of the SCS. Video 1.7 is available from the electronic supplementary material ESM-LE Video 1.7.4. Several SCSs appear on the left side of each streak, totally 10 streaks, 48. In fact, there are several SCSs inside each streak, and each SCS induces a vortex on the right side of the streak. The streak formation and the mechanism for that the SCS induces the vortex are the same as that described by Lei and Wu 1. Reproduced with permission from P. Experiments on oblique transition in wall-bounded shear flows. D. Thesis, KTH Royal Institute of Technology, Department of Mechanics, Stockholm, 1998. 2 turbulent production channels, arrows PP1 and PP2, in K-type transition by Lei and Wu 1. Each streak is composed of several SCSs. On the left side of each streak, several SCSs can be seen clearly, totally 2 streaks. Reproduced with permission from C.B. Lei and J.Z. Wu, transition in wall-bounded flows. Mech. Rev. 61.3, 30802, 2008. Copyright 2008 American Society of Mechanical Engineers, ASME. The SCS is closely related to the low-speed streaks pattern observed near the wall. Figure 130 shows the streak formation in the near-wall region during K-transition 1. Several SCSs appear on the left side of the streak. In other words, the streak is composed of several SCSs. In fact, the streak shown in Fig. 1.29 is the same as that in Fig. 1.3. The streak is also composed of several SCSs. 5051 emphasized the importance of oblique waves and their breakdown in turbulence generation, underscoring the role of paired oblique waves. In Flow al. 52 noted the importance of oblique waves and attributed turbulent spot formation to oblique wave breakdown. Their experiments vividly depicted the evolution of multiple streaks, but primarily emphasized oblique wave breakdown while neglecting the internal structure of streaks. As a result, they missed the opportunity to identify the SCS. Experiments like highlighted oblique wave breakdown. Currently, we cannot provide explanations on their behalf. However, it is important to emphasize that localized three-dimensional waves, SCS, and oblique waves are fundamentally distinct phenomena. Essentially, the streaks observed in their experiments are consistent with 34 streaks. His remarks on streak importance were unequivocal, and the observed three-dimensional structures from oblique wave breakdown may have represented the growth of SCS amplitudes within streaks. Simply attributing turbulent spot formation to oblique wave breakdown oversimplifies the phenomenon. Until Li 26 demonstrated that streaks are composed of SCSs, the central role of the SCS remained underappreciated. While oblique waves are undeniably significant, the SCS remains the primary mechanism of turbulence generation. This underscores our recent efforts to experimentally validate the generation of the SCS through oblique wave interactions 4-6. Although evidence of 2 oblique waves producing the SCS has been found in limited experiments, this mechanism remains underexplored. The 2019 Review 2 collated and analyzed literature on the SCS, garnering approximately 150 positive citations, including recognition from some peer experts who praised its depth and comprehensiveness. Al. 53, even comparing our work to the seminal works of and Rist al. 54 al. 55 Wu 56. Among overlooked classics is al. 52 experimental work on flow turbulence, which stands as one of the finest depictions of turbulent spot evolution to date. They provided a clear depiction of the evolution of multiple streaks. However, their focus on oblique wave breakdown and neglect of streak internal structures cost them the opportunity to identify the SCS. Let us revisit Hama's seminal work, as Hama was the first to identify the vortex structure, a fact worth reiterating. Hama's studies, particularly the three-dimensional S-wave pocket 1257, largely align with the interpretations of 52 and 50. These researchers were undoubtedly aware of the importance of three-dimensional waves. However, the waves they described were not localized three-dimensional waves. Crucially, a single three-dimensional oblique wave cannot produce what we define as the SCS. For the localized three-dimensional waves, the concept of localized is fundamental to this distinction. Why do we believe that the SCS better represents the essence of these three-dimensional waves? To answer this, we must revisit its definition of bursting, which underscores the SCS as the dominant mechanism in turbulence bursts. In naturally occurring turbulence, the spatiotemporal characteristics of bursts vary with the conditions of the incoming flow, often manifesting as localized phenomena. Unlike artificially induced transitions, where the SCS aligns uniformly into low-speed streaks, natural turbulence bursts may occur sequentially along the flow direction, forming streaks due to their similar numbers. These structures may also appear as isolated events at different locations and times. Thus, referring to these three-dimensional waves as SCS is more appropriate, as it captures their localized and inherently transient nature. 1.6 New Direction of Turbulence Research. One of the hallmarks of a significant scientific discovery lies in its ability to elucidate phenomena previously unexplained, resolve long-standing challenges, or at least provide solutions and insights toward addressing them. As the saying goes, a craftsman who wishes to do his work well must first sharpen his tools. At a minimum, the experimental methods and data processing techniques we have improved and developed during the course of SCS research offer valuable references for future studies. For instance, the improved hydrogen bubble method used in Fig. 1.5 Side view of the flow field provides a clearer representation of turbulence bursts. Similarly, the timelines and material surfaces we have developed 2029 and utilized allow for the distinction between wave and vortex structures. These advancements represent some of the most critical aspects of fluid mechanics research, where even minor adjustments can open up entirely new frontiers in the field. The figure is the left part of Fig. 1.29 by 48. Believed that the arrow V point out the streak breakdown. In fact, arrow V point out vortices, and each vortex is induced by each SCS instead of the streak breakdown. Reproduced with permission from P, experiments on oblique transition in wall-bounded shear flows. D. Thesis, KTH Royal Institute of Technology, Department of Mechanics, Stockholm, 1998. It is imperative to explore new perspectives. For example, Al. 58 noted the concept of transition without the formation of turbulent spots, and these profound statements can be succinctly explained if the SCS is understood as the primary driver of turbulence generation. The formation of turbulent spots is not a requisite process for the onset of turbulence. In water tunnels or wind tunnels with low turbulence level, K-type transition typically involves the interaction of a fundamental wave with two three-dimensional oblique waves, leading to the formation of the SCS. The instability of the SCS gives rise to vortices, while secondary instability of the SCS results in secondary closed vortex. The interplay between the vortices and the secondary closed vortex generates the chain of ring vortices, whose breakup and dissipation lead to turbulence without any intermediate formation of turbulent spots. Thus, turbulent spots are not essential for the initiation of turbulence. As illustrated in Fig. 1.3, only two independent turbulent production channels are present, each completing the entire process of turbulence generation without the emergence of turbulent spots. In flow fields with higher turbulence level, more turbulent production channels arise, distributed across various locations. The temporal and spatial overlap of SCS formation in these channels, i.e., especially those originating early at the center near the leading edge, facilitates the emergence of vortices downstream. The superposition of the SCS and related vortices results in the formation of turbulent spots, as elaborated in our recent publications 31-32. Recently, Spanish scholar 59 recently demonstrated that streaks are not required for the maintenance of wall-bounded turbulence. Streaks are also not necessary for turbulence generation. To understand this, it is essential to revisit how streaks are formed. In controlled transition scenarios where the imposed conditions are periodic, SCSs are typically generated periodically at the same locations, leading to the formation of streaks, Figs. 1.29 and 131. In contrast, during natural transition or within turbulent boundary layers, the generation of the SCS depends on initial conditions. If the initial conditions are analogous to those in controlled transitions, multiple instances of the SCS may be produced at adjacent moments in the same location, resulting in the formation of streaks. However, if only a single SCS is generated at a given location, it will evolve independently to produce turbulence without forming a streak. Let us consider another issue. Some scholars are deeply invested in studying fluctuations in the outer layer of turbulent boundary layers, which in essence is also a misnomer. Turbulence itself is inherently unsteady, characterized by the rise and fall of different structures over time and space. The spatiotemporal variability of its boundary is fundamentally a straightforward phenomenon. Yet it is perplexing that significant time and effort have been spent investigating this matter. Essentially, the generation of the SCS depends on initial conditions, and where the SCS arises, the boundary layer thickness evolves and convex downstream with it. This problem, if it even exists, is a minor one. Drag reduction is a long-standing theme. However, the issue of turbulent drag, particularly turbulent skin friction, deserves more attention. Research efforts aimed at reducing drag in boundary layers have become an enduring pursuit, with generations of researchers following in one another's footsteps. However, without a clear understanding of the mechanisms underlying turbulent drag formation, much of this research has been aimless. While there are a few successful cases, most of studies have been inconclusive. Fundamentally, the primary contributor to turbulent drag is the SCS. As illustrated in Fig. 1.4, the SCS obstructs flow, and its contribution to skin friction is qualitatively significant. From the perspective of its convection velocity, the SCS convex downstream at approximately 0.6 to 0.8 times the velocity, occupying the entire bottom layer of the boundary layer. During the evolution of the SCS in this region, from a laminar velocity profile to a turbulent one, it contributes significantly to drag. This is because the bottom layer of the boundary layer contains no other flow structures. The SCS alone dominates it. Therefore, the SCS is the principal contributor to turbulent skin friction. To reduce drag, it is clear that the properties of the SCS must be altered. This is the core of drag reduction, and it explains why progress in reducing turbulent skin friction has been so limited. The intrinsic soliton wave nature of the SCS makes altering its properties a physically challenging task. The issue of turbulence remains unavoidable. Fundamentally, turbulence is not a well-defined problem as it lacks a precise definition. Therefore, the solution to turbulence is itself a misnomer. However, by concretizing the turbulence problem, we can approach it more meaningfully. Specifically, we focus on the generation and development of boundary layer turbulence. This discussion can be divided into three levels: understanding the physical process, theoretical prediction, and control and utilization. The first level involves understanding the generation and development of boundary layer turbulence. Using current theoretical calculations and experimental methods, it is possible to achieve a comprehensive understanding of these processes. Existing DNS can also effectively capture the major processes involved in the generation and development of boundary layer turbulence. In this sense, the first-level problem, i.e., the process of boundary layer turbulence generation and development, can be resolved. Similarly, for other specific flow-related problems, current methodologies can provide solutions. The second and third levels, i.e., predictive theories and the control and utilization of turbulence, are in principle achievable in the foreseeable future. It is worth noting that in 2004, traveling waves were discovered in a pipe flow 60, which are essentially the same physical structure as SCS. Since 2004, the term traveling wave has also been used in boundary layer research, though this will not be discussed here. The primary reason is that we discovered the SCS 9 years earlier than the identification of traveling waves, and our discovery established a self-contained system. Competing interests. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. C.B. Lai, J.Z. Wu. Mech. Rev. 61-3, 30802, 2008. Org 10111512909605. 2. C.B. Lai, XY. Fluids 3111, 111301, 2019. Org 10106315121810. 3. J. Waves and Fluids, Cambridge University Press, 1978. 4. C.B. Lai in IUTAM Symposium on Data Assimilation in Fluid Flow, Beijing, China, 2124-2024. Invited talk. 5. C.R. Yang and P.Y. Wu, C.B. Lai in the 26th International Conference of the Theoretical and Applied Mechanics, ICTAM 2024, Korea 2530-2024. 6. C.R. Yang Z.H. C.B. Lai. Fluids 37-2, 21714, 2025. Org 10106350258057. 7. C.B. Lai in IUTAM Symposium Potsdam, Nonlinear Instability of Flows Springer, NY, USA, July 26-31, 1993, IUTAM Symposia. Invited talk. 8. Y.S. Rev. Fluid Mech. 26-411, 1994. 9. C.B. Lai in IUTAM Symposium on Nonlinear Instability and Transition in Three-Dimensional Boundary Layers, Manchester, UK, July 17-20, 1995. Invited talk. 10. C.B. Lai. A 247-6, 397, 1998. Org 101016S0375960-198005829. 11. PSKD LM J Fluid Mech. 12-1-1-1962. Org 101017S0022-112062000014. 12. Fr. Hama J in Proceeding of 1963 Heat Transfer and Fluid Mechanics Institute, University Press, Alto, CA 1963, 7793. 13. YSOS FT Smith J Fluid Mech. 251, 273, 1993 net. 14. S. Bake HHYS. J. Mech. B. Fluids 19-1-1-2000. Org 101016S0997754600001084. 15. C.B. Lai. Rev. E62-3, 3659-2000. Org 101103, Rev. E62-3659. 16. MVAT Bull. IM. Soj. 39-1-1994. 17. Oida D. J. Fluid Mech. 52, 393, 1971. Org 101017 S0022 1120 71002635 net. 18. T. Rev. Fluid Mech. 21, 487, 1988. Org 101146 201010188002 19. MESW J Fluid Mech. 207, 97, 1989. Org 101017 S0022 1120890025 xnet. 20. XYCB Lay X CR Smith PF Linden J Fluid Mech. 890 A11 2020. Org 10101720200107. 21. XYCB Lay CR Smith JW PF Linden J Fluid Mech. 903 A6 2020. Org 10101720200617. 22. CB Lay ZX YSVI VV Exp. Fluids 28-3 243 2000. Org 101007 S003480050384. 23. AMU Hydrodynamic Instability and Transition to Turbulence, Fluid Mechanics and its Applications. 100 Springer Netherlands Dordrecht 2012. DOI Org 1010079789400742 742376. 24. CB Lay S Exp. Fluids 33 354 2001. Org 101007 S003480000200. 25. CB Lay RQ Lay J. 8 N55 2007. Org 101080146852406009251163. 26. CB Lay SY in Transition and Turbulence Control, Lecture Notes Series, Institute for Mathematical Sciences, National University of Singapore. 8 Guide. By M. Gad L. H. M. World Scientific 2005. 3985. Org 1011429789 81270089600002. 27. SC Lay Interface Focus 5 20,150,020 2015. Org 10109820150020. 28 WJ Numerical Simulations of Boundary Layer Transition by Combined Compact Difference Methods. D. Thesis, Technological University, Singapore 2013. 29. XYDW CB Lay CR Smith PF Linden J Fluid Mech. 914 A4 2021. Org 10101720201023. 30. XY in IUTAM Special Event, Fluid Mechanics in the Spirit of GK Online, March 29-31, 2021. 31. NYD CB Lay CR Smith J Fluid Mech. 1008 A37 2025. Org 10101720252202. 32. NBY CB Lay. Fluids 37-2, 21703 2025. Org 10106350254741. 33. T. In Proceedings of the Second Midwestern Conference on Fluid Mechanics, Engineering Series. 21 Ohio State University, Columbus, Ohio, March 17-19, 1952, Engineering Series. 21. 119. 34. SJWC FA PW J Fluid Mech. 34 741 1967. Org 101017 S0022 112067001740. 35. BH Sun. Fluids 36, 8, 83,616, 2024. Org 10106350225957. 36. XYA PF Linden J Fluid Mech. 947 A30 2022. Org 10101720222588. 37. LHS CQJO WQSU. Fluids 37-1, 14,111 2025. Org 10106350251193. 38. BLTA. Fluids 35-3, 33,307 2023. Org 10106350140841. 39. JLZL. Fluids 37-7, 71,704 2025. Org 10106350277845. 40 JL XYZL J Fluid Mech. 2025. Accepted. 41. ZYYT Yang QD. Detection and analysis of soliton-like coherent structures in free-round jet flow. Fluids 37-8, 85,174, 2025. Org 10106350280336. 42. PY Wu DW XY CB Lay. Fluids 37-2, 24,125, 2025. Org 10106350255936. 43. AP Software X6 124 2017. 44. JO Turbulence 2nd. Hill 1975. 45. RE Falco. Trans. 336, 1641, 103, 1991. Org 10109, 8199100069. 46. C.R. Smith, J.D.A. Walker, in Fluid Vortices, Fluid Mechanics and its Applications. 30. By S.I. Green, Springer, Netherlands, Dordrecht, 1995. 230-5289. DOI Org 101007978940 11024906. 47. J. Joe R.J. Adrian S. T.M. J. Fluid Mech. 387, 353, 1999. Org 101017S0022 112099004667XNet. 48P Experiments on Oblique Transition in Wall-Bounded Shear Flows. D. Thesis KTH Royal Institute of Technology, Department of Mechanics, Stockholm 1998. 49. R.J. Adrian C.D. J. Fluid Mech. 422 1-2000 net. 50. IJHRE J. Fluid Mech. 92-3, 505 1979. Org 101017S0022 112079000756. 51. AYI J Fluid Mech. 198 1989. Org 101017S0022 112089000017. 52. DRSE-MF J Fluid Mech. 121 487 1982. 53. MDDJOKAD. Fluids 33-9, 94,115 2021. Org 10106350063948. 54. YXWTG URIST J Fluid Mech. 945 A20 2022. Org 1010172022 55. KRSWP SE J Fluid Mech. 953, A34, 2022. Org 10101720222962. 56. XH Wu. Rev. Fluid Mech. 5545, 2023. Org 101146 Fluid 1207200021813. 57. FR Hama JD Long JCJ. 28-4, 388, 1957. Org 10106311722760. 58. YSVVVY Fluid Dyne. 12-3, 383, 1977. 59. JJ Fluid Mech. 945 R3, 2022. Org 10101720222572. 60. BCWH Van J FTM HBH RRF Science 305 5690 1594 2004. Org 101126 Science 1100393. 2. New features of soliton-like coherent structures and the formation of vortices. Abstract. This work investigates, mainly by means of flow visualization, experimental aspects of nonlinear stages, aiming at the K-regime in boundary layer transition. Soliton-like coherent structures, CS solitons, and a new physical mechanism for the formation of vortices along the border of the CS soliton are found. Supplementary information. The online version contains supplementary material available at org 10100 7978 980 195 244 This chapter is reproduced with permission from C.B. Lay, New Features of CS Solitons and the Formation of Vortices. A 247-6, 397-4, 1998. Copyright 1998. The content of the article has been slightly revised. At that time, the author cannot distinguish the differences between the SCS discovered by Lee and the CS solitons discovered by. Lee thought that the SCS might be the same as the CS solitons. In fact, they are different flow structures. 2.1 Introduction. The transition to turbulence in boundary layer flows within a low disturbance environment usually starts from the instability of the basic state. Since the works of the CS solitons, soliton-like coherent structures, have attracted increasing attention of researchers. Soliton properties of spikes were found experimentally by N1 and later studied in more detail 2.5. CS solitons are generated by the transitional flow in the K-regime of the boundary layer transition in the so-called peak position, and they move further downstream up to the region where nearly developed turbulent flow is observed. And 6.7 proposed that coherent structures observed in the turbulent boundary layer also represent CS solitons or patterns close to them. Attempts to apply the soliton solution of the Benjamin equation to the experimental investigation of large amplitude disturbance were undertaken in 8.9. In the works of Lee 10.19, both CS solitons and vortex rings were clearly visualized by means of the hydrogen bubble timeline technique and hot film measurements. Flow structures were obtained by and. In the present work, some new features of CS solitons and the physical process of vortex formation are studied. 2.2 Experimental facilities. Orientation and nomenclature of bubble wires and camera view. 2.3 Experimental results. 2.3 Visualization of the CS solitons. Side view of the CS solitons, rate 11 see Fig. 2.1c. A DT0, 0.66, 1, 1.3s respectively. Plan view of traces of CS solitons, rate 139. This figure has restoration processing. Velocity disturbance distributions inside CS solitons, in the x direction, B in the y direction. Figure 2.2 shows the formation of the CS solitons and their propagation. In Fig. 2.2b, C, arrows and B indicate the side views of the CS soliton. shows the direction of the flow inside the CS soliton, and the other two arrows indicate the flow direction outside of the CS soliton. See Fig. 2.2d. The typical spike-like structures quickly move away from the wall during their formation. Here a spike is used to indicate the peak of the CS solitons in the y direction, rather than to indicate the measurement results in the x direction as before. In fact, the coherent structures can generate spikes in 3 dimensions. The hydrogen bubble line is placed at x80 from the leading edge of the flat plate, and continuous electric current is used to generate hydrogen bubble lines. The soliton-like coherent structures acquire a rather conservative form, which remains essentially unchanged even further downstream, x80 110. The clear evolution inside the CS solitons are shown in the figure from x80 to 110. At the later stage of transition and the nearly developed turbulent flow, Fig. 2.2d, the traces of CS solitons are also visualized very clearly. The basic frames of the CS solitons are similar at all stages from their formation to turbulence. CS solitons were considered to be the toroidal vortex by end. In addition to the features described by 9, some new ones are found here. 1. The CS soliton appears from the near wall region to the edge of the boundary layer. In other words, the CS solitons suggested by Al are just the head parts of the whole structure. 2. They exhibit wave-like properties rather than vortices. Can the CS solitons have generated the spikes on time traces of U component of the velocity of 30 years ago and in recent years of? In fact, both the vorticity wave and the vortices may induce the spikes. At the initial stage of 3-dimensional structure formation, the spikes are generated by CS solitons. It is also very difficult to divide the boundary layer structures into 2 layers. CS solitons in the outer part of the boundary layer and the tooth-like structures in the near wall region, by means of the measurement results, as was suggested by Al. The formation of CS solitons may be due to the wave resonance suggested by 9. The direct visual results show that the CS solitons appear in the whole boundary layer from the near wall region to the external edge of the boundary layer. The plan view of the CS solitons is shown in Fig. 2.3. The structures often appear in the downstream low-speed streak region in a developed turbulent boundary layer. From the development of these structures, the CS solitons at all stages appear downstream the low-speed region, which is the same as measured by Al. 20 and Al. This important fact will be discussed in the next section in detail. The typical velocity distributions of the disturbance inside the CS solitons in both x and y directions are shown in Fig. 2.4. They are calculated directly by means of the hydrogen bubble timeline technique. The results are very similar to our recent experiments in the controlled transition conducted in Beijing 21. Detailed information of side view for the vortex, a formation along the borders of the CS solitons B, rate 1, see Fig. 2.1c, and the corresponding schematic side view diagrams. A T1.66 SBT 1.75 SCT 2.0, 8 SDT 2.16 SE schematic side view diagram for A, the vortex starts to form. F schematic side view diagram for B, the vortex grows. G schematic side view diagram for C, the vortex almost forms. H schematic side view diagram for E, the vortex completely forms. Sketch of the formation. A formation of CS solitons B, formation of high shear layer C, formation of vortex. The evolution of the SCS and the vortex extracted from video 1.2, which is available from the electronic supplementary material ESM-LE video 124. A formation of the SCS. B, formation of the vortex. C, growth of the SCS and the vortex. D, further evolution of the vortex. 232, formation of the high shear layers and vortices along the borders of the CS solitons. Where and when do high shear layers and the vortices appear? This answer was not very clear before. Figure 2.5a shows that high shear layers appear along the borders of the CS solitons. Figure 2.5b, dice shows the formation of vortices and their evolution. It is clear that the flow directions inside and outside the CS solitons are opposite. The flow inside the CS solitons is lifted up, and the flow outside is swept down. See Fig. 2.2d. Schematic side view sketches provided in Fig. 2.5e H illustrate the gradual formation and evolution of the vortex around the soliton-like coherent structure, SCS. Why the high shear layer is formed along the borders of the CS solitons is not very difficult to understand. Two reasons are most important: mass conservation and the low convection velocity of the CS solitons, 0.809 of the free stream speed. On the right-hand side of the CS solitons, the flow is swept down from the free stream to the right-hand side of the CS solitons. In order to conserve the mass, the flows above the CS solitons would sweep down to their right side. Otherwise, a vacuum region would be formed. For the same reasons, the fluid in the middle region of the boundary layer upstream would sweep the CS solitons down to the near wall region too. As a result, the near wall region, one spikes on the time traces of the high shear layers, and the vortices should form along the borders of the CS solitons. Figure 2.6 Asai sketches this mechanism. In the external edge of boundary layer and near wall region, one spikes on the time traces of the U component of the velocity are generated by the CS soliton. In the middle of the boundary layer, both the CS soliton and the two sides of the vortex may generate 3 spikes. We also created video 1.2, see Fig. 1.11 to illustrate the evolution process of the SCS and the vortex, as shown in Fig. 2.7. Initially, the SCS forms and lifts up the fluid flow inside it. To conserve mass, the adjacent fluid must sweep down to compensate for the ascending motion, as illustrated by the yellow arrows in Fig. 2.7 As the SCS grows, the upward and downward motions generate increasingly stronger shear, forming a high shear layer, and then a vortex occurs as shown in Fig. 2.7b with further development of the SCS in Fig. 2.7c, the vortex intensifies correspondingly. Ultimately, the amplitude of the SCS saturates and decays while the vortex continues to grow, as demonstrated in Fig. 2.7d Visualization of SCSs. A plan view of the SCSs are in B, rate 1.3, B a hypothesized LSS model consisting of 2 connected SCSs and schematic plan views of the LSS model at 2 different heights. 2.3.3 Relation between CS solitons and turbulent spots. As described by N23, kidney-shaped wave pockets then develop in the elongated delta-shaped turbulent spots by nonlinear effects. In fact, a turbulent spot is a 3-dimensional wave structure. The velocity figures of the turbulent spot given by N24 show it can generate the spike on the time trace of the velocity. Since the observation of CS solitons, there exists confusion with regard to CS solitons, vortices, and the turbulent spots. The reason for the confusion is twofold. Firstly, the above physical mechanism for the formation of vortices was not clear until recently. Secondly, the full field information in the transitional process cannot be obtained by means of the hot wire measurement. The results shown in Fig. 2.8 gives a clear picture of the CS soliton and its bounded vortex. The CS solitons and the vortices are not always separately to be seen as in Fig. 2.8 of the structures enclosed by the diamond-shaped cyan-dashed line are in B in Fig. 2.8 are the CS solitons SCS, and the vortices around the SCSs are marked by the red arrows. Sometimes CS solitons and their bounded vortices are considered as turbulent spots at a later stage of transition, or the origins of the CS solitons are considered as turbulent spots at an initial stage of the transition. The difference between the 3 kinds of structures has been discussed in more detail in 1921. Figure 2.8b represents a schematic model of the low-speed streak, LSS, which assumes several contiguous localized 3D waves, SCS, align in the direction and constitute the LSS. These localized 3D waves propagate from left to right and move away from the wall gradually. The hypothesized plan view of the LSS model near the wall at height 1 appears an interconnected domain composed of the two waves, which indicates a continuous structure. Away from the wall at height 2, isolated wave patterns appear as separate diamond-shaped structures, corresponding to an B in Fig. 2.8 A 2-4 conclusion. In general, the high shear layer and vortices mainly appear along the borders of the CS solitons. The CS soliton is considered as a wave-like structure or vorticity wave, which is a kind of coherent structure in both transitional and nearly developed turbulent boundary layers. We would like to thank Ms. C.Y. and Mr. Y.T. for their help. The author also thanks Professor Dr. S. and Professor V.V., who have influenced this work through stimulating discussions. Competing interests. This work was supported by the NSF of China, the NSFC International No. 196,11,121,904, the JX Foundation, and the Russian Foundation for Basic Research, No. 96,01001C. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. Appendix. Figure 2.8 shows the plan view of the CS solitons and vortex B in the controlled transition 1921. This result is similar to the result obtained in the natural transition. It helps us to understand the difference between CS solitons, vortices, and turbulent spot. Formerly, both CS solitons and vortices were not very easy to visualize separately as in Fig. 2.8. Therefore, they were not very easy to distinguish from the time traces of the velocity and the visualization. References. 1. VIYS. SIBA. SSSR, Sir. 1865-1988. 2. VIYS in Proc. Scientific and Seminar on Ship Hydrodynamics, 19th session. 2. Bulgarian Ship Hydrodynamics Center, Varna, Bulgaria 16-1990. 2. 99-199-10. 3. VIYS in eddy structure identification in free turbulent shear flows. IUTAM. Poitiers Springer, Poitiers, France, 1214-1992. XI31, XI39. 4. VIYS in nonlinear instability of flows, EID. By S.B. W.R.C. Phillips, D.T. Valentine, Springer, Berlin, Heidelberg, 1993. 6980. DOI org 10100 7978 3642 850 8444. 5. YSVV VY Fluid Dyne. 12-3 383 1977. 6. YSOS in Boundary Layer Transition and Control, Proceedings of the Conference, United Kingdom, 8/21 April 1991. 3452. 7. YSOS FT Smith J Fluid Mech. 251 273 1993 net. 8. YS in Nonlinear Instability of Flows, EID. By S.B. W.R.C. Phillips, D.T. Valentine, Springer, Berlin, Heidelberg, 1993. 2151. 9. YS. Rev. Fluid Mech. 26-411, 1994. 10. CB Lay QX SF in Nonlinear Instability of Flows. IDA. By S.B. W.R.C. Phillips, D.T. Valentine Springer, Berlin, Heidelberg, 1993, 213231. 11. C.B. Lay in IUTAM Symposium on Nonlinear Instability and Transition in Three-Dimensional Boundary Layers, Manchester, UK, 1720, July 1995. 12. C.B. Lay S.F. Exp. Fluids 193, 143, 1995. Org 101007 BF00, 189702. 13. C.B. Lay, Transition Research on Accelerating Boundary Layer. D. Thesis, Beijing University of Aeronautics and Astronautics, 1995. 14. C.B. Lai Chen. Tech. 163, 1995. 15. C.B. Lai Chen. Tech. 2 137, 1996. 16. C.B. Lai Chen. Tech. 2 145, 1996. 17. C.B. Lay in Proc. 10th National. On Hydrodynamics, Ocean Press, 1996. 18. C.B. Lay in Conf. Of X. Fluid Mech. Moscow, 1997. 19. C.B. Lai Chen. J. Arrow. Measurement 12-8, 1998. 20. PSKD LM J. Fluid Mech. 12-1-1, 1962. Org 101017 S0022 112062000014. 21. C. Lay YV GVV. J. Heat Fluid Mech. To be published. 22. Fr. Hama J. in Proc. Heat Transfer and Fluid Mech. Press A. CA 1963. 7793. 23. WO LSG J. Fluid Mech. 14-1, 59, 1962 net. 24 GB, PS, Contributions on the Mechanics of Boundary Layer Transition. Tech. Note NACA TN 3489, National Advisory Committee for Aeronautics, Washington, 1955. 3. Possible Universal Transitional Scenario in a Flat Plate Boundary Layer, Measurement and Visualization. Abstract. An experimental investigation was undertaken to reveal the characteristic flow structure in the regime of nonlinear boundary layer instability and onset of turbulence. A controlled wave was introduced into a two-dimensional boundary layer over a flat plate to study the growth and evolution of the controlled disturbances using both hot film measurements and an improved hydrogen bubble visualization technique. The results demonstrate that the actual breakdown of the laminar boundary layer and the breakdown of the vortices do not imply the immediate onset of turbulence. Rather, the onset occurs later with the breakdown of the long streaks. Therefore, an alternative transitional scenario was developed. This chapter is reproduced with permission from C.B. Lay, Possible Universal Transitional Scenario in a Flat Plate Boundary Layer, Measurement and Visualization. Rev. E623, 3659 3670 2000. Copyright 2000 American Physical Society. The content of the article has been slightly revised. Starting from this article, a formal distinction is established between the SCS discovered by Lay and the CS solitons by. The K-type transition experiments conducted at Peking University confirmed that the SCS is different from the CS solitons. 3.1 Introduction. The problem of the onset of turbulence in a flat plate boundary layer has attracted the attention of investigators for more than a century. Despite its complexity, interest in the laminar, turbulent transition has increased during the past few decades owing to its importance in both fundamental and applied aspects of classic physics. Boundary layer flow has been a canonical flow. Theoretical and experimental studies have been discussed in various books and reviews 1-8. The first physical study of laminar flow breakdown in the boundary layer was carried out by N9. This work served as the experimental basis for the concept of hydrodynamic instability and provided the first details of the nonlinear mechanisms of transition. The fundamental experiments conducted by Al. 10 and Al. 11 laid the foundation for many ideas about the nature of laminar boundary layer breakdown. Al. 11 studied the mechanisms of laminar flow breakdown in detail and critically evaluated the applicability of a series of theoretical models and hypotheses. Almost simultaneously, Al. 12 investigated three-dimensional flow velocity and vorticity in the same transitional region. Hama and 13 complemented hot wire measurements with visual observations using the hydrogen bubble flow visualization technique. Based on these observations, White 14 summarized the K regime. K stands for of boundary layer transition as the following sequential stages: I. Stable flows, unstable waves, formation of three-dimensional waves and vortices, breakdown of vortices, V. Formation of turbulent spots, developed turbulence. The famous experiments of and 10 and Al. 11 showed that the nonlinear wave development at the later stages further downstream is characterized by the appearance of powerful flashes of disturbances on velocity oscilloscope traces in the form of narrow spikes. Extremely careful experiments performed by Al. 15 revealed the appearance of multiple spikes, which are due to high-frequency flow structures, on the velocity oscilloscope traces. See also 8. Williams Al. 16 found that a vortex loop forms just before the spike formation in the K transition. Al. 17 experimentally studied the local secondary instability and compared the observations with linear calculations. And 18 numerically and experimentally investigated the process of the formation of peaks and valleys. They found a threshold character for the K transition in a plane channel flow. 8 suggested some new hypotheses concerning the formation of spikes and multiple spikes on the time traces. The structures of the boundary layer flows are considered to be composed of tooth-like structures in the near-wall region, spike solitons at the external edge of the boundary layer, and chaotic flows in the middle of the boundary layer. Very recently, Li al. 1924 and al. 25 have proposed a new scenario for transition, which involves the formation of both low and high-frequency vortices. This paper concentrates on experimental observations in the later stage of the nonlinear breakdown of the boundary layer in controlled transition, and presents direct evidence toward establishing a possible universal transitional scenario in boundary layers. 3.2 Experimental Techniques and Facilities. Experimental setup. The disturbance generator, wave generator, was a slit in the plate of length 150 mm and width 1 on the working side, mounted at a distance x 200 mm from the leading edge of the plate. Water was periodically pumped in and out of the slit at a frequency of 2. A water tank was connected to both the slit and 2 tubes on opposite sides of the plate. A loudspeaker was set on top of a round barrel with the 2 tubes mounted on the outer edge of the barrel's bottom. The instability waves had a frequency of 2 and an amplitude of 1.6% of the free stream velocity U0 as set by the voltage input to the loudspeaker. The development of the disturbances in the boundary layer and the structure of the mean flow were investigated with a hot wire anemometer made by company. The hot films were made by TSI. The sensitive part of the probe was less than 2 mm long. Experimental data were acquired from X2 48700. At each measured point, 3 characteristics were measured: the mean value of the velocity U0 and the amplitude and phase of the disturbance velocity, U, filtered at the fundamental frequency. The distributions of these characteristics were measured along the direction X, normal to the plate Y, and along the direction Z. Along with these measurements, an improved hydrogen bubble technique was used to carefully visualize the flow structures. Complete visualization of the flow structures was accomplished by placing the hydrogen bubble wire at positions from X 250-700 min steps of 50, and from Y 0.56 min steps of 0.25. This technique made it possible to clearly visualize the spatial flow structures. As shown in Fig. 3.2, different sections in the plan view were obtained by placing the electrode wire at different Y positions. If the flow was laminar, several hydrogen bubble planes were obtained. Fig. 3.2. Continuous plan views of hydrogen bubbles were produced to visualize the flow structures. Visualization techniques. Profiles at different X positions without excitation. 3.3 main flow without excitation. Boundary layer displacement thickness variation with coordinate without excitation. Velocity profile with excitation. 3.4 experimental results. 3.4.1 preliminary results with excitation. Y profile of the wave amplitudes at 250. Y profile of the wave amplitudes at 400. Amplitude distributions in the X direction. Black evolution of TS wave and formation of chain of ring vortices. A plan view of TS wave T and its evolution to structure C black D and small-scale vortices A and B. The figure is 1/4/3 of the actual size, and the flow is from left to right for equal to 215. Schematic side view, relation between the vortex and the ring vortex. See schematic side view, formation of chain of ring vortices. In the initial region with relatively low local numbers, the instability wave IA. Boundary layer usually called a typical wave, and its evolution can be seen from left to right in Fig. 3.9. As the figure clearly shows, the TS wave develops into a structure and later into several secondary high-frequency vortices. In this and all the following photos, the flow is from left to right. This figure shows the typical characteristics of the K regime of boundary layer transition as obtained in 11. Black and Fig. 3.9. The dashed blue circle marks the detachment of a ring vortex from the tip of the vortex C, as indicated in Fig. 3.9b. Two ring vortices A and B appear at nearly the same time from another vortex D, as shown in Fig. 3.9c, which signifies the simultaneous emergence of several ring vortices, leading to the formation of chain of ring vortices. 3.4.2 Organized flow structures. Flow structures in different X, Z plan views, 1/3/8 scale of the actual photos at equal to 350 and the corresponding schematic diagrams. A black plan view of low speed streak A, long streak B, and structures at Y 0.5. B black plan view of butterfly-like structure B and structure C at Y1. C black plan view of butterfly-like structure B and structure C at Y1.5. D black plan view of structure C at Y2. Schematic side view diagram of a hypothesized LSS model composed of 4 contiguous SCSs. F schematic plan view of the LSS model in E at height 1, manifested as a continuous structure. G schematic plan view of the LSS model in E at height 2, manifested as isolated patterns. H schematic plan view of the LSS model in E at height 3, presenting SCSs and vortices. H schematic plan view of the LSS model in E at height 4, presenting vortices only. Figure 310 shows the X, Z sectional flow structures at different Y positions from the near wall region to the outer layer, the corresponding schematic diagrams to explain the physical mechanism in them. If the hydrogen bubble wire is placed very near the wall, a low-speed streak appears A in the peak position, see Fig. 3.1 Us. In addition to the low-speed streaks, a long streak B is present at the peak positions, and several pairs appear on both sides of the long streak. Each pair contains 2 structures which are nearly symmetric on the 2 sides of the long streak. Placing the hydrogen bubble wire close to the wall at Y1 reveals a butterfly-like structure Fig. 3.1b. The head of the structure disappears and a new structure B is present at the center of the peak position. When the hydrogen bubble wire is shifted slightly to Y1.5, both a structure C and a structure B within the structure appear Fig. 3.1c. The structure Fig. 3.1d is clearly seen when the wire is at Y2. Almost all the structures visualized here appear at the frequency of 2. Black figure 310E shows a hypothesized model for low-speed streak, LSS, which assumes that the LSS is composed of several soliton-like coherent structures, SCSs. Each SCS is accompanied by a vortex evolving from the high shear layer. With the lifting of the SCS, the fluid flow inside it also lifts up. According to mass conservation, the fluid around the SCS will sweep down to compensate for the lifting motion, and then the strong shear due to the upward and downward motions forms a distinct high shear layer, which subsequently evolves into the vortex. Figure 310F shows the schematic plan view of the LSS model at different heights. Near the wall at height 1, as shown in Fig. 3.1F, the plan view appears as a continuous structure, in which the 4 SCSs combine to form an interconnected domain, corresponding to the long streak B in Fig. 3.1 at higher location height 2 in Fig. 3.1G, the plan view as isolated wave patterns, which is similar to the structure B in Fig. 3.1B, further away from the wall at height 3, as shown in Fig. 3.1H, only a minor portion of the SCSs remains discernible, whereas the vortex structures manifest with pronounced clarity. At height 4 in Fig. 3.1I, only vortices can be visualized. The LSS model recognized the LSS as the combination of the SCSs, which explains the reason that the flow manifests distinct structures at different heights and demonstrates the relation between the LSS, the SCSs, and the vortices. In Fig. 3.1, the long streak appears nearly at the center of the butterfly-like structure, peak positions 10, and part of its structure appears on both sides of the long streak at a frequency of 2. The observations show that the structure cannot induce these kinds of structures. A closed vortex is formed as a result of 2 structures connecting with a low-speed streak on their left-hand side in the near-wall region and connecting with a structure on their right-hand side. The structure is part of the total flow structure. The structure lies at the center of the butterfly-like structure, Fig. 3.1. The structure was referred to as soliton-like coherent structures, CS solitons, in our previous works 1923. The time interval must be selected carefully to obtain the different photos in Fig. 3.1. Time interval should be decreased to as short as possible since all the structures periodically appear, and since the distance between 2 neighboring Y positions is short, 0.25 m. At first, we chose which photos taken at 2 neighboring Y positions are in the same period. Then we chose the best fit 2 photos with the smallest time interval from the total of 24 photos, the camera frames per second, and the period of the flow structures was 0.5 s, so 12 frames could be obtained per period at each Y position. The minimum time interval was less than 0.04 s. In addition, the time interval was also related to other information to have the desired fundamental wave far from the peak position appear at all stages of the transition. With a proper time interval, visual observations could be used to redraw the flow structures, as in Li 1920. In the appendix, the redrawn picture will be given. The side view of similar structures was obtained by Hama and more than 36 years ago 13, as discussed in Li al. 1923. 343. The CS solitons and their properties. Amplitudes of disturbances of CS solitons at different Y positions, x 400 m. Oscilloscope traces of velocity disturbances at different x for Y 1.6. Curves 1 and 2 are for 248 and 350 m respectively. The timescale of one period is 0.5 s. Oscilloscope traces of velocity disturbances at various distances from the wall at x 400. Curves 12, 18 for Y 0.22, 0.49, 0.75, 1, 1.25, 1.88, 2.27, 3.24, 3.62, 4, 4.5, 4.99, 5.5, 6, 7, 7.5, 8.12, and 10.25. The curves from 1 to 8 are divided by 8 so they can fit in the figure. Oscilloscope traces of velocity disturbances at different x for Y 0.6. Curves 12-7 are for x 300, 350, 400, 450, 500, 550, and 600. Figure 312 shows the time traces measured at 248 and 350 for the same y1.6. At x 248, additional spikes are not found because both the structure and the low speed streak have not yet appeared. The fluctuations in curve 1 are generated by just the CS solitons. At 350, additional spikes are found in both the peak and the valley on the time trace as indicated by the arrows. Additional spikes in the peak on the time traces were generated by vortices, and the spikes in the valley by the low speed streaks. The main fluctuations in this curve were still generated by the CS solitons called structures in Fig. 3.1. The measured results curve 2 in Fig. 3.12 and the observations in Fig. 3.1 agree very well with each other qualitatively. Figure 313 shows a typical set of oscilloscope traces measured at various distances from the wall. Two main features can be seen. The main fluctuations are present not only in the near wall region, but also in the outer layer. The phases of these fluctuations are nearly the same at all y locations. Because the fluctuation amplitudes in the near wall region, y3.24 are much greater than those in the outer layer, the scales of the fluctuations for the first 8 positions were reduced so that all the time traces would fit in the same figure. Referring to Figs 3.1, 3.12, and 3.13, the spatial scales of the CS solitons in the x direction are greater than that of the leading edge of the structures at the peak position. Since the low-frequency fluctuations have the same frequencies at different y positions, the low-frequency, high-amplitude fluctuations in Fig. 3.13 were generated by the CS solitons at different y positions. In fact, the additional spikes in Fig. 3.13 occurred in curve 2 of Fig. 3.12. The reason the spikes are not clearly observed is that the scale used in the figure is not good for seeing these additional spikes. Figure 314 shows the evolution of the CS solitons from their formation to their later stage before breakdown. The main shapes of the CS solitons remain practically unchanged further downstream. In summary, experimental results show the following. The CS solitons are present not only in the near wall region, but also near the external part of the boundary layer. The CS solitons are present not only in the near wall region, but also near the external part of the boundary layer. The main features of the CS solitons remain unchanged before their breakdown, which is why they are called CS solitons. The main features of the CS solitons remain unchanged before their breakdown, which is why they are called CS solitons. 344 Chain of vortices. Black plan view of formation of a chain of vortices, 1/4 scale from the actual size from 420, y1. A black plan view of first vortex formation, a T0s. B black plan view of second vortex formation, B, T0.166s. C black plan view of third vortex formation, C, T0.291s. The explanation of this figure is the same as that in Fig. 3.9. Oscilloscope traces of velocity disturbances at various distances from the wall at x 450. Arrows indicate the multiple spikes generated by a chain of vortices. Curves 1 to 4 for y0.61, 1, 1.8, and 3.4. In Fig. 3.17, positive and negative spikes are periodically induced by the chain of vortices and the closed vortex. Each vortex induces one positive spike and one negative spike, i.e., a spike pair. 5 spike pairs appeared, which is one more than the number of vortices, implying that the closed vortex generates an extra spike pair. The spike on the left-hand side of the pair on the measured time traces is generated by the right-hand side of the part of the vortex in the visualization figure and vice versa. Because the plane spanned by a vortex is inclined at more than 45 black to the wall, the time traces of the velocity at a fixed y position do not show all the pairs. The inclination angle of the vortex plane can be seen clearly from the video and movie taken simultaneously during a test. In the near-wall region, the spike corresponds to the right side of the time traces in one period because the local velocity is only affected by the left part of the vortices. The spike pairs appear on the time traces in the central layer Fig. 3.16 and 8. Generally, the main features relevant to the chain of vortices are as follows. The chain of vortices appears with the same frequency as the fundamental wave. The chain of vortices appears with the same frequency as the fundamental wave. The traces show single, double, or more spikes which influence the flow in the near-wall region and the flow near the external part of the boundary layer. These kinds of multiple spikes are generated by the chain of vortices and the closed vortex. The traces show single, double, or more spikes which influence the flow in the near-wall region and the flow near the external part of the boundary layer. These kinds of multiple spikes are generated by the chain of vortices and the closed vortex. Oscilloscope traces of velocity disturbances at various distances from the wall at x 500. Curves 1 to 4 for y 0.22, 2.1, 3.2, and 8. Black plan view of formation of one of the vortices in a chain of vortices, 150 scale from the actual size, the corresponding schematic sketches. A black plan view of leading edge of the vortex, 1 inside the structure C, T0S. B black plan view of the vortex, 1 separated from a CS soliton B, T12S. C black plan view, vortex is formed T16S. D black plan view, vortex is clearly shown T14S. E black plan view, vortex stretched T13S. Schematic plan view diagram for B, initial status of the ring vortex. G schematic plan view diagram for C, formation of the ring vortex. H schematic plan view diagram for D, stretching and deformation of the ring vortex. I schematic plan view diagram for E, further development of the ring vortex. The time interval between the neighboring vortices in the chain is equal to that of the neighboring spikes on the measured time traces. The vortices separate from the tip of the structure, and the two legs of the vortex are reconnected into a closed vortex by the law of vortex dynamics Fig. 3.15. This physical process, which is similar to the self-induction effects observed by Al. 26, was suggested by 25. The present experiments show that a vortex in the chain is not directly separated from the tip of the structure during the vortex formation. Figure 3.18 shows the formation process of a vortex, which demonstrates that this structure is directly separated from the border of a CS soliton inside the butterfly-like structure. Figure 3.18 shows the leading edge of the vortex, 1 inside the structure C. Figure 3.18b shows that the head part of the vortex is separated from the border of the CS soliton B, and this structure appears in the mouth of the structure. Unfortunately, the photos are not as clear as the moving process seen in the video. A typical vortex shape is formed 1 Fig. 3.18c, and the vortex is accelerated by the structure and its rotational speed increases. In Fig. 3.18d, the vortex 1 moves downstream at a higher convection velocity than that of both the structure and the CS soliton. Black to illustrate the process described by Fig. 3.18 more clearly, schematic diagrams for Fig. 3.18b, are shown in Fig. 3.18f, respectively. The ring vortex forms and detaches from the vortex. As it grows, the ring vortex stretches and deforms gradually. Black similarly in Fig. 3.18c, the dashed circles marked as A1, A2, and A3 also indicate the evolution of another ring vortex from the tip of the vortex D. A1 represents the formation of the ring vortex, which further lifts up and stretches as indicated by A2 and finally develops as shown by A3. The angle between the plate and the plane spanned by the vortex increases, 70, as clearly shown in the movie and video. This process appears at a frequency of 2. The physical mechanism for the formation of the rest of the vortices is not yet clear. They probably result from a physical mechanism similar to the vortex. However, further experimental evidence is necessary. The shaped part of the vortex suggested by N27 is the first vortex observed here. Falco 28 identified a relatively small-scale coherent motion, which he labeled a typical eddy. He proposed that the eddy was the direct result of in the outer region of a smoke-filled, turbulent boundary layer. Li al. 2123 found a chain of vortices in the outer region of the turbulent boundary layer, which are very similar to that in Fig. 3.15. The effect of the formation of the vortex ring along the border of the CS Soliton in natural transition 1920 should also be analyzed. The high shear layers and the closed vortex formation along the borders of the CS Solitons occur due to mass conservation and the low convection speed of the CS Solitons. On the right-hand side of the CS Soliton, the flow sweeps down from the free stream to the right side of the CS Soliton. The flow upstream of the CS Soliton would sweep down to the near-wall region on the left-hand side of the CS Soliton. Consequently, the high shear layer and the closed vortex form along the border of the CS Soliton. As mentioned by Li 1920, the vortex ring formation process along the border of the CS Soliton can be seen in the work by Hama al. 13. An improved experimental study for understanding the physical process, which provided further information on the formation of the chain of vortices, will be discussed in a later publication. The mechanism for a vortex to separate from a CS soliton is not yet clear. The separation may occur because the vortex convection velocity is greater than the velocity of the CS soliton because of a lift-up effect such as the bursting processes in a turbulent boundary layer flow 29. Additional evidence is needed to confirm this preliminary explanation. An additional experiment for understanding the rapid increase of the angle between the flat plate and the vortex plane is currently. More detailed information is necessary to better understand the present results. Because different parts of a flow structure and different flow structures appear in different ways depending on where the hydrogen bubble wire is mounted, more attention should be paid to check the flow structures and determine their properties. Several plan view sections or side view sections must be used to produce clear three-dimensional flow structures. 345 long streaks in a transitional boundary layer. Plan view of a long streak B and its breakdown, 1/3/8 scale from the actual size and the schematic sketch. A plan view of long streak. B plan view of breakdown. See schematic side view and plan view diagrams for the breakdown of the long streak in B. There exists the effects of the ring vortex. Black plan view from a CS soliton A1 to a part of a long streak, black A2, 1/3/8 scale from the actual size. A Y1, BY 1.5. Schematic side view, relation between the SCS, the LSS, and the vortex. D schematic plan view of SCSs at height 1. Isolated waves. E schematic plan view of SCSs at height 2, SCSs and vortices. Black plan view of a complete long streak is composed of several CS solitons, 1/40 scale from the actual size. Schematic side view, relation between the SCS and the LSS. See schematic plan view of SCSs at height 1, SCSs and vortices. 3.5 Discussion. 351 Differences between a CS soliton, a chain of vortices, and a turbulent spot. The CS solitons observed by Li 19 differ from those by N 8 and the turbulent spot. Both the visual results and the experimental measurements demonstrate the existence of the CS solitons from the initial stage of three-dimensional structure formation, X260, to the later stage of transition and the onset of turbulence. According to the definition of, and his coworkers 8, the CS solitons they observed are the outer part of the chain of vortices. It is well known that a turbulent spot appears at the later stage of transition 14. Very recently, 8 suggested a transitional path without turbulent spot transition. Some other researchers suggested another path called direct to turbulent spot transition, or bypass transition 33-34. The controversy has two aspects. The formation process for the CS solitons and the vortices has not been clearly visualized in 19. The main differences between the turbulent spot and the CS soliton have not been clearly distinguished. A regular turbulent spot represents the features of localized turbulence involving several structures 35. The turbulent spot is very similar to several CS solitons and their bounded vortices at the same Z position, but quite different from that in bypass or direct to turbulent spot transition. Actually, the turbulent spot suggested in bypass or direct to turbulent spot transition is the CS soliton observed in this work. There was only one peak position in the experiment conducted by Al. 8, but there were 4 peak positions in the experiment by Al. 11. A real turbulent spot such as in 35 cannot form, but the CS solitons exist, see Fig. 30 and 8. The lack of detailed visualized results in the initial stage of this structure in previous publications has prevented proper interpretation of the CS solitons in the early stage of transition. Because of the importance of this structure in a transitional boundary layer, and since it was found in other flow fields, this structure can be assumed to be one of the coherent structures in transitional and nearly developed turbulent boundary layers. Furthermore, Li 19 proposed that this structure is of a deterministic nature. CS solitons appear at conditions called controlled transition 8-23, direct to turbulent spot transition, or bypass transition 33, 34, and natural transition 19. Our recent studies 21-24 gave a new physical process for the vortex formation along the borders of the CS solitons. In fact, some differences exist between the regular turbulent spot and the structure with the same name in some bypass transition or direct to turbulent spot transition observations. 352 Physical mechanism for the CS soliton formation. Receptivity is defined as the mechanism by which disturbances enter the boundary layer and create the initial conditions for unstable waves. The following discussion considers which kinds of unstable waves can generate the CS solitons in the plan view. The wave-resonant concept has been suggested 8 on the basis of a detailed analysis of experiments by and 36 as well as analysis of the theoretical results by Crack 37 and 38 and 39, 4 and others. The results obtained by and 8 showed that the system of the parametric subharmonic resonance postulated within the framework of the wave resonance concept is actually observed in the K regime of boundary layer breakdown at the stage of spike formation. Simulations of oblique wave interactions in a boundary layer were performed by Al. 40. The simulations showed that oblique wave interaction generates a strong dependent mean flow distortion. No two-dimensional TS waves take part in this process, but CS solitons can generate this kind of strong dependent mean flow distortion. The results of 41 and 42 reveal a honeycomb pattern that is considered to be a direct result of the interaction between oblique shedding vortices and two-dimensional large-scale waves that grow in the far wake. One possible physical reason is that the CS solitons are generated by the interaction between two oblique waves. However, in this work, the CS solitons would have to be generated by the two-dimensional TS waves. A theoretical approach called phase-locked-in by Wu and Stewart 43 showed that two-dimensional TS waves have a catalytic effect on the three-dimensional structure formation. The results in Fig. 3.2 show that the above two effects are quite possible. Some scientists believed that the CS solitons are secondary structures generated by the structures. No direct evidence in Figs. 3.1 and 3.2 showed that the structures were formed before the formation of the CS soliton. The motion pictures from the video and films show that the CS solitons were formed slightly before the structures. This evolution is very similar to the process suggested in 1923. Generally, the CS solitons are proposed to be the direct results of the interaction between two oblique waves, and the two-dimensional TS waves are proposed to have a catalytic effect on their formation. 353 Similarity between transitional and developed turbulent boundary layer. The structural similarity between transitional and developed turbulent boundary layers was first briefly discussed by 44. 8. Discuss the connection between the K breakdown and developed turbulence. The flow structures in developed turbulence obtained in the works of Al. 45 and Thomas Al. 46 are very similar to that by an 8. 3 kinds of coherent structures exist in a transitional boundary layer: the CS solitons, the closed vortices, and the chains of vortices. All 3 structures can also be found in developed turbulent boundary layers 19, 23. Several CS solitons appear in the boundary layer in the form of a long streak in the near wall region, or in the form of a black spot in the outer layer. A closed vortex is not easily seen because of the angle between the vortex plane and the flat plate. Therefore, only part of a closed vortex is normally seen using flow visualization. The chain of vortices, which generate high-frequency fluctuations, is often considered to be chaotic flow structures because no one believes they have periodic features in a developed turbulent boundary layer, including even Falco 28. The localized periodic features of these structures were found in a few studies 19, 23, but not mentioned clearly at that time, because the present transitional boundary layer results had not yet been obtained. Table 3.1 compares the number of the vortices in a chain in transitional and developed turbulent boundary layers. The number of the vortices in a chain associated with a large-scale motion is the same for different experiments, indicating this may be a constant. Note that Hama al. 13 suggested a fourfold cascading breakdown instead of the formation of a chain of vortices, CRV, suggested in the present paper. Number of vortices in one chain associated with a large-scale motion. Sources: Name: Turbulent BL, Transitional BL, Falco 28, Typical eddy, 4, Lay 19, No name, 4, 11, No name, 4, Hama 13, No name, 4, 8, Spike solitons, 4, Present, CRV, 4, 3.6 Conclusions. The present experimental study in a transitional boundary layer reveals a complete flow structure called the butterfly-like structure, which consists of a CS soliton, a closed vortex, and a chain of vortices with small time scales as the basic building blocks. These results provide an improved understanding of the transitional scenario. The experimental observations show that the multiple spikes, which were observed over one period of the fundamental wave in a transitional flat plate boundary layer, were generated by a chain of vortices and a closed vortex. The structure is part of the whole butterfly-like structure, from the stage of the obvious three-dimensional structure formation to nearly developed turbulent flow. Inside the butterfly-like structure, the CS solitons, which were observed by Lee 1923 and referred to as kinks by Hama many years ago 13, are observed here to exist over most of the boundary layer. The observation of the chain of vortices during one period of the fundamental wave can be used to explain the physical process for the formation of the multiple spikes on the time traces measured by end. No exceptional examples of boundary layer flows for both different geometric conditions and different initial flow conditions 29, 30, 33, 49, 50, which have some fundamental conflicts with the present scenario for the onset of turbulence, have been found. Perhaps the bursting process observed by Al. 29 for the onset of turbulence is the real universal transition mechanism for boundary layer flows for different conditions. Actually, the present scenario is an improved version or an interpretation of the bursting process. Redrawn flow structures and their sectional views at different Y positions. A sketch of the flow structure in Fig. 3.1. BAA sectional view, which is similar to Fig. 3.1d. See B-bay sectional view, which is similar to Fig. 3.1c. DC sectional view, which is similar to Fig. 3.1b. ED-day sectional view, which is similar to Fig. 3.1 Competing interests. This project was supported by the Chinese NSF, RFBR under Grant No. 9600100001C Russian Foundation for Basic Research, the KC Foundation, and the Chief Foundation of the Department of Mathematics and Physics of the Chinese NSF for special support. Part of this work was supported by the Isaac Newton Institute for Mathematical Sciences, University of Cambridge. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. We would like to thank CY, YT, Professor Q. D. Wei SKLTR, and XT for their help during our experiments. We also thank Professor Z. M. Jin, Chinese NSF, for his very kind encouragement. Lee is grateful to Professor J. T. Stewart, FRS, UK, Professor M. Gaster, FRS, UK, and Dr. X. Wu, Imperial College, for helpful comments. The suggestions by Professor J. Z. Wu, the University of Tennessee Space Institute, and SKLTR, were very valuable for improving the paper. Professor Wu has helped the author to carefully revise the manuscript. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. Appendix. To further understand the flow structure in Fig. 3.1, a redrawn picture of the sketch of the real three-dimensional flow structure is shown in Fig. 3.22, which was given previously in 19. This figure also gives several sectional plane views, which are very similar to the real plan view flow structures in Fig. 3.1. The side view of the CS solitons and their bounded vortices were clearly described in 19. References: 1AD Wave Interactions and Fluid Flows, Cambridge University Press, 1985. 2VA Sib. Div Publ. In Russian P282, 1987. 3A NAYFEH, in 25th AIAA Aerospace Sciences Meeting, 1987. AIAA Paper 80-70044. 4T. Rev. Fluid Mech. 20-487, 1988. 5 HL Reed, W.S. Rev. Fluid Mech. 21-235, 1989. 6H in Laminar Turbulent Transition, Ed. By D.R. IUTAM Symposium, Springer, Toulouse, France, 11-15-1989. 580-7598. 7L.T.A. Rev. Fluid Mech. 23-495, 1991. 8YS. Rev. Fluid Mech. 26-1-411, 1994. 9GB HK J Rays. Burn. Stand. 38-251, 1947. 10GB PS. Contributions on the Mechanics of Boundary Layer Transition. Tech. Report NACA TR 1289, National Advisory Committee for Aeronautics, Washington, 1956. 11 PS KL J Fluid Mech. 12-1-1962. 12 LS HBR in Proc. 1962 Heat Transfer and Fluid Mechanics Institute, University Press, Alto, CA, 1962. 126. 13 FR Hama J in Proc. 1963 Heat Transfer and Fluid Mechanics Institute, University Press, Alto, CA, 1963. 7793. 14 FM White Viscous Fluid Flow First. Hill, New York, 1974. 15 YS in Laminar Turbulent Transition, Ed. By Dr. IUTAM Symposium, Springer, Toulouse, France, 11/15/1989. 6580. 16 Dr. Williams, H. Fr. Hama, J. Fluid Mech. 149, 179, 1984. 17 M.S. in Laminar Turbulent Transition, Ed. By R. H. IUTAM Symposia, Springer, Stuttgart, Germany, 1622-1979. 3746. 18 M. J. Fluid Mech. 208 1s 1989. 19 C.B. Lay. A 247-6, 397 1998. Org 101016 S0375960 198005829. 20 CB Lay ZX YSVI VV Chin. J. 23-2, 227 1999. Org 1038878J1 006989519990 21 CB Lay S Chin. 97508 2000. Org 101088100919639707. 22 CB Lay S Chin. 178 583 2000. Org 101088025563 07x178014. 23 CB Lay ZX YSVI VV Exp. Fluids 28-3, 243 2000. Org 10107 S0034800500384. 24 CB Lay S Exp. Fluids 33, 354 2001. Org 10107 S0034800000200. 25 VVRYS CB Lay QX in Proc. The International Conference on the Methods of Research, ICMAR 98, Institute of Theoretical and Applied Mechanics, Novosibirsk, Russia, June 29-July 3, 1998. 2429. 26 P.A.J. Fluids 29-4, 955 1986. Org 101063186560. 27 CF PJ AIAJ 61, 29 1968. Org 102514344337. 28 RE Falco. Fluids 2010 S124 1977. Org 10106318611721. 29 SJ WC FA PW J Fluid Mech. 34 741 1967. Org 101017 S002 112067001740. 30 QX J Fluid Mech. 215 101 1990. Org 101017 S002 112090002579. 31 ER ARC. 15-2 97 1959. 32 AR ARC. 15-6 503 1959. 33 MV E in Laminar Turbulent Transition ED. By Dr. IUTAM Symposium, Springer, Toulouse, France, 11/15/1989. 329. 34J in 18th Fluid Dynamics and in Lasers Conference, American Institute of Aeronautics and Astronautics, Cincinnati, OH, USA, 1985. AIAA Paper 851695. 10.251461985165. 35 M. Van Dyke, An Album of Fluid Motion First. Parabolic Press, California, 1982. 36 YS VY J Fluid Mech. 138 209 1984. 37 A.D J Fluid Mech. 52 393 1971. Org 101017 S002 112071002635. 38 MB II J Fluid Mech. 252, 449, 1993. 39 IHAN. Fluids 22-5, 805, 1979. Org 101063186260. 40 RD CL CL. Fluid Dyne. 46 271, 1993. Org 101007 BF00 418777. 41 CHK J Fluid Mech. 243 393, 1992. Org 101017 S0022 112092002763. 42 CHK A. Fluids of 57, 1854, 1993. Org 10106318588810. 43 XS Wu PA Stewart J Fluid Mech. 316, 335, 1996. Org 101017 S0022 112096000572. 44 RFs. Fluids 2610, 2807, 1983. Org 10106318640047. 45Y HO in 19th AIAA Fluid Dynamics, Plasma Dynamics and Lasers Conference, American Institute of Aeronautics and Astronautics, Honolulu, HI, USA, Fluid Dynamics and Co-Located Conferences. AIAA Paper 80 712531987. Org 10251461987123. 46 ASW Thomas, WS Bull. IM. Zosian. 26 1252 1981. 47 HT SJ WC J Fluid Mech. 51 133 1971. 48 RF JH J Fluid Mech. 132 87 1983. 49 RE Falco. Trans. R Social. A 336 1641, 103 1991. Org 10109 8199100069. 50 CR Smith SB J Fluid Mech. 129 27 1983. Org 101017 S0022 112083000634. 51 JH J Fluid Mech. 397 119 1999. Org 101017 S0022 112099006138. 4. Flow structures in transitional and turbulent boundary layers. Abstract. The basic problems of transition in both incompressible and compressible boundary layers are reviewed. Flow structures in low-speed transitional and developed turbulent boundary layers are presented, together with almost all of the physical mechanisms that have been proposed for their formation. Comparisons of different descriptions of the same flow structures are discussed as objectively as possible. The importance of basic structure such as soliton-like coherent structure is addressed. For compressible flows, the receptivity and instability of boundary layer are reviewed, including the effect of different parameters on the transition. Finally, the principle of aerodynamic heating of hypersonic boundary layer is presented. This chapter is reproduced under CC BY from CB Lay and XY, flow structures in transitional and turbulent boundary layers. Fluids 3111, 111301, 2019. Copyright 2019 AIP Publishing. The content of the article has been slightly revised, and the section, Flow Structures in a Hypersonic Transition Boundary Layer, has been removed. 4.1 Introduction. Experimental and numerical studies of wall-bounded flows reveal the ubiquitous presence of flow structures, the formation and maintenance of which continue to be fundamental problems in fluid mechanics. There have been many studies and reviews of transition and turbulence in boundary layers 119. In this article, an objective description of incompressible flows is presented, taking account of some viewpoints in previous studies. Compressible flows, in particular hypersonic flows, have been studied for more than 50 years, and a large volume of the literature concerned has been accumulated. The important achievements in this area are reflected in this article. Although previous works have considered most of the aspects of the problem at hand, a number of issues are confronted when examining these works and writing this article. 1. It is not easy for readers to learn or use different names for the same physical structure, and there is a need to avoid possible confusion arising in this situation. 2. It is also very confusing when several different physical explanations have been proposed for the same physical phenomenon. We will discuss why there often exist such disparate interpretations. 3. Some researchers have treated combined patterns as large structures. In general, this approach is a viable one. However, it is important to avoid combining different types of structures into a large one, since this will hamper understanding. 4. Since previous studies and reviews have presented some misleading results, it is necessary to clarify some concepts and some inappropriate formulations. 5. In a compressible boundary layer, typical flow structures such as vortex, three-dimensional wave packet, especially the first mode and second mode instability waves, and the role they play in the transition process have not been well understood. 6. The effect of Mach number, roughness, wall temperature, and other factors on the development of the flow structures require a better and clearer understanding. This article is divided into 2 parts. The first part focuses on the incompressible boundary layer. The general background of different flow structures and the limitation of visualization techniques are reviewed firstly, sect. 4.2 and the structures of incompressible flow are described in detail, sect. 4.3 including experimental and numerical visualization of structures, the similarity between different transition types, the nature of turbulent burst, and a discussion of hairpin packets and similarity between transitional and turbulent boundary layers. The second part focuses on the topic of compressible flows. In sect. 4.4, the receptivity and instability theory in hypersonic flows are first introduced, then the effect of different parameters on the transition is reviewed. The conclusions are given in sect. 4.5. 4.2 General background. Numerous efforts have been devoted to examining the characteristics of the structures and identifying their functions in the onset and production of turbulence 2025. The structures are observed in a wide variety in their shapes and sizes, and there is no current consensus on how they come into being and what is the elemental structure. Before discussing about the essence and relation of the structures, there is a need to give a summary of some suggested flow structures and the visualization limitations. 4.2.1 Summary of suggested flow structures. In an incompressible boundary layer, typical coherent structures include vortices, soliton-like coherent structure SCS, hairpin vortices with their asymmetric and composite variations, pocket structure, typical eddies, high-low speed streaks, vortices, ring-like vortices, turbulent spots, dark spots, very large-scale motions, VLSM, and so on. 13.26.32. A brief introduction on some of these typical structures is given in this section. 4.2.1.1 Hairpin vortices. 33 presented a hypothesis to explain the formation of the vortex. According to this hypothesis, a two-dimensional vortex line in a boundary layer moves away from the wall because of environmental disturbance. Because the velocity away from the wall is higher than that near the wall, the middle part of the vortex line is stretched into a shaped structure, called a vortex. Horseshoe vortices grow outward from the wall with heads inclined downstream at 45, and dimensions proportional to the distance from the wall. Head and 34 presented the flow visualization pictures of vortex. These images suggested strongly that the edge of the layer at reasonably high numbers was composed very largely of smoke-filled features, with smoke-free fissures inclined in the region at a characteristic angle of 40-50 to the surface. Figure 4.1 shows the schematic view of the hairpin vortex geometry at different numbers based on the flow visualization of 34. At high numbers, the hairpin vortex pairs are strongly elongated, while at low numbers they behave as vortex loops with much less elongation. Geometry of horseshoe hairpin vortices at different numbers 29. Reproduced with permission from coherent motions in the turbulent boundary layer. Rev. Fluid Mech. 23 601 639, 1991. Copyright 1991 Annual Reviews. Dual view of a dimarked single hairpin vortex 35. Reproduced with permission from and Smith, the generation and regeneration of single hairpin vortices, J. Fluid Mech. 277, 135 162, 1994. Copyright 1994 Cambridge University Press. Photographs of typical eddies in turbulent boundary layers 36. A 753, B. 21300. Reproduced with permission from Falco, a coherent structure model of the turbulent boundary layer and its ability to predict number dependence, Phil. Trans. R. Soc. A 336, 103 129, 1991. Copyright 1991 Royal Society. A temporal sequence of 4 phases of the evolution of typical eddies, TA, in plan and side views 36. A TE moving over the wall inducing a pair of streaks, B. The TE moving closer to the wall, causing vortices, C. Formation of pocket and primary hairpin vortex, D. Pocket amplification and stretching, inducing the secondary hairpin vortex. Reproduced with permission from Falco, a coherent structure model of the turbulent boundary layer and its ability to predict number dependence, Phil. Trans. R. Soc. A 336, 103 129, 1991. Copyright 1991 Royal Society. 4212 Typical eddies. Falco 37 used simultaneous hot-wire anemometry and flow visualization to show the microscale coherent motions all across the outer region of a boundary layer 38. They were called typical eddies, TEs, and were observed to be strongest when riding along the upstream boundary of large-scale motions, LSMs of O, Fig. 4.3. Falco 37 also suggested that the TEs significantly influenced the LSMs at low numbers. A strong correlation among TEs, ejection sweep behavior, pockets, and hairpin vortices was found in the wall region 3942. TEs were observed to directly create pockets and some of the hairpins near the wall. TEs have a vortex ring-like configuration and evolution, as opposed to an attached hairpin eddy configuration and evolution, Fig. 4.4. At low and moderate numbers, TEs appear to be laminar vortex rings, and thus are viscous-governed. At higher numbers, they have been observed to appear as wavy chord vortex rings. At still higher numbers, such as those characteristic of the atmospheric boundary layer, completely turbulent TE motions have also been observed. The formation and evolution of TEs in a highly perturbed vortical environment strongly govern the shape of these eddies. There are indications that at least 2 mechanisms are involved. Formation could take place by pinch-off and reconnection of hairpins, observed to lift up from the wall. The other likely mechanism is the formation of TEs from an instability of a local region of highly vortical fluid to an applied force, as described by the solutions in 43. These solutions describe the formation of vortex rings in an infinite fluid through the action of an impulsive force on a vortical region. When TEs are observed at the upstream boundary of large-scale motions, they produce the largest fluctuations in the U, V, and signals. Furthermore, in experiments, TEs have been observed to form at the backs of large-scale motions. TE formation results in a contortion of the boundary of a large-scale motion. When a TE forms in the outer part of the layer, it is observed to convect faster than the large-scale motion, and thus it will move toward the front of that motion. The sweep motion described by N44 looks exactly like a TE, and its normal scale is the average TE scale. When TEs emerge from large-scale motions in the logarithmic region, they are generally observed to be convected toward the wall. When TEs move toward the wall, there will be sweep motions. 4213 Pocket structures and hairpin packets. The hairpin vortex packet produced by the simulations in 48. Flow is in the positive x direction. Reproduced with permission from Joe Al. Mechanisms for generating coherent packets of hairpin vortices in channel flow, J fluid mech. 387, 353, 396, 1999. Copyright 1999, Cambridge University Press. Conceptual scenario of nested packets of hairpins aligned coherently in the direction 30. Reproduced with permission from Adrian Al. Vortex organization in the outer region of the turbulent boundary layer, J fluid mech. 422, 154, 2000. Copyright 2000, Cambridge University Press. 4214 Vortices. The SSP Model 51. Reproduced from on a self-sustaining process in shear flows. Fluids 9, 883, 900, 1997. Copyright 1997, AIP Publishing. Conceptual model of the basic structure of quasi-vortices 52. A downstream secondary quasi-vortices, B primary quasi-vortices, C upstream quasi-vortices. Reproduced with permission from Al. The regeneration of quasi-vortices in the near-wall region, JSME J Sir. B40, 257, 264, 1997. Copyright 1997, the Japan Society of Mechanical Engineers. And 52 found that a quasi-flow vortex could induce new flow vortices at its upstream and downstream endpoints, respectively. The direction of rotation of these new flow vortices was opposite to that of the mainstream vortex. The quasi-vortex was regenerated by the mature parent vortex. The rotation of the newborn vortex was opposite to that of the parent, leading to the formation of a zigzag vortex line, see Fig. 4.8. Regeneration could occur at the upstream and downstream ends of the parent vortex. Nominally, wall normal vorticity made the greatest contribution to flow from the parent vortex. The new vortex in the infant stage had grown and was in full development. The stretch of the vorticity itself made a contribution. 4215 Low speed streaks. Low speed streaks 27. Reproduced with permission from Al. The structure of turbulent boundary layers, J fluid mech. 30, 741, 773, 1967. Copyright 1967, Cambridge University Press. Smith al. 28. Explain the origin of low-speed streaks in a systematic manner. A predominant feature of near-wall turbulent flow is the persistence of low-speed streaks having a typical scaled spacing of 100 viscous lengths over a range of numbers 55. It has long been generally believed that low-speed streaks are key to the bursting process and are caused by long counter-rotating vortices, c. e.g. 5659. The key experiments of and Smith 60 and in Smith 35 supported the belief. In their experiments, the fluid was injected at the surface through a narrow slot with a limited amount of control. The injected fluid interacted with the boundary layer to form an unstable boundary layer that rolled up to form a single hairpin vortex. Hun and Walker 61 used the linearized Stokes equations in generalized optimal perturbation theory to predict the spacing of the near-wall streaks. The slow fluid was pushed away from the wall by the wall normal motion, and then streaks were generated. However, not all experimental or numerical results support the belief that low-speed streaks are caused by vortices. And 62 examined two conceptual frameworks and concluded that the lift-up of the mean profile in combination with shear stress and viscous diffusion together dictated the formation of the streaky pattern. In a transitional boundary layer, Lee and Wu 13 found that several 3D wave structures constituted low-speed streaks, thus concluded that low-speed streaks are formed by soliton-like coherent structures. 4216 Turbulent spots. A turbulent spot in a laminar boundary layer 63, 64 provides an example of an isolated coherent structure that may have important properties in common with structures in a fully developed turbulent boundary layer. Coles and Barker 65 took this point of view when making some exploratory measurements of flow in a turbulent spot. The turbulent spot was a combination of horseshoe and hairpin vortices, 66. When several spots at different locations merge, the flow develops into a turbulent boundary layer, 63. Previous research on artificially generated turbulent spots utilized mostly point measurement methods and visualization techniques, with the latter indicating that hairpin structures evolved at the trailing edge of the spot, 67, and wavy streaks close to the wall, 68. Modeling of unsteady events such as sweeps and ejections in the coherent substructures, observed by hot wire anemometry, required the application of Taylor's hypothesis. Some basic features of the spots have been measured and have been described in terms of spreading angle, shape, altitude, growth, and linear instability in the vicinity of the spots 69, 70. Further results 71 have been achieved by conditional averaging, which gives valuable information on the overall structure and also of the convection velocity and inclination angle, about 45 of the substructures. It has been concluded that the growth characteristics and shape of spots in flat-plate boundary layer flows depend on the number, pressure gradient, surface roughness, turbulence level, disturbance amplitude, and wavelength 72. Perry al. 73 observed an obvious turbulent spot structure with flow visualization. They believed it to be mainly composed of a set of vortices. Recent numerical simulations of turbulent spots and cascades of evolving hairpin vortices have achieved considerable accuracy and spatial resolution. They are in substantial agreement with experimental observations 74-75. The substructures of turbulent spots seem to maintain self-similarity in all cases and have been recognized as low and high-speed streaks and hairpin-like vortices very similar to those appearing in fully developed turbulent boundary layers, but more orderly, 76. Similar behavior was reported by Al. 77, who applied the time-resolved stereo PIV technique to turbulent spots, namely, puffs in a pipe flow, where the ensemble of substructures also consisted of a limited number of streaks near the wall and hairpin-like vortices organizing the turbulent flow exchange. More quantitative information is still desired about the instantaneous topology of the substructures within the spot that are mainly responsible for the turbulent mixing process. Some aspects of this process have been elucidated with the help of experiments performed with PIV in conjunction with liquid crystal thermography 78, providing additional insight into the heat transfer characteristics of spots, which are associated with the local topology of the substructures. 4217 Very large-scale coherent motion and superstructures. Very large-scale coherent motion, VLSM, is concentrated in the logarithmic region of the turbulent boundary layer, with lengths of about 10 outer scales, e.g. the radius of a circular tube or the thickness of the boundary layer, 79. And Adrian 80 observed very large-scale coherent structures in developed turbulent flow, which were characterized by flow velocity fluctuations in the extremely long wavelength region. They suggested that the VLSM was composed of turbulent bulges or packets of hairpin vortices. And 81 found extremely long wavelength positive-negative velocity fluctuations in the boundary layer, called superstructures. And Adrian 82 confirmed the existence of VLSM in pipe flow, channel flow, and boundary layers by an energy spectrum analysis. Al. 83 confirmed that VLSM had a correction effect on the near-wall small-scale structure, and that the larger the number, the stronger was the correction effect. And Nichols 85 observed VLSM by PIV and a conditional averaging treatment in a boundary layer experiment. The coherent structures were composed of a long high or low speed streak and a surrounding hairpin vortex. 422 Visualization techniques and their limitation. Flow visualization is one of the most important methods in the study of transition and turbulence. A good flow visualization technique can find and confirm the existence of a wide variety of flow structures, such as pockets 39, soliton-like coherent structures 86, vortices 26, hairpin vortices 34, vortex packets 30, typical eddies 46, low-speed streaks 27, chains of ring-like vortices 7, and secondary closed vortices 87. Other important observations are those of turbulent spots 63 and very large-scale motions 80, composed of several different structures. Such visualizations of fluid structure, especially in the 1980s, played an essential role in the study of coherent structures in turbulent flow. Without these achievements, it is hard to imagine how modern fluid mechanics would have developed. Modern flow visualization methods are based on developments in optics. Progress in laser technology has brought revolutionary changes to flow visualization. Measurement techniques like particle image, PIV, have been combined with advanced data processing technology. The observation of nested packets of hairpin vortices is a good example of what can be achieved with these approaches. Traditional flow visualization provides qualitative observations of flow structures with pictures or videos acquired in experiments. However, to a large extent, flow visualization fails to recognize the exact status of flow structures. Although regions of highly concentrated vorticity can be clearly recognized from dye visualization, in regions with lower vorticity concentration, which are less accessible to dyed liquid, flow structures are difficult to distinguish. For example, flow visualization loses effectiveness in distinguishing certain wave structures in the near-wall region, especially in their initial stage when vorticity has not become concentrated. Even if these near-wall wave structures are captured by flow visualization, they are likely to be neglected owing to a lack of clarity in their appearance. It is for this reason that near-wall wave structures have received limited attention in studies of the evolution of turbulence. Hama and 26 discovered a kink from visualization and believed it to be a flow structure that subsequently transformed into a vortex. However, such a kink is in fact a geometric structure rather than a flow structure. Hama and were misled by the two-dimensional visualization images. Falco 39 discovered pocket structures and a pair of streaks along the sides of the pocket in boundary layers, but the long streak pair is more likely to be vortices, which is not the same as the low-speed streak observed in 88. In general, the incompleteness and vagueness of traditional visualization have tended to result in a limited understanding of the observations obtained. Advances in experimental methods and numerical simulations in recent years have led to considerable progress in flow visualization. PIV, especially three-dimensional time-resolved PIV 89, and computational fluid dynamics CFD 90, with the associated data processing techniques have provided detailed data on flow fields and have allowed penetrating insight into flow structures. The experimental or numerical data acquired can be utilized to reconstruct flow fields. Unfortunately, however, the results are often misunderstood. For example, in the case of a simple vortex ring with varying vorticity distribution in a boundary layer, neither PIV nor CFD can describe its complete evolution. 423 Objective criteria for flow structures. Main conclusions on the generation mechanism of hairpins. Authors. Date. Mechanism. 33. 1952. 2D vortex tube lifted by a disturbance. Adrian Al. 30. 2000. Low-speed region lift-up generates hairpin. And Smith 60, 88. 1987. Low-speed streak generates hairpin. Smith L. 28. 1991. Self-induction. Lay 86. 1998. SCS generates vortex. The main mechanisms proposed for the generation of hairpin vortices are listed in Table 4.1. Except for theory, which was derived from a hypothesis, these proposals were based directly on experimental results. Both Falco's experiment 45 and that of and Smith 60, 88 led to the conclusion that hairpin vortices were generated by a more fundamental structure. The question then naturally arises whether it is possible that the pocket mechanism proposed by Falco and the low-speed streak proposed by and Smith are in fact the same phenomenon. Before answering this question, it must be clarified that the long streak generated near the pocket proposed by Falco 36 is a vortex rather than a low-speed streak as discussed in this article, since it can be clearly observed from Falco's visualization image that the long streak is probably a rotating vortex structure. On this basis, we might as well make the somewhat daring speculation that the low-speed streak is composed of waves, and that the pocket is a local three-dimensional wave. The fact that the low-speed streak is composed of waves has been, by a study of boundary layer transition 13. Therefore, Falco's conclusion can be readily unified with that of and Smith, as long as the pocket is considered as a local three-dimensional wave. How the fluid inside the boundary layer moves away from the wall is also discussed in Sect. 4.3. 4.3 Flow structures in incompressible flow. 4.3.1 Soliton-like coherent structures. A sequence of visualization of the formation of an SCS A and a vortex B13. A T0 BT0 plus 16S, CT0 plus 13S. The different stages of development of the SCS and the vortex can also be seen. Reproduced with permission from Lei and Wu, transition in wall-bounded flows. Mecca, Rev. 61 30802, 2008. Copyright 2008 American Society of Mechanical Engineers. Visualization of a secondary closed vortex and SCS's 13. Reproduced with permission from Lei and Wu, transition in wall-bounded flows. Mecca, Rev. 61 30802, 2008. Copyright 2008 American Society of Mechanical Engineers. Velocity distribution at different heights in the y direction inside an SCS 13. In the figure 0U12, where x0 is the initial location where disturbances are forced. Reproduced with permission from Lei and Wu, transition in wall-bounded flows. Mecca, Rev. 61 30802, 2008. Copyright 2008 American Society of Mechanical Engineers. One of the key issues in transition is the mechanism by which the low-frequency structures turn into the high-frequency ones. Before work 91, it was widely accepted that a vortex breaks down into high-frequency vortices. In his measurements using fine hot wires, spotted periodic spikes in the hot wire signals, which he claimed to represent soliton structures not equivalent to SCS. His work also showed that the spikes were reflections in the signals of velocity fluctuations of vortex chains 7. He adopted Crow's long-wave instability to explain the process of formation of a vortex chain originating from the two parallel legs of a vortex. In collaboration with, was able to obtain the first visualization of a chain of ring vortices. By decreasing the distance between each visualization plane from 0.5 to 0.25, further experiments showed that secondary closed vortices appeared near the middle of the vortex Fig. 4.11. Such secondary closed vortices are generated by an instability along the boundary of the SCS due to the velocity in the y direction of the SCS, which can reach 8-10% U Fig. 4.12. Lifetime of observed coherent structures in a transitional boundary layer 13. Reproduced with permission from Lei and Wu, transition in wall-bounded flows. Mecca, Rev. 61 30802, 2008. Copyright 2008 American Society of Mechanical Engineers. Flow structure. PID B. DSCS. 1.28. 3.15. 1.93. 7.36. Vortex. 1.4. 2.3. 0.85. 4.1. Vortex. 2. 2.9. 0.9. 5.7. Secondary closed vortex. 2.1. 2.55. 0.45. 1.5. Chain of ring vortices. 2.5. 3.18. 0.68. 4.1. A dimensionless position at which the structure appears, normalized with the distance from the blow-suction slot to the leading edge. B. Dimensionless position at which the structure disappears. C. Dimensionless distance that the structure exists. D. Duration of the structure normalized with the period of T, S wave. 4 types of wall-bounded turbulence generation. K-type, L92. Interaction between a 2D primary wave and an oblique wave with the same frequency. N-type, 7. Based on three-wave resonance mechanism 93 and the secondary instability mechanism proposed by 94, subharmonic oscillations, which are resonances of a 2D wave and a pair of half-frequency oblique waves with the same wave angle but opposite directions. O-type, and 5. The transition due to a pair of oblique waves with the same angle but in opposite directions. Bypass. When the degree of turbulence in the free stream is high, boundary layer transitions can be observed without an increase in waves but generally with low-speed streaks. 432 similar flow structures in K-type, N-type, and O-type transitions. Visualization for K-type transition. Left column, plan view, right column, side view. The tracers are colored by the wall normal distances. The red triangle denotes the place where the skin friction coefficient starts to increase. The visualizations are shown in both plan and side views in Fig. 4.13. In a plan view, the passive tracers initially lie in the plane Y5 and are released at T0. In a side view, the passive tracers initially lie in the plane Z0 and then are also released at T0. The period of the seated TS wave is about 120. The SCS and the structure and high shear layer can be clearly observed in both the plan and side views. Deformation of material surfaces at T2T initiated at Y171 and 5.89, a K-type, B-O-type, C N-type 99. Reproduced with permission from Enlay, numerical simulation of K, N, and origine boundary layer transition at early nonlinear stage, INCAS Bulletin 11 7786 2019. Copyright 2019 Author S. Licensed under a Creative Commons Attribution 4 CC BY license. Visualization of low-speed streaks formed by SCS's 13. Reproduced with permission from Lei and Wu, transition in wall-bounded flows. Mech. Rev. 61 30802, 2008. Copyright 2008 American Society of Mechanical Engineers. In the natural transition, as well as the K-type transition, Lee's experiment has conformed to the existence of SCSs, and this has been by recent DNS results 101-102. For the N and O-type transitions, the existence of SCSs prior to structures has been indicated by numerical simulations based on linear stability theory, LSTPSC, and by a novel method to visualize the flow structure using tracers. The bypass transition scenario is similar to either the natural transition or a turbulent boundary layer. Therefore, if SCSs are confirmed to exist in turbulent boundary layers, it can be claimed that the SCS is a fundamental structure for all transition scenarios. Tomographic PIV has been utilized to prove that low-speed streaks are composed of SCSs. 1. Find the region of interest ROI, i.e. a low-speed streak in the volume of the 3D velocity field. Find the region of interest ROI, i.e. a low-speed streak in the volume of the 3D velocity field. 2. Apply tracking to the fluid element by integrating the following ordinary differential equation over the real-time interval T0 T1 with an appropriate initial condition, IC, Vxt dxt. 4.4. The IC could be a specific point, straight line, curve, surface, or volume grid. Then the position of each particle from a specific initial condition will be determined as time develops. To examine the characteristics of a turbulent boundary layer, an initially placed straight line, either horizontal or vertical, can be integrated, and this will represent the patterns of the timelines, or, as in the traditional visualization of hydrogen bubble lines, see Fig. 4.16. The 3D timeline surface can also be computed to visualize the development of a low-speed streak 89. 3. The generated timelines will form the patterns of a low-speed streak, and the 3D coordinates are extracted by detecting the peak of the streak. The evolution of the streak will be obtained if the profiles at different times are superposed. The amplitude of the wall normal variation along the streak is shown in Fig. 4.16c, which is based on the evolution of the low-speed streak at y plus 36 in Fig. 4.16. The generated timelines will form the patterns of a low-speed streak, and the 3D coordinates are extracted by detecting the peak of the streak. The evolution of the streak will be obtained if the profiles at different times are superposed. The amplitude of the wall normal variation along the streak is shown in Fig. 4.16c, which is based on the evolution of the low-speed streak at y plus 36 in Fig. 4.16. Characteristics of a low-speed streak. A low-speed streak computed from the velocity field of PIV 32. Reproduced with permission from revisiting coherent structures in low-speed turbulent boundary layers. Maths, Mecca, Ida. 40 261 272, 2019. Copyright 2019 Springer Nature. B. Temporal evolution of the wall normal amplitude of the low-speed streak, LSS1, shown in Figure 416 shows that the low-speed streak in a turbulent boundary layer represents a wave-like behavior similar to a transitional boundary layer, which indicates that SCSs may exist in turbulent boundary layers. Note that the PIV measurements were implemented at a certain region where low-speed streaks appear. Although the streak bursting seems to be unpredictable, the measurements performed were able to capture the flow structures when certain structures passing though. 433 Nature of turbulent bursting. Bursting is of great significance in the production of turbulence in boundary layers. However, the definition of bursting has been a matter of controversy ever since Al. 100 first used the term bursting to describe the phenomenon of turbulence production. Al. 27 defined bursting as a process of violent breakup of low-speed streaks after lifting. The streaks interact with the outer portions of the flow through a process of gradual lift-up, sudden oscillation, bursting, and ejection. Al. 103 divided the process into 3 steps. First, a low-speed streak lifts slowly until a shift occurs involving more rapid outward motion of the streak. At this time, an inflected instantaneous velocity profile is observed. Second, rapid growth of an oscillatory motion is observed downstream of the inflected zone. Third, the oscillation is terminated by the onset of breakup. Ejection and sweep are 2 important motions in bursting, and there exists another definition of a burst 29 as a shear layer interface sandwiched between an upstream high-speed sweep and a downstream low-speed ejection. The ejection and sweep during bursting contribute the majority of the stress and drag. The majority of the turbulence produced in the entire boundary layer occurs in the buffer region, with intermittent violent outward ejections of low-speed fluid and inrushes of high-speed fluid at a shallow angle toward the wall. This near-wall turbulence production process is considered to be an intermittent, quasi-cyclic sequence. But there is no consensus as to which observed features of near-wall activity are essential to the continuity of the cycle. The model proposed by Smith 1 of 4 describes both the kinematics and dynamics of hairpin vortices and their relationships to low-speed streaks, the bursting process, near-wall shear layers, ejections, and sweeps. He proposed that the bursting of a low-speed streak was the visual and probe signature of vortex roll-up in the unstable shear layer formed on the top and sides of the streak. Several techniques have been developed to detect individual events, bursts, and ejections. Al. 105 used bandpass filtered velocity signals to detect time periods. And 106 used variable interval time averaging veta to detect large variances in the velocity signal. And 107 used other velocity signal characteristics to detect bursts. Alternative names for flow structures. Type, flow structure. Authors, year, I vortex, Hama and 26. 1963. Hairpin, Williams 114. 1958. Horseshoe, 33. 1952. II. Typical eddy. Falco 38. 1974. Chain of ring-like vortices. L. 115. 2002. Chain of ring vortices. Lay 116. 2000. Vortex chain. Patterson 117. 1940. SIS. L. 91s. 1993. I. Pocket. Falco 40. 1980. SIS. Lay 86. 1998. Dark spot. L. 118. 1986. Black spot. 119. 1999. IV. Long streak. Lay 116. 2000. Low speed streak. L. 120. 1955. V long streak. 121. 1990. Falco 36. 1991. Vortex. Brown and 122. 1971. Due to the complexity of bursting, the majority of studies have used various experimental or computational methods, although a few theoretical results have been obtained. In 109-111, it was suggested that quasi-periodic bursting can be described by periodic solutions to the Stokes equation under proper boundary conditions. In 58-112-113, a proper orthogonal decomposition was used to identify near-wall coherent motions in the form of an array of counter-rotating pairs of vortices. It was demonstrated that such coherent motions would generate bursts. 434 hairpin vortex packets and other flow structures. Adrian al. 30 proposed that different sizes of vortex packets coexist in a boundary layer, and that they are usually layered one on top of the other. Small vortex packages fall in the low momentum regions induced by large vortices, and large eddy packets are also wrapped by larger vortex packets in their low momentum regions. A uniform long low momentum region is formed, induced by sets of vortices, that is longer than that induced by a single hairpin vortex. Adrian al. 30 did not consider the interaction between vortices, but they observed that the vortex packets are very coherent and that the hairpin vortices, sometimes more than 10, in the hairpin vortex packet retain their relative positions and shapes for a long time as they move downstream with little dissipation. The uniform momentum region containing these hairpin vortex packets was considered as a passive product of the packets. The structure of these packets is very complicated, and their dynamical evolution is unclear. Adrian al. 30 assumed that hairpin vortex packets originate from wall disturbances that can produce upward low momentum regions. Although they did not describe the physical process involved, they pointed out that the generation mechanism is similar to the viscous-inviscid interaction mechanism proposed by Smith al. 28. Table 4.4 lists a variety of types of flow structures that have been given different names by different authors. For example, chains of ring vortices, type II in Table 4.4, have been called typical eddies when they occur in a turbulent boundary layer and the other four names in a transition boundary layer. But for these cases, we suggest that chain of ring vortices be used as the appropriate terminology. Schematic of SCS and the induction of vortices, a generation of high shear layer, B vortex develops from high shear layer. The formation of low-speed streaks, LSS, from several SCSs has been discussed by Ley and Wu 13, see Fig. 4.18. If there are two or more waves moving from left to right in the direction, as shown in the side view of an LSS in Fig. 4.18, the rightward speed of the wave is fast, while the leftward speed is slow, and so is the adjacent wave. Between the two waves, if there is dyed liquid or a hydrogen bubble, the dye will move to the middle of the two waves, and consequently it appears that the two waves combine to form a streak. This phenomenon is vividly shown in Fig. 4.18b-d. However, this slug effect is not apparent if the marked particles are initially at higher positions, because of the greater flow velocity and greater distance between the adjacent waves. In that case, one may see a soliton-like pattern similar to that in Fig. 4.18b. This is why one cannot see the streak at greater heights in the boundary layer. Schematic views of a low-speed streak LSS that consists of several SCSs, a side view of LSS, B-plan view of LSS at height level 1 at T1, C-plan view of LSS at T2, D-plan view of LSS at T313. Reproduced with permission from Lei and Wu, transition in wall-bounded flows.
Mecca, Rev.
61 30802, 2008. Copyright 2008 American Society of Mechanical Engineers. 435 Linking DNS data to real flow structures. The development of CFD, especially the acquisition of massive amounts of data from DNS, has brought new opportunities to better understand turbulence 123. Modern PIV, especially time-resolved 3D PIV, and CFD both generate large amounts of data that can be used to reconstruct flow fields in a dynamic manner. However, problems can arise when deciding on the numerical method to be used. The method of equivalent isolines, or has been employed by some investigators, but because it is difficult to obtain a complete flow structure with this approach, the wrong conclusions can be drawn from such simulations. For example, when vortex rings appear in the boundary layer evolution, neither PIV nor CFD can give a full description of its evolution. The use of equivalent isolines and to deal with DNS data has given great impetus to the study of very large-scale motions, VLSMs, and vortical structures, VISs. At the same time, the massive amount of data produced by DNS poses a great challenge, because although in theory the flow structure inversion is relatively simple, it is difficult to elucidate the real structures from the flow data in the absence of a satisfactory method for reconstructing the flow fields, especially when there are two or more structures in the boundary layer. When the structures are interacting, the method is powerless. The structures derived from considering alone are often incomplete and may even be incorrect. It is therefore necessary to establish a general data reconstruction criterion, which remains a very difficult task. One suggestion is to start with transition flow data from DNS and reconstruct the flow field using the tracer method. This method has shown its effectiveness 89/124. Of course, the flow structures in 125 are relatively simple, and the interaction between them is not initially very strong. It is to be hoped that deep learning techniques will allow reconstruction of flow fields from the big datasets provided by PIV and DNS. Basic and composite flow structures.
Type, flow structures. Basic structures.
Vortex horseshoe hairpin vortex.
SIS.
Typical eddies chain of ring-like vortices.
Transverse vortex.
Secondly closed vortex.
Composite structures. Low-speed streaks. Hairpin pockets.
VLSM superstructures.
Turbulent spots.
436 Similarity between transitional and turbulent boundary layers. Transitional and turbulent boundary layers have been studied for more than 100 years. However, many of the viewpoints that have arisen over the years cannot be reconciled. Hereafter, a simple consensus view is presented, and then some reasonable extensions are made. Obviously, the experiment conducted in a low-turbulence water tunnel at Peking University 3297 was a repeat of countless classical experiments in the past, but the measurement of a randomly generated low-speed streak was conducted, which became possible by using both PIV and hydrogen bubble visualization. Because the space and time scales of the experiment were large, it was possible to capture low-speed streaks generated at any time and to track their evolution over a long time. Combining the PIV results with the hydrogen bubble timeline visualization, the low-speed streaks turned out to be formed from 3D waves, similar to the results in transitional boundary layer 13. Thus, the study of the complex structure in turbulence such as low-speed streak may be shifted into the study of the formation of 3D waves. In this context, significant work has been done by and 62, who suggested that lift-up was derived from linear interactions. Lee 86, 126, pointed out that the interaction between two oblique waves would produce 3D waves. Experiments have confirmed that low-speed streaks are formed from SCSs in a transitional boundary layer, and the ejection of a burst cycle is the behavior of the SCS 1397. The problem, then, is how the waves generate vortices. By following a low-speed streak using PIV 3289, it's found that the boundary of a wave produces a high-shear layer which progressively develops into a vortex. By re-examining burst in a low-speed streak region, it was found that burst is also the behavior of a 3D wave 1397-127. Although it is not easy to see that a low-speed streak is a wave structure, this is a reasonable supposition. There are two basic physical structures in fluid mechanics, namely waves and vortices, which may be distinguished from a viewpoint. Due to the fact that low-speed streaks have never been reported to be vortex structures, as can be easily confirmed from flow visualization with hydrogen bubbles, thus the streak burst in a turbulent boundary layer may be considered as a behavior of wave structure. The burst in the late stage of a transitional boundary layer is more deterministic compared to that in a turbulent boundary layer. This is because that both the wave and vortices that randomly distributed in the turbulent boundary layer contribute to the bursting process. Turbulent spots are, of course, a familiar phenomenon, but to understand these structures is not easy at all. To examine the turbulent spot transition, 7 studied a single channel for the production of boundary layer turbulence in the T324 wind tunnel using sophisticated experimental techniques, including those for flow visualization. Lee al. 126 adopted this approach to study two turbulence production channels in a flat plate boundary layer in the water tunnel at Peking University, PKU. Gadel al. 68 suggested that there are many vortex structures inside a turbulent spot, which is thus a composite of dynamic structures. The experiments by Lee al. show that a sufficiently high turbulence level will result in the generation of a set of turbulence production channels, and thus the occurrence of turbulent spots. Oblique wave interaction is a necessary condition for the generation of turbulence, and if some disturbance produces a set of oblique waves at the leading edge of a flat plate boundary layer, then a set of turbulence production channels will also be generated, and a turbulent spot should be formed at a certain point downstream. In this sense, transitional boundary layer is a reduced-order representation of turbulent boundary layer that bears similar flow structures and behaviors. From a structure-based viewpoint, the vortices and chain of ring vortices in a transitional boundary layer are essentially the same as hairpin horseshoe vortices and typical eddies in a turbulent boundary layer, respectively. SCS may be one of the key structures that are responsible for the appearance of low-speed streak and bursting process in both transitional and turbulent boundary layers. 4.4 Instability in compressible flows, especially hypersonic flows. 4.4.1 Receptivity. Receptivity of a hypersonic boundary layer 14. Reproduced with permission from, and direct numerical simulation on the receptivity, instability, and transition of hypersonic boundary layers. Rev. Fluid Mech. 44 527 561 2012. Copyright 2012 Annual Reviews. 3 processes involving unstable waves in a boundary layer 136. Reproduced with permission from receptivity of a high-speed boundary layer to acoustic disturbances, J. Fluid Mech. 491, 101, 129, 2003. Copyright 2003 Cambridge University Press. Research on the receptivity of hypersonic boundary layers is focused mainly on theory and numerical simulation. The technical requirements on facilities and measurement techniques for experimental studies are high, and traditional hotwire methods and field measurements based on particle image, PIV, technology have encountered difficulties. These are due mainly to the flow characteristics of high temperature, high pressure, high speed, and high frequency, which make harsh demands on sensor response frequency and particle tracking. Receptivity studies require strict control of disturbances. Therefore, it is necessary to carry out experiments in a quiet wind tunnel to avoid background noise and wall influence. In research into the mechanisms of receptivity, the theoretical analysis has relied mostly on asymptotic methods 132, 133, multiple mode methods 134, and the parabolic method 135. Hypersonic boundary layers contain unstable modes, Mach first and second modes, etc., and stable modes, modes II, etc., and developed a theory of leading-edge receptivity and modal transformation, and obtained a series of results. They suggested that there were two boundary layer instability modes near the leading edge 136, namely a slow mode, mode S, and a fast mode, mode F, and analyzed the development of the second modes, see Fig. 4.2. They showed that the excitation of unstable waves requires three processes. 1. Near the leading edge, fast and slow modes are synchronized with fast and slow sound waves, respectively. 2. Along the direction, the fast mode phase velocity reaches the phase velocity of the entropy wave vortex wave, with interaction between the fast mode and the entropy wave eddy phase. 3. Further downstream, the fast mode synchronizes with the slow mode, and then one of the modes becomes unstable. The incidence angle plays the dominant role in the processes of reflection, diffraction, and scattering of sound waves, and established a progressive structure to analyze the receptivity of the leading edge, and proposed two mechanisms through which receptivity is affected by the incidence angle 136. 1. There is interaction of incident and reflected sound waves based on the flow effect. 2. Scattering of the incident sound wave at the leading edge produces a secondary sound field, which at the leading edge stimulates the fast and slow modes by diffraction and affects their synchronization. The relative importance of the two mechanisms is closely related to the magnitude and direction of the incident angle. Using multimodal analysis, N 137 found that the fast mode is very important in the receptivity process. It might stimulate the Mach second modes near the synchronization point and facilitate energy transfer between the fast and slow modes based on the weak flow effect. Numerical simulations by 138 showed that vortex waves could either directly excite the Mach second mode or first excite the fast mode. Numerical results by Ma and 139 showed that the fast mode was the main component near the leading edge. In different situations, the relative importance of the leading-edge receptivity mechanism and the modal transformation mechanism may be different. At low disturbance frequencies and with an adiabatic wall, the receptivity of slow sound waves is 50-70 times that of fast sound waves. For an adiabatic wall, the receptivity of the leading edge is stronger than the mode transformation mechanism, but the opposite is true for a cooling wall 140. This is because a cold wall can suppress the first Mach mode and strengthen the interaction of the fast and slow modes. In this case, the initial disturbance has strong receptivity only when it is far upstream from the synchronization point. Therefore, the relationship between leading-edge receptivity and modal transformation mechanism is strongly dependent on the location of the synchronization points. Effect of wall temperature on receptivity and transition, 142. Reproduced with permission from Enlay, Review of Research on the Receptivity of Hypersonic Boundary Layer, JEXP. Fluid Mech. In Chinese, 31-111, 2017. Copyright 2017, editorial by Journal of Experiments in Fluid Mechanics. Research Group. Model, Mod, Method, Wall Condition, Conclusion, L. 2003. Plate 6. Tiha. Adiabatic. Receptivity of slow acoustic wave is 50 times greater than that of fast acoustic wave. Cooling. Mode F may be unstable. Ma and 2001. Plate 4.5. And adiabatic. Isothermal. Receptivity coefficient of isothermal wall is less than that of adiabatic wall. 2015. Wedge. Cone. 6. NS.
Adiabatic cooling. Adiabatic receptivity of slow acoustic wave is 20 times greater than that of fast acoustic wave. Cooling sharp cone transition is earlier. L. 2007-2008. Wedge cone 6 INS. Adiabatic cooling. Receptivity of slow acoustic wave is 67 times greater than that of fast acoustic wave. Transition is advanced when wall is cooled. 1995. Cone 6 Adiabatic cooling. Transition is advanced. 1978. Cone 8 IXB 0.4108. Transition is advanced. And 1984. Plate 246 IXB 0.31. Cooling has no effect on acoustic wave. The first mode becomes more stable, and the second mode becomes less stable. 1972. Cone 56.6 IXB 0.204. Transition is advanced. Stetson Al. 1989. Cone 8 IXB 042. Transition is advanced. When the wall is cooled, the frequency of the Mach second mode increases, as does the growth rate. 2011. Plate 5.4 THNS. Cooling heating. Transition is advanced. When the wall is cooled and the location of cooling affects the transition. L. 2015. Cone 6 IXB-NS. Local cooling. Local heating. Local cooling, Mach second mode is reduced and transition is delayed. L. 2009. Plate 6 INS. Temperature jump. Temperature jump affects receptivity. Carlo L. 1965. Sharp. Cone 8.8. IXB 0.0804. No obvious effect. A theory. Base simulation. See experiment. The physical properties of the wall also have a great impact on the transition. However, a unified understanding of the effect of wall cooling on transition has not yet been achieved. See Table 4.6. It is necessary to consider whether the leading mode of transition is the Mach first mode or second mode. The results of Ma and 139 on the special cases of adiabatic or isothermal conditions showed that the receptivity of fast sound waves under the condition of an isothermal wall is smaller than that under the adiabatic condition. L. 143 used LST and numerical simulation to study the effect of different cooling heating elements on the stability of a hypersonic boundary layer. They found that cooling could delay transition, with the delay being related to the position of the cooling source. L. 144 used the LST and DNS to study the receptivity of a sound field in a hypersonic boundary layer with a porous layer on the wall. The effect of roughness elements on the stability of the boundary layer on a cone was calculated by Al. 145, who found that the distance between the roughness element and the synchronization point and the ratio of that distance to the boundary layer thickness were important factors affecting the receptivity process. Paths of receptivity processes in the hypersonic boundary layer 142. Reproduced with permission from Enlay, Review of Research on the Receptivity of Hypersonic Boundary Layer, JEXP. Fluid Mech. In Chinese, 31-111-2017. Copyright 2017, editorial by Journal of Experiments in Fluid Mechanics. Finally, to help understand hypersonic boundary layer receptivity,
the hypersonic boundary layer instability wave excitation paths can be summarized as follows. See Fig. 4.21. Paths 1-4 represent the receptivity of the front edge to a sound wave. Paths 5-7 represent the process of transforming the fast and slow modes into an unstable mode. Paths 8 and 9 represent vortex wave, entropy wave, and temperature spot perturbations. In Path 10, the nonlinear interaction of fast and slow waves can evolve directly into an unstable mode. By studying the receptivity problem, the initial amplitude of disturbance growth for different wall features, roughness elements, temperature, etc., and different forms and frequencies of disturbance can be obtained. This allows, for example, better prediction of the transition position in the boundary layer of a hypersonic vehicle, which is very important for aircraft design and thermal protection. 4.42 Instability theory in hypersonic flows. Neutral stability curve of the Mach 4.8 boundary layer obtained in 153, including the first and second modes. Plan view of contours of velocity for a Mach 6 flat plate boundary transition induced by first mode oblique waves 163. Reproduced with permission from and breakdown mechanisms and heat transfer overshoot in hypersonic zero pressure gradient boundary layers, J fluid mech. 730, 491, 532, 2013. Copyright 2013, Cambridge University Press. When the profile of the main flow changes in 2 or 3 directions rather than in just one, such as in square cavity flow, a 3D wake, non-axisymmetric body flow, and cross-flow instability, 2D or 3D stability analysis or global stability analysis, biglobal analysis and global analysis should be considered. The solution of 2D stability analysis is the same as that of LSD, but the calculations are far more complicated than those in LSD, and the requirements on algorithms and computer power are more demanding. There were no numerical examples until the 1980s. Computation of 3D stability faces even greater challenges. Specific examples can be found in the review by 156 and the doctoral dissertation of Pairds 157. The latter also developed a 3D PSC method to study instabilities of streaks. By the 1990s, non-normal stability analysis or transient growth was proposed. Details of its background and applications can be found in the review by 158. 4.42.1 Secondary instability. Owing to nonlinear effects, a 2D unstable wave will reach saturation. The 2D wave is superimposed on the original boundary layer flow and forms a new flow field with spatiotemporal variations. When the fundamental wave is a saturated 3D wave, there may also be secondary instability, such as streak instability in a boundary layer, see Fig. 4.23 Vortex instability in a concave surface boundary layer and cross-flow instability in a 3D boundary layer. 159 tried to explain the causes of secondary instabilities by using theory and laid the theoretical framework for the study of secondary instabilities. And 160 and L161 considered secondary instabilities of a high-speed boundary layer. They found that 1, the Mach number has an inhibitory effect on secondary instabilities, and 2, being consistent with the low velocity, the fundamental resonance is dominant for a large amplitude 2D fundamental wave, while a small amplitude 2D fundamental wave is more prone to instability. Wren and 162 studied the secondary instabilities of vortices in a high-speed boundary layer and found that antisymmetric modes dominated the transition. 4.422 Weakly nonlinear theory and mode interaction. Secondary instabilities can also be studied by the nonlinear PSC, NPSC method. The NPSC is only applicable in the case of weak nonlinearity. It was first proposed by Al. 154. Al. 164 studied the interaction between second modes and low-frequency waves in a Mach 6 flared cone boundary layer using the NPSC and secondary instability theory, and found that the second mode could greatly promote the growth of low-frequency waves. Pairds Al. 165 found in a Mach 6 sharp cone that a streak structure had a stabilizing effect on the 2D second mode, mainly caused by the mean flow distortion produced by the streak, but it could make the oblique second mode and the first mode becomes more unstable. In addition to NPSE, the high-number asymptotic method 166 is also a common method of analysis. The advantage of this method is that it can obtain approximate analytic expressions and facilitate the study of parameters. The disadvantage is that assumptions are required, and the method has a limited scope of application. AL 167, using the high-number asymptotic method and phase-locked resonance theory, studied the interaction between the first and second modes and found that the second mode could promote the growth of the first mode. The interaction between the second mode of the Mach 6 plate boundary layer and a single first mode oblique wave was also studied using the PSE by and LUO 168. They found that the second mode could promote the growth of the first mode in a wide frequency band, and there was still a stage of suppression before the start of growth. Evolution of a 3D wave packet for a Mach 6 cone boundary layer. A linear B nonlinear. The contours of wall pressure are shown 172. Reproduced with permission from and numerical investigation of the development of three-dimensional in a sharp cone boundary layer at Mach 6, J fluid mech. 756, 606-49, 2014. Copyright 2014, Cambridge University Press. 443, The effect of Mach number and other parameters. 4431, Effects of Mach number on boundary layer transition. Outer layer Mach number, effect on the transition number and transition prediction criteria. Data are from 174, and consolidated data from blunt cone experiments at Peking University's hypersonic wind tunnel. The National Aerospace Plane, NASP, BLT series are a set of mature criteria for the prediction of hypersonic smooth wall transition 173. They have been proposed for smooth-bodied aircraft and have been successfully applied to the prediction of natural transitions for the boundary layers of the Space Shuttle and the X-33 and X-43A hypersonic vehicles. Effect of cooling on transition in a hypersonic boundary layer 176. Reproduced with permission from Stetson al. Surface temperature effects on boundary layer transition, AIA J30, 2782-2783, 1992. Copyright 1992, American Institute of Aeronautics and Astronautics. 4432, Effects of wall temperature on boundary layer transition. Pressure disturbances for different wall temperature conditions, 139. Reproduced with permission from Ma and receptivity of a supersonic boundary layer over a flat plate. Part 2. Receptivity to freestream sound, J fluid mech. 488, 179121, 2003. Copyright 2003, Cambridge University Press. L. 140, studied the influence of a cooling wall on the receptivity coefficient. They found that on a cooling wall, the boundary layer was more sensitive to fast sound waves, there was a stabilizing effect on the Mach first mode, and the transition position was advanced. L. 177, similarly considered the influence of adiabatic and cooling walls on a hypersonic boundary layer by means of numerical calculation. For a sharp cone, the receptivity of the leading edge to a sound wave on a cooling wall is 1/100 of that on the adiabatic wall. The Mach first mode tends to be stable on a cooling wall, but the Mach second mode becomes more unstable. These results are in agreement with results of LST and with experimental results on a cooling wall 146, 148, 178. However, the effects of local cooling and global cooling on unstable modes are different. The experiments and calculations of AL. 179 showed that with local cooling, the Mach second mode was suppressed and the boundary layer transition was delayed. With local heating, the transition position moved upstream. The effects of different cooling heating elements on the stability of a hypersonic boundary layer were investigated using LST and numerical simulation by AL. 143. They found that cooling could delay transition, but the position of the cooling source was very important and it should not be too far downstream. When the boundary layer was too thick, disturbances above the cooling source position were obviously leading to an advanced transition. L. 180 found that a temperature jump in the thermal protection layer on the surface of a hypersonic vehicle would affect the receptivity process in the boundary layer. And 181 also found that the position of the heating source, the distance from the leading edge and the distance from the wall surface, has different effects when the laminar flow is controlled by the heating method and when the Mach second mode wave is dominant. These results are in accordance with the calculations by Al. 143. If the heating source is upstream of the neutral point and close to the outer edge of the boundary layer, it has a stabilizing effect. If it is downstream of the neutral point and inside the boundary layer, this effect will become weaker. The stabilizing effect is greatest when the hot spot is near the critical layer and the neutral point. There is no general law governing the influence of wall temperature on receptivity and transition, and it is necessary to consider the geometry of the body under investigation and which mode dominates the transition, the Mach first or second mode. The physical and dynamical processes that affect aerodynamic heating are yet to be explored. The relevant experimental studies are of great significance for engineering guidance. 4433 Effect of entropy layer on transition. Density fluctuation cloud map obtained by adding a 2D acoustic wave before a blunt head 182. Reproduced with permission from and transition prediction in hypersonic boundary layers using receptivity and spectra, AIA J56, 193-2, 8, 2018. Copyright 2018 American Institute of Aeronautics and Astronautics. Windward second mode N factors with different degrees of blunt cones. A 1% bluntness, B 5% bluntness. The dashed line represents the entropy swallow position 184. Reproduced with permission from Tufts and analysis of windward side hypersonic boundary layer transition on blunted cones at angle of attack, AIAA paper 2017-764, 2017. Copyright 2017, American Institute of Aeronautics and Astronautics. In 1973, and 185 pointed out that in many cases the isentropic hypothesis regarding the flow outside a boundary layer was unreasonable. In 1984, Stetson and 186 were the first to measure entropy layer disturbance experimentally. They found that the perturbation of the entropy layer was located at the inflection point of the Mach profile and had a frequency lower than 100 K. The entropy layer itself has an inviscid instability, which produces the entropy mode. Before the entropy layer enters the boundary layer, the entropy mode goes through a slow growth attenuation stage, but the entropy layer grows rapidly after entering the boundary layer 181, 187. Transition number versus number defined by the head radius 193. A data from 194, B data from 195. Reproduced with permission from Ley and linear stability analysis of nose bluntness effects on hypersonic boundary layer transition, J. Rockets 49, 2437, 2012. Copyright 2012, American Institute of Aeronautics and Astronautics. Compared with a sharp cone boundary layer, the boundary layer is more stable when the blunt radius is smaller. The second mode wave rises further back on the body, and the transition position is delayed 188, 191, 192. Recent calculations have shown that the location of the second mode wave begins to increase and is associated with the entropy swallow point 14, 184. When the blunt radius exceeds a certain critical value, the transition number decreases with increasing degree of bluntness, which is called transition reversal caused by the blunt head, see Fig. 4.3. Stetson and observed transition reversal phenomena 194, 196, and Stetson believed that the transition reversal was related to instability of the entropy layer itself. Much theoretical work has been done to explain the phenomenon of transition reversal. The instability of the entropy layer is a kind of inviscid instability 192, 197, 198. And Con 199 took the entropy layer into account using the progressive matching method. They believed that the entropy layer played a stabilizing role in the boundary layer disturbance before entropy swallowing. After entropy swallowing, the boundary layer became the same as a sharp cone boundary layer. They also calculated the pressure perturbation in the entropy layer, which was similar to the first mode. On the basis of these results and others, a linear theoretical analysis of internal disturbances in the entropy layer was carried out by 198. It was found that the boundary layer had a stabilizing effect on entropy layer disturbances, but after the entropy swallowing, the distances to the boundary layer disturbance and the entropy layer disturbance were very close. Once the entropy layer disturbance entered the boundary layer, the disturbance in the boundary layer increased rapidly. And 181 further analyzed perturbations of the entropy level and suggested that disturbances of entropy layer and the boundary layer might lead to inversion of the transition. 200 analyzed the stability of Stetson's blunt cone and obtained a weakly evolving entropy mode that agreed well with experiment. He also found that the most unstable entropy mode was two-dimensional. Recently, Ley and 193 have analyzed the linear stability of Stetson's blunt cone 194. They found that with increasing radius of the blunt head, the second-mode waves became more and more stable, and there was no transition reversal phenomenon. And 182 studied the receptivity of sound waves to a blunt cone by DNS. They found that external sound waves disturbed the entropy layer after the shock wave. These disturbances developed downstream and affected the boundary layer. The development of the disturbances in the entropy layer was different from that of the disturbances in the boundary layer. Compared with a sharp cone, the blunt cone reduced the receptivity of sound waves, but there was no transition reversal phenomenon. Greenwood 201 used hot wire measurements to observe the evolution of entropy layer disturbances for a cylinder with a sharp head cone. He found that the disturbance increased slowly first, went through a short decay time, and then increased rapidly. He believed this behavior to be due to the entropy layer entering the boundary layer. L. 202 performed transition experiments on tapered and blunt cones at Ma 10. They found that the second-mode wave amplitude was very small at the transition position observed in the case of a large blunt head, which indicated that there existed some other mechanism. They believed transient growth and entropy layer instability existed. L. 203 found a transition reversal phenomenon at Ma 5 using the blunt arch model. This result indicates that the transition reversal phenomenon is not related to surface roughness or to disturbance. 4434 effects of roughness on transition. In a hypersonic boundary layer, transition caused by roughness is very common. Roughness is generally divided into isolated roughness and distributed roughness. Distributed roughness can be considered as a combination of isolated roughnesses, and its influence is more complex than that of isolated roughness. This paper discusses only isolated roughness. Roughness is mainly due to joints, manufacturing defects, and surface ablation of aircraft surfaces. When roughness elements are large, bypass transition can occur. A common passive control method in aeronautical engineering is to enhance transition by installing roughness at specific positions on the surface of an aircraft. The transition position is thereby advanced. It is currently believed that the main factor affecting transition is the roughness height, although other factors include number, wall temperature, Mach number, roughness shape, and section area. To further understand the mechanisms of transition triggered by roughness, a variety of experiments, numerical simulations, and theoretical analyses have been performed. However, a consensus on the relevant mechanisms has yet to be achieved. 204 suggested that there were three possible ways to cause transition by roughness: instability in the wake, rapid development of flow structures caused by cross-flows or instability behind roughness, and increased instability of first and second modes caused by interaction between sound disturbances in the free stream and the surface of the roughness. In low-speed flow, the front edge of a roughness element leads to an area of separation due to the reverse pressure gradient. Depending on the number, there will be stable or unstable vortex structures consisting of a pair, two pairs, or three pairs, the so-called horseshoe vortex. The horseshoe vortex forms a vortex structure downstream of the roughness element. The roughness element produces a low-pressure area, which generates reflux and causes the formation of a pair of downstream trailing vortices, which are rotating vortices. In high-speed flow, the same flow topology appears around the roughness element. L. 205, using nitric oxide planar laser-induced fluorescence, revealed the structure of the horseshoe vortex caused by a roughness element. L. 206 used planar PIV and infrared thermography to observe the vortex structure downstream of a roughness element. They found clear high and low temperature strips behind the roughness element. These strips were caused by the horseshoe vortex and the downstream flow vortices. They also used the Schlieren method to observe the shock structure near the roughness element, i.e., the shock wave in the front separation area, the upper edge of the detached shock wave, and the shock wave after the roughness element. PIV revealed a vortex structure comprising 3 pairs of rotating vortices in the upstream separation area of the roughness element. These vortex structures cause changes in the heat flow on the wall. L. 207 used the hot wire method to study the influence of the shape of the roughness element on the transition. There was a clear high and low velocity strip distribution behind the roughness element, with a mushroom-like appearance on the mass flow cloud graph. Modal shape expressed by disturbance velocity after a cylindrical roughness. A even mode, B odd mode 208. Reproduced with permission from, and investigation on the wake flow instability behind isolated roughness elements on the of a blunt generic reentry capsule, Prague. Flight 9-451-480, 2017. Copyright 2017, IDP Sciences. To predict the transition position caused by roughness elements, many experiments have been done in both traditional and static wind tunnels. Flight tests have also been conducted. 204 summarized and compared the results of previous studies. It was found that is an important parameter determining the effect of roughness elements on transition. This parameter was first introduced by Van Dries 214, using dimensional analysis. 215, also derived from rapid growth theory. A mixed number W has also been proposed as a parameter, in which is replaced by. However, predictions of transition based on have large errors under different working conditions. The experimental data points are often scattered around the predicted curve, which is due to the fact that the turbulence, Mach number, and wall temperature are not considered. In fact, this method is an empirical one and does not include roughness effects. Attempts have been made to develop a model based on physical mechanisms to describe transition with roughness effects. Up to now, however, only a semi-empirical model, similar to the EN model, has been proposed. 4435 Effect of cross-flow instability on transition. A significant pressure gradient of the flow field will introduce a new instability mechanism called transverse instability. Transverse instability may have a significant impact on the transition process of the boundary layer. Typical causes of transverse instabilities include swept wings, ellipsoids, and cones with angle of attack. L. 216 carried out a transverse flow experiment on an NLF 20415 wing in the ASU wind tunnel. The sweep angle of the wing was 45, and the angle of attack was minus. For the experimental results showed that the transverse flow was driven mainly by the disturbance perpendicular to the flow. In the experiment, a spanning array was used to control the disturbance. An experiment at the DLR at a low speed of 1725 ms tested several groups of models of wing-like plates under natural and controlled conditions to provide a basis for development of a transverse flow theory and for test comparisons 217. It was found that the propagation of the disturbance was dependent on the lower frequency oblique traveling waves and the zero frequency stationary vortices. The axis direction of the stationary vortices was approximately in the local and viscid direction. Steady bumps and oscillating membranes were used to control the flow. The above experiments were all concerned with low-speed crossflows. The crossflow transition at high speeds is sometimes similar to, but sometimes different from that at low speeds. Stetson 218 carried out a cone test at Mach 6 and small angles of attack. The dependence of transition position on angle of attack and nose bluntness was found, but detailed results in the boundary layer were not obtained. 219 performed a flight test on an elliptical cone at Mach 7.5. This experiment mainly explored the transition of the boundary layer and the influence of complex shock waves on boundary layer transition in ultra-high-speed flight. Another purpose was to confirm the results of some calculations. And 220 conducted a cone test under a working condition of Mach 6 in a quiet wind tunnel. Normal temperature hot wire measurements gave an instability frequency of 180 K. Stationary crossflow waves, traveling waves, and type I secondary waves were observed, which were similar to those found at low speed. However, type II secondary instability and transition were not observed. Borg al. 221 conducted an elliptical cone test in a Mach 6 quiet wind tunnel and observed traveling crossflow waves. The phase speed and wave angle of traveling crossflow waves calculated from the pressure spectrum agreed well with the values predicted by LST. It was found that traveling crossflow instability was not the main transition mechanism in quiet or noisy wind tunnels, because traveling crossflow waves did not exhibit nonlinear growth. Al. 189 conducted boundary layer transition and heat flow tests with the RE5 model in the Boeing AFOSR Mach 6 quiet wind tunnel. Temperature-sensitive paint was used to measure the surface heat flow. They found two transition modes. One was transition along the centerline, which was suspected to develop from second-mode waves in the boundary layer. The other transition appeared between the centerline and the leading edge, and was caused by breakup of cross-current vortices. With the noise in the wind tunnel being reduced, the two transitions were delayed. Increasing the angle of attack delayed the cross-flow transition on the windward side. Numerically, Malik al. 222 used the PSE to investigate the cylindrical problem with a 76 sweep angle in the case of Mach 3.5. Two unstable modes were found, one generated by the velocity gradient in the direction and the other by the velocity gradient in the wall normal direction. And 223 proposed a transition prediction model. Al. 224 developed a prediction model based on parameters. Al. 225 extended and's model to take account of cross-stream effects. And 226 proposed a model in which cross-flow information could be predicted by the cross-flow number. Al. 227 improved and's model by including helicity parameters. Peards and 228 performed biglobal instability analysis to investigate the secondary instability of vortices in a hypersonic elliptic cone boundary layer. They found unstable Y modes, including sinuous type and varicose type modes. Li al. 229 used similar method to find that there are also unstable Z modes. They proposed inflection point analysis for biglobal instability in hypersonic boundary layers, and their analysis showed that these unstable modes are caused by inviscid inflection instability of shearing basic flow. Su al. 230 used theory to study secondary instabilities of stationary crossflow vortices in a hypersonic swept wing boundary layer. They identified a new unstably Y mode at the trough of the stationary crossflow vortex, which was not found in incompressible swept wing boundary layers. They performed kinetic energy balance analysis and found that pressure diffusion enhances the growth of the Z mode, and that the pressure dilatation term arising from non-vanishing velocity divergence reduces the growth of all modes. Han al. 231 focused on the transition mechanism of a similar model with Su al. With the help of direct numerical simulations and stability analysis. Their results show that high-frequency disturbances of secondary instabilities cause rapid growth of low-frequency and stationary disturbances, which in turn induce abrupt rise of the wall friction coefficient. 4436, the effect of instability on transition. When fluid flows past a curved surface, it is possible to have centrifugal instability and to form vortices. A vortex is a pair of flow vortices that are caused by an imbalance between the centrifugal force and the normal pressure gradient. There is an associated criterion for instability, similar to criterion for instability of swirling flow. Generally, fluid flowing past a concave surface produces instability, and the vortices will advance the transition as a result of secondary instability or interactions with other modes. This is a topic that has recently attracted growing attention. The vortex itself does not cause the transition. The mean flow has an inflection point in both the wall normal direction and the direction of spread. It is easy for secondary instabilities to arise, after which turbulence is produced 232-235. Hall and Horseman 236 found that there were two completely different modes of secondary instability, an odd mode and an even mode, which were consistent with the vortex breakdown observed in experiments. Lai and Malik 237 used 2D LSD and 3D PSC to study nonlinear secondary instabilities. They found that the flow field was controlled by the basic odd mode and even mode. The odd mode 236 was most unstable. The relative importance of the second modes depends on the wavelength. When the wavelength is large, the even mode is stronger, and when it is small, the odd mode is stronger. There have been relatively few studies of vortices in the context of secondary instabilities of compressible flows. Wang and 238 found that during the secondary instability process, two unstable modes coexisted, the sinuous mode and the varicose mode. The sinuous mode and the spread velocity gradient were linked, as were the varicose mode and the normal velocity gradient. This agrees with the results of previous low-velocity incompressible flow studies 235. Under the conditions considered, a linear theoretical analysis suggested that the varicose mode was more unstable than the sinuous mode. Calculations based on the model of Al. 239 for the nonlinear development of a vortex on a flared cone indicated that there were three different transition mechanisms. 1. The secondary instability of the vortex itself caused the transition. 2. The vortex interacted with the waves of both modes, amplified the second mode waves, and led to the transition. And 3. Interaction between the vortex and the oblique second mode wave with non-zero in the circumferential direction led to the transition. Ren and 240 used LSD and the PSC to study the role of vortices in the transition process in a hypersonic boundary layer. They found that the most unstable mode for a blunt cone was the Mach mode, while for a compressible wedge, the vortex played the leading role in the transition process. The spreading wavelength of the vortex was TUM according to LSD. They later studied secondary instability of the vortices using Theory 162, and discovered secondary instability modes that had not been described by Lay and Malik 237, called odd mode II. They studied the effect of compressibility on vortices by changing the Mach number and concluded, consistent with previous studies, that the growth rate of vortices decreases with increasing Mach number. Compressibility has the effect of maintaining stability. A new secondary instability mode was also found in this study, which was called the sinuous type II mode by the authors. Disturbances due to the secondary instability mode were found mainly near the stem area and played a role in the subsonic and low supersonic flow transition process at low Mach number. When the Mach number increased, the form of the vortex changed from the mushroom structure into a ring structure, and there was a very thin layer at the bottom of the boundary layer that was not disturbed by the vortex. The main form of the disturbance changed from a velocity perturbation into temperature and density disturbances. The relationship between the main mode of secondary instability and the spreading wavelength obtained by Lai and Malik 237 is no longer appropriate for hypersonic flow. When the Mach number is 4.5 or higher, the secondary instability mode is sinuous type I under certain conditions. Vortex generators not only excite the primary vortex with a wavelength equal to the spacing of the vortex generators, but also trigger the first harmonic with a comparable amplitude. The harmonic can, in turn, grow and induce secondary streaks between the primary streaks, as has been reported by several experimental and numerical studies 234, 241. Recently, Al. 242 has performed comprehensive computations of vortices and their secondary instability at Mach 6.5 using DNS and temporal analysis of secondary instability theory. Multiple modes have been identified in the secondary instability stage, some of which originate from the primary instabilities, the Mach first and second modes. They demonstrated that the secondary streaks can destabilize the vortices, therefore they advance the transition. In particular, the first mode can be destabilized to either a varicose mode or sinuous mode streak instability, depending on its frequency and wavelength, whereas the second mode undergoes a stabilizing stage before turning into a varicose mode. 4.5 Conclusions and Perspectives. This article attempts to clarify the basic problems of transition. How does the vortex come into being? How is the low-speed streak formed? What is the basic structural behavior of turbulent bursts? The main purpose of this paper is to draw a simple and clear conclusion about the onset of turbulence. In the past, the study of turbulent structure paid little attention to investigating the waves concerned. Thus, some dynamic processes are missing without considering the role of waves, especially the role of soliton-like coherent structures. The main reason is that it is not easy to distinguish waves in turbulent flow field. Modern experimental methods, especially PIV and corresponding data processing scheme, have brought us new opportunities to re-examine the flow structure. Turbulent bursting used to be difficult to quantify now, which is possible to be quantitatively measured. This, therefore, can avoid arbitrariness brought about by artificial interpretation. Different names for the same flow structures are classified. Low-speed streak is found to consist of soliton-like coherent structures, which dominates the turbulent bursts. Paths to turbulence in boundary layer flows. More and more evidences show that the turbulent structure cannot be infinitely smaller, like the whirlpool forest. The turbulent structure method presented by the method of is non-physical. Establishing a basic principle that can be used to reconstruct flow structures from the massive amount of data from CFD and PIV is an urgent and challenging task. Controlled turbulent generation, transition, and natural turbulent bursting have inherent similarities. These similarities provide new opportunities for understanding of the generation of turbulent structures. Turbulent structures must be recognized in conjunction with real flow visualizations, experimentally or numerically. In future, the role of wave structures in the transition needs to be paid much more attention. C.B. Lay would like to acknowledge the support of all of his D students who prepared the preliminary materials. The authors are also grateful to Professors Wu and Su for their useful help. Competing interests, this work was supported by the National Natural Science Foundation of China grant knows. 10,921,202, 11,221,061, 11,632,002, 11,521,091, 11,602,005, and also the research projects of the Chinese NSF Physical Mechanisms of the Formation, Evolution, and Interaction of Turbulent Structures, grant no. 91,752,000. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 MV in viscous drag reduction, ed. by C.S. Wells, Springer, New York, 1969. 131. 2a. Rev. Fluid Mech. 81 311, 1976 ADS. 3 H. L. Reed, W.S., in American Society of Mechanical Engineers, New York, 1987. 457-468. 4 B.J. S.A.T. Rev. Fluid Mech. 21 359, 1988. Org 10114620101880020043. 5 ME SW J Fluid Mech. 207 97, 1989 net. 6 LTA. Rev. Fluid Mech. 23 1 495, 1991. 7 YS. Rev. Fluid Mech. 26 1 411, 1994 ads. 8 HL Reed WSD. Rev. Fluid Mech. 28 1 389, 1996. Org 10114628010196002133. 9 T. Rev. Fluid Mech. 29 1 245, 1997 net. 10 WS HL Reed EB White. Rev. Fluid Mech. 35 413, 2003 ADS. 11 P XH Wu. Rev. Fluid Mech. 39 107, 2007 ads. 12 B TM BJ. Rev. Fluid Mech. 39 447, 2007 ADS. 13 CB Lei JZ Wu. Mech. Rev. 61 3 30802, 2008. 14 XX. Rev. Fluid Mech. 44 527, 2012 ads. 15 IE CG Miller III. Rev. Fluid Mech. 22 1 419, 1990 ads. 16 SB Prague. 41 2 1 2004. 17 A. Rev. Fluid Mech. 43 79, 2011 ads. 18 J Fluid Mech. 842 513, 2018. 19 XS Wu. Rev. Fluid Mech. 51 1 451, 2019 ADS. 20 SK MI. Fluids 27 6, 65,113, 2015. 21 JHM WR Wolf. Fluids 29 8, 85,104, 2017 ADS. 22 MR AMM. Fluids 29 10, 103,601, 2017. 23 YHJ. Tan Xley YJ FJ Sheng. Fluids 3011, 111,702, 2018. 24 XQ. Fluids 3010, 104,102, 2018. 25 YJ WX CXU. Fluids 31-2, 21,204, 2019. 26 FR Hama, J. in Proceedings of the Heat Transfer and Fluid Mechanics Institute, University Press, 1963. 7793. 27 SJ WC FA PW J Fluid Mech. 34 741, 1967 ADS. 28 CR Smith, JDA Walker, AHU Phil. Trans. R. Soch. A 336 1641, 131, 1991 ADS. 29 SK. Rev. Fluid Mech. 23 1 601, 1991 ADS. 30 RJ Adrian Sadi CD J Fluid Mech. 422 1 2000 net. 31 I JP. Rev. Fluid Mech. 51 1 2019. 32 XY. Maths. Mech. Ada. 42 261, 2019. 33T in Proceedings of the Second Midwestern Conference on Fluid Mechanics, Ohio State U, Columbus, Ohio, 1952. 34 Amar Head, P. J. Fluid Mech. 107 297, 1981 ADS. 35 AH, C.R. Smith, J. Fluid Mech. 277, 135, 1994 ads. 36 R.E. Falco, Phil. Trans. R. Soch. A 336 1641, 103, 1991 ADS. 37 R.E. Falco. Fluids 2010, S124, 1977 ADS. 38 R. Falco, in 12th Aerospace Sciences Meeting, Washington, D.C., 1974, P99. 39 R.E. Falco, in Coherent Structure of Turbulent Boundary Layer, EAD. By C.R. Smith, D.E., AFOSR Workshop, 1978. 448 461. 40 R. Falco, in 13th Fluid and Plasma Dynamics Conference, Colorado, 1980, P1356. 41 R.E. Falco, in Structure of Turbulence in Heat and Mass Transfer, EAD. By Z. Hemisphere Publishing Corp., 1982. 4357. 42 R. Falco, in 21st Aerospace Sciences Meeting, Nevada, Reno, 1983, P377. 43 BJ, J. Fluid Mech. 173, 159, 1986 ads. 44 GR, SJ, J. Fluid Mech. 72, 209, 1975 ads. 45 RE Falco, J. Fluids. 102 2, 174, 1980. 46 CC, RE Falco, Exp. Fluids 65, 305, 1988. 47 Sadi, RJ Adrian. Fluids 74, 694, 1995 ads. 48 J. Joe, RJ Adrian S. Fluids 81, 288, 1996 ads. 49 J. Joe, RJ Adrian STM, J. Fluid Mech. 387, 353, 1999 net. 50 JW, Ty J. Fluids of 54, 1011, 1993 ADS. 51 Fs. Fluids 94, 883, 1997 ads. 52 YRT, JSME, JSIR. B. Fluids Thermal. 42, 257, 1997. 53 S. EJ33, 329, 1957 ADS. 54 JT Stewart, the production of intense shear layers by vortex stretching and convection. Tech. Rep. AGARD R514, 1965. 55 CR Smith, SB, J. Fluid Mech. 129, 27, 1983 ads. 56 RF H. J. Fluid Mech. 94 3, 577, 1979 ADS. 57 DT Ty J. J. Fluid Mech. 95 4, 655, 1979 ads. 58 N. P. Holmes, J.L. E. Stone, J. Fluid Mech. 192, 115, 1988 net. 59 J.D.A. Walker, S. in Transport Phenomena in Turbulent Flows, Theory, Experiment, and Numerical Simulation, 1988. 145, 156. 60 MS, C.R. Smith, J. Fluid Mech. 175, 43, 1987 ADS. 61 T.L. Hun, J.D. Walker, An Analysis of the Motion and Effects of Hairpin Vortices. Tech. Rep. FM 11. Of Mechanical Engineering and Mechanics, University, 1987. 62 SI MF, J. Fluid Mech. 544, 99, 2005 net. 63 HW, J. Aeronaut. 187, 490, 1951 math net. 64 GB PS, contributions on the mechanics of boundary layer transition.
Tech, Rep.
NACA TN 3489, 1955. 65 D. Coles, S.J. Barker, in Turbulent Mixing in Non-Reactive and Reactive Flows, Springer, 1975. 285 293. 66 AC, C.W. Van Otta, J. Fluid Mech. 148 319, 1984 ads. 67 T in Laminar Turbulent Transition, Berlin, 1980. 288 296. 68 M. Gadel, RF, J.J. Riley, J. Fluid Mech. 110 73 1981 ADS. 69 B. D. Coles, P. Fluids 2010, S291 1977 ADS. 70 I. M. J.H. J. Fluid Mech. 123 69 1982 ads. 71 R. M. R.A. J. Fluid Mech. 197 389 1988 ADS. 72 J.P. N. G.J. Walker, J. 118 4 737 1996. 73 A.E. Perry, Tati, A.W. J. Fluid Mech. 104 387 1981 ADS. 74 B.A. Singer. Fluids 82 509 1996 net. 75 H.M. P.F. in Proceedings of the 1999 ACM IEE Conference on Supercomputing, Portland, OR, USA, November, ACM 1999, P68. 76 A. J. Exp. Fluids 36 1, 82 2004. 77 CWH Van B. RHJU in Proceedings of 5th International Symposium on Particle Image, South Korea, September 2003. 2224. 78 D. C. Smith, Exp. Fluids 33 1, 13 2002 ADS. 79 BJ, J. Fluid Mech. 817 P1 2017 ADS. 80 KC RJ Adrian. Fluids 11 2, 417 1999 net. 81 N I J Fluid Mech. 579 1 2007 ads. 82 BJ RJ Adrian.
Trans, R. Soch.
A 365 1852, 665 2007. 83 R JPNI. Fluids 2111, 111,703 2009. 84 DJC TB Nichols J Fluid Mech. 673 180 2011 ADS. 85 DJC TB Nichols J Fluid Mech. 673 218 2011 ADS. 86 CB Lai. A 247 6 397 1998 ADS. 87 CB Lai S Exp. Fluids 33 354 2001. 88 MS CR Smith J Fluid Mech. 175 1 1987 ADS. 89 XY ADV.
Math, Mech.
11 640 2019 Math Net. 90 X Woo.
Rev. Fluid Mech.
49 23 2017 ADS. 91 YS OS FT Smith J Fluid Mech. 251 273 1993 net. 92 PS KD LM J Fluid Mech. 12 1 1 1962 ADS. 93 A.D J Fluid Mech. 52 393 1971 net. 94 T Bull.
IM.
Soch 26 1257 1981. 95 RF JH J Fluid Mech. 132 87 1983 ADS. 96 S Berlin MDS J Fluid Mech. 393, 23, 1999 ADS. 97 CB Lay, RQ Lay J. 8 N55, 2007. Org 101080146852406009251163. 98 CL MR Malik J Fluid Mech. 273, 323, 1994 ads. 99 XY CB Lay INCAS Bull. 11-3, 77, 2019. 100 PW SJ WC, an experimental investigation of the flow structure of the turbulent boundary layer.
Tech, Rep, Mech, Rep.
MD 8, 1963. 101W, numerical simulation of boundary layer transition by combined compact difference method. D. Thesis, Technological University, Ave, Singapore, 2013. 102W, Y Yang S. Fluids 28-3, 35,110, 2016. 103H, SJ, WC, J Fluid Mech. 51, 133, 1971 ADS. 104 C.R. Smith, in Proceedings of the 8th Symposium on Turbulence, Ed. By J. and G., University of Missouri, 1984. 299, 325. 105 KN, R. MAB, J Fluid Mech. 48-2, 339, 1971 ads. 106 RF, RE, J Fluid Mech. 76-1, 89, 1976 ads. 107 SS, WW, J Fluid Mech. 63, 481, 1973 ADS. 108 DG, WG, J Fluid Mech. 162, 389, 1986 ads. 109 JM Hamilton, JF, J Fluid Mech. 287, 317, 1995 ads. 110 G, S, J Fluid Mech. 449, 291, 2001 net. 111 D, J Fluid Mech. 580, 339, 2007 net. 112 HP. JL. Fluids 10-9, 1880, 1967 ADS. 113 S, the large-scale structure in the near-wall region of turbulent pipe flow. D. Thesis, Department Mechanical Engineering, University, Ithaca, New York, 1986. 114 D. T. Williams. 347, 1959 ADS. 115 VI, VR, YS, DGW, U Rist, QX, CB Lay. Fluid Dyne. 15.5, 317, 2002. 116 CB Lay. Rev. E62.3, 3659, 2000 ADS. 117 S. Patterson, London, Edinburgh, Dublin. Mag. J. 3203, 437, 1940. 118 AM, JMG, J Fluid Mech. 163, 459, 1986 ads. 119 QX, ACTA. Mech. Sen. 15.3, 193, 1999 ads. 120 JK, FM Richardson, KO. And 47-1, 29, 1955. 121 QX, J Fluid Mech. 215, 101, 1990 ads. 122 GL Brown, A. Turbulent Shear Flows AGARD CP93, 23, 1971. 123 X Wu, P. RJ Adrian Jr. Proc. ACAD. 112-26, 79-20, 2015 ads. 124 Y Yang S. J Fluid Mech. 802, 2016. 125 Y Yang S. J Fluid Mech. 793, 840, 2016 net. 126 CB lay, ZX, YSVI, VV, exp. Fluids 28.3, 243, 2000. 127 CB lay, SY, in transition and turbulent control. 2 World Scientific, 2006. 3986. 128 PJ, DS, Stability and Transition in Shear Flows, Springer, 2012. 129 J. Luo, J. Aeronaut. 36-1, 357, 2015. 130 KJA, AA, VV, PH. J. Mech. B. Fluids 17.6, 823, 1998. 131 VI, AV, YS, AP, J. Fluid Mech. 716, 487, 2013 net. 132 AV, AP, Fluid Dyne. 26-4, 531, 1991 ADS. 133 AV, AP, ASME Fluid. Conv. 151, 1s 1993. 134 AV, ND, AHG, AIAJ 39-4, 605 2001 ADS. 135 T, N in 23rd Fluid Dynamics and Lasers Conference, Orlando, FL 1993, P3053. 136 AV, J. Fluid Mech. 491, 101, 2003 ADS. 137 AV, AP. Fluid Dyne. 14.6, 359, 2001. 138 P in 45th AIAA Fluid Dynamics Conference, Dallas, Texas, 2015, P2473. 139 YMA, X, J. Fluid Mech. 488, 79, 2003 net. 140 K, P, O in 45th AIAA Aerospace Sciences Meeting and Exhibit, Nevada, Reno, 2007, P945. 141 YD, DX, YW Ma, XL Lay. China 5111, 1682, 2008. 142 XY, CB Lay, J. Exp. Fluid Mech. Chen. 31-2, 1, 2017. 143 P, YAAM, GMJ, in Proceedings of the SFB TRR 40 Summer Program, Munich, Germany, 2011. 121, 138. 144 IV, AV, VG, J. Fluid Mech. 601, 165, 2008 net. 145 KD, XY, XGR, RA Fisher, SB, AIAJ 5310, 3138, 2015. Org 10-25141J0, 54100. 146 AE, GV, an experimental investigation of wall cooling effects on hypersonic boundary layer stability in a quiet wind tunnel. Tech, Rep. NASA CR 198287, 1996. 147A, in 26th Heat Transfer and Fluid Mechanics Institute Meeting, Wash, Pullman, 1978. 3955. 148 VI, AA, J. Fluid Mech. 147, 39, 1984 ads. 149 AA, AN, AAD, J. Fluid Mech. 426, 73, 2001 ADS. 150 L lays, the stability of the laminar boundary layer in a compressible fluid. Tech, Rep. NACA TR 876, 1947. 151 LM MAC, Space Programs. 37, 297, 1963. 152 LM MAC, Space Programs. 4, 165, 1964. 153 LM MAC, Boundary Layer Linear Stability Theory. Tech, Rep. AGARD R709, 1984. 154 FP, T, PR, J. Fluid Mech. 242, 441, 1992 net. 155 Y, C. Math, Mech. 36.7, 835, 2015 MathNet. 156V, Prague. 39.4, 249, 2003. 157P Pairs, Advances in Global Instability Computations, from Incompressible to Hypersonic Flow. D. Thesis, Technical University of Madrid, Madrid, Spain, 2014. 158 PJ. Rev. Fluid Mech. 39, 129, 2007 ads. 159 T. Rev. Fluid Mech. 21, 487, 1988 ADS. 160 LLG. Fluids a 44, 710, 1992 ADS. 161 NML. Fluids a 44, 727, 1992 ADS. 162 JREN S. J Fluid Mech. 781, 388, 2015 net. 163 KJ SK J Fluid Mech. 730, 491, 2013 net. 164X YD CBLA J Fluid Mech. 820, 693, 2017 net. 165P Pairs FLA in 55th AIA Aerospace Sciences Meeting, Grapevine, Texas, January 2017 P66. 166 XS Wu ACTA. Mech. Sen. 24, 327, 2004 ads. 167 A. Al. Nonlinear modal interactions in a compressible boundary layer. D. Thesis, Imperial College London, University of London, London 2003. 168 C. J. Luo. Maths. Mech. 38.8, 1109, 2017 MathNet. 169 G. M. in 19th AIA Fluid Dynamics, Plasma Dynamics and Lasers Conference, Honolulu, Hawaii, 1987, P1416. 170, Numerical Investigations of Transition in Hypersonic Flows over Circular Cones. D. Thesis, the University of Arizona, Tucson, Arizona, 2008. 171 X. Lee, D. Wyma, AIA J4611, 2899, 2008 ADS. 172 J. HF J Fluid Mech. 756, 600, 2014 ADS. 173 H. Joe, C. Y. Transition Mechanisms and Prediction of Supersonic Hypersonic Flows, in Chinese, Science Press China, Beijing, 2015. 174 SB, J. Rockets 36-1, 8, 1999 ads. 175 Y. X in AIA 200108892 2001, P 892. 176 KF Stetson, RL, AIA J 3011, 2782 1992 ADS. 177 K P O in 38th Fluid Dynamics Conference and Exhibit 2008, P 3734. 178A J Fluid Mech. 73, 385, 1960 ads. 179A YD A Prague. Flight 7, 549, 2015. 180 VG, IV, AV, in 6th European Symposium on for Space Vehicles. 659, 2009. 181A, AIA J421, 89, 2004 ads. 182P, AIA J561, 193, 2018 ads. 183 NR, Effects of Nose Bluntness on the Boundary Layer Characteristics of Conical Bodies at Hypersonic Speeds. Tech, Rep. NYU AW 6666, 1966. 184 MW Tufts, RL, in AIA 2017764, 2017, P764. 185 PA, WKOZIAK, AIA J115, 730, 1973. 186 KF Stetson, in AIAA 22nd Aerospace Sciences Meeting, Nevada, Reno, 1984, p6. 187 K. Stetson, E.J.L. in AIAA 831761 1984, p1761. 188 K. Stetson, R. in AIAA 920737 1992, p737. 189 Tai J. M.P. Borg, S.B. AIAA J534, 832 2015 ADS. 190 SB, DA, YV, DV, AN, AIP Conf.
Prague.
1771, 30057, 2016. 191 M. Malik, R. Spall, CL, in AIAA 90112, 1990, P112. 192 G. S. Fluids 11-1, 7, 1999 ads. 193 J. Lay, X. J. Rockets 49-1, 24, 2012 ads. 194 GH, KF Stetson, AIAA J55, 899, 1967 ADS. 195 E in GE Space Science Lab, R68 SD14, 1968. 196 BC, IJ, RE, AIAA J72, 257, 1969 ADS. 197 VI, J.
Mecca.
31-6, 868, 1990 ads. 198 AV, J.
Mecca.
31-5, 722, 1990 ads. 199 E, MMS Con, in IUTAM Symposium on Laminar Turbulent Transition, EAD. By R. and H. Springer, 1980. 186 190. 200 S. ERCOFTAC Bull. 74 57 2007. 201 RT Greenwood, measurements of entropy layer instabilities over cone ogive cylinders at Mach 6. Day Thesis, University, West Lafayette, Indiana, USA, 2014. 202 EC, GC, DR Lewis, JD, JF, RM, JA Smith, in 19th AIAA International Spaceplanes and Hypersonic Systems and Technologies Conference, Atlanta, GA, June 2014, P3108. 203 A, AV, A, in UCSS 2017120, 2017. 2224. 204 SB, J. Rockets 45-2. 193 2008 ADS. 205 PBC J. S. Jones, in 47th AIAA Aerospace Sciences Meeting including the New Horizons Forum and Aerospace Exposition, Florida, Orlando, 2009, P394. 206 FD FFJ FG AIAJ. 1892-1900, 2016. 207 MA, R.A. King, M. F. Lee, A.T., in 7th AIAA Theoretical Fluid Mechanics Conference, Atlanta, GA, 2014, P2501. 208 A. S. Prague.
Flight
9451, 2017. 209 KM Casper, H.B. Johnson, S.B.J. Rockets 48-3, 406, 2011 ads. 210 F, FFJ-G. Fluids 28-2, 24,106, 2016. 211 B. Wheaton, S. M. P. G. Candler, in AIAA Paper 2011-3248, 2011, P3248. 212 B. M. Wheaton, S.B. AIAA J56, 1245, 2012 ads. 213 B. M. Wheaton, S.B. J. Rockets 51-1, 327, 2013 ADS. 214 E.R. Van Dryest, J. 29-8, 909, 1962. 215 E. AIA J45-7, 1441, 2007 ads. 216 W. S. M. Musa, in AIA 880053, 1988, P53. 217 H. H. J. Fluid Mech. 316, 73, 1996 ads. 218 KF Stetson, J. Rockets 19.5, 397, 1982 ads. 219D in 15th AIA International Spaceplanes and Hypersonic Systems and Technologies Conference, Ohio, Dayton, 2008, p. 2581. 220 SA WS Proc. IUTAM 14, 15, 2015. 221 MP Borg, RL SJ. Rockets 52-3, 664, 2015 ads. 222 MR Malik, FLA, CL, in IUTAM Symposium on Nonlinear Instability and Transition in Three-Dimensional Boundary Layers, Manchester, UK Springer, 1996. 257 266. 223 RB, FR, AIA J4712, 2894, 2009 ADS. 224 YT, STY in AIA Paper 2009-1145 2009, p. 1145. 225 C, AJ. 55 1533, 2013 ADS. 226 SJ in 21st AIA Computational Fluid Dynamics Conference, San CA June 2013, p. 3081. 227 Y, JJ T Yang, J Aeronaut. 3 780, 2016. 228 P Pairds V in AIA 2013280, 2013, p. 2880. 229 X Lay, SJZ J Luo Y Acta. Sen 36-2, 256, 2018. 230 Jisoo, JG S Dong S J Fluid Mech. 873, 914, 2019 net. 231 YF Han, SX Ma CH Acta. Sen 37, 522, 2019. 232 WS. Rev. Fluid Mech. 26-1, 379, 1994 ADS. 233 NL, AK, in 14th Fluid and Plasma Dynamics Conference, Alto, California, 1981, p. 1278. 234H, SH, DA Shaw. Fluid 1611, 3983, 2004 ads. 235 JD, RF, J Fluid Mech. 182, 255, 1987 ADS. 236 P Hall, NJ Horseman, J Fluid Mech. 232, 357, 1991 net. 237 FLA, MR Malik, J Fluid Mech. 297, 77, 1995 net. 238 C Wang, X, in 39th Aerospace Sciences Meeting and Exhibit, Reston, Virginia 2001, p. 273. 239 M, FLA, CL J Edwards M, R King, in 48th AIA Aerospace Sciences Meeting including the New Horizons Forum and Aerospace Exposition, Orlando, Florida 2010, p. 1575. 240 J Ren, S. China, Mecca. 57-6, 1178, 2014. 241A V JSM in 53rd AIA Aerospace Sciences Meeting American Institute of Aeronautics and Astronautics, Kissimmee, Florida, 2015. AIAA Paper 2015-0275. Org 1025-14620-150275. 242X GL CB Lay J Fluid Mech. 865-1 2019. Org 1010-1720-1924 net. 243 MV Bull. IM Zojin. 39 1882 1994. 5. Structure evolution at early stage of boundary layer transition, simulation and experiment. Abstract. The beginning of laminar, turbulent transition is usually associated with a wave-like disturbance, but its evolution and role in precipitating the development of other flow structures are not well understood from a structure-based view. Nonlinear stability equations, NPSC, were solved numerically to simulate the transition of K regime, N regime, and O regime. However, only the K regime transition was examined experimentally using both hydrogen bubble visualization and time-resolved tomographic particle image, PIV. Based on the NPSC visualization and tomographic visualization, at least 4 common characteristics of the generic transition process were identified. Inflectional regions representing high shear layers HSL that develop in vertical velocity profiles, accompanied by ejection sweep, low-speed streak LSS patterns manifested in horizontal timelines that seem to consist of several three-dimensional 3D waves. A warped wavefront WWF pattern displaying multiple folding processes which develops adjacent to the LSS in the near-wall region prior to the appearance of vortices. A coherent 3D wavefront similar to a soliton in the upper boundary layer, accompanied by regions of depression along the flanks of the wave. It was determined that the amplification and lift-up of a 3D wave causes the development of the HSL, WWF, and multiple folding of material surfaces that all contribute to the development of a vortex. The amplified 3D wave is hypothesized as a soliton-like coherent structure, SCS. Based on our results, a path to transition is proposed, which hypothesizes the function of the WWF in boundary layer transition. Supplementary information. The online version contains supplementary material available at org 10-100 7978 980 195 244 195. Keywords. This chapter is reproduced with permission from XY, CB Lay, X, CR Smith, and PF Linden. Structure evolution at early stage of boundary layer transition. Simulation and experiment, J Fluid Mech. 890, A11, 2020. Copyright 2020, Cambridge University Press. The content of the article has been slightly revised. 5.1 Introduction. The transition of fluid motion from a laminar state to a turbulent state has been an unresolved conundrum in wall-bounded shear flows. Typically, there are 3 transition regimes for boundary layer flow, which demonstrate different features during the transition process, namely the K regime, N regime, and O regime. The 3 transition processes are mainly investigated from a spectral point of view and a structure-based view 1-2. The former view usually employs frequency Fourier analysis to obtain the amplification rates of different modes. A structure-based view mainly examines the spatial temporal flow structures extracted from experimental or numerical data sets. Generally, when described in terms of frequency, where the is the fundamental frequency, and a K-regime transition is usually initiated by a primary T, S wave 0, and a pair of symmetric oblique waves with the same frequency as that of the primary two-dimensional 2D wave. The K-regime is named after Al. 3, who studied the three-dimensional nature of boundary layer instability under controlled conditions, and the typical pattern for this regime was characterized as peak and valley regions with very high amplitudes of the perturbations in the peak positions. They determined that a 2dt S wave will interact with the mean flow and then rapidly develop into a 3D wave, forming aligned structures, which finally breaks down to turbulence. For the N regime transition, an initially primary planar wave, 0, interacts with a pair of subharmonic oblique waves with frequency equal to half the primary wave, i.e. 2, to form structures positioned in a staggered order. The N regime is also called the subharmonic regime 4, or the H regime, after 5, both of who provided theoretical formulations of the resonant amplification of the subharmonic modes. The detailed experimental work on N regime breakdown was carried out at Novosibirsk 6-7, where it was determined that the N regime is also characterized by amplification of a wide low-frequency disturbance around the subharmonic frequency 2 and growth of disturbances at frequency of 2N3, 5, 7. Finally, the O regime discovered by N8 and N9 is induced by a pair of oblique waves with equal but opposite angles. These oblique waves will drive a rapidly growing zero-frequency mode, 0-2, which is associated with low-speed streaks and or vortices. Mutual and self-interactions of the vortex streaks and the oblique waves result in the rapid growth of other harmonic waves and form a pattern of staggered vortices within the subsequent transition. The similarity between the regimes mentioned above has been assessed 2-10-11, especially for the K and N regimes 12-13. The K and N regimes were incorporated into the framework of a wave resonance concept by 14, and it was shown that the two regimes can be transformed to each other depending on the initial conditions 15.
Bake al.
13 compared the late stage of K and N regime transition experimentally, and they observed that these two regimes bear a strong similarity in the local processes of nonlinear disturbance and the features of the developing flow structures.
Al.
16 evaluated the breakdown of K and N regimes to turbulence during late-stage transition using DNS, and determined that the flow statistics and near-wall dynamics are similar, which led them to propose that the late-stage transition manifested by hairpin packets as a reduced-order model of a turbulent boundary layer.
1.
Or hairpin-shaped structures during late-stage transition, characterized by aligned or staggered order 16-17. Or hairpin-shaped structures during late-stage transition, characterized by aligned or staggered order 16-17.
2.
Negative peaks in the velocity time traces termed spikes, occurring in the peak region, which doubled, tripled, etc. Downstream, representing strictly a deterministic and periodic structure 1-7-18. Negative peaks in the velocity time traces termed spikes, occurring in the peak region, which doubled, tripled, etc. Downstream, representing strictly a deterministic and periodic structure 1-7-18.
3.
A structure similar to ring-like vortices, termed coherent structures Soliton CS Soliton, describing the soliton of velocity spikes 1922. A structure similar to ring-like vortices, termed coherent structures Soliton CS Soliton, describing the soliton of velocity spikes 1922.
4.
A localized and intensified warped wave front 2324, accompanied by a kinked high shear layer 25, appearing prior to the development of a vortex. A localized and intensified warped wave front 2324, accompanied by a kinked high shear layer 25, appearing prior to the development of a vortex.
5.
A three-dimensional wave-like structure, termed a soliton-like coherent structure SCS, appearing farther upstream prior to development of a vortex 26-28. A three-dimensional wave-like structure, termed a soliton-like coherent structure SCS, appearing farther upstream prior to development of a vortex 26-28.
6.
Wave packets that involve a T, S-wave 29, or temporal wave front STWF 30. Wave packets that involve a T, S-wave 29, or temporal wave front STWF 30.
7.
Streaks that are surrounded by warped wave fronts 31, or flanked by vortices 232. Streaks that are surrounded by warped wave fronts 31, or flanked by vortices 232. Different hypotheses have been made regarding the mechanisms responsible for the generation of the velocity spikes and low-speed streaks. Some of these hypotheses are correlated with vortical structures, e.g. hairpin vortices, but others are based on non-vortical structures, e.g. wave packets, and there is no current consensus on the relationship between the wave packets and vortices. The similarity between different transition regimes in previous studies usually focused on the late stage of transition, where hairpin vortices, hairpin packets, ring-like vortices, or multiple spikes have already appeared. In the present study, we focus on the coherent wave states 4-5, which emerged during the early nonlinear stages, prior to the appearance of any apparent vortices. In the classical work of Hama and his colleagues, which employed hydrogen bubble visualization to observe structures within a transitional boundary layer 23-33, they observed that the T-S wave warps 3 during amplification, acquiring a longitudinal vorticity component along its swept-back front. This region of concentrated high shear layer, which appears as an inflection in vertical hydrogen bubble timelines, a kink, subsequently develops into a hairpin-shaped discrete vortex. This localized and intensified warped or kinked structure was considered as the source of subsequent hairpin-shaped vortices. Here we refer to this kinked structure as a warped wave front, WWF. This warping process and kinked profiles were frequently observed experimentally or numerically in transitional boundary layers 1, 12, 24, 26, 31, 34. However, the roles of a WWF in transition are often underrated, and the manner in which a WWF originates and evolves is not well understood. This emphasizes the need to examine the details of the warping process and the development of a WWF prior to the emergence of vortices. A hypothesis based on a three-dimensional wave-like structure has been proposed as an explanation of the velocity profile kink 2635. Such a 3D wave-like structure was observed within the whole boundary layer, covering the near-wall region to the outer edge, in almost all dynamic processes for both the early and later stages of a transitional boundary layer. The structure was later termed a soliton-like coherent structure, SCS 273637. Using DNS 28 confirmed the existence of a SCS and its dominant role in the vortex evolution process. However, the above-mentioned experimental results were based on flow visualizations or hot wire measurements, while the numerical study is mainly based on the assessment of isosurfaces or instantaneous fields. The objective of the present paper is to characterize the 3D wave structures during the early nonlinear stage of transition and to understand how a WWF evolves into a vortex. In a framework, we focus on a piece of history of the flow, employing a visualization method based on tracking the basic trajectories of marked particles 38-39. We use both time-resolved tomographic particle image, PIV, measurements and the solution of nonlinear stability equations, NPSC, to obtain three-dimensional data sets of the spatial-temporal transition process. These data sets are then used to examine the details of the wave warping process and to examine the relationship between 3D waves, low-speed streaks, and vortices in transitional boundary layers. The remainder of this paper is organized as follows, in sect. 5.2 The method of NPSC is described, including the numerical settings for the three transition regimes and the method of tracking, in sect. 5.3 The results of the NPSC calculations, including K-regime, O-regime, and N-regime, are presented, in sect. 5.4 The experimental procedure is described, and the results of the experiments, only the K-regime, are compared with the simulations, in sect. 5.5 The underlying physical mechanism is discussed, and a possible unified transition path is proposed based on the experimental numerical comparisons, and conclusions are given in sect. 5.6 5.2 Method of numerical simulation. 5.2 1 Nonlinear stability equation. 5.2 Numerical setting and mode description. Numerical settings for all three simulations. A normalized notation is used in mode description. The first digit indicates multiples of the fundamental frequency, and the second digit refers to multiples of the fundamental. Transition regime. 2-day wave. 3-day wave. Mode. F106. A mode. F106. AK regime. 10. 106. 0.2% U11. 106. 0.05. 0.14% UN regime. 10. 106. 0.2% U 0.51. 53. 0.05. 0.14% UO regime. 1 1s. 106. 0.05. 0.2% U523 method of tracking. Three-dimensional data sets of the spatial-temporal transition process are obtained from the solution to the NPSC and also from the PIV measurements. These data sets are used to reconstruct flow structures by employing tracking of marked particles. So it is helpful to revisit the concepts of the and timelines. In the present study, fluid trajectories are extracted from the three-dimensional data sets based on the integration of 5.8. This is achieved using a MATLAB algorithm that employs an ODE solver and interpolation scheme. The Prince method ODE 45 in MATLAB is chosen as the solver for trajectory advection, and the absolute and relative tolerances of the ordinary differential equation, ODE solver, were set at 10.6. Equation 5.8 is integrated over a time interval t0, t1 for an initial condition. The initial condition can be either a specific point, straight line, curve, surface, or a grid volume. In order to generate timelines similar to hydrogen bubble timelines, the initial condition is set as a fixed horizontal or vertical line, and the integration is implemented iteratively with an updating release time. Timeline patterns are formed by determining and displaying a sequence of timelines generated at a fixed frequency. Emulating the term of hot wire visualization introduced by Al. 45. The patterns extracted from the NPSC and PIV databases using this integration process are referred to as NPSC visualization and tomographic visualizations, respectively. Note that the result of flow visualizations should be interpreted with caution. As mentioned in 46, the visible patterns are not the structures themselves, but their footprints. Many of the previous studies of wall-bounded flow were based on technique of manual or automated image processing of pictures of hydrogen bubble timelines taken using a single-view or dual-view system 46-50. These approaches proved effective and useful for assessing the spatial temporal characteristics of boundary layers and detection of coherent flow structures. However, acquisition of sequences of instantaneous, quantitative, three-dimensional velocity data is not feasible using hydrogen bubble visualization. The solution of NPSC and time-resolved PIV can obtain such types of spatial temporal velocity field data, making the detection of three-dimensional, unsteady velocity vector fields, even vorticity fields, possible. Such spatial temporal data can then be interrogated, and timelines can be generated for comparison with hydrogen bubble images and for assessing and identifying three-dimensional flow. 5.3 Numerical results. 5.3.1 Basic features of three transition scenarios. Skin friction coefficient for the three transition regimes, A and mode amplitude evolution for K regime transition B, O regime transition C, and N regime transition D. The arrows in B and C indicate a slightly declination of the primary wave. The numbers in bracket denote normalized frequency as described in sect. 5.2.2 Table 5.1. MDF in C means main flow distortion. Figure 5.1c illustrates the evolution of four primary modes for O regime transition. The modes 0, 2, 0, 4 and mean flow distortion, MFD mode 0, 0 are excited nonlinearly due to the interaction of modes 1, 1. After generation, the streak mode 0, 2 undergoes a transient growth stage due to a lift-up effect 52 and then becomes saturated for R650. Mode 04 also grows rapidly and becomes saturated driven by mode 02 until R670, where it again begins to amplify, eventually surpassing the amplitude of mode 02. The last growth of mode 04 is likely due to a secondary instability of the streaks. The location where the mode 04 surpasses the primary oblique mode is consistent with the location where the skin friction begins to deviate from its laminar value in Fig. 5.1 So, the first deviation of the skin friction curve is due to the growth of the streak mode, while the second deviation, which begins at R708, might be explained by the secondary instability of the streaks. For N regime transition in Fig. 5.1d, during the amplification of the oblique mode, the primary wave undergoes a slight decrease, which is similar to the K regime C arrows in the figure. But the streak mode does not develop during the initial stage. Thus, the nonlinear amplification of the 3D wave is mainly attributed to the growth of subharmonic oblique disturbances, which is consistent with previous results of experiments and DNS 53. Contour of velocity U, the shading at Y2.5 and T0.8T, superimposed with isosurfaces of Q criteria detected structures, the red regions, Q0000022. A K regime transition, B O regime transition, C N regime transition. The flow is from left to right. For the O regime and N regime, Fig. 5.2b, C, the LMZs appear as staggered patterns. The staggered 3D waves, dark regions within the dashed circles, for the O regime develop nonlinearly from a pair of oblique waves, 1, 1, appearing farther upstream than for the N regime, with a wavelength of 12566. The streaks, the dashed lines shown for the O regime, are spaced by 26283 as a result of the growing streak mode 2. The low-speed streak LSS-1 in Fig. 5.2b consists of several 3D waves, indicated by the dashed circles along the streak. The vortices are observed to develop in conjunction with LSS regions, in a staggered pattern. For the N regime Fig. 5.2c shows that the LMZs and vortices that develop well downstream are larger than those for the K and O regimes, since the wavelength of the amplified 3D wave is twice that of the primary 2D wave. No streak is observed in Fig. 5.2c, which agrees with the development of mode amplitudes in Fig. 5.1d because the 3D waves appear prior to a vortex, as indicated by the position of the LMZs in the figure. A vortex is most likely produced by the nonlinear 3D wave. It will be shown later that the 3D waves are very similar to the soliton-like wave structure mentioned previously. 5.3.2 K-regime transition. 5.3.2 evolution of timelines and K-regime timelines initiated at x1011, y1.71 with dt12. A T5.6T BT6.1T WWF warped wavefront K kink structure R rollup LSS low-speed streak. Figure 5.3 shows two snapshots of timelines initiated at y1.71 after development times of T5.6T and 6.1T. Here T is the normalized time period of the primary wave defined in sect. 5.2.2. The timeline surface is displayed in scale, where the vertical location of the surface indicated by the scale to the right of the images, darker is nearer the wall and lighter farther from the wall. This represents a continuous timeline surface, similar to a timeline sheet formed by continuously releasing hydrogen bubbles. The translucency of the surface is set as 70% to allow observation of the deformation of the timeline sheet. The volumetric rendering is sketched in the right schematic diagram. So the shading in the figure shows the overlap of the surface, caused by the folding of the timeline's surface. Figure 5.3 shows the deformation of the timeline sheet at T56T, the of which is identified by a series of stages 1 to 5, showing the evolution from the initial T, S wave to a vortex. Figure 5.3b shows the spatial development of the timeline surface patterns at T61T, a half-primary period later relative to Fig. 5.3 Figure 5.3 clearly shows how a vortex develops. Starting at stage 1, the 2dt S wave is distorted into a three-dimensional wave, 3D wave, with its wavefront warped, indicated as a warped wavefront, the wavefront of a modulated two-dimensional wave that is strongly warped, as evidenced by the accumulation of times lines at stage 2. During stage 2, the WWF develops a fold in the timeline sheet, and a low-speed streak appears, indicated by the retardation and downward motion of the timelines, as LSS. By stage 3, the 3D wave lifts up, with the WWF beginning to accelerate, leading to an initial roll-up of the wave front by stage 4, see R1 and R2 in stage 4. This initial roll-up subsequently develops into an apparent vortex, at stage 5 in Fig. 5.3 on stage 4 in Fig. 5.3 The roll-up causes multiple folds of the surface, reflected by the darker shaded regions of the translucent sheet. During the folding process, depressions V1 and V2 of the sheet towards the wall appear flanking the hairpin vortex, which subsequently develop into vortices, SV and Fig. 5.3 Meanwhile, the kink structure, K, is observed to develop a chevron-shaped structure at a downstream position, C. The details of the folding process are shown further in Figs. 5.4 and 5.5. Plan view of the evolution of a single structure based on K-regime timelines, the upper row, and a timeline surface, the lower row, initiated at y1.71, with release interval dt0.2t, a bt5.1t, cdt5.6t, ft6.1t, ght6.6t, ijt7.1t. First F, first folding, second F, second folding, SV, vortex. See the supplementary Movie 1 for the complete evolution. End view of K-regime timelines, looking downstream at the same time intervals as Fig. 5.4 A T5.1t, BT5.6t, CT6.1t, DT6.6t, ET7.1t L, lift up. In Fig. 5.4f, it is observed that the surface appears to develop a new fold, second f, which projects outward and above the portion of the surface marking the WWF. This second surface fold is more obvious at the later time of t and will progressively develop into a vortex, as shown in Fig. 5.4h, when a vortex appears, the timeline's surface comprising the WWF begins to squeeze together and lift up, as the sequence of Fig. 5.4e shows. Previous studies assumed that the first folding, first F, leads to the development of a vortex 23. However, Fig. 5.4 clearly demonstrates that a vortex develops from the second folding, second F of the wave front. The lifting of the 3D wave deforms the 2D timelines and causes the first and second folding. It should be noted that the chevron-like structure, see in Fig. 5.4FH is actually a reflection of the low-speed streak developing near the wall along the center line, red line in the figure. The two high-speed valleys, V1, V2, that were previously identified in Fig. 5.3, which flank the chevron-like structure C, are shown in Fig. 5.4H, to develop into rotational vortices, SV1, SV2. Note that the above warping process is unobservable when the timelines are initiated at a higher position, such as Y383. In that case, the evolution of three-dimensional wave is obvious. See the supplementary movie 2 for the complete evolution. Figure 5.5 shows the corresponding end views of the 5 timeline patterns shown in the top row of Fig. 5.4. These end view patterns clearly demonstrate the lift-up, L in the figures of a 3D wave. Note that Fig. 5.5d, E shows that the second folding of the timelines protrudes above the first folding, which develops into the head of a vortex. The development of the two vortices is also clearly shown in Fig. 5.5c, SV1 and SV2 flanking the sides of the lifted WWF. The breakdown of a wave motion into hairpin eddies has been demonstrated to be a consequence of the instability arising from three-dimensional wave 3. Suggested the instability was similar to a secondary inflectional instability. The results of the present investigation also indicate that the vortex develops from a 3D wave-induced inflectional instability. Figure 5.6 shows the evolution of vertical timelines initiated at Z126, near the center plane shown as red line in Fig. 5.4, with release intervals of dt0.16t. The extent shown for the x direction is almost 5.5, whereas the wavelength of the primary t, s wave. The instantaneous velocity profiles at t2t, 3t, 4t, 5t are markedly similar to those shown by Hama and 23 using hydrogen bubble timelines. As shown in Fig. 5.6, an inflectional high shear layer, HSL, develops as the 3D wave lifts up. This is followed by the development of a warped wavefront, as shown in Fig. 5.6b. Figure 5.6c shows that the WWF undergoes further stretching and develops the first folding of timelines, first F, with the kink structure K also developing during the folding process. The leading edge B of a WWF creates a strong downward sweep S as transition proceeds. Finally, as shown in Fig. 5.6d, rotation R of the WWF progressively evolves into the head of a vortex, which results in the entrainment of higher speed outer flow into the vortex and towards the wall. Side view of vertical timelines initiated at Z126, near center plane for K-regime transition, with release intervals dt0.16t. A T2t, BT3t, CT4t, DT5t. The wavelength 52.7. HS high shear layer W, 3D wave B, wavefront leading edge WWF, warped wavefront L, lift up R, rotation K, kink structure S, downward sweep. See the supplementary movie 7 for the complete evolution. Evolution of K-regime initiated at Y1.71 and 3.83 on the plane of Z126, red line for T04T, black line for T0 plus 072T, L, lift up. 5.322, evolution of material surfaces. Evolution of a material surface initiated at y1.71 for K-regime transition. A T1T, BT2T, CT3T. Note that the wall normal coordinate scale is 10 times. 533 O regime and N regime transition. The evolution of a single structure based on O regime timelines initiated at y1.71 with release interval dt0.3t. Upper row end view of timelines, middle row plan view of timelines, lower row plan view of a rendered timeline surface. A CT4TD FT5TG IT6TJ LT7TM OT8T. See the supplementary movie 3 for the complete evolution. The evolution of a single structure based on timelines generated for the O regime is shown in Fig. 5.9. See the supplementary movie 3 for the complete evolution of how a 3D wave develops into a vortex in O regime transition. Figure 5.9. A D, G, J, M shows end views of 5 timeline patterns from T4T to 8T. Similar to the patterns shown in Fig. 5.5 for the K regime, the 3D wave is initially very weak Fig. 5.9 but then develops into a WWF and expands in both the normal and directions, moving progressively upward. Some instability occurs adjacent to the two sides of the WWF, as illustrated by the intertwining timelines in Fig. 5.9 M. Figure 5.9b, E, H, K, N, and C, FILO show the corresponding plan view of the development of a vortex in O regime transition, both for individual timeline B, E, H, K, N and as a developing timeline surface C, FILO. First, the interaction of oblique waves produces a 3D wave, manifested as weakly retarded timelines LSS or a small bulge red dashed circle, Fig. 5.9b. See next, the lift-up of the 3D wave produces a warped wave front, with rhombic creases appearing on the timeline surface, as indicated by the red dashed lines in Fig. 5.9 F. The first folding, first F of the surface strengthens the creases, red dashed lines, that flank the WWF Fig. 5.9 I. During the strengthening process, regions of apparent depression V1, V2, SV1, SV2 form, similar to those shown in Fig. 5.3. Subsequently, a chevron-like structure C develops below the WWF, constituting a more confined LSS as shown in Fig. 5.9 K L. Finally, the second folding develops on the timeline surface to form a vortex, during which the previous rhombic creases begin to rotate, developing vortices from the initial regions of depression Fig. 5.9 N. O. Note that the above multi-folding process is not discernible when the timelines are initiated at Y383. In that case, the evolution of three-dimensional wave is clearly observed, which seems to constitute a low-speed streak. See the supplementary movie 4 for the complete evolution. The evolution of a single structure based on N-regime timelines initiated at Y1.71 with release interval dt0.3t. First row end view of timelines, second row plan view of timelines, third row plan view of rendered timeline surface. A CT 5.1TD, FT 6.4TG, IT 7TJ, LT 7.5T, JLT8T vertical timelines of O regime transition at a T3T and BT 4.6T, initiated near the center plane Z126. See the supplementary movie 7 for the complete evolution. Vertical timelines of N regime transition at a T3T and BT 4.6T, initiated near the center plane Z126. See the supplementary movie 7 for the complete evolution. Evolution of for O regime transition initiated at different wall normal positions Y0. A Y0 1.71 and 3.83, BY0 2.54 and 4.25. T0 4T red, T1 4.72T black. Evolution of for N regime transition initiated at different wall normal positions Y0. A Y0 1.71 and 3.83, BY0 2.54 and 4.25. T0 4T red, T1 4.72T black. Figures 5.13 and 5.14 show the evolution of for both O regime and N regime transitions. They are initiated at 4 different wall normal positions, i.e. Y0 1.71, 2.54, 3.83 and 4.25, and show patterns for two different development periods. For the origime, at the near wall position Y0 1.71 are stretched into a thin filament projecting strongly into the outer layer in the figure, indicating a severe wave deformation. When compared with patterns shown in Fig. 5.9, the location of the thin, stretched filament is consistent with the location where a vortex develops. However, note that comparably strong wave deformation does not occur for the initiated at Y0 3.83 and 4.25, which behave essentially as a modest wave-like amplification. The initiated at Y0 2.54 in Fig. 5.13b shows the development of the first folding of the wave front, which is striking in its similarity to for the K-regime transition, generated at Y0 1.71 Fig. 5.7 for N-regime transition shown in Fig. 5.14, the initiated at the upper locations also reflect a modest wave-like amplification similar to the O-regime, although they do not move outward and appear more amplified than for the O-regime of Fig. 5.13, the waveform shows a superposition of the primary wave of wavelength of and its subharmonic of wavelength of 2, similar to the K-regime in Fig. 5.7, as shown by the initiated at Y0 3.83 and 4.25 in Fig. 5.14, the subharmonic wavelength 2 is strongly amplified downstream and becomes the dominant wavelength. This amplification may be a reflection of typical subharmonic resonance. Note that prior to the strong amplification to a 3D wave, there appears to be a relatively quiet zone, E in Fig. 5.14. The presence of this quiet zone is hypothesized to be the result of a nonlinear interaction between waves, i.e., the attenuation of the primary wave and the growth of a low-frequency disturbance at nearly 2. Indeed, the location of the quiet zone is identical to the position of the attenuation of the primary wave shown in Fig. 5.1d. Clearly, the mechanism for development of this quiet zone merits further study. Material surfaces at T1T, initiated at 795, 1309, 77, 175, Y0 3.83. A K-regime transition, BO regime transition, CN regime transition. Figure 5.15 shows the deformation of an initially flat material surface, 795, 1309, 77, 175, initiated at Y 3.83. For the three transition regimes at T1T, the black contour lines illustrate respective changes in Y height and show the development and growth of three-dimensional waves. Figure 5.15 shows that for the K regime, an upstream 2D wave progressively amplifies into an apparent 3D wave, appearing at about x1200. This 3D wave subsequently amplifies with its wave front, P, lifting up. At the front of the 3D wave, there is a region of depression S, which may be the result of a downward sweep event. As the 3D wave develops downstream, this region of depression evolves into two regions, V1, V2, flanking both sides of the rising 3D wave. Note that the wave front at this position does not undergo as severe a warping as shown in Fig. 5.8, which was for a material sheet, initiated much closer to the wall. For O-regime transition, Fig. 5.15b shows that a rising 3D wave, P, develops much sooner than the K-regime, which is also accompanied by regions of depression, S1 and S2. However, Fig. 5.15b shows the development of four longitudinal depressions or valleys, V1, V2, V3, V4, flanking the sides of the 3D wave fronts, which is markedly different from Fig. 5.15. These valleys span several wavelengths of the 3D wave in the direction. For the K-regime of Fig. 5.15, the spacing 1 between the valleys V1 and V2 is approximately 1,2, where the is the wavelength of the introduced oblique waves. However, the spacing 2 between valleys V3 and V4 in Fig. 5.15b for the O-regime is approximately half that of V1 and V2, i.e. 1,4. Two longitudinal streaks, LSS1 and LSS2, are observed outside the valleys V3 and V4, which are also spaced at about 1, similar to the spacing between V1 and V2. These streaks are identified as low-speed streaks, which are a result of low-speed fluid moving upwards due to some type of uplift events. Figure 515C shows the deformation of the material surface for N-regime transition, which looks similar to the K-regime, except that the dimensions of the 3D wave are larger, and the 3D waves develop later in the transition process. Regions of depression V1, V2, and S0, S1 surround the 3D wave, forming a staggered pattern. No longitudinal streaks or valleys are observed at this point of development for the N-regime. In the present section, kernel studies of both the O and N regimes followed the evolution of a 3D wave into a vortex. These studies were facilitated using spatial temporal visualizations of synthetic multiperspective timelines and material surfaces initiated at different heights and amplification periods. The results of O and N regime transition are compared to those of K regime shown in Sect 532, and the similarities of WWF and its warping process are pointed out. A mutual comparison of the deformation of material surfaces for all three regimes illustrates a similar pattern of 3D wave development in the transition process. 5.4 Comparison with experiments. 541 Description of the experiments. 5411 Facility and model. The experiments were performed in the PWT, Peking University Water Tunnel, an open-surface recirculating water channel with a cross-section of 0.4m04 m and length of 6 m. The tunnel velocity range is from 0.113 ms, with a turbulence level of 0.77% at the velocity of 0.17 ms for simplicity. Only experiments of K-regime transition were done, because it was easier to assure that the flow was comparable to prior studies at Peking University 37. The flat plate and disturbance generator were the same as those used by Lei and Li 37, which had been to be effective in producing T, S-wave, and K-regime transition. The flat plate test section, shown in Fig. 5.16, has a length of 1.8 m, a span of 0.8 m, and a thickness of 15. The flat plate was mounted vertically on the center line of the tunnel at 0 angle of attack, with an adjustable flap mounted at the trailing edge. The organized perturbations for the developing laminar boundary layer were generated using periodic suction and blowing at the wall, through a wall slit, 115 by 1, located on the working side of the plate, 200 from the leading edge. As shown in Fig. 5.16, a loudspeaker mounted on the top of a water tank generated a controlled 2-sinusoidal, via a signal generator, fluid injection suction pattern from the slit via a tube connected from the water tank to a plenum behind the slit. The amplitude of the force disturbance was approximately 1.1% U. 5412 Experimental techniques and data acquisition. Experimental setup of tomographic PIV, a plan view of setup for hydrogen bubble visualization, B schematic layout of the arrangement of the PIV system. Measurements of two boundary layer profiles compared with the profile. The PIV sampling frequency was 500, with a maximum sampling time of 20 s. The final residual calibration errors for all cameras was less than 0.1 pixel. The calibration field of view had a digital resolution of 74.8 m per pixel. The measurement domain extended 78 m in the direction and 78 m in the direction. Volume self-calibration 59 was used on the preprocessed particle images. Sequential motion tracking enhancement 60 was applied to volume reconstruction. The reconstructed volume was 1041-10-48187 voxels. A multipass approach of 4 steps was carried out for the volume correlation, and the interrogation volume size for the final pass was 16-16-16 voxels, 1.21212-3, with a 75% overlap. As a final step, a smoothing filter of 333 was applied to the velocity data. Proper orthogonal decomposition, POD, analysis has shown to be effective for noise removal and extraction of high modes in turbulent flow 61-62. In the present paper, POD analysis was applied to the smoothed velocity data sets, and the first 4 leading order POD modes are extracted, in accordance with the methods of AL.
63.
The pod-approximated vector fields are the data sets used in the following post-processing and analyses. 5413 Properties of the boundary layers and PIV accuracy. Characteristic boundary layer parameters and resolution parameters of PIV measurements is the momentum thickness based, number is the momentum thickness, and is the displacement thickness, h is the shape factor.
UMS, S
181, 170, 1.07, 2.77, 2.59, 0.3, 0.002. 542 Comparison with flow visualization. Hydrogen bubble visualization of transitional boundary layer. A plan view timelines at Y035. B continuous bubble visualization at Y035. C low speed streak and vortex at Y01527. D NPSC visualization of timelines initiated at Y0171 for K-regime transition. The flow is left to right. 543 Comparison with PIV visualization. Low-speed streak development in a controlled transitional boundary layer at T024S after initiation. A timelines generated from PIV, x0 is a relative coordinate representing x3785, with A, B, C, D indicating the location of the four cross-sections shown in Fig. 5.19b B cross-sections of velocity contours at A x225 and B x7 C and D x24. For the injection suction controlled transition, the position of the low-speed streak is nearly stable, as shown in Fig. 5.19. Figure 519 is a plan view timeline visualization of a low-speed streak, Fig. 5.19b shows N-view cross-sections of velocity contours for the lifted low-speed streak. Figure 519b shows U contours at a sequence of 4 different locations in the Z, Y-plane x225 mm, 8.5 mm 24 mm that illustrate the development of the LSS. As shown by the modest hump region in these U contours in plane A, the low-speed streak is initially very weak near the wall. As the streak develops downstream, planes BCD, the low-velocity region expands in both the normal and directions, moving progressively upward. The presence and expansion of the low-velocity region is also apparent in Fig. 5.19, as revealed by the continued retardation of the simulated timelines. Note that these patterns of streak development are consistent with the of timeline patterns shown in N-view in Fig. 5.5. Figure 520 shows the spatial and temporal evolution of an LSS in a controlled transitional boundary layer. Figure 520 is superposed timeline patterns for timelines initiated at 2 different wall normal heights. These patterns clearly show that the low-speed region, the peak region P in the figure, is more pronounced near the bounding wall Y04 red timelines, with significantly less retardation when the distance from the wall is doubled, Y08 black timelines. Spatial temporal evolution of a low-speed streak reconstructed from the PIV data of a controlled transitional boundary layer. A plan view of superposed timelines at Y04, red line, and Y08, black solid line. B vertical timelines released at Z, 13.7. Markers indicate particles released at Y02, Y04, Y08, and B respectively indicate locations of lift-up and downward sweep events. See oblique view of the timeline pattern for timelines released at Y08, D temporal evolution, T0, T1, of initiated at a wall normal position of Y08, with time period T008T between realizations. Evolution of material surfaces reconstructed from the PIV data. The 2 surfaces are initiated at Y046 and 061, initial flat surfaces shown at far right, a T0.16T, BT0.32T, CT0.48T, DT0.64T as pointed out in Sect. 523 If the initial condition for tracking is a planar surface, the subsequent is that of an evolving material surface. Figure 521 shows the evolution of such a material surface for the present transitional boundary layer. The inset at the lower right of Fig. 5.21 shows 2 planar Z, X material surfaces initiated at y 0.46 and 0.61, initially flat surfaces shown at the far right of Fig. 5.21. As these surfaces evolve in time, Fig. 5.21 and D, they undergo a transverse warping, developing a peak valley commented on previously that is construed as the development of a fluid lift-up, flanked by apparent fluid sweeps towards the surface. The lower surface in Fig. 5.21b, obtained at T 0.32t, illustrates the initial transverse warping of the material surface, with a peak P developing at Z20, the region where an LSS is observed. Downstream of the peak P, the material surface moves towards the center and develops a chevron-like pattern C. By T 0.48t, Fig. 5.21c, the peak P is flanked by two material valleys V1 and V2 due to the downward sweep motions. By T 0.64t, Fig. 5.21d, a pronounced peak P has developed for both surfaces, which reflects the outward penetration of the LSS. The ejection sweep motions create an HSL around the peak dashed line in the figure, where an initial roll-up develops. The two distinct material valleys, V1 and V2, begin to subsequently roll up to form the legs of a vortex. The chevron-like pattern looks markedly similar to the hydrogen bubble visualization in Fig. 5.18, suggesting that an LSS is located beneath the peak region. Note that the upper material surface does not appear as warped as the lower surface, i.e., the peak and the chevron-like pattern are more distinct on the lower surface, indicating that the HSL is also more pronounced at lower levels. The evolution of the material surfaces shown in Fig. 5.21 are supplements for the timeline patterns in Figs. 5.18 and 5.20. The bubble sheets appear much more convoluted than the material surfaces. But the evolution of the material surfaces caused by the developing flow field provides a more complete picture of the flow than the timelines. Both the evolution of the material surfaces, Fig. 5.21, and that of the hydrogen bubble sheet, Fig. 5.18, show that the LSS is flanked by developing vortices. And the LSS in Fig. 5.21 appears to lift up as a 3D wave, the waveform of which is similar to that shown in Figs. 5.15 and 520c. This suggests that the LSS revealed by the hydrogen bubble timelines of Fig. 5.18 is a 3D wave structure, with the formation of vortices initiated by the lift-up and breakdown of this 3D wave. 5.5 Discussion. The linear stage of boundary layer transition is relatively well understood, based on numerous experimental and linear stability studies. As the disturbances reach a finite amplitude where nonlinear effects become important, the flow becomes much more complicated because of nonlinear interaction between modes leading to energy exchange and the development of new stages of three-dimensional instability. These subsequent stages are accompanied by different flow structures and motions whose cause and effect are difficult to resolve. The most common structures include 3D waves, low-speed streaks, vortices, hairpin and ring-like vortices, and hairpin packets, which are usually associated with other fluid motions such as lift-ups, downward sweeps, roll-ups, and entrainment. In previous studies, there is no consensus on what causes the inflectional region and the low-speed streak formation. Additionally, details of how a warped wave front develops into a vortex are not well understood. 23-27. The present study investigated the transitional boundary layer using a combination of selectively visualized NPSC and PIV data. The results of the present study allow these questions to be addressed, as well as revealing variations in the flow structure between different transition regimes. All these findings reveal the importance of three-dimensional waves in boundary layer transition. 551 Warped wave front. The results of the experiments and simulations show that the structures in the near wall region sustain a higher shear than the upper region, with the material patterns near the wall revealing the development of an inclined and warped wave front. The concept of warped wave front was first proposed by Hama and 23 to describe the process of three-dimensional wave deformation prior to the formation of a discrete vortex. The WWF is observed to lift upward and amplify, with the front often stretched into thin filaments. This is clearly shown by the patterns of Figs 5.7, 5.13, and 5.14. The WWF in the near wall region is observed to roll up as it propagates downstream. This roll-up is observed as a folding of material surfaces, as shown in Figs 5.3 and 5.8, and also in previous studies 23, 24, 37. The roll-up indicates the development of a vorticity concentration along the border of the wave front, which progressively develops into a discrete vortex. The processes of lift-up, amplification, and roll-up usually cause the formation of inflectional points and three-dimensional high-shear layers. The WWF is less warped in the upper region of the transitional boundary layer. As shown by Fig 5.15 and also the supplementary movies of Movie 2, Movie 4, Movie 6, all three transition regimes, K, O, and N, display the same phenomenon of a lifted and amplified three-dimensional wave front accompanied by nearby regions of depression. The depression of the surface is considered to be caused by a downward sweep event compensating for the lifting low-speed fluid. Thus, it appears that the whole boundary layer during early-stage transition is dominated by amplified 3D waves, which appear as strongly warped wave fronts in the near-wall region and less warped or soliton-like wave front in the upper region. The WWF is a three-dimensional wave packet with convection speeds determined by tracking the wave front of 0.4045 U during the early transition stage for all the three regimes. 5.52 Relation between 3D wave structure and vortex. The roll-up of timelines or material surfaces can be easily misinterpreted as a vortex. Hama 57 pointed out that the roll-up of a does not necessarily indicate the presence of discrete vortices. The present study determined that the vortex will not develop until the multiple folding of a material surface occurs. The multiple folding here means that the continuing amplification of a 3D wave causes the lower portion of a warped wave front to lift up and progressively dominate the wave front. The kernel studies for the three transition regimes show the details of how a vortex develops from a 3D wave, Figs 5.4, 5.5, 5.9, 5.10, which agrees with the observations of Al. 3 and Hama and 23, that three-dimensionality appears prior to an appreciable vorticity concentration along the swept-back sides of the wave front. What we found is that the multi-folding process caused by a lifting 3D wave has a close relationship to the formation of a vortex. It implies that the 3D wave plays an active role in vorticity concentration that results in the formation of a vortex. Schematic view of the development of a 3D wave. An initial 3D wave causes the development of a warped wave front. B amplified 3D wave induces the second folding. C vortex appears. 0.8 indicates the wall normal position of 0.8 U. The black dashed line adjacent to the 3D wave models the development of a. The red line indicates the development from a high shear layer, HSL, to a vortex. E ejection event, S downward sweep event, K kink structure. Figure 522b shows that as the 3D wave amplifies, it extends rapidly upward, causing the high shear layer to strengthen, a concentration of vorticity to develop, followed by an initial vortical roll-up of the HSL red lines. The Fig 5.22b reflects a second folding, with a lower portion of the warped wave front projecting upward above the leading edge of the wave. In the timeline visualization of Fig 5.4, the initial vortical roll-up develops along the swept-back portion of the wave front, which is the initial appearance of a vortex. As the 3D wave advex downstream, Fig 5.22c, it continues to grow outward, eventually extending above the critical layer where it loses symmetry and begins to break down to a vortex. As Fig 5.22c shows, a vortex subsequently forms from the HSL with its head inclined upward, similar to the ring-like vortex model suggested by previous studies 66-68. The second folding of the will progressively become a second warped wave front. The location of this second folding was found to form the head of a vortex. Note that this second folding was not observed in the simulation of a shear flow perturbed by one or two traveling waves 57-58. This further supports the importance of the amplified 3D wave in the formation of a vortex. Figure 522c also models a lower portion of the as deforming strongly to yield a sharp ridge filament, D, which moves upward and rearward, modeled after the shown in Fig. 5.14. This ridge formation is due to a combined lift-up of fluid by the amplified 3D wave and a retardation caused by the developing counter-rotating legs of the vortex. 553 Low-speed streaks in transition. Schematic views of a transitional low-speed streak. A schematic side view of a hypothesized low-speed streak model comprised of 3 contiguous SCSs. B. Schematic plan view of the LSS model at height level 1. C. Schematic view of plan view of the model at height level 2. D. Relation between 3D wave, low-speed streak, and vortices. Figure 523D provides a conceptual model showing the relation between 3D waves, low-speed streaks, and vortices. As mentioned previously, a low-speed streak develops beneath a passing 3D wave, which suggests that amplification of the 3D wave produces the LSS pattern at early-stage transition. However, as the attached vortex finally develops into a discrete hairpin vortex, it will in turn induce a low-momentum region at the center of its legs. Thus, streaky structures in late-stage transition or within a turbulent boundary layer are longer and narrower, characterized by oscillation and undulation 69-71. Therefore, the LSSs in less organized boundary layers, late transition turbulent, are possibly the result of a combined interaction between 3D waves and hairpin vortices or packets, which needs to be further investigated. Note that the model shown in Figs. 5.22 and 523 is similar to the model of hairpin vortex generation by the breakup of a synthetic LSS shown in and Smith 72. It was hypothesized by Smith 73 that the passage of a vorticity concentration created upstream can create a transient, spatially varying pressure gradient which could precipitate the local deceleration and three-dimensional oscillation. Instead, the current discussion attributes the cause of the oscillation and vorticity concentration to the amplification and lift-up of a 3D wave. The differences and similarities between the various transition regimes have been discussed in a number of studies 2, 10, 13, 31, 35, 74, 75, most of which focused on late-stage transition. The results of the present study indicate that a universal transition mechanism may exist and can account for the similarities and differences of the 3 regimes. The possible common root may rely on the amplified warped wave front. All the 3 regimes share oblique modes, the interaction of which results in WWF and streaks. Near the wall within a laminar boundary layer, the lift-up of a WWF amplifies the already higher shear layer, creating in a strong localized 3D high shear layer, which subsequently forms the initial vortex. Later, the development of the vortex and its variants complicate the near-wall fluid, which will further contribute to the ejection sweep cycle or bursting process. The WWF discussed in this study is similar to Soliton-like coherent structure 36, especially in the outer region of the boundary layer. 5.6 Conclusions. In this study, solutions to a nonlinear stability equation, NPSC, and the results of complementary experiments are used to investigate the early-stage process of boundary layer transition. 3 kinds of transition regimes were considered, i.e., K regime, N regime, and O regime. However, only the K regime transition was examined experimentally using both hydrogen bubble visualization and time-resolved tomographic particle image, PIV. A structure-based view was provided in this paper, combined with analysis of mode evolution. Using Fourier decomposition, it was determined that small oblique disturbances are strongly amplified by resonance with the larger fundamental disturbances for the K and N regime, and that zero-frequency modes grow fast due to the interaction of oblique modes for the O regime. Particle tracking was applied on the NPSC and PIV database to extract the evolution of structures. According to the numerical and experimental visualizations, at least 4 common characteristics of the generic transition process were identified, An inflectional region appears in vertical velocity profiles, accompanied by ejection sweep. Horizontal timelines display a chevron-like structure in the near-wall region, which subsequently develops into a long, narrowed, streaky structure, LSS. A warped wavefront, WWF, displaying multiple folding and wave-like amplification damping, which develops adjacent to the LSS in the near-wall region, prior to the appearance of vortices. Development of a coherent 3D wavefront similar to a soliton within the upper boundary layer, accompanied by regions of depression along the flanks of the wave. The results revealed that an amplified WWF comprising the LSS causes multiple folding, leading to a vortex in the near-wall region. Based on the similarities between the different transition regimes, the following hypothesis for general transition is proposed. The transition is initiated by the growth of 2DT, S-wave and oblique waves, only oblique waves for orogene transition, with zero-frequency modes growing progressively at later stages further downstream. The nonlinear interaction of oblique waves seems to be the core of the wave resonance, which contributes to an amplified 3D wave appearing as a WWF. During the wave amplification process, an LSS develops near the wall, which is composed of several WWFs. A subsequent lift-up of a WWF disturbs the boundary layer by ejecting low-speed fluid upward from the near-wall region, resulting in the development of kink structures in both vertical and horizontal velocity profiles. Due to mass conservation, higher-speed fluid in the outer region sweeps downward, creating a forward-inclined, localized 3D high-shear layer, LHSL, at the edge of the 3D wave. The amplification of the WWF further strengthens the LHSL, leading to a concentration of vorticity within the LHSL that initiates a vortical roll-up process. This vortical roll-up of the LHSL creates a vortex, which subsequently separates from the wave front as a distinct flow structure. The counter-rotating legs of the vortex, or hairpin vortex, help concentrate low-momentum fluids on its plane of symmetry, reinforcing the LSS and the WWF. However, the upper portion of the WWF is longer-lived, propagating downstream like a soliton, which indicates that the WWF is the same structure as soliton-like coherent structure, SCS. The model proposed above is based primarily on our assessment of the reconstructed timeline and surface visualization patterns, which are not without approximation, and are of course open to the bias of the viewer. However, our assessment of the patterns, and the synthesis of these assessments into a model of the generic transition process, provides a rational structural description of how early-stage transition develops. Clearly, more study is necessary to confirm the model, but it is clearly a reasonable starting point. The model also provides a platform to move on to the assessment of the more irksome counterpart to transition, the process for sustaining turbulent in a boundary layer. Competing interests, this work was supported by the National Natural Science Foundation of China grant knows. 10,921,202, 11,221,061, 11,632,002, 11,521,091, 11,602,005, and the National Key Project grant no. GJXM 92579. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Supplementary movies are available at org 10101720201007 open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License (org licenses by 4.0), which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source. Provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Urest H. J. Fluid Mech. 298, 211, 1995. Org 101017S0022 112095003284.
2.
Esperlin MDS J Fluid Mech. 393, 23, 1999.
3.
PSKD LM J Fluid Mech. 12, 1, 1962.
4.
MBII J Fluid Mech. 252, 449, 1993 net.
5.
T in 22 Aerospace Sciences Meeting, American Institute of Aeronautics and Astronautics, Reno, NV, USA, 1984. AIA Paper 840009. Org 102514619849.
6.
YSVV VY Fluid Dyne. 12-3, 383, 1977.
7.
YSVY J Fluid Mech. 138, 209, 1984.
8.
MESW J Fluid Mech. 207, 97, 1989 net.
9. PD.
Fluids 49, 1986, 1992. Org 10106318583667 net.
10.
PJDS, Instability and Transition in Shear Flows, Springer, New York, 2001. 401, 475. Org 10-100-7978-146-130-18519.
11.
GRVV, in Physics of Transitional Shear Flows, Instability and Laminar Turbulent Transition in Incompressible Near-Wall Shear Layers, Springer, Netherlands, Dordrecht, 2012. 223, 242. Org 10-100-7978-9400-7249-8312.
12.
ELJ Fluid Mech. 199, 403, 1989. Org 10-101-7S0022-1120-89000042X.
13. SBake HHYS.
J Mech. B Fluids 19, 1, 2000.
14.
YS J Fluid Mech. 184, 1, 43, 1987. Org 10-101-7S0022-1120-87002805.
15. YS. Rev. Fluid Mech.
26, 1, 411, 1994.
16.
TCWP J Fluid Mech. 724, 480, 2013. Org 10-101-1720-13142.
17.
TPJ JWP J Fluid Mech. 748, 278, 2014. Org 10-101-1720-14184.
18.
LSG HBRD in Proc. Heat Transfer and Fluid Mech. University Press, 1962.
126. 19.
YS in Advances in Turbulence 3.
Id.
By A.V. P.H. Springer, Berlin, Heidelberg, 1991, 4251.
20.
YSOS F.T. Smith J Fluid Mech. 251, 273, 1993 net.
21.
DGW URIST VI VR YSQX CB Lay in Laminar Turbulent Transition ED. By HFWS Springer, Berlin, Berlin, 2000. 167, 172.
22.
VI VR YS DGW URIST QX CB Lay.
Fluid Dyne.
15-5, 317, 2002. Org 10-1007 S00-1620-100054.
23.
FR Hama J in Proc. Heat Transfer and Fluid Mech. University Press, 1963. 7793.
24.
Effects in Advances in Fluid Mechanics. By E. Springer, Berlin, Heidelberg, 1981, 268279. 25. MMS in Transition and Turbulence, ed. By R.E. Academic Press, 1981. 113 126. 26. C.B. Lay. A 247-6, 397 1998. Org 101016 S0375960 198005829. 27. C.B. Lai J.Z. Wu. Mech. Rev. 61 30802 2008. 28. W. Numerical Simulation of Boundary Layer Transition by Combined Compact Difference Method. D. Thesis, Technological University, Ave, Singapore, 2013. 29. J. Kayas J.H. J. Fluid Mech. 225 575 1991. 30. STK. Rev. E89-4, 43018 2014. 31. AV KJI BGB VV PH J Fluid Mech. 281 219 1994. Org 101017 S0022 11209400 3095. 32. RPA. Fluids 2811 114105 2016. Org 10106314966978. 33. FR Hama J.D. Long J.C.J. 28-4 388 1957. Org 10106311722760. 34. Y. Yang S.Y. J. Fluid Mech. 793 840 2016. Org 10101720 net. 35. C.B. Lay. Rev. E62-3 3659 2000. 36. C.B. Lay S.Y. in Transition and Turbulence Control, ed. By M. Jeed L. H. M. World Scientific 2006. 3985. 37. C.B. Lay R.Q. Lay J. 855-1 2007. Org 101080146852406009251163. 38. XY Adv. Maths Mech. 11 640 2019. 39. XY Maths Mech. 42 261 2019. 40. FPT PR J Fluid Mech. 242 441 1992 net. 41. CL MR Malik J Fluid Mech. 273 323 1994. Org 101017 S0022 112094001965. 42. XD Tang Chin. J. Aeronauts. 23-3 283 2010. Org 101016 S10009361096021 X Math.net. 43. YDCB Lay X, JZ Wu SY M Gadel J Fluid Mech. 855 152 2018. Org 10101720 44. XYD CB Lay J Fluid Mech. 820 693 2017. Net. 45. VGVVLHHJ. 94 437 2006. Org 101007 BF031817883. 46. MSCR Smith J Fluid Mech. 175 1 1987. Org 101017 S0022 112087000272. 47. HSJWC J Fluid Mech. 50 133 1971. 48. KKS in 5 Biennial Symposium on Turbulence, Ed. By GK JL 1979. 280 7293. 49. CR Smith RD Exp. Fluids 11 43 1983. Org 101007 BF00 282266. 50. LJ CR Smith Exp. Fluids 36 349 1985. Org 101007 BF0 1830195. 51. T. Rev. Fluid Mech. 21 487 1988. Org 101146 201010188002 52. Esperlin A.D. Fluid 66 1949 1994. Org 101063186820. 53. T. Rev. Fluid Mech. 29 1 245 1997. Org 101146 Fluid 29 1245 net. 54 JCR Hunt, AA, P, eddies, stream, and convergence zones in turbulent flows. Tech. Rep. CTRS 88, Center for Turbulence Research Report 1988. 55. WDWR J Fluid Mech. 228 387 1991. Org 101017 S0022 112091002756. 56. AJL Partridge Q Joe SB CP PF Linden J Fluid Mech. 848 508 2018. Org 10101720 18324. 57. FR Hama. Fluids 56 644 1962. Org 101063 11706678. 58. DR Williams FR Hama. Fluids 23 442 1980. Org 10106318630012. 59. B Exp. Fluids 45 549 2008. Org 101007 S00348008052115. 60. KP Lynch F Exp. Fluids 56 66 2015. Org 101007 S003480151936. 61. PRD J Fluid Mech. 200 471 1989. Org 101017 S0022 112089000741 net. 62. LHO AJ Smits Phil. Trans. R Soch. A 375 2089 20,160,086 2017. Org 10109820160086. 63. HYCY HP JJ J Fluid Mech. 831 743 2017. Org 10101720174647. 64. FM White Viscous Fluid Flow 3rd. Hill, Singapore 2006. 65. F. Technol. 24-1-12001 2013. Org 101088095702332410120001. 66. CB Lay S Exp. Fluids 33, 354, 2001.
67.
IHCR Smith, J. Fluid Mech. 277, 135, 1994. Org 101017S002 112094002715.
68.
HVIYS-CPAN JJQX SFJ. 1134 1 2010.
69.
SJWC FA PW J Fluid Mech. 34 741 1967. Org 101017S002 112067001740.
70.
NDL J Fluid Mech. 245 319 1992. Org 101017S002 112092000048X.
71.
RJ Adrian CD J Fluid Mech. 422 1 2000 net.
72.
MSCR Smith J Fluid Mech. 175 43 1987. Org 101017S002 112087000284.
73.
C.R. Smith in Proceedings of the 8th Symposium of Turbulence, Ed. By G.K. J.L. University of Missouri, 1984.
127.
74. M.D. Joe T.S. in Perspectives in Turbulence Studies.
Id.
By H.U. P. Springer, Berlin, Heidelberg, 1987, 4770. 75p. Experiments on oblique transition in wall-bounded shear flows. D. Thesis KTH, Department of Mechanics, Stockholm, 1998.
6.
Experimental study on low-speed streaks in a turbulent boundary layer at low number.
Abstract.
A study of low-speed streaks, LSSs, embedded in the near-wall region of a turbulent boundary layer is performed using selective visualization and analysis of time-resolved tomographic particle image, PIV. First, a three-dimensional velocity field database is acquired using time-resolved PIV for an early turbulent boundary layer. Second, detailed timeline flow patterns are obtained from the low-order reconstructed database using tomographic visualizations by tracking. These timeline patterns compare remarkably well with previously observed patterns using hydrogen bubble flow visualization and allow local identification of LSSs within the database. Third, the flow in proximity to selected LSSs is examined at varying wall distances, 10y plus 100, and assessed using timeline and material surface evolution to reveal the flow structure and evolution of a streak and the flow structure evolving from streak development. It is observed that three-dimensional wave of the detected LSSs appears to develop into associated near-wall vortex flow structures in a process somewhat similar to transitional boundary layer. Fourth, the presence of coherent structures is assessed in proximity to the LSSs using an averaged vorticity deviation process. It is observed that quasi-vortices, adjacent to the sides of the streak-associated three-dimensional wave, precipitate an interaction with the streak. Finally, a hypothesis based on the of Soliton-like coherent structures, SCS, is made which explains the process of LSS formation, bursting, and the generation of hairpin vortices. Comparison with other models is also discussed.
Keywords.
This chapter is reproduced with permission from XY, CB Lay, CR Smith, JW, and PF Linden. Experimental study on low-speed streaks in a turbulent boundary layer at low number, J Fluid Mech. 903 A6, 2020. Copyright 2020, Cambridge University Press. The content of the article has been slightly revised. 6.1 Introduction. The streaky structure characterized as filaments of low-speed fluid is ubiquitous in wall-bounded turbulent flows and has been studied more than 5 decades since the initial observation by Al.
1.
As one of the most significant coherent structures in both transitional and turbulent boundary layers, a low-speed streak, LSS, is highly relevant to the bursting process and turbulence production. There are differing interpretations of LSSs, from their formation mechanism to streak instability and their role in transition and turbulence. The prevailing hairpin-like interpretations ascribe the formation of the LSSs to the lift-up effect caused by hairpin-like structures. By systematic investigation of near-wall turbulent flow, AL. 1 and ALS. 2 identified and characterized LSS and turbulent bursting. The mechanism for streak formation they proposed was based on stretched and lifted vortex elements. Head and 3, based on observations of laser-illuminated smoke visualizations, proposed that individual streaks are the result of and between the legs of lifted hairpin vortices. Based on extensive experimental work, Smith and his co-authors hypothesized a model of LSSs and bursting, which suggests that the elongated LSSs, spaced at +100, are lower-speed regions of upwelling flow induced by the legs of a sequence of lifting hairpins 4, 6, and 7 studied the structures and dynamics of turbulence in the near-wall region using a minimal channel flow, and observed very long intermittency cycles that were closely related to near-wall streaks. And 8 further proposed that an autonomous turbulence regeneration cycle exists in near-wall region, involving quasi-vortices and longitudinal velocity streaks. In contrast to previous research that mainly focused on the near-wall region of turbulent boundary layers, Adrian al. 9 performed a quantitative experiment at higher number by applying PIV primarily to the outer region of a turbulent boundary layer. Based on their results, they argued that LSSs are part of uniform momentum zones created by induction of the hairpin packets. However, there is no clear consensus on the origin of the vortices. 10 proposed a self-sustaining process, SSB, to explain the turbulence regeneration process. The SSB consists of 3 phases: 1. Formation of streaks by vortical rolls, 2. Streak instability, and 3. Nonlinear feedback to the rolls. He emphasized that what drives the SSB is the instability of the streaks. And 11 used direct numerical simulation, DNS, to study the relationship between structure generation and streak instability, and determined that near-wall vortices sometimes arise from the instability of LSSs. They stressed that the streak transient growth mechanism is more important for streak breakdown and vortex generation. A mechanism for inner-outer region crosstalk, suggested by Al. 12 and later by experiment, is that large-scale motions, LSMs, and very large-scale motions, VLSMs, appear to organize the SSP cycle 13. LSSs are not always the result of vortical structures. It is known that low-speed streaks disappear if the VUY term is removed from the governing equation, where U is the averaged velocity, and V is the wall normal velocity fluctuation 1416. Therefore, the streaky structure in a turbulent shear layer must be dependent on the wall normal fluctuation velocity. A linear inviscid model was proposed by 1718, who hypothesized that LSSs will develop from any initial, local three-dimensional 3D disturbance with non-zero net vertical momentum. Such disturbances could be initiated from a local region of inflectional instability with asymmetry, such as the case of an oblique wave disturbance. And 16 proposed that LSSs form from the combined action of 1. A lift-up of wall region fluid, 2. Amplification within the mean shear, and 3. Viscous diffusion, without the need of hairpin vortices. Hama and 19 proposed that an amplified perturbation wave in the wall shear layer, termed a kink, has a strong tendency to form three-dimensional vortex loops. The kink structure was found to be a three-dimensional wave packet called Soliton-like Coherent Structures, SCS, 2022, which spans the whole boundary layer from the near-wall region to the edge of the boundary layer. LSSs in the transitional boundary layer were observed to consist of several SCSs 23, 24. Hairpin vortices were hypothesized to develop from the edges of an SCS, as the SCS moves away from the wall. The similarity between late-stage transition and developed turbulence has been examined in several investigations. The experiments by Al. 25 and 26 may be the first to show a close similarity between the near-wall structure activity in the late stage of the transition K-regime breakdown and the near-wall coherent structure motion in wall turbulence. The evolution from a local high-shear layer to the appearance of discrete vortices was presented quantitatively. In their papers, occurrence of hairpin vortices was explained from the high-frequency secondary instability. The finding that a hairpin is a manifestation of a secondary instability due to a pre-existing distortion of the boundary layer is also supported by a recent investigation of Hack and 27, who further proposed that the patch of low-momentum fluid, LSSs, at the center of the hairpin is not primarily an outcome of the hairpin itself, although the latter may contribute to it. L28 evaluated the breakdown of K and N regimes to turbulence during late-stage transition using DNS, and they determined that the flow statistics and near-wall dynamics are similar to a turbulent boundary layer. Based on that observation, they proposed late-stage transition, manifested by hairpin packets, as a reduced-order model of a turbulent boundary layer. The collective simulation and experimental studies reached no consensus on the near-wall turbulence production cycle regarding the types of flow structures and their development, hierarchy, and symbiosis. LSS's hairpin vortices, the so-called bursts, and the of these structures events are subject to a number of different interpretations. Some of these disparate interpretations arise from the limitation of experimental techniques that rely on qualitative visualization or restrictive two-dimensional 2D measurements localized in space and time. Other issues arise from the flaws in post-processing methods, such as methods or frame-dependent criterion for structure detection. The present investigation attempts to establish the essential skeleton of the LSSs by using a combination of both qualitative and quantitative techniques to assess and compare the flow structure of a turbulent boundary layer. In contrast to previous three-dimensional PIV experiments applied to fully developed turbulent boundary layers at relative high, number 2931, the present study focuses on early turbulent flow at low number, in order to illustrate the early origin and metamorphosis of turbulent flow structure. Tracing methods are applied to time-resolved three-dimensional data obtained from PIV, illustrating the temporal evolution of LSSs, as well as details of the bursting process. This is done using a process of averaged vorticity deviation to detect vortices within the datasets. The evolution of detected coherent structures and streak vortex interaction is also illustrated, which has not been effectively addressed in previous studies. Based on the data analysis, detailed comparisons and synthesis are done to establish the apparent flow structure present and its symbiosis, leading to hypothesized mechanisms for the streak formation process, the bursting process, and the generation of hairpin vortices. 6.2 Experiment Setup and Data Processing. 6.2.1 Experimental Techniques. Experimental setup of PIV. A side view of setup for hydrogen bubble visualization. B. Plan view of setup for hydrogen bubble visualization. C. Schematic view of horizontal wire. D. Schematic view of vertical wire. E. Schematic layout of the arrangement of the PIV system. F. A picture showing the camera configuration. The present study was done using both qualitative hydrogen bubble flow visualization and selective, detailed PIV studies. Since hydrogen bubble visualization was the method employed for the initial identification of LSSs, the present hydrogen bubble studies were done to provide comparative timeline studies of the near wall of the low-number turbulent boundary layer to assure that the flow structure was comparable to prior studies 1, 2, 5. A series of hydrogen bubble timeline visualizations were done employing both horizontal wire and vertical wire configurations as described by Lee and Lee 22 and al. 32 See Fig. 6.1c D. The hydrogen bubble wire was 0.03 diameter platinum wire. For plan view visualization, a horizontal wire is kept taut by a weight hung on the opposite side of the working surface. The distance of the wire from the plate surface was adjusted using insulated spacers beneath the wire Fig. 6.1c For side view visualizations, a vertical wire was configured using a probe support employing a non-conductive human hair. The vertical bubble wire was tied around the center of the, placed in moderate tension, and soldered to the upper wire support Fig. 6.1d A portion of wire was left extending below the, to show near-wall flow. By pulsing the current through the hydrogen bubble wire at a constant frequency, a pattern of timelines is created, as shown in Fig. 6.1c D. These hydrogen bubble visualization studies were used to confirm the qualitative near-wall flow structure and guide the measurements using PIV, focusing on the near-wall region where LSSs develop. The free stream velocity employed for both the hydrogen bubble and PIV was approximately 0.17 ms, and the distance x'd from leading edge to the center of the measurement region was 500 toom. The PIV configuration is shown in Fig. 6.1e f4 high-speed CMOS cameras, FASTCAM SA4, with resolution of 1024-1024 pixels at framing rates up to 3600 frames per second were used in a cross-configuration arrangement. The cameras are fitted with lenses of 200 mm focal length with aperture of f11. Illumination was provided by a high-speed laser generator from Beijing ZK Laser DCQ30Q, a single-cavity double-pulse laser system emitting a beam of wavelengths 527-30 mJ at 1K. The 4 cameras and laser system were synchronized using a LaVision's PTU timing controller. The thickness of light volume generated by optical lenses and the mirror was nearly 310 viscous units within the regions of interest, illuminating tracers of hollow glass particles from Potter Industries. The mean diameter 11 particles were introduced into the water tunnel 6m downstream of the test section to assure that the particles were fully mixed and uniformly distributed after circulating to the measurement site. Experiments were conducted at a particle image density of 0.098 particle per pixel, which corresponds to particle concentrations of approximately 2.3 particles m3. The PIV sampling frequency 500, i.e. the time increments plus 0.42 viscous time units. All cameras were carefully adjusted in the condition, i.e. applying the condition between the image plane, lens plane and subject plane assures that the final residual calibration errors for all cameras were less than 0.1 pixels. The digital resolution was 13.37 pixels for the calibration field of view. The measurement domain extended 815 viscous length units in both the and direction. Before reconstruction process, image pre-processing with a smoothing filter 3 pixels was applied on the raw particle images. Volume self-calibration 33 was used on the pre-processed particle images. Volume reconstruction was achieved by sequential motion tracking enhancement 34. The reconstructed volume was 1041, 1048, 187 voxels. A multipass approach of 4 steps was carried out for the volume correlation, and the interrogation volume size for the final pass was 16 voxels, corresponding to spatial resolution of 12.52, 12.52, 12.52 wall units, with a 75% overlap, yielding 0.3 grid spacing, 3.13 wall units. As a final step, a smoothing filter of 3 vectors was applied to the velocity data. Proper orthogonal decomposition, POD, analysis is effective for noise removal and extraction of the higher modes in turbulent flow 35. In the present paper, POD analysis was applied to the smoothed velocity datasets, and the first 4 leading order POD modes are extracted. As an additional note, the detail of POD filtering and its low-order representation is discussed in Appendix 1. 6.2.2 Properties of the boundary layers and PIV accuracy. A turbulent boundary layer mean velocity profile plotted on log linear coordinate. Fitting curves using models of 36 and Spalding 37. 0.41 B5. B root mean square and velocity profile comparison. Pluses present PIV results, circles, Wu and 38 at 900, triangles, 39 at 670, stars, al. 40 at 465, dashed lines, velocity approximation based on the first 4 pod modes, red, blue, the position of the wall is usually an important source of uncertainty 41. The wall deviation, defined as the difference of nominal wall position y0 and real wall position y0, is considered in this study. By using a gradient descent algorithm, which is an iterative optimization procedure updating parameters based on the gradient of the objective function 42, both friction velocity and wall deviation are obtained. The final result gives 0.0104 ms and 0.38. Thus, all the wall normal coordinates are corrected as YY. The other source of uncertainty is the experimental error from the non-uniformity of the laser light. The thickness of the laser volume, i.e., the vertical height of the data window, is 10y plus 150, which is the region of interest in this study. This data window contains part of the buffer layer and the log-law region of a turbulent boundary layer. The light volume is parallel to the flat plate, which means the spatial resolution may decrease slightly in the region of y plus 100 due to a weaker light intensity at the edge of the laser volume. The calibration inaccuracies were reduced to less than 0.01 pixels, 0.08 wall units, by applying volume self-calibration on the preprocessed images. The reconstruction accuracy of the PIV was determined by the reconstruction signal-to-noise ratio, SNR, defined as the intensity level encountered in the reconstructed region compared with that outside the illumination region. The condition of SNR2 is considered as the lower limit identifying tomographic experiment with good reconstruction quality 43. The distribution of light intensity across the depth of the measurement volume was determined using a MART tomographic algorithm, which gave an SNR 2.17, which was considered an acceptable reconstruction level. 6.3 Experimental results. 631 Flow visualization. 6311 Hydrogen bubble visualization. Hydrogen bubble visualization of turbulent boundary layers, a plan view timelines at y plus 20, B/C side view timelines. The yellow brackets on the images indicate the physical scales in viscous lengths. E ejection S downward sweep R rotation. The flow is from left to right. When they are compared, the images of Fig. 6.3 are in accord with similar images of AL. 2, Smith 5 and in Smith 44, indicating that the low-number boundary layer of the present study does reflect the same type of flow structure and as observed in past visualization studies. A detailed review of the hydrogen bubble data appears to support the previous dynamical model suggested by AL. 2. In this model, upward ejection of fluid from an LSS is perceived as the driving mechanism that results in the development of and vortices. It is our hypothesis that this breakdown and ejection of the LSS is initiated by the amplification of 3D wave. In the following section, we will provide several types of timeline and material surface visualizations of the PIV results to examine this hypothesis, which links LSS breakdown and subsequently the bursting process to a process of 3D wave development. 632 LSSs in tomographic visualization. A sequence of timelines at t plus 164, generated 50 and initiated at y plus 27, illustrating LSSs in a turbulent boundary layer. The markers trace the location of the center of two LSSs, designated I and II. Plan view and side view timeline patterns showing the evolution of the streak eye from Fig. 6.4. C-plan views of horizontal timelines initiated at y plus 27 as they appear, respectively at a t plus 164, bt plus 183, and ct plus 203. DF side views of vertical timelines initiated at z plus 32 as they appear, respectively, again at dt plus 164, et plus 183, and ft plus 203. The sequences of red dot markers superposed on the timelines reflect streakline for markers initiated at y plus 27 and 36. In order to better understand the spatial temporal evolution of LSSI, patterns of vertical timelines synchronized with the plan views of Fig. 6.5 C were generated using timelines initiated at z plus 32. Essentially the center of the passing streak eye. These patterns are markedly similar to the vertical timeline patterns for a controlled transitional boundary layer 45, as well as the instantaneous velocity profile results for the near wall of a turbulent boundary layer shown in and Smith 44. The dot markers in Fig. 6.5D F indicate streakline originating from both y plus 27 and 36. When compared to the plan view patterns of Fig. 6.5 A C Fig. 6.5D, F indicate that where the plan views reflect a strong LSS, the side view patterns display an obvious inflectional region in the corresponding vertical profiles. Plan and side view timeline patterns showing the evolution of streak II from Fig. 6.4. A C-plan views of horizontal timelines initiated at y plus 27 as they appear, respectively at a t plus 131, bt plus 151, and ct plus 170. The sequence of markers in a C correspond to streak lines initiated at z plus 59. DF side views of vertical timelines initiated at z plus 59 again the same respective times as a C, dt plus 131, et plus 151, and ft plus 170. The sequence of red dot markers in D, F are streak lines initiated from y plus 21, 27, and 36. The wall normal variation of LSSs at t plus 164, extracted from the timelines initiated at y plus 27, corresponding to Fig. 6.4. The contours indicate the wall normal position of the timeline surface. White dashed lines on the figure indicate identified LSSs. Histograms showing the distribution of 125 identified LSS categorized according to their geometry. A length L plus B shift S plus. Timeline patterns shown in Figs. 6.5 and 6.6 are different from the timeline patterns reconstructed from a flow field with a distinct vortex. See examples shown in Figs. 6.28 and 6.29 in Appendix 2 for a vortex and a vortex, respectively. In the presence of a vortex, timeline patterns are characterized as folding and twining lines. But when there is only a high shear layer, timelines tend to intersect and crimp, but do not appear as a vortex-shaped pattern, such as the timelines shown in Fig. 6.28, a Fourier-regime transition prior the appearance of a vortex. When there is a wave structure in a flow field, 3D timelines appear as concentrations and dispersions, manifesting as a hump-like pattern without an intersection of timelines. See the example of Fourier-regime transition in Fig. 6.3. Thus Figs 6.5 and 6.6 indicate that the LSS is not a vortex structure, and high shear layers develop at the sides of LSSs. Figure 6.7 shows contours of wall normal position superposed with the expanded timeline surface corresponding to Fig. 6.4. LSSs were identified by tracing the peak of the timelines, as indicated by the white dashed lines on the figure. The contours show that an LSS usually appears as a localized hump, accompanied by regions of depression, high-speed streaks HSS, flanking the side of the LSS. The interface between an LSS and an HSS is the location where high shear layers develop. Note that the timelines shown in Fig. 6.7 are 3D, thus the geometry of an LSS can be obtained from its position. The length L plus of an LSS is calculated as P1x P0x, and the shift S plus is obtained from P1z P0z, where P0 and P1 are the start and end positions of an LSS, determined manually, as indicated in Fig. 6.7. Temporal evolution of LSS. A temporal evolution of LSSI, see Fig. 6.4 from T plus 111 to 190. This shows the temporal variations in the timeline patterns of span plus 41, using a compressed Z plus scale, encompassing the span of the LSSI. B. Temporal evolution of 4 selected LSSs, tracing the temporal normal displacement of the peak of the streak pattern initiated at y plus 27, with time interval of plus 874. The changes in the timeline patterns are shown from left to right for increasing time, as indicated by the dotted lines. W indicates a second 3D amplification. 6.3.3 Temporal evolution of LSSs. It is difficult to determine the exact location of LSSs and their development without use of some quantitative assessment process. Using tomographic visualization, the temporal evolution of LSSs can be examined. The temporal evolution of LSSI is shown in Fig. 6.9, which is a composite illustration of the temporal changes in the timeline patterns as the LSSI spatial temporally evolves. The black lines trace the peak of the LSSI. The dotted line on Fig. 6.9 traces the temporal normal displacement of the peak of the streak pattern. In Fig. 6.9, timeline segments of width z plus 41 are shown for progressively increasing times from t plus 111 to 190. Each timeline segment is centered on the peak of the timeline patterns visualizing LSSI. The progressive evolution of the streak pattern is shown left to right for the indicated t plus times. Evolution of material surfaces initiated at y plus 27, 33, 39, and 49 within the region of LSSI with different oblique views. A t plus 164, bt plus 173, ct plus 181, dt plus 190. The wave-like undulation and oscillation of LSSs is further examined by applying tracing of several material surfaces initiated in the region of LSSI, as shown in Fig. 6.1. These are flat material surfaces initially spanning 0x plus 420 by 52 that are allowed to evolve within the database flow field to illustrate the surface deformation in time-space. In order to illustrate the detail of the flow development, two different perspective views of the four developing material surfaces are shown in both the left and right columns of Fig. 6.1. The left column shows oblique views of the surfaces as viewed from their left side, as they move with time in the positive x direction. The right column shows oblique views of the same surfaces as viewed from their right side, as they again move in the x direction. The four initial material surfaces at y plus 27, 33, 39, and 49 are shown in Fig. 6.1. After a time increment of plus 9, Fig. 6.1b at t plus 173 shows a small wave-like structure K forming near the trailing edge of the material sheets at approximately z plus 30. The LSS region revealed in the horizontal timeline patterns of Fig. 6.5 and the inflectional region appearing in the vertical timeline patterns of Fig. 6.5d are possible reflections of the lift-up of this 3D wave-like structure. K. As time proceeds, this wave structure becomes more pronounced, P, and the edges of the surfaces appear to warp upwards at locations R0, R1, and R2 in Fig. 6.1c, D oblique view of the timelines shown in Fig. 6.6b, C for the identified LSSI with the accompanying streak lines. The solid timelines were initiated at y plus 27 at a frequency 50. The companion red streak lines are initiated at z plus 59. A is the realization at t plus 151, b is at t plus 170. Is the time after the timeline initiation. The red arrows indicate the directions of fluid movement. Evolution of material surface initiated at y plus 27, 33, 39, and 49 at the region of LSSI. A t plus 131, bt plus 138, ct plus 144, dt plus 151. The evolution of material surfaces located within the region of LSSI is shown in Fig. 6.12. The surfaces undergo a similar transverse warping as observed in Fig. 6.1 for LSSI, revealing substantial variation. The evolution of the peak-valley patterns reflected by the material surfaces shows strong movement upward, away from the wall, revealing a lift-up, which is consistent with the timelines shown in Fig. 6.11. The initial peak of the streak, K on Fig. 6.12 initiates near the wall and progressively develops a 3D wave-like pattern, indicated by the dashed lines on Fig. 6.12 p. The lifted wave-like peak is also flanked by two distinct material valleys, which both increasingly deepen, with the sides warping upward as time progresses, R1 in Fig. 6.12. This looks markedly similar to the evolution of LSSI shown in Fig. 6.1, indicating that LSSI and LSSI are associated with the same type of development process. Evolution of material surface of initial size plus 366 plus 82, initiated at y plus 27, a t plus 131, bt plus 138, ct plus 144, and dt plus 151. Based on the results in Figs. 6.1, 6.12, and 6.13, we hypothesize that it is the development of 3D wave-like of the LSS that results in these material surface deformations, and that also creates the characteristic timeline streak patterns shown previously in Figs.
6.466.
As was shown, these 3D waves develop near the wall and propagate outward. The advection speed of this 3D wave was calculated from a temporal sequence of the wave peak locations. The average advection speed of the wave-like structures associated with the LSSI is 65% of free stream velocity, which is close to the value of 64% U calculated from the distorted band of timelines in Fig. 6.5 SC and 60% U calculated from streak development in Fig.
6.9.
The upward wall normal velocity of the wave was determined from the temporal change of the wave crest locations, examined over a time range of t plus 131-151. The results indicate that the upward wave velocity decreases from 5.8% to 1.4% U, as the distance from the wall increases from y plus 14 to y plus 77. This indicates that the strongest wave amplification and lift-up occurs near the wall. This hypothesis of the bursting process as the breakdown of a 3D wave structure S is examined in sect.
6.34.
6.34 bursting process in the LSSs. The vorticity distributions within the region of LSSI corresponding to Fig.
6.6 and also Figs.
6.11 and 6.12 are shown in Figs. 6.14 and 6.15 at t plus 131, 151, and 170.
The distributions of shown in Fig.
6.14 reveal the variation of evolution of wall normal vorticity in the region of LSSI at y plus 27, shown superimposed with three-dimensional timelines corresponding to Fig.
6.6.
A t plus 131, bt plus 151, and ct plus 170. The planes numbered 19 are y, z planes, and the planes L, M, N are x, y planes, showing the location of the vorticity contours shown in Figs.
6.15 and 6.16. Evolution of vorticity on a series of z, y planes.
The slices 19 and the superimposed timelines are the same as those shown in Fig.
6.14.
A contours of at t plus 131, as they appear respectively at x plus 282, x plus 73, and x plus 105. B contours of at t plus 151, the same respective locations as a. C contours of at t plus 170, the same respective locations as a. Evolution of vorticity in the region of LSSI at z plus 89, corresponding to the planes L, M, N in Fig.
6.14.
A t plus 131, bt plus 151, and ct plus 170. Vorticity and vortices in the region of LSSI. A contours of wall normal vorticity on an x, z plane at y plus 27, shown juxtaposed with contour lines of the deformed material plane shown in Fig.
6.13d.
B contours of vorticity on a series of z, y planes, again shown with the deformed material surface contour lines. Symbols A, B, C, D, E, F denote a zy plane at x plus 125, minus 73, minus 23, 42, 105, 165. C vortices green are visualized for an of 250s 2. The blue surface indicates a velocity of UU0, 47. Distributions of wall normal y and x vorticity, as well as vortical, detected using the median of the three eigenvalues of 2 plus S2, 2 criterion 52, are shown in Fig. 6.17 for the LSSI at t plus 151. Here 2 is the second eigenvalue of 2 plus S2, where VVT2 is the vorticity tensor, and SV plus VT2 is the rate of strain tensor.
The vorticity distributions of Fig.
6.17, a B are shown as contours, superimposed on red line contours representing the deformed material surface of LSSI shown in Fig.
6.13d.
Figure 6.17 reflects opposing sign wall normal vorticity extending in the x direction and flanking the streak region. The opposing sign vorticity flanking the trailing wave, W2, is more balanced than that adjacent to the leading wave, W1. Figure 6.17b indicates that vorticity is concentrated to the sides of the streak, with the positive vorticity, right side, much stronger than the negative vorticity, left side, as indicated by the larger red area on the right. The regions of negative vorticity, left side, also do not appear to be contiguously connected. Figure 6.17c shows the region identified as vortices green, using the 2 criterion with 252. In Fig. 6.17c, the blue surface reflects the LSS visualized by n of UU 0.47. From this figure, there appear to be vortical arch structures straddling the streak, although there is not much evidence of trailing legs for these arch structures' vortices. Additionally, the arch structures do not appear to develop into contiguous hairpin-type vortices, and the 2 identified structures appear to be distributed erratically. Snapshots of LSSs and vortex boundaries, identified based on criterion 53, at t plus 152. The surface shows the of UU 79%, with contour lines showing the wall normal distance. Contours on the slices indicate the distribution of larger than 0.5, with black showing the boundaries of vortices, 0.52. A histogram showing the distribution of vortices, n, according to their distance from the center of the nearest LSS plus. B scatter plot of the strength of vortices, and their distance to the center of the nearest LSS plus. Is the maximum of at the vortex core within the boundary of 0.52. Figure 6.19 shows the distribution of based vortices near the LSSs. Figure 6.19 shows the statistical distribution of vortices relative to their distance from the center of the nearest LSS in the same y-z plane. The position of the vortex was identified according to the maximum of within the boundary of 0.52, and the center of the LSS was identified as the highest region of the of UU 79%. Figure 6.19 indicates that most of vortices flank the sides, indicated by P1 and P2 in the distribution of LSSs in closer proximity to the center of the LSS. Almost 90% vortices are within a distance of plus 50, which is not surprising, considering that the spacing of 2 neighboring LSSs in most of cases is plus 100. Figure 6.19b shows a scatter plot of the vortex strength, relative to their distance from the center of the nearest LSS plus. The figure reveals no relationship between and plus correlation coefficient R003, which indicates that the lift-up of an LSS may not be due to the induction of organized vortices. If a vortex is identified as a strong vortex with 80, then Fig. 6.19b shows that 80% of the identified vortices are not strong vortices, green filled markers in Fig. 6.19b. These vortices may be caused by the breakdown of a 3D wave structure, LSS, or the result of streak instability 7. Note also that the vortices identified as strong, 80 red-filled markers show no consistent or organized pattern that suggests that an LSS is the result of vortex interaction. Based on our present results for an early turbulent boundary layer, the evolution of material surfaces timelines and vorticity distributions, it is reasonable to draw the conclusion that the formation and lift-up of an LSS are not the result of vortex interactions in the near-wall region. Because of the observed warping of the material surfaces shown in Figs. 6.1 and 6.12, we speculate that the initiation and development of LSSs are more likely the result of 3D wave, the amplification and breakdown of which result in the initial streak bursting and generation of hairpin vortices. The vortex-streak interaction process is further examined in Sect. 6.4. 6.4 Vortices in proximity to LSSs. Most coherent structures in a turbulent boundary layer are vortices of one form or another, but there is no universal method for detecting these vortices. Some identification schemes are based on regions of high vorticity according to the instantaneous scalar field values 52, 55, 57, while others are based on a finite time view, considering a set of fluid trajectories 5861. The latter approach defines a coherent vortex as a region with material invariance. In this paper, objective vortex determination is done using a criterion called averaged vorticity deviation, LAVD, based on the technique of Al. 61. This technique is used in conjunction with the velocity field database to detect vortex boundaries and analyze the dynamics of the interaction between coherent vortices and LSSs. In view contours of LAVD and timelines in the region adjacent to the location of the LSSI at LAVD 164.203x0 at time t plus 164, location x plus 105, red dashed lines are timelines at t plus 164. BLAVD 183.203x0 at time t plus 183, location x plus 0, red dashed lines are timelines at t plus 183. Flow direction is out of the plane of the paper. Side view contour of LAVD and timelines in the region adjacent to the location of the LSSI at LAVD 164.203x0 at time t plus 164 and z plus 32 LSSI. The superimposed dashed lines are vertical timelines at t plus 164, corresponding to Fig. 6.5d. BLAVD 183.203x0 at time t plus 183 and z plus 32. The superimposed dashed lines are vertical timelines at t plus 183, corresponding to Fig. 6.5e. The 3D LCVs green extracted using 3D LAVD contours of LAVD 151170x0 in the region of LSSI at t plus 151, superimposed with an isovelocity contour surface of UU 0.65 blue. B. The material surface of Fig. 6.13d. Temporal evolution of LCVs, initially extracted from 3D LAVD 151170x0 field, in comparison with the evolution of three material surfaces, 1, 2, 3, initiated at t plus 131 and y plus 27, 39 and 49 in the region adjacent to the location of the LSSI. See oblique views of LCVs and material surfaces as they appear, respectively, at a t plus 151, bt plus 161 and ct plus 170. DFN views looking upstream of LCVs and material surfaces as they appear, respectively again at dt plus 151, et plus 161 and ft plus 170. In Fig. 6.22b, the two vortices are remarkably coincident with the two humps of the material surface previously determined in Fig. 6.13d. This appears to support the conjecture that Kane vortices are generated in proximity to an LSS, or more precisely on the flanks of 3D waves. It may be argued that the two humps in the LSS, apparent wave structures, are induced by the vortices. However, evolution of the material surface shown in Figs. 6.12 and 6.13 clearly displays that the 3D wave structures are much larger than the Kane vortices, and further examination of material surface development initiating farther from the wall shows that the 3D wave extends from the very near wall region to y plus 80. In addition, the highest vertical velocity of the wave structures occurs in the near wall region, y plus 20, rather than adjacent to the vortices. The instantaneous vorticity field results of Figs. 6.14617, as well as the results from the 2D LAVD, all support the conclusion that 3D wave structures associated with LSSs are what give rise to the vortices and not vice versa. Turbulent bursts at LSS. A tomographic visualization of LSSs and high-speed region, B schematic view of physical of burst in low-speed region. Adapted from 66. 6.5 discussion. The results of the present study suggest that LSSs may be characterized as propagating 3D wave motions accompanied by ejection and sweep. The tomographic visualization results appear to be in accord with hydrogen bubble line visualizations, which suggest that the kink structure in vertical timeline patterns is consistent with the development of an incipient 3D wave, which evolves into an amplified wave structures as it advects downstream. A hypothesized model of the bursting process juxtaposed on an experimental image of LSSs, is shown in Fig. 6.24. The LSSs shown in Fig. 6.24 are reconstructed from PIV datasets at Y+30, and the hypothesized bursting process is characterized as a combined process of LSS ejection and HSS sweep, as shown in Fig. 6.24b. Smith 5 proposed that the bursting process of an LSS involves vortex roll-up of the unstable shear layer formed on the top and sides of an LSS. The process consists of 4 stages: 1. Lift-up and oscillation of an LSS, 2. Initiation of vortex roll-up, 3. Vortex development, amplification, and concentration, and 4. Vortex ejection, stretching, and interaction. The first stage was explained by the growth of the LSS in the presence of an impressed local adverse pressure gradient, which leads to local fluid deceleration and development of a 3D inflectional profile. Once an inflection develops, the streak will become locally unstable, precipitating a breakdown, conceptualized as a burst. However, the origin of the LSS and the origin of the local adverse pressure gradient were not identified. It was hypothesized by Smith 5 that the passage of a vorticity concentration created upstream can create a transient, spatially varying pressure gradient, which could precipitate the local deceleration. That is supported by the classical kernel studies of isolated vortices, such as the hairpin vortex shedding from a hemisphere protuberance being shown to precipitate downstream fluid ejections from near the bounding wall 47-65. However, for a boundary layer on a smooth, flat plate without impressed disturbances, the natural process that causes the development and breakdown of LSSs is not readily apparent. In order to address that question, we will consider the process of transition in an initially laminar boundary layer, e.g. 1924, see also Appendix 2. A comparison of the timeline patterns for a controlled transitional boundary layer reveals markedly similar patterns to those for LSSs in a turbulent boundary layer, Figs. 6.466. This suggests that the process and the structures developing in the transitional boundary layer may reflect a similar process and structure in the near-wall turbulent boundary layer. In previous studies, spikes were found in the late-stage transition, and they were found to originate from the high-frequency secondary instability, 25-26. Chains of ring-like vortices, termed CS Soliton, were also suggested to explain the spikes in the outer part of the boundary layer 67-68. The model of Smith 5 is similar to the concept of an instability-induced hairpin scenario of Al. 25 and Hack and 27, which attributed the origin of hairpin vortices to the instability of LSSs. The studies of streak instability have shown that a varicose instability of an LSS is able to create arch vortices, and the sinuous instability of an LSS produces quasi-vortices on the sides of the LSS. The wave structure within the LSS observed in the present study may be a manifestation of a varicose instability of an LSS. The wave-like undulation of an LSS varicose instability in turbulent boundary layers leads to a wave-like vorticity concentration and a local 3D high shear layer, which are considered as the necessary conditions for the development of a hairpin vortex or arch vortex. As noted in 11, the transient growth of streaks can generate the well-documented structures near the wall from an initially quiescent streak region containing no initial vortices. The growth of a wave-like LSS, as suggested by this study, may reflect a transient growth process because the proper wavelength of the streak, L+, is close to the most amplified disturbance calculated from the liner stability by an 11. But this, of course, needs further investigation. A sequenced model of the hypothesized temporal development of a 3D wave structure leading to subsequent vortex generation. It is hypothesized that a 3D wave, appearing as a warped wave front 24, develops as a nonlinear interaction of a pair of opposing angle oblique waves, as are observed in boundary layer transition, see Fig. 6.3. As the generated 3D wave travels downstream at a speed of approximately 65% u, it moves upward to retard the outer fluid, similar to the action of a pulsed wall jet. This deflection of the outer fluid results in a local change in the pressure gradient, as well as creating inflections in the and transverse velocities. The result is the development of a 3D inflectional profile, as depicted in Smith 5. As the fluid encompassed by the 3D wave moves upward, the surrounding flow is displaced downward due to mass conservation. During this process, the differential in flow velocities between the wave and the downward moving fluid will create a high shear interface at the 3D wave boundaries, shown as stage A in Fig. 6.25. The lift-up speed for the 3D wave is maximum in the near-wall region, and as the wave moves upward within the boundary layer, it will deform into an inclined 3D wave as it encounters higher velocity fluid at its crest, shown as stage B in Fig. 6.25. The ejections and sweeps that are stimulated by the 3D wave lift-up create a high vorticity, 3D shear layer encompassing the wave, which subsequently breaks down, rolling up into hairpin or other vortices. This process is similar to the advected instability caused by the 3D separation from a hemisphere or a transverse fluid injection from the wall 47, 65, 71. The so-called vorticity concentrations in the low-momentum streak region 5, or the vorticity intensification near the bulge ridge 49, may be caused by the ejection of the 3D wave structure according to vorticity transfer theory 72. The initial vortex rollup caused by the lift-up and the resultant wallward sweep motions are presumed to be inclined at an angle to the wall, as modeled by the initial rollup shown in stage B of Fig. 6.25. It is also presumed that the inrush-induced shear layer near the lower trailing portion of the wave will be weak due to the background shear, and thus the initial vortex rollup will appear as a shaped vortex. Once the vortex rollup develops along the high shear boundaries of the 3D wave, the vortex will then shed and be stretched into a hairpin vortex, as shown in stage C of Fig. 6.25. This shedding and stretching process is dominated by self-induced motions and viscous inviscid mechanisms, resulting in subsequent vortex ejection, stretching, and interaction. Note that the model shown in Fig. 6.25 is an idealized process, for which the vortices develop symmetrically without consideration of other events occurring in proximity to the wave, which will, of course, have a secondary influence on there. It is known that most vortices detected in turbulent boundary layers are asymmetric and appear predominantly as distorted one-legged hairpins or cane-like structures 6, 30, 64, 73, 74. These vortex characteristics are also supported by the results of the present study. However, the assessment using timeline and vorticity distributions shown in Figs. 6.14619 reveal no apparent large-scale vortices associated with the LSSs. However, using an assessment via LAVD processing, quasi-vortices adjacent to the 3D waves were detected, which are speculated to arise from initial vortex rollups evolving from the high shear layer interface of the 3D wave. The reason the LAVD method can detect these vortices is that methods inspect and trace a domain of fluid for a finite time, from which it is easier to extract the dominant flow structures and with less effect of extraneous noise. LSSs are abundant in bypass transition and are similar to the flow topology of LSSs in turbulent boundary layers. Streak breakdown and bypass transition has been studied experimentally 46, 75, 76, and using simulations 77, 78. A sinuous streak instability mode developing into a train of vortices is commonly observed. From an instability viewpoint, the streak breakdown into hairpin vortices in the present study seems to be due to the varicose instability of the 3D high shear layer lifted away from the wall. This process is manifested as the lift-up and amplification of a 3D wave-like structure in a perspective. This observation is different from the ubiquitous sinuous instability of LSSs in bypass transition. Recently, Wu al. 79 proposed the presence of transitional turbulent spots, TRTSs, and turbulent spots, TUTSs, in boundary layers. The inception mechanism of TRTSs in bypass transition is analogous to the secondary instability of natural boundary layer transition 25. However, Wu al. 79 determined that the existing TRTSs will influence the meandering, waviness, and breakdown of long streaks, although the streaks are not the mechanisms for the inception of TRTSs. Al. 70 used a base structure identification method to study the inception of turbulent spots and their lateral growth. They observed that the vortex surface in the inception of tutzes first forms a triangular bulge and then evolves into the primary hairpin-like structure by a rolling up of the lateral edges of the bulge. The roll-up of the hairpin-like bulges further induces sinuous perturbations and triggers a Kelvin instability in the direction. The vortex surface deformation is similar to the initial deformation of temperature during the initial formation of TUTS 79. The triangular bulge observed in bypass transition 70, 79, and also K-regime transition 49 appears similar to the wave-like structures of the streaks observed in the present study, e.g. Fig. 6.11. This suggests that a similar 3D wave amplification of the LSSs is responsible for the generation of wall region hairpin and other types of vortices in turbulent boundary layers. The meandering of the LSSs, Fig. 6.8b, which can be as much as 50 wall units, documented and discussed in Sect. 6.4 and also by Al. 70 is speculated to be result of subsequent streak vortex interactions. Once a hairpin vortex develops, including its asymmetric types, it will induce fluid near the bounding surface to lift up and promote the ejection of the 3D wave, which may be construed as the bursting process in a developed turbulent boundary layer. This may unify the two general concepts applied to the term bursting 73, in that this model suggests that the development of both local instabilities and quasi-vortices are associated with 3D waves. It is hypothesized that low-momentum fluid developing between the legs of hairpin vortices, or adjacent to quasi-vortices, combines with fluid ejected by the breakdown of the 3D wave to form further low-speed regions 27, 74. The continued quasi-periodic generation of hairpin vortices by this breakdown of 3D waves will result in the development of hairpin packets by a complicated process of self-induction and vortex interactions, which will subsequently result in the generation of larger uniform momentum zones. Additionally, the interaction of the initially generated vortices with subsequent 3D waves can act as a perturbation to cause continued wave breakdown, resulting in continued regeneration of hairpin-like vortices and providing the mechanism for sustaining wall-bounded turbulence. 6.6 Conclusion. In the present paper, the near-wall structures of an early turbulent boundary layer have been investigated using timeline and material surface visualization synthesized from a pod-filtered PIV, as well as identification of coherent vortices, LCVs, using averaged vorticity deviation, LAVD. The timeline visualizations confirm that LSSs are spaced with plus 100, and the bursting process is observed to be comprised of ejection sweep events. The 3D evaluation of the tomographic timelines demonstrates that the so-called bursting process is closely associated with 3D wave of LSSs. A wave-induced burst is observed to consist of a slow lift-up of near-wall fluid, followed by an amplification and breakdown. The temporal deformation of advected material surfaces, Figs. 6.1, 6.12, and 6.13 reveals a 3D wave of the LSS, with the subsequent breakdown resulting in ejections and sweeps associated with the bursting process. As shown by the evolution of material surfaces at varying distances from the wall, the 3D wave structure propagates downstream at a speed of nearly 65% of the free stream velocity, determined by the wave crest movement, which is essentially the same speed as that determined by tracking the kinked band visualizing a streak within the timeline patterns. The maximum upward velocity of a 3D wave, as determined by the translation of wave crests, is nearly 6% of the free stream velocity at y plus 49, decreasing as the wave moves away from the wall. The vorticity distribution results appear to support the hypothesis that 3D wave amplification is the active process that leads to the development of LSSs and not the result of vortex interactions. To further investigate the relationship between LSSs and vortices, both 2D and 3D LAVDs 61 were applied to near-wall regions where LSSs were present. These vortices are identified as roll-ups occurring adjacent to the high-shear interface of 3D waves on a streak, but which are not mature enough to evolve into a hairpin vortex. These detected LAVD vortices also support the hypothesis that hairpin vortices originate from the unstable high shear layer generated at the interface between lifted-up low-speed, near-wall fluid and downward sweeps of high-speed log-region fluid 48, and are not the cause of such lift-ups. Large-scale quasi-vortices, detected using 3D LAVD criterion, show that such vortices develop adjacent to the lateral sides of an LSS. These cane-like vortices are hypothesized to be generated by the amplification and breakdown of the 3D wave of the LSS. The present study suggests that LSSs appear to evolve as 3D waves. These 3D waves with low advection speed 60–80% of U are hypothesized to have their origin in the near-wall fluid, creating an interfacial shear layer with higher speed outer fluid, similar to Soliton-like coherent structures, 2023. The process results in the generation of local 3D pressure gradients and the subsequent wave-like amplification of the shear layer. The burst sequence model observed by the present study is similar to that hypothesized by Smith 5. However, we suggest that the oscillation and undulations of an LSS, as well as the initial breakdown and roll-up to form vortices, are products of the streak behaving as a 3D wave within the near-wall fluid. The initial breakdown and roll-up of an LSS will develop along the bounding high shear layer of the 3D waves. These shear layers will subsequently evolve into several inclined vortices adjacent to the waves, which will further develop into hairpin-like or other vortices. The vortices observed in the viscous wall region usually manifest themselves as quasi-vortices. Thus, the two general concepts of the term bursting by 73 may be unified, in that the development of streak instability and the generation of quasi-vortices may both be associated with 3D waves. It must be admitted that establishing the framework of coherent structures and extracting their cause and effect within a turbulent boundary layer is a formidable challenge. The joint theoretical and experimental efforts of investigators have resulted in many classical models, although some of them display many discrepancies. The present study has attempted to understand the process of development and breakdown of LSSs and the associated bursting within the near-wall region at low number, y+100. The models proposed in this paper are not free from bias, but the ideas are initiated and motivated by the work of many respective researchers. In developing our present model of near-wall turbulent, we have tried to rectify the results of previous studies with the results and observations of the present study. We hope that our results and perceived model of near-wall turbulence will facilitate a better understanding of turbulent boundary layer. The authors would like to express great appreciation to Prof. J.Z. Wu, Professor Y. Yang, and Prof. S.I. for their valuable and constructive advice. The authors gratefully acknowledge Prof. for providing a DNS database. The authors are also grateful to Dr. Y. Dr. X. Dr. A. and Dr. C. for valuable discussions on this research work. Competing interests. This work was supported by the National Natural Science Foundation of China grant Nos. 10,921,202, 11,221,061, 11,632,002, 11,521,091, 11,602,005, and the National Key Project grant No. GJXM 92579. The authors have no conflicts of interest to declare that are relevant to the content of this chapter. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial 4 International License, org licenses by 4.0, which permits any non-commercial use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. Appendix 1, Pod Analysis and the Low-Order Representation. Energy distribution of the pod modes for different selected sizes of the pod sample. Velocity contour at y plus 30 and t plus 164 based on different pod approximations. A pod approximation based on first 80 leading order pod modes. B pod approximation based on first 22 leading order pod modes. C pod approximation based on first 4 leading order pod modes. D original flow fields after a smoothing filter with 555 vectors, superimposed within a view U 73.5%. E pod approximation based on first 4 leading order pod modes, superimposed within a view U 73.5% blue region. The flow field can be represented in terms of the finite or truncated series, only within the first R modes 82. Lower rank approximations of the velocity field at y plus 30 and t plus 164 are shown in Fig. 6.27 SC, with R being selected as 80, 22 and 4 respectively. A comparison between Fig. 6.27 SC shows that the velocity field based on pod approximation from the first 4 leading order pod modes contains less small structures, while retaining the large-scale structures. Low-speed streaks represented by an of UU 73.5% blue regions are shown in Fig. 6.27d, E for both the original velocity field after a smoothing with 555 vectors, and for a pod-approximated field with R4 respectively. A comparison between Fig. 6.27d with Fig. 6.27e shows that pod is effective for retaining the larger-scale low-speed streaks. Figure 6.2b shows the effect of the pod filtering of PIV on fluctuating velocity profiles. The underestimation of velocity fluctuation U is 40% in the vicinity of the wall, while the underestimation of V can be as high as 80%. This indicates that the method of low-order approximation based on the first 4 pod modes is similar to an appropriate filtering with a large box filter, as is commonly used for turbulent shear flows 83. Appendix 2, Tracking based on marked particles. Vortex. A timelines reconstructed from a DNS dataset for K-regime boundary layer transition on a flat plate at MOS 0.586, initiated at Y 33.2%. B structures detected based on Q criterion from the same DNS dataset. Blue of velocity UU 36.7%, green of Q 0.0023 S2. Vortex. A timelines reconstructed from a DNS dataset for a laminar boundary layer with a straight vortex tube 87. Timelines were initiated at Y 50%. B structures detected based on Q criterion. Blue of velocity UU 36.7%, green of Q 0017s2. Timelines reconstructed from NPSE database for O-type boundary layer transition, initiated at Y 50%. LSS is within the white dashed region, as indicated to the upper left of the figure. Wave structure. In order to show a wave structure in a boundary layer, a database obtained from the solution of nonlinear stability equations, NPSE, was used to reconstruct a timeline surface for a 3D O-type transition wave 24. A pair of oblique disturbances was introduced in the flow, causing the creation of 3D waves, which amplified due to mode interaction as they traveled downstream. This O-type transition, shown in Fig. 6.3, is characterized by the appearance of LSSs. Note that a 3D wave W0, as it appears in the early stage of O-regime transition, is identified in Fig. 6.3. The subsequent development of an LSS is observed to consist of several wave structures, W1, W2, and W3 in Fig. 6.3. References: 1SJ WC FA PW J Fluid Mech. 34 741 1967. Org 101017 S0022 112067001740. 2H SJWC J Fluid Mech. 50 133 1971. 3 MR Head P J Fluid Mech. 107 297 1981. Org 10-10-17S0022-1120-8100-1791. 4CR Smith, SB, J. Fluid Mech. 129-27-1983. Org 10-10-17S0022-1120-83000634. 5CR Smith, in Proceedings of the 8th Symposium of Turbulence, Ed. By G.K. J.L., University of Missouri, 1984. 127. 6CR Smith, J.D.A. Walker, A.H.U.
Trans. R. Soc.
London.
Sir. A.
336-1641, 131, 1991. 7J. P. J. Fluid Mech. 225-213, 1991. 8J. A. J. Fluid Mech. 389-335, 1999 net. 9RJ Adrian, CD, J. Fluid Mech. 422-1-2000 net.
10F.
Fluids 94, 883, 1997. Org 10-10-63186-9185. 11W-F J Fluid Mech. 453-57 2002. Org 10-101-7S0022-112001006667 net. 12IRN Science 329-5988, 193 2010. Org 10-1126 Science 1188765 net. 13YM-JM SJP-SOB J Fluid Mech. 771-624 2015. Org 10-10-1720-15158. 14 FR Hama. Fluids 56, 644 1962. Org 10-10-63-1170-6678. 15 J. Fluids 12-8, 1885-2000. Org 10-10-63-1870-437 net. 16 SI MF J Fluid Mech. 544, 99 2005. Org 10-10-17 S0022-112005006506 net. 17 MT J Fluid Mech. 98-2, 1980. Org 10-10-17 S0022-1120-80000122 net. 18 MT J Fluid Mech. 212-1, 593, 1990. Org 10-10-17 S0022-1120900002-105. 19 FR Hama, J. In Proceedings of the Heat Transfer and Fluid Mechanics Institute, University Press, 1963. 77-93. 20 CB Lay. A 247-6, 397, 1998. Org 10-10-16 S0375960198005829. 21 CB Lay.
Rev.
E62-3, 3659 2000. 22 CB Lay, RQ Lay J. 855-1 2007. Org 10-10-801-46852-40600925-163. 23 CB Lay, JZ Wu.
Mech. Rev.
61 30802, 2008. 24 XY CB Lay X CR Smith PF Linden J Fluid Mech. 890 A11 2020. Org 10-10-1720-20107. 25 M.S. in Transition and Turbulence, Ed. By R.E. Academic Press, 1981. 113-126. 26 M.M. in Turbulence and Chaotic Phenomena in Fluids, Ed. By T. North Holland, 1984. 8I-792. 27 MJP Hack P J Fluid Mech. 844 917 2018. Org 1010-1720-18202. 28T CWP J Fluid Mech. 724 480 2013. Org 1010-1720-13142. 29 ARGE FU Exp. Fluids 44-2, 305 2008. Org 101007 S0034800 704032. 30 DJC TB Nichols J Fluid Mech. 673 180 2011. Org 101017 S0022 1120 6324. 31 QC IE Exp. Fluids 5412 2013. Org 101007 S003480 32 DR TJ CV Seal SCR and Flow Visualization, Techniques and Examples ED. By A.J. Smith, T. Imperial College Press, London 2012. 2745. 33B Exp. Fluids 45-4, 549 2008. Org 101007 S003480 5215. 34 KP Lynch F Exp. Fluids 56-3, 66 2015. Org 101007 S003480 1519346. 35P RD J Fluid Mech. 200 471 1989. Org 101017 S0022 11208900 741 net. 36 AJ AIAJ 176 655 1979. Org 102514361193. 37 DB Spalding J. Mech. 28-3 455 1961. Org 10111513641728. 38X Wu P J Fluid Mech. 630-5 2009. Org 101017 S0022 112009006624 net. 39 PR J Fluid Mech. 187 61 1988. Org 101017 S0022 112088000345. 40 LP PSF. Fluids 24-5, 802 1981. Org 101063186345 41N SH Exp. Fluids 56-8, 159 2015. Org 101007 S003480 1520245. 42S S. Ben David, Understanding Machine Learning, From Theory to Algorithms, Cambridge University Press, 2014. Org 101017 CB0978110 0729801943F. Technol 24-1-12001 2013. Org 101088095702332410120001. 44 LJ CR Smith J Fluid Mech. 232 303 1991. Org 101017 S0022 112091003701. 45 FX in Advances in Fluid Mechanics, ED. By E. Springer, Berlin, Heidelberg, 1981. 268 279. 46 MYYM J Fluid Mech. 586 371 2007. Org 101017 S0022 112007000688. 47 MS CR Smith J Fluid Mech. 175 43 1987. Org 101017 S0022 112087000284. 48 AH CR Smith J Fluid Mech. 277 135 1994. Org 101017 S0022 112094002715. 49Y Y Yang SY J Fluid Mech. 793 840 2016. Org 10101720 net. 50J P J Fluid Mech. 162 339 1986. Org 101017 S0022 112086002070. 51 Sibile ZX YSVI VV Exp. Fluids 283 243 2000. Org 101007 S003480050384. 52J F J Fluid Mech. 285 69 1995. Org 101017 S0022 112095000462 net. 53C Y Y Yang Z.
China, Mecca.
59 8 684,711 2016. Org 101007 S11433016000226. 54S YX Dong C J Fluid Mech. 849 312 2018. Org 10101720184006 net. 55 JCR Hunt AAP Eddies, Stream and Convergence Zones in Turbulent Flows.
Tech, Rep.
CTR S88 Center for Turbulence Research Report 1988. 56 MS AE Perry BJ. Fluids 25 765 1990. Org 10106318577730 net. 57 PS RJ Adrian J Fluid Mech. 535 189 2005. Org 101017 S0022 112005004726 net. 58G J Fluid Mech. 525 1 2005. Org 101017 S0022 112004002526 net. 59 SC JO JA. Fluids 184 47105 2006. Org 10106312189885 net. 60 MA Green SWG J Fluid Mech. 572 111 2007 net. 61 GAM F J Fluid Mech. 795 2016. Org 10101720165151. 62 G J Mech. Solids 86 70 2016. Org 101016J2015100002 net. 63 GE DJ BW Van F in 45th AIA Aerospace Sciences Meeting and Exhibit, Reno, U.S. 2007. 64 M.
Rev.
Fluids 2 100506 2017. 65 MS CR Smith J Fluid Mech. 175 1 1987. Org 101017 S0022 112087000272. 66 CR Smith, in Proceedings of the International Symposium on Seawater Drag Reduction, Office of Naval Research, 1998. 3945. 67 YS.
Rev. Fluid Mech.
26 1 411 1994. 68 VI VR YS DGW URIST QX CB Lay. Fluid Dyne. 15 5 317 2002. Org 101007 S00 1620100054. 69 W Numerical Simulation of Boundary Layer Transition by combined compact difference method. D. Thesis, Technological University, Ave, Singapore, 2013. 70Y S. Y Yang S. Rev. Fluids 37, 74701, 2018. Org 101103, Rev. Fluids 3074701. 71 DRT, Exp. Fluids 571 1, 2016. Org 101007 S00348015208991. 72 JZ Wu, HY Ma, MD Joe, Vortical Structures in Transitional and Turbulent Shear Flows, Springer, Berlin, Heidelberg, 2015. 361 404. Org 10100797836662 47061911. 73 SK. Rev. Fluid Mech. 23 601 1991. 74 RJ Adrian. Fluids 19-4, 41301 2007. 75 MPH J Fluid Mech. 430 149 2001. 76 J Mans HC AA Van. Fluids 19-8, 88101 2007. Org 10106312750684. 77 LDS J Fluid Mech. 472 229 2002. Org 101017 S0022 112002002331 net. 78 X Wu P. Fluids 22-8, 85105 2010. Org 10106313475816. 79 X Wu P JMJA JP Hickey Proc. ACAD. 11427 E5292 2017. Org 1010731704671114. 80 Y Wu. Fluids 26-4, 45113 2014. Org 10106314873199. 81 S C Pan J Jihe J Fluid Mech. 844 635 2018. Org 10101720181160 net. 82K SL SDM Dawson CWT BJ OT SV LS AIAJ 5512 4013 2017. Org 10251441J0 56060. 83C NA OJ Exp. Fluids 55-1 1654 2014. Org 101007 S00348013165548. 84 ELJ Fluid Mech. 199 403 1989. Org 101017 S0022 112089000042. 85 PS Bernard, AIA J518, 1828 2013. Org 10251441J0 51811. 86 KKN. J. Meth. Heat Fluid Flow 28-5, 1187 2018 0508Z. Org 101108 HFF 0620 170253. 87K. J. Meth. X. 474 2016. 7. A metamorphosis of soliton-like coherent structures in transitional and turbulent boundary layers. Abstract. Laminar turbulent transition in boundary layers is characterized by the generation and metamorphosis of flow structures. However, the process of the evolution from a three-dimensional 3D wave to a vortex is not fully understood. In order to develop a deeper understanding of the spatiotemporal wave warping process, we present numerical studies of both K-regime transition and bypass transition. A qualitative comparison of flow visualizations between a K-regime zero pressure gradient ZPG case and an adverse pressure gradient APG case is done, based on the method of tracking of marked particles. In bypass transition, the development of a 3D wave packet before the breakdown into a turbulent spot was visualized for both the linear and nonlinear stages. The underlying vortex dynamics was investigated using a proposed method of averaged. The study illustrates that a vortex develops from a 3D warped wave front WWF, which undergoes multiple folding processes. It is observed that the APG case undergoes a more rapid evolution, precipitating a stronger viscous-inviscid interaction within the boundary layer. It is hypothesized that the amplification and lift-up of a 3D wave causes the development of high-shear layers and a WWF. In order to seek a relationship between transitional and turbulent boundary layers, methods were also applied to an experimental data set from a turbulent boundary layer at low number. Similarity of flow are observed, which further supports the hypothesis that the amplification of a 3D wave precipitates low-speed streaks and rotational structures in wall-bounded flows. Supplementary information. The online version contains supplementary material available at org 10-100 7978 980 195 244 197. Keywords. Xianyang and Dingwei are the authors contributed equally to this work. This chapter is reproduced with permission from XY, DW, CB Lei, CR Smith, and P.F. Linden, a metamorphosis of three-dimensional wave structure in transitional and turbulent boundary layers, J. Fluid Mech. 914, A4, 2021. Copyright 2021, Cambridge University Press. The content of the article has been slightly revised. 7.1 Introduction. The origin of wall-bounded turbulence has been one of the most classic research problems for the fluid mechanics community. This problem has attracted much attention because of the fundamental significance in understanding the process of turbulence production and the considerable difficulties encountered in identifying the building blocks of coherent structures in laminar, turbulent transition. There have been many reviews related to the coherent structures in transitional and well-developed turbulent boundary layers 1-8. However, most research investigating the generation or regeneration of turbulent structures usually does not take into account the early transition stage, where three-dimensional 3D waves play important roles. The origin of hairpin vortices that many studies take as the dominant flow structure of turbulent boundary layers is not well understood. 9. In the present study, a comparative analysis is made between a zero-gradient boundary layer ZPG and a FS flow with an adverse pressure gradient APG. In addition, a direct numerical simulation DNS study of a turbulent spot and an experimentally determined low-number turbulent boundary layer are also presented for comparison with the transitional flows. In the classical work of Hama and his colleagues, which employed hydrogen bubble visualization to observe structures within a transitional boundary layer 10-11, they observed that a TS wave warps 3 during amplification, acquiring a longitudinal vorticity component along its swept back front. This layer of concentrated high shear, which appears as an inflection in vertical hydrogen bubble timelines, i.e., a kink, subsequently develops into a hairpin-shaped discrete vortex. This localized and intensified warped wave front, WWF, was considered as the source of subsequent hairpin-shaped vortices. The warping process and kinked profiles were frequently observed experimentally or numerically in transitional boundary layers 12-15. L16 systematically investigated the development of a WWF in the early stage of K, N, and O regime transition, demonstrating qualitative similarity between the stages. However, the roles of a WWF in APG transition are not clear, and the manner in which a WWF originates and evolves in an APG is not well understood. This emphasizes the need to examine the details of the warping process and the development of a WWF prior to the emergence of vortices in an APG flow. A hypothesis based on a 3D wave-like structure, termed a soliton-like coherent structure SCS, has been proposed by 15 to explain the velocity profile kink. Such a 3D wave-like structure was observed within the whole boundary layer, in both the early and later stages of a transitional boundary layer 5-17. 18 confirmed the existence of an SCS and its dominant role in the vortex evolution process using DNS. 19 investigated the evolution of material surfaces in channel flow and determined that a triangular material bulge forms before the roll-up of a vortex sheet, which is similar to the results of 18 and Lei and Wu 5. Their simulation shows that the heads of primary hairpin-like structures develop directly from those triangular bulges. A decelerating flow parameter H018 was investigated by N20 using DNS. They observed that the resulting breakdown process for an adverse pressure gradient is dramatically more complex than a K-regime breakdown for a flow. They observed that a lower characteristic high shear layer, HSL, formed between the primary vortex and plays a key role in precipitating an ultimate breakdown to turbulence. 21 implemented an experimental study of coherent structures for a late-stage APG boundary layer, H0115. Formation of vortices, shaped 3D HSLs and ring-like vortices was observed, and were shown to be qualitatively similar to those found in ZPG boundary layers. They pointed out that the instantaneous velocity and vorticity fields seem to correspond qualitatively to those present in the near-wall region of a developed turbulent boundary layer. Lee 22 discussed the similarity between the physical mechanisms for the structure formation in both transitional and developed turbulent boundary layers, and proposed a universal path to transition based on the concept of SCS. 2324 evaluated flow statistics and near-wall dynamics for K and N-regime breakdown during late-stage transition, and proposed late-stage transition, manifested by hairpin packets, as a reduced-order model of a turbulent boundary layer. The key structure that supports the similarity is the low-speed streak, LSS, which plays key roles in turbulence production 25-27. And 28 investigated a turbulent channel flow using linear theory and DNS. They identified a streak transient growth, known as SDG mechanism, by which streaks generate vortices and hence sustain turbulence. However, the collective simulation and experimental studies reached no consensus on the near-wall turbulence production cycle. The relationship between LSS, or hairpin vortices, and the so-called bursts in both transitional and turbulent boundary layers merit further investigation. Turbulent spots can be found frequently in both the bypass transition flow and turbulent flow. Park Al. 29 investigated turbulent spots and fully developed turbulence by examining the numerical flow data of a flat plate boundary layer with a passively heated wall, and found little difference in the structure and transport processes between these two cases. Recently, Wu al. 30 observed that two different types of hairpin vortices develop in a pipe flow: reverse hairpin vortices in the near-wall region and forward hairpin vortices in core region. A patch of negative skin friction, which is caused by a reverse hairpin vortex, occurs both in the transitional region and the fully developed turbulent flow region. The inception mechanism for turbulent spots is a common concern in the study of bypass transition. Wu al. 31 observed that the transitional turbulent spot inception mechanism is analogous to the secondary instability of a transitional boundary layer, with a spot originating from a vortex filament and a vortex. They also observed turbulent spots in the inner layer of a developed turbulent boundary layer, which coincide with local concentrations of high levels of. Lee and Wu 5 pointed out that the turbulent spot is a composite structure, which is a combination of several 3D wave structures, SCS, and the residual vortices within the spot boundaries. However, there is still a lack of understanding of the process by which a wave packet develops into a turbulent spot. There are many methods that have been used to study the dynamic process behind the visualized metamorphosis of flow structures, either using approaches 32, 34, or approaches 35, 36. Coherent structures, LCSs, are distinguished as surfaces of trajectories in a dynamical system that form the skeletons of particle dynamics over a time interval of interest 37-38. Averaged vorticity deviation, LAVD, is one of the representative LCS detection methods that extract the influence of vortices on nearby flow 39. However, due to the non-uniformity of background vorticity in boundary layers, the value of LAVD may rely on the selected initial fluid volume. Recently, the determination of the field has been applied to stratified flows to identify turbulent non-turbulent interfaces, known as TNTI-40. The evolution of is closely related to vortex stretching effects, which is a critical kinematic mechanism in a shearing process. In the present work, a method of averaged LAE is employed to analyze wall-bounded flows, using the integral of the IE. 2 along fluid trajectories over a finite time interval of interest. The objective of the present paper is to characterize the development of 3D waves during transition and to understand the underlying dynamic process that gives rise to vortices, especially in APG cases and for turbulent spots. We also examine the connections between transitional and turbulent flows. The remainder of this paper is organized as follows, in sect. 7.2 The methods of nonlinear stability equations, NPSC, and DNS are described, including the method of tracking, in sect. 7.3 A comparative study of numerical flow visualization and corresponding LCS based on LAE is presented for ZPG and APG cases, in sect. 7.4 The development of a 3D wave packet into a turbulent spot is illustrated, including an analysis of the intensity, in sect. 7.5 Methods, the same as employed for the transition cases, are applied to an experimental data set from a turbulent boundary layer, attempting to understand the streak in near-wall turbulence, in sect. 7.6 The underlying physical mechanisms for the 3 different flows are discussed, and concluding remarks are given in sect. 7.7 7.2 Numerical approaches. 7.2.1 PySC. Numerical settings for the 2 K-regime transition simulations. A normalized notation is used in mode description. The first digit indicates multiples of the fundamental frequency. The second digit refers to multiples of the fundamental. Case 2D wave, 3D wave, parameter H, mode F106, A mode F106, A ZPG 10 106 0.2% U11 106 0.05 0.14% U0 IPJ 10 435 4% U11 435 0.18 0.2% U0062. Here, NPSC was utilized to study the flow patterns for K-type transitions, for both a ZPG and an APG. In the language of frequency, the notion is used, where and denote the frequency and respectively. For simplicity, and are normalized on the corresponding primary waves. For K-regime transition with a ZPG, a two-dimensional 2D TS wave of normalized frequency F16106 corresponds to period T1482, and a pair of oblique waves at the same frequency were introduced at the inlet X0400 with a relatively smaller amplitude, i.e. modes 10 and 11. For K-regime transition with an APG, a 2D TS wave of normalized frequency F435-106 corresponding to period T560 was forced at the inlet by a pair of oblique waves at the same frequency, X0258. The profile of an FS boundary layer is characterized by a power law dependence on the free stream velocity u in the coordinate direction, i.e. ux. The parameter related to m by h2 m1 plus m0062 is a measure of the strength of the mean pressure gradient. The detailed information for the wave components forced at the inlet of the simulation for these transition scenarios is shown in Table 7.1. Neutral stability curves for a boundary layer based on PSC, red line, and linear stability theory, LST, blue line, and an FS boundary layer based on NPSC, green line. The input normalized frequency for the boundary layer is F16106. The corresponding data of AL 41 are represented by triangles and circles, respectively. The parameter for the FS boundary layer is H0062, with an input normalized frequency of F435-106. Mode amplitude evolution for K-regime transitions with ZPG dashed lines and APG solid lines. The development of the Y maxima of the selected Fourier amplitudes for both the transitions of ZPG and APG is shown in Fig. 7.2. For the ZPG boundary layer, after the initiation of a fundamental 2D TS wave, 1, 0 and oblique waves 1, 1, streak mode 0, 1 progressively develop downstream, exceeding the amplitude of the fundamental disturbance 1, 0 at approximately R680 x 1156. A similar growth in the amplitude of the streak modes and oblique modes is observed for the APG case, the amplitude exceeding the initial characteristics at approximately R345 x 224. The NPSC simulation for the ZPG case becomes invalid at R728 x 1325, while the APG simulation becomes invalid at R377 x 267. 722 DNS. The simulation in this paper is governed by the compressible Stokes equations, which are listed in Appendix. The code was developed and by Lee al. 45. The calculations were performed on the He2 at the Joe Supercomputer Center. Schematic mesh of DNS. DNS parameters. Mod. Ray0 M1. T0 KK. Zim. R0 M. 3. 6106. 0.72. 350. 125. 8. 12. 58. 62. 2.09. 2. For boundary conditions, the inflow boundary is set as the laminar flow at x10 to reduce the computational cost. Free stream parameters are applied at the upper boundary, and a non-reflecting boundary condition is used for the upper and outflow boundary. No-slip and isothermal conditions are at the wall surface, where 5 and the localized disturbance generated by blowing and suction is added at x20. A periodic condition is applied in the direction. 723 method of tracking of marked particles. In this paper, results are primarily based on marked particles, which are followed using tracking methods. Flow visualizations that are reconstructed from the NPSC velocity field data are termed NPSC visualization 16. A brief introduction to the tracking method employed is given here. Tracking of marked particles, a B tracking of a material surface consisting a grid of particles, C D timelines. 7.3 K-type transition with ZPG and APG. 7.3.1 numerical flow visualization. Timelines initiated at Y171 24% for K-type transition with a zero pressure gradient and B adverse pressure gradient. Particles released at X1011.2 and 164.5 for ZPG and APG, respectively. Evolution of timeline surfaces initiated at Y171 24% for K-regime transition with ZPG at a T6.1T, BT 7.1T, and for K-regime transition with APG at CT 3.2T, DT 4.2T. Here T is the period of corresponding primary waves, SV is a vortex, and F is a fold of the surface. For K-regime transition with an APG, Fig. 7.5b shows a qualitatively similar timeline pattern, initiated at X164.5, including the development of a vortex, albeit much more intense and rapidly developing than the ZPG case. However, the backswept HSL of the WWF is not observed, with the vortex appearing initially as a bow-shaped structure at X235, which seems to originate from a tilted transverse vortex tube upstream. Farther downstream, the vortex develops into an shaped vortex, with its round tip moving rapidly away from the main body, creating a vortex with an open tip. Figure 7.6 shows two stages of flow structure development for both the ZPG and APG cases, illustrated by the deformation of a continuous timeline surface, similar to a continuous hydrogen bubble pattern obtained experimentally. The surface is displayed in with the vertical location of the surface indicated by the scale to the right of the images.
For the ZPG case in Fig.
7.6, it is observed that the surface appears to develop a new fold, second F, which projects outwards and above the portion of the surface marking the WWF corresponds to the first fold, first F. This second fold corresponds to the HSL in Fig. 7.5, where marked particles accumulate in a backswept delta shape. Figure 7.6b shows that as time progresses, the second fold moves upwards and develops into a shaped structure at T71T, corresponding to the vortex that was observed and in Fig. 7.5b Figure 7.6b also shows the development of two vortices, SV1 and SV2 near the legs of the vortices. Material surface initiated at Y383, 53%, for K-type transition at TT with a 3ZPG16 and BAPG. Figure 7.7 shows the deformation of an initially flat material surface initiated at Y3.83 for the two transition cases at T1T. The black contour lines illustrate respective changes in Y height and show the development and growth of 3D waves.
In Fig.
7.7, the K-regime transition with APG, an upstream 2D TS wave progressively amplifies into an apparent 3D wave, appearing at approximately x1200. This 3D wave subsequently amplifies with its wave front P lifting up, accompanied by regions of depression along and in front of the wave, S1 and S2.
For the K-regime transition with APG, shown in Fig. 7.7b, the deformation of the material surface is similar to the case of the ZPG.
As the 3D wave develops downstream, a region of depression, S1, develops into a larger depression in front of the rising 3D wave, S2. These depressions appear to be caused by the downward sweep of fluid from the outer layer due to the lift-up of the 3D waves.
7.3.2 LCS.
The LAE for K-type transition with a ZPG, a 3D based on LAE detection, LAE 0034T156, by wall normal position, B contours of LAE in XY plane at Z114.7, C contours of LAE in Z, Y plane at X1228, using the same as panel B.
7.3.2.1 LAE.
7.3.2.2 LAE-based structures in transitional flows. Figure 7.8 shows 3D structures and 2D contours identified using the LAE method, based on the integral of the IE. 2 along fluid trajectories in K-regime transition with ZPG. The fluid domain X0 is initiated at 1020x1270, 75Z175 and 0Y6. To assure that the traced fluid domain XT, X0 is within the geometry range of the PSE data sets, a tracking time interval of T0, T1 is set as 0, 034T. Three-dimensional of LAE are extracted, LAE 0034T156 is 1, as shown in Fig. 7.8 of the surface reflect the respective wall normal position. The surfaces clearly show the development from a 3D wave-like structure into a shaped structure. Prior to the appearance of a shaped structure, a tongue-shaped bulge appears, B, which is analogous to the triangular bulge observed in the transitional channel flow investigated by Al.
19.
Structure B agrees with the backswept HSL of the WWF in Fig. 7.5, which is responsible for the second fold of the timelines. Note that the tongue-shaped head, C of the vortex, is different from a conventional one. This is because the LAE field for the boundary layer represents stretching caused by either a background field or induced locally by the vortex itself. It is known that there already exists transverse vorticity in a boundary layer, which cannot be distinguished in 7.5 from the transverse vorticity created by a developing vortex within the boundary layer. Thus, an increased concentration of LAE near the head of a vortex will be reflected by the of LAE initially manifesting as a tongue-shaped structure. The contours of LAE in an X, Y plane at Z114.7 near the and a Z, Y cross-section at X1228 are shown in Fig. 7.8b and C. The strongest stretching is observed to occur at two locations. One is in the region H in Fig. 7.8b, representing strong transverse stretching. The other is in two near-wall regions L2 and R2 in Fig. 7.8c, representing strong stretching, which appears coincident with the regions SV1 and SV2 in the timeline surface of Fig. 7.6. These patterns are considered to be quasi-vortices reflecting the legs of a previous hairpin residing under the region D in Fig. 7.8. As time progresses, these legs move towards the wall R1D, with their inclination angle decreasing, and the head of the vortex moving upwards from the main body. Of the distributions from the regions E, F to G, H agrees